So what is the syllabus? Here you can see that syllabus that is covering architecture, virtualization, infrastructure, network assurance, security, and automation. Actually, the syllabus is quite robust, and in this training course, what I try to do that I have covered each and every single topic in greater detail. So for example, if we are talking about the architecture, so I have covered architecture related to the campus area network, then architecture related to WLC design, then SD-WAN, a small piece of SDA, software defined access as well. QS you'll find in detail, and whatever topics that you're seeing here in the list, each and every topic point by point I have covered in this curriculum. Then virtualization also has been covered in detail. Even I have gone beyond this syllabus, and then I have added virtualization that is core for VMware networking or for VMware. So that things also I have added in these sections. Then infrastructure. So if you go and check this entire syllabus, you'll find that the core of this CCNP core itself is the infrastructure module. So in this module, you'll find that you have to know about layer 2 technology, layer 3 technology, wireless, and then IP services. And this is actually one of the lengthiest uh, module we have in this particular curriculum. This is very important where you are learning the layer 2, layer 3 wireless and IP services. So that will again add the tools inside your core fundamental of the networking technology. Then we have the network assurance. Inside that, you have to configure the basic troubleshooting and monitoring stuffs. Then finally, we have the security topic. Again, this security topic is as it is that we have in the old CCNP as well, I can say. So you have to know about the ACLs, the COP, some of the wireless security stuffs, some of the upcoming security stuffs as well. And then finally, we have 15% weightage for automation. We should know and understand say Python, JSON, APIs, how the APIs are working, Cisco EEM scripts, then finally the Chef, Puppet, Ansible, and Salt Stack. So in general, you will find this syllabus is quite robust and even challenging as well, because not only we have to know the existing, or you can say the old stuff as well, but you have to understand the new stuffs as well. And Cisco has taken care of this thing in the mind that maybe tomorrow you have to migrate your WAN to the SD-WAN or your LAN to SD-Access or SDA. So all these things has been taken care in this CCNP enterprise syllabus. Either it's a CCNP curriculum or it's a CCI curriculum. Each and everything has been taken care. Whenever Cisco has formed this or drafted this syllabus, they have taken care of this thing in the mind that there are cases that you are supporting the existing network, or there are cases that you are doing the migration, or there may be case that you are supporting the brand new upgraded SD-WAN or SDA network. I'm going to walk you through the CCNP Enterprise certification, and we'll see that what are the changes that Cisco is putting from this coming Feb inside the certification. There is complete strategy change you can see inside the CCNP Enterprise. We know that Cisco certifications are always valuable. You will get much salary hike, means compared to other certifications in the market. You will get much more reputation, and they are highly valuable certifications. We have complete sort of certification, means different type of certification like associate, professional, and expert. And as per your certification, even you can negotiate with the companies in terms of salary and other aspects. So they, as per your certification, they will think that you have the right knowledge, skill. You are very skilled in the IT. You are a skilled IT professional, and then you can go and ask for the salary because you are able to take the responsibility. So that's the reason the company will pay you. Here you can see that 99% of organization use certification to make hiring decision, because these certifications are structured in a way that they are going to test your different level of skills. So for example, if you see the old certification stack that we have, means now it's 28th of Feb. So now this become old, and now in the next slide I'll show you the new that will be available from 24th of Feb. So this old certification, you can see most of the people at the moment, at this point of time, they have, we have associate level certification, professional level, then the expert level, and different type of technologies are there. So for example, routing, switching, security, service provider, wireless, others. Now this has been changed in this. So now you can see that certification has been simplified, but on other hand, that will become much more focused. So now this CCNA, that is the associate level certification, this is the basic for all the professionals, and then again you can go for the expert. But CCNA become basic for the professional level. Now this CCNA will serve the purpose for enterprise, service provider, data center, collaboration, and security. And parallelly, you may have the expert level certifications in that particular domain. Now again, Cisco has other certification as well, and that is the DevOps, and their track is different. But you can see that 95% or maybe 90% of things relates with associate CCNA, and then the professional, and then the expert. Now here you can see that if you've done your CCI, so you know that inside CCI, you initially, means before this program, you have the theory and the lab, and that is 8 hour, very difficult type of exam. And there you must need very high percentage, for example 75 to 80% of marks in all the sections to pass your CCI. Now, comparative to CCI, CCNP exam is also very highly skilled type of things that they are going to ask you. It means they are going to check your depth knowledge inside that particular domain. Here you can see that you have the enterprise core, security core, service provider core, collaboration, data center core. So things has been grouped strategically inside different type of core. So you have one foundation, you have one core, and then you can choose the expert level, or more precisely the specialist level. So you have the core. First of all, you can see that you have the CCNA, and then you have core in these, say for example 5 domain. So you need core knowledge, and then you can go and get your CCNP, and then you can go and get your CCI. So from your core, now you can see that you don't have written and a lab exam, although your core, after your core you can go and write your lab exam. Okay, so choose between 2 lab exam inside this enterprise core. And what are 2 lab exam? If I go back, you can see that you have enterprise infrastructure, you have enterprise wireless, correct? So like that you have to choose. Now if you are in the security, choose your concentration, means you do your core, choose your concentration, and then take the lab. Like that you have all the tracks. You can see that from the slide, it's very much clear and what to do at what point of time. Again, here you can see that you have enterprise, security, service provider. For everything you have core exam, and you can go and have your CCNP. Means CCNP has 2 paper. One is core and one is the concentration, or one is the focused exam, and then you can go and write the lab exam. So for example, for enterprise, you have enterprise lab related to wireless and the CCI infrastructure, where you have different things like SD-WAN and SDA. Those new things are also added. All right, so now you can see that today means again, today is 27th or 28th. So now we are in this certification track. So 24th of February, we have Enterprise Core, that is mandatory, and then you can choose one. So either it's advanced routing or SD-WAN or enterprise, wireless or wireless implement. Like that, you can choose the certifications. Summary, that Cisco has tried to reduce the number of amount of certificates, and it has been focused and grouped well logically inside single technology, or inside single group, and is still and even they have removed the CCI written as well. So you can do your CCNP core and you can write your CCI. You can do your CCNP core and then you can go and focus on any of the specialized exam, like say for example SD-WAN or enterprise design, etc. All right, so this is the track. Everyone has a home, everyone gains, everyone maintains their certification, everyone awarded badges. So obviously by the end of day, once you complete the track, you can see that you have different type of badges. You have a specialist, then you have CCNA, then you have CCNP, and then you have CCIE. So you can start your journey and then you can slowly move your career from a specialist to the expert, and that's the goal. And once you complete your CCNA up to CCI in one particular domain, then you can move to the other domain. Okay, so there is a wealth of knowledge available, and if you want to gain it, if you want to become expert, go to one technology, complete it, and then move to other technology. That will be the strategy. This particular course is focused on CCNP Enterprise, and once we have one of the core topic, then we'll go and check the SD-WAN. Alternatively, we can go and check the other stuffs as well, like design, advanced routing, enterprise automation. But at this point of time, we can check CCNP Enterprise and the SD-WAN, because the combination of enterprise and SD-WAN will give you weightage. At the moment, SD-WAN is very hot in the market. It's very demanding, and if we combine like these two, core plus SD-WAN, so market value will be very good. What are the core skills you need? We'll see that we have complete syllabus. You can go and check. So now this was the past, where you have route switch, reshoot, arc, and other stuffs. Now in future, now present, I better tell this. This is the present. So you have enterprise core batch. You have a specialist. Uh, then you have the advanced routing batch, wireless batch. Means for individual exam also you will get that exam certificate, but better that will go and club. So CCNP Enterprise with any of the four, correct? All right, so now here again you can see the summary that you have. Like if you want CCNP Enterprise, you do the core and you can do the advanced, or you can do the core, you can do wireless, any of these two. You can do the core and then you can do the design. And here you can see that CCNP Enterprise, Enterprise. Okay, and just try to tell that how it is equivalent to CCNP RNS, CCNP wireless, CCNP DP. So suppose if you want to do CCNP DP, you do the core and then design, and you are the DP. If you want to do CCNP in wireless, the do all these three, and then you are CCNP in wireless. If you want to do CCNP RNS, do these two and you are CCNP RNS. If you want to be CCNP in SD-WAN, you do core and SD-WAN and you are the CCNP in SD-WAN. All right, so this was the certification changes, and I hope that you understand that what type of changes, what certifications we have to obtain our new CCNP, and from there we can go and prepare for CCIE as well. Hi everyone, welcome to CCNP Enterprise Core course. This course is divided into 6 different parts. Here you can see, starting from architecture, virtualization, infra, network assurance, security, and automation. You'll find the detail of these topics and the subtopics in this particular link. I hope this course will be informative and you'll gain new knowledge from this course. Thank you. Let us start with 1.0. That is the architecture, and what are the things we have to learn in this? We need to understand the design principle, the resiliency, the scalability, the redundancy, the WAN deployment options, etc. So here you can see that you have a long list actually, starting from 1.1, then 1.2, 3, and then 4, 5, 6, 7, up to 1.1 to 1.7 you have. Now here you can see that inside 1.4, you have to understand the SD-WAN design principle. 1.5, you have to understand about DNA or SD-Access design principle. 1.5, you have this QoS, both in wired and wireless. And then 1.7 is taken from the old curriculum. Even in the this 1.6, that is the QoS, that is also taken from the old curriculum. So it's again the mix of the old CCNP plus whatever new technologies we have, and why we have such type of mix, that I will explain you in the upcoming maybe third or maybe fourth slide. You'll understand that. Now let's cover point number 1.1a up to B. And what is the agenda for that? So you have to understand the enterprise network design, such as tier 2, 3, what is fabric capacity planning, etc. And then the high availability and redundancy, like first of redundancy protocol and SSO. We'll see that, because although this is only point 1.1a and B, but we have multiple videos to cover these topics, because again, this is a big topic. So let's try to understand this 1.1, and let's try to figure out that what type of design principle we have and why we have. So once we understand that why we are using this, that will solve our purpose. So we should understand that why we need this. Now let's see this WAN transport technologies. In this slide, you can see that the evolution of the architecture and design principle. So early network, we have the fixed and the bridge network, maybe 35 years back, when Cisco has invented routers and again the switches, and they try to connect different type of network. Here you can see that actually if we go from back behind that, say if we go and check the ARPANET and their principle and the TCP/IP discovery and their evolution, you can see that when the protocol first invented, and then again when Cisco come into the picture, and they have revolutionized the complete network domain or the industry. So here you can see that from 1990, when we have the multi-protocol and the business support model for IT, and at that time we have various protocol like OSPF, BGP. Those are the commercial protocol. Still in some of the places you can see that we are using RIP RIP. This again the old traditional methodology. Even we are using frame relay. Still some places we are using frame relay or X.25, etc. But now we are moving. So now if you see the journey from 1990 to 2000, where we have mission critical network, where we are supporting real-time traffic, we don't have even 1 minute of downtime, etc., etc. Means it's a highly mission critical network, and uh, if we are dealing for those topologies, how we are going to build those topologies. And again, if you move from 20, this is 2000 to 2020, now you can see that the evolution of SDN, and companies they are start deploying the SDN, either it's SD-WAN or LAN or campus automation or DNA, etc. So now is this the complete movement. Now again, this is the movement of network. So if you know the architecture principle, that what we are using in mid 90s or 2000 and now what we are going to use in 2020, actually each and everything has covered in this core. So we can start from our fundamental BGP, OSPF or other routing protocols, and then we can move and check that what type of protocol has been used inside SD-WAN or DNA. So for example, BGP, OSPF we are using here in the existing network, and OMP and TLOC we can use in SD-WAN, or Lisp we can use in DNA, etc. Okay, so we should have the clear picture, and if you're doing the migration from your existing network to the upcoming network, so if you know your existing network, if you know the upcoming technology and network, then only you can do the migration, and uh, a less number of issues will be there. All right, so this will be your summary slide, what we are moving, what we have at this point of time, and what we need in the upcoming network cycle. I mean, when we are refreshing the cycle or when we are migrating the cycle, and what type of challenges we have here. You can see that's again the uh, a small thing, means everywhere in all the places you will find the same type of challenges. Means the challenges are not as small, but in terms of gathering the facts, that's the common. So what are the common factors you want to improve, or what are the challenges you have that you don't want inside the SD-WAN or in the next gen network? So we know that scalability is one of the biggest issue. Means you can't scale. So you have this scalability, and we can discuss a lot and lot about the scalability. Now when we are talking about scalability not only in terms of your network or how many devices you have, but scalability in terms of routing capability, your IPsec capability, or even you can go and do some sort of deployment over the cloud. So scalability plus cloud integration means you can mix these things and you can think all in a single bucket. Then how you are going to integrate with IoT, Internet of Things, because again this is a big huge topic, and we know that Cisco DNA, Digital Network Architecture or SD-Access, they have the capability to understand. Even Cisco is making the IoT related products as well. So we have the chance that we can integrate IoT devices inside the enterprise network. Then what is the fast IT changes? What is the next? Can you do the automation programming? Do you have single pane of glass from where you are managing all the devices? Okay, so if I go and summarize these topics, again I told you that all these problem and the complexity that we have, they are common at this point of time. And if you see the existing network, still we are using the access distribution and core routing layers or L3 layers. So we have some sort of C and then P and then P, and then the network, they are divided into multiple routing instances or forwarding virtual routing forwarding instances, etc., etc. So you can go and support the network level virtualization as well. So what I will do, let me quickly mark here that what is the common issue we have in the existing network. I will not add cost at the moment, leave this. We can discuss cost later on with this cost aspect, because you may find that cost is also one of the driver to make or to do the refresh in the network. So what we want scalability. And this scalability we want in routing and we want in IPsec as well. And that's why we have DMVPN versus new SD-WAN IPsec or new SDN IPsec. Second thing what we want as a network, that we want integrated security. So at the moment I bring up my controllers, control plane, data plane, etc. I should have one solid, common, unified, secure fabric. Correct? So that's why this is also very, very important. Thirdly, what you want, we want that the overall cloud integration means now it is to, again, this have some cost effect. So companies, they don't want to go to the central hub or data center and then they want to go and use either DIA, direct internet access, or direct cloud access. Rather, from branch they want to do local breakout, and then they don't want to use the resources hosted over internet or the cloud. So that's again important in cloud integration. Now these things you have. Apart from that, one very important thing here I will add it, that is possible in the existing network as well. In the SDN solution, it's by default, that is the segmentation. So once you do the segmentation, the scalability, security, cloud integration, and segmentation. Apart from that, you want other features like you should have full visibility. Then you want monitoring. You want single pane of glass from where you want to do all these monitoring. You want solid reporting. You want easy way to do the troubleshooting, etc., etc. Correct? So these are the things and these are the terms we have, and we should consider these things inside the architecture principle. So let's just stop here, and in next section, uh, let's continue the same architecture principle, and I will add some more valuable point in the upcoming sessions. Let us continue our discussion and understand more that what we have discussed earlier. So we have discussed that yes, we have different technology, means in terms of evolution of network. So we can check the 1990 network, then 2000, then 2010, and then 2020 and coming forward. So what is the major change and how we are going to reduce the complexity in terms of design deployment? That actually it's very interesting. So here you can see that with the evolution of MPLS, and when the MPLS network it's start gaining the popularity, at that point of time you can see that how you can visualize the network. So here in the diagram you can clearly see that you have hub network and then you have a spoke. Somehow this design, this is giving some sort of idea that in upcoming iteration we are going to use some sort of spine and leaf structure. Sometimes it is referred as a cloth fabric. So you have your leaf, you have your spine, all the leaves, they are connected with the spines, and these leaves, they are not connecting to each other. And that's the thing we are achieving. Now again, when you are achieving this type of topology or this type of network where you have all the devices by default, they are one hop away. At that point of time, are you able to do the segmentation? For segmentation, we have already VRF, virtual routing and forwarding, and this is now from the years. So we are using the VRF technology, and later on you will come to know that in SD-WAN we are using VPN, that is nothing but the VRF only. Name or the term going to be used as a VPN, but logically or technically also they are also VRF, virtual routing forwarding. So now the complexity will increase when you have multiple devices, when you have different type of traffic and you mark those traffic as different type of VRF, how you're going to do the routing or maybe overlay routing, etc., etc. This is still we are using in the existing network, it is possible, but the thing is that we need to write actually the more line of codes, more number of configuration you need it. Okay, but still we are using, and you can see that we have multiple technologies like VRF Lite or MPLS VPN, because BGP is a nice protocol which is supporting all sort of address family related to VRF and even other address families as well. Now again, in this design principle, uh, how we are going to deploy the network. Do I have a single provider design? Do I have dual provider design? Again, if you go from single to dual, obviously the cost will increase. The high availability and the redundancy feature will increase. But anyways, the cost will increase. Or you are going to use the overlay network design. And this is actually the future. Cisco has started their overlay network design, means technically we are telling this independent of transport. So either you have a dual or three or four different type of ISPs, you don't care. You are creating tunnel on top of that, that's the overlay tunnel. And Cisco has introduced their intelligent WAN where they are using DM VPN as a overlay tunnel. Okay, but again, we are using IWAN and DMVPN, although so many companies they are using it, but again you have to write n number of codes or more number of lengthy configuration. So Cisco is telling all their existing network that from IWAN you can migrate to Cisco SD-WAN. Okay, why? Because again you can see the cones that increase design complexity, additional technology needed for SLA over commodity transport. So there are some extra overhead that is there, although the design and the solution is neat and clean and beautiful, but still you have some extra things that you can't do in the SD-WAN and the automation and the SDN solution that is there in the IWAN. So that's why this movement is there. Now let me quickly show you some of the slides related to single carrier and double carrier or dual carrier. So here you can see your network may look like that. So although you have different link, but you have single carrier. Suppose if one of the carrier, or because obviously you have single carrier, but suppose if that carrier will go down, at that time you have loss, and that's why it is listed here in the con that bound to single carrier for feature velocity does not protect against MPLS cloud failure with single provider. Obviously, if that cloud will go down, I don't have resiliency or availability that I can go via the other carrier. Obviously, this thing I have in the dual carrier, but again, the complexity is there, the cost is there. So you can compare here the pros and the cons. The con is that increase bandwidth paying for bandwidth twice, increase overall design complexity, may be reduced to common denominator between the carriers. Means overall you are increasing the resiliency, but cost wise there is issue. Now considering this diagram and this diagram, and again considering the overlay network design, if we have best out of all these three, so that will be the exact solution we are looking for, and that's why we are looking forward for SD-WAN solution. Again, we can see this all these things inside section 1.5. So let me quickly show you that 1.4. So we have 1.4 and 1.5 where we can address those design issues and how SD-WAN and the DNA or SD-Access combine together, and they're going to solve these issues. That also we can discuss in the upcoming sections. We are still in the basic section where we are learning what type of existing terminologies we have, and then what are the new things we are going to learn in the new CCNP curriculum. So let's discuss the WAN overlay technologies. Inside this, we have a layer 2 overlay and a layer 3 overlay. Means this overlay technology or terminology is not new actually. This is coming from the old technologies. Now we'll see in the SD-WAN and the DNA and maybe in ACI, that is again the data center topic, that this overlay terms will come again and again and again. So now we have something called underlay, that is your physical infrastructure, and then on top of that you are creating virtual dynamic tunnels. This can be layer 2, this can be layer 3. Layer 2 tunnel examples, here you can see that you may have layer 2 tunneling protocol L2TP version 3. You may have OTP or VXLAN, that's the very popular term we have, VXLAN, and this we'll learn more and more in the upcoming session. When we are talking about layer 3 overlays, we have IPsec, we have GRE, we have Lisp as well. Now this list I'm going to cover in the next slide, but at least you can understand that yeah, you are extending layer 2 fabric or you are extending layer 3 fabric, or to extend the fabric either you need layer 2 or you need layer 3 address families or addresses, etc. Now what is there in the SD-WAN or what is there in DNA is that we are going to automate this process, so you need not worry. So for example, in SD-WAN, to create the IPsec tunnels, like in I-WAN we are creating the DMVP and phase 3 tunnels. Here you're not worried to create the IPsec tunnel. At the moment you bring up the fabric, automatically those tunnels will get formed. Now when we are talking about the tunneling technology, a normal IP packet, a normal packet, we have the payload and the IP header. In GRE, again you have the payload and the IP header, and then you have extra overhead for GRE. Correct? In IPsec mode, either you are using IPsec mode in transport or tunnel mode. In transport mode, you have less overhead in terms of packet, but in tunnel mode that is much more secure, and by default most of the technology they are using the IPsec tunnel mode, where you have the inner header and the outer header. So at that point of time, obviously your header size will increase, but the level of security will also get increased. Correct. I'm not going deep inside the IPsec and how IPsec is working and GRE and how GRE is working. It's just the overview. We have just started the course, and as per the agenda, whenever these things will come and it will tell in the exam or in the curriculum that we have to go deep dive in this particular topic, I'll go deep in this, that I'll do the packet capture, we'll analyze the packet, etc., etc. But at the moment, we are just getting familiarity with these technologies. Already these technologies are existing, and what new we are going to get in the uh, new enterprise setup or in the CCNP enterprise. And now, for example, Lisp, locator ID separation protocol or identifier separation protocol. Now, if you understand Lisp, so for example, I already told you that you have LAN based SDN. So SDN solution, you have three things. You have LAN or SDN for LAN, SDN for WAN, and then you have SDN for data center as well. So data center. Now for LAN, the common term is SD-Access. Obviously, I'm talking only in terms of Cisco. So in Cisco, we have DNA is a name, but the SD-Access is the technology. In WAN, we have SD-WAN, and in data center, we have application-centric infrastructure or ACI. Now, if you go and learn deep all these technology, you will find that everywhere you have some sort of leaf spine type of a structure. So suppose if I have two spine and then leaves like this. Say again, I'll take one more leaf so I can show you the redundancy. So all these leaves will go and connect with the spine, and leaf they will never connect. These spines, they are working as a route reflector, means these spines, they have the database. So now these leaves, whatever endpoints or whatever devices are connected with these leaves, in DNA they are termed as a edge node or edge devices. So these edge devices, whatever network, whatever entries, MAC address, IP address, etc., etc., whatever they have, they are sharing with their spine or their parent. Now, this spine in DNA is mapping system or mapping resolver. Now, this spine in ACI is spine and leaf. The spine and leaf is a term inside ACI. Now, in SD-WAN, loosely if you analyze, you'll find that you have something called Smart Controller who has all the database for all the routing information. He is the controller or the control plane device, and he is working as a route reflector. In ACI also, these spines are working as a route reflector. And suppose if you are not knowing all this technology, so there are chance that you will get confused that, oh, what I am telling that, okay, in SD-WAN the Smart, in ACI this fine, in DNA uh, it's actually the control plane device. Sometimes we are telling this as a control plane routers or maybe border router, etc. So again, we'll see later on, but what at this point of time you can mark or understand is that you have some common authority. You have say common authority, just like DNS server, where they have all the topology information, all the database information. You think that you have the database information. Now these endpoints, they have offloaded with the information. So they don't have entire topology information. They know their local system or local endpoints, local entries. Once they have their local entries, they are teaching or they are telling the common authority that this local system I have, this local IP MAC I have, you please store at you. Likewise, he will also tell, okay, you please store with you. And when this guy wants to communicate with this guy and he don't know how to reach it, he will send the query packet to him. I want to reach there, and he will reply in a way that now they can communicate directly. Okay, so these are working as a proxy on behalf of, and most of the technology, most of the SDN technology, we have the same analogy. All right, so now we can understand all the different technology. If you say, for example, if you know other non-Cisco technology as well, for example, NSX T or any other SDN solution, there also you'll find the same type of thing is happening. Okay, and then once you start comparing these technology, it will become easier to learn and understand, because again, every day some new thing will come and it's almost impossible to learn and memorize all those things. So better you start comparing different technology, and then we can learn it easily. In section 1.1a, we need to discuss about quality of service as well. Now we are going to see the design aspect of this, because we should understand the core quality of service things, and then we should understand the SD-WAN quality of service things. Now the basic principle will not change. So how we are going to do the classification, marking, policing, shaping, scheduling, etc., those things will not change. So what are the things are going to change? The way that we are going to implement to the devices, those things are going to be changed in the SD-WAN. So I have already uploaded complete course for SD-WAN. There you can go and check how we are going to use this QoS actually inside the SD-WAN. Now at this point of time, let's focus that what are the basic components of quality of service. So here you can see that we have three important things: classification and marking. You classify the traffic, you mark it. We have policing. Policing is something like you have some sort of a strict rule with the traffic. So if certain limit or threshold will breach, it will start dropping the packet. And then we have this scheduling, including queuing and dropping. Means you want to give some sort of buffer in case if you have congestion. Means you don't want to directly drop the traffic, but you have some sort of buffer for that. Now here on top, you can see that you have different type of class of traffic. Say I have voice class of traffic, then I have video class of traffic, telepresence and data. Now for all these type of traffic, they have different requirement. So some of the traffic are UDP based, some of the traffic are TCP based, some of the traffic that we have need high latency, some can tolerate with delay, etc. etc. So now you can see in the bottom that say for voice traffic, you have UDP priority, but latency should be less than 150 millisecond. Otherwise, this voice will auto destroy. There is no meaning for that. Means whenever we are sending the voice packet, you think that your TTL is set with 150 millisecond. If it is not delivered between that time, it will get lost, something like that. You can see the jitter should be less than 30 millisecond, loss should be less than 1%. Now why we are discussing this? Because the first fundamental of QoS is classification and marking. So you can do the classification of the traffic, and you are understanding that what is the loss, latency and jitter requirement for different type of traffic, including that what type of protocol they are supporting. So you can see this voice, video and telepresence, they have UDP, means they are very much real-time traffic, but you want trustworthiness as well, you want security as well, and that's why you have the business traffic, or you have business data that is using TCP protocol. And that's why here you can see in the bottom that you have mission critical application, maybe SAP, maybe any type of database, etc. etc. Now the bottom line that you are seeing here, that is actually important when you are going to create the QoS policy. In other words, when you are going to create the policy, if you breach certain SLA as specified in the bottom, then that policy can take some decision. So dynamically changing the route, etc. etc. And that's it. And this particular feature has been optimized in the SD-WAN solution. So here it's very much coding based. You have to understand the protocol, means the device should understand the protocol. According to that, you have to write the code and then it will take action. Correct? So first thing is that to do the classification of traffic, there are several methods in QoS that you can go and deploy it. Here you can see one of the example for that. So you are creating the policy map, then you have class voice, because this is high priority traffic. You're giving priority for voice, you're giving priority for video. Then you have the critical data, you're giving 15% for that. You're using some random detect DSCP based. Again, there are different type of drop methodology. Means you're going to use RAID, random early detection. You're going to use tail drop. So those methods you can use. Again, you can see the data bandwidth percentage is 19%. This is again just an example. Your scavenger traffic, you are giving a less bandwidth percentage. Network critical, you are giving this 3%, etc. etc. So bottom line is that you need to write the code for all the devices inside your enterprise infrastructure, and then you have to configure it manually one by one. See, suppose if you have same type of hardware at 1,000 places, you have to write this code, or at least you have to do the copy paste to all those 1,000 devices, rather than if you do this thing via the SD-WAN. It's like you have, once you created the template, you can push from the management plane to all the devices. Correct? And here you can see that how this queue look like. So the important thing here is that you need to do the classification and then you have to map with the queue. So classification or forwarding classes to queue mapping, that will be the step number one. Again on top you can see this is for low latency queue or class based weighted fair queue, where you're adding the voice, video, etc. Now we have a nice example here that is clearly telling us that traffic shaping. So without shaping, how it look like. Once you apply the shaping, then how it look like. Once you apply the shaping, then the shaper typically delay excess traffic, smoothing burst, and preventing the unnecessary drop. If it is polisher, it will chop up, it will directly drop the traffic. Again, we have other example. So suppose this is your configuration, and once you apply it, obviously you have one bandwidth pipe, and generally we are applying this policy to the WAN facing interface. So suppose if you have 300 Mbps speed, correct? So you have 1 gig interface, but as per your agreement, you have 300 Mbps speed. Now, how you are going to use that uh, classes, and how you're going to allocate that 300 Mbps speed with priority, with some scheduling, with some RAID to the device that you can see here in the example. And again, we are making this as a child is called under inside the parent. Inside the parent we have the shaping, we have some buffer limit. Okay, so this is the way that we can go and apply the QoS. Again, we have one nice example here that you have your enterprise devices, you have your MPLS devices, where means in inbound what type of policy you want to apply. And these examples that you are seeing here is the standard one that Cisco is recommending. Still, if you want to learn more about QoS, you can go and check the QoS, Cisco QoS deployment guides, and there are tons of information we have um, over Cisco URL that we can go and get it. But this is something like a standard format. So all the companies, they have this type of existing network where they want to apply QoS. Now here you can say that you can't apply QoS to the ISP side. So whatever QoS you have to the ISP side, the same thing you want to match to your side as well. And that's why if you go and check the E and F configuration, so outbound policies, you can see the outbound policies as LLQ or class-based weighted fair queue, remark, real-time traffic, class-based weighted fair queue, etc., etc. Then you can go and check the service provider in the bottom. So what is there in the outbound? What is there in the inbound? So obviously my outbound will be the inbound for the service provider, correct? So we are going to manage this enterprise network, and then according to our QoS, we can consult the service provider and we can tell them, okay, you can map this DSCP, this policy from your side as well. As long as we have the common agreement, the common configuration, things will be better. Again, this design strategy that you are seeing here, there is major change in the SD-WAN. Now to reduce the cost for the SD-WAN MPLS, because you know that MPLS cost is too much, what customers are doing, instead using 100 Mbps MPLS, they are using 1 gig internet. So you will see even here also, in upcoming sections, I will give you some slight design related things or stuffs that you can compare later on in your study as well, that what is existing design means what is existing hybrid design, internet plus MPLS, and then when we are moving to next generation SD-WAN type of network, what design possibilities we have. And again, you can argue that okay, MPLS has this advantage, internet has this drawback, etc., etc. But nowadays the big enterprise, they are using dual internet connection, primary, secondary, both they are using 1 gig or maybe 2 gig internet interfaces, and then they are load balancing the traffic. All right, so if you have GRE or IPsec QoS consideration, on top you can see that you have normal packet without QoS. Obviously, we know that in IP header we have TOS type of service. Now, if you are QS with GRE. So you have your inner header, you have your GRE header, you have your outer header, and then you can see this TOS is propagating from inside to outside. Likewise, if you have IPsec encapsulation where you have inner header and outer header in case of IPsec tunnel mode, so you can see that we are retaining the QS marking. All right, so these are the examples related to QS, and just again, this is again very much high level, but you should understand, and as per our curriculum, exam or the Cisco expect that we should know these variations. We should know that what we have in the existing and what we are going to have in the upcoming SD-WAN QS. All right, so let's stop here. This session is quite interesting because we are going to discuss about the WAN and the LAN architecture designs. And actually we have started this course and we are studying about design principle, what is existing, what is going to become, or what is the SD-WAN or DNA, etc. As per this the scope of the CCNP exam. Now, thing is there. So I have one dedicated slide. I'll come after 2 to 3 minutes to this particular blank slide. Let me quickly walk you through 2-3 slides. So we know that there is demand, there's drastic demand in the networking, means there are so many things that try to connect with the network. Means we have IoT, we have so many handheld devices, we are managing different type of mobility features or mobility devices. We are managing everything maybe from the cloud, so we can integrate with the cloud. We have different applications. We want to do the visibility for the applications. To manage all these devices, the complexity will be very high. If you directly going to the cloud, your threat surface will increase. So you should provide security even from the inside or outside your, etc., etc. So the bottom line is this, that you have demand because you have to integrate different type of devices inside your networking infrastructure, and then due to that complexity will increase, manageability will be the challenge. In that case, your security, or you may have the holes in the security. So everything should be integrated, should be tight. And what will be the solution? So the solution is that instead using the monolithic, or instead using the existing way to manage the IT infrastructure, you can check the SDN, software defined type of architecture. Now what SDN will provide, at least at this point of time, is that you can focus on application. So SDN, the true capability of SDN is that now we can build the policy based infrastructure. Now what does it mean? So for that reason, I have this particular slide. So I'm going to draw one very nice difference in between all the technologies that we have, all the technology related to SD-WAN, and this will give you nice idea about different type of complexity that we have in existing and where we are moving actually. So for example, we have LAN, we have WAN, and we know that we have data center as well. Now for all these devices, if we are connecting LAN, obviously you have LAN. If you have multiple ISP, you can go and connect with the WAN, and then somewhere you may have your data center, correct? This is something like your existing network where you have spread branches and you're using existing methodologies to manage your IT infrastructure. Now what is the different when I'm going to use SDN approach in to manage the LAN, WAN, and data center? For LAN, we have something called DNA or SD-Access. For WAN, we know that we have Cisco SD-WAN. For data center, we have ACI. Now we know at this point of time that all these infrastructure, all these component of the IT infrastructure, they have control plane, they have management plane, they have data plane, they have policy plane. somewhere you will find the orchestrator plane as well. So who is the control plane for DNA, the management plane for DNA, data plane and policy plane, etc. So now this thing you have to study, and you can compare different technologies. So the control plane is again you will see that Lisp is a protocol who is managing the control, or who is providing the control plane information. But for that you have border routers. For SD-WAN we have OMP, Overlay Management Protocol, who is managing this, but the controller is vSmart. ACI, we know that we have a spine and leaf architecture, and we know that we have the COOP protocol. Maybe you have MP BGP protocol to manage the control information. Correct? What about management plane? For management plane, we have a DNAC center, that is nothing but Epic EM, Epic Enterprise Module. This ACI, they are also using Epic, but this Epic and this Epic is 100% different. This is for your DNA or DNAC at this point of time, we can understand. And this is there for your data center manageability. Then what about SD-WAN? In SD-WAN you have vManage. Then the data plane, you are going to use VXLAN. You have edge routers. For SD-WAN, your data plane is nothing but IPsec tunnels, but you are using vEdge or CEdge, the Cisco edge devices, Cisco routers or Viptela routers. ACI, you have leaf and a spine structure. So your leaf will be your Nexus devices. Here in the spine also, those are the Nexus devices that you can check the reference sheet or data sheet. But Cisco is using IVXLAN, something you can tell that intelligent VXLAN, because they have this one field for having the contract information as well. Okay, or maybe policy information as well. Some extra bits are there in that VXLAN format. Then the policy plane, who is the policy plane? The ICE we are integrating with DNA. So ICE is the policy plane. For SD-WAN, your vSmart is the policy plane, and for ACI again your Epic is the policy plane, because there you can go and build the policy and then you're pushing to different type of devices. This is the reference, and we can see, and now you can think that, oh my god, my existing network is better than what these stuff. So now you have to learn, understand DNA, SD-WAN, and if you are doing your data center study, you have to learn ACI and lots of programming as well. Okay, so this is the overview we have for all the upcoming technology. At least you will learn the SD-WAN and the DNA plus the WLCs. I haven't shown you where the WLC is fitting in the picture. I will check later on in the DNA section. Again, this is the DNA framework that you're constantly learning the network, and then you can take the decision. We'll discuss more and more about this framework in the upcoming session. But at least you can see that you can manage the entire network from the cloud management. Then you have this full automation capability. You have analytic engine inside DNA. It's a big UCS box that DNA boxes are. You have full visibility, because these devices, these catalyst devices that we are using, or the hardware that we are using for DNA, they are very smart, intelligent, and they have programming chip inside that. And due to that, the telemetry feature by default will be there. So we have the full visualization for all those events and things are happening with help of DNA. We can visualize the network. Then we have the full programming facilities, either for the physical or the virtual infrastructure. Everything is integrated inside the security. We know that we have the policy plane, that is nothing but ICE, from where we can push the policy to the DNA devices. So the principles are open, programmable, API driven, and obviously we can do everything that whatever we can do with the CLI or GUI, we can do with the API as well. Now here you can see in the diagram that you have the DNA center, that's your management plane. You have SD-Access and SD. So DNA is a term and SD-Access is the technology actually that is used. Then you have the hardware as a Catalyst 9K, and then you have the security features that you have in encrypted traffic analytics. It's a big thing. Actually, DNA is a big thing. SD-WAN is also big because now whatever we have a study, we have to rethink our study, or we have to redo the study. And if you compare, or if you try to compare that what we have done in the existing network and what we are doing here in the DNA or SD-WAN, so actually there is no much a scope of comparison. We should think that this is the new thing we are learning, and then we can start from the scratch. All right, so let's just stop here, and next section is interesting. That is our core existing technology that I'm going to discuss in campus design, and other topics are also there. This section we are going to discuss about the technology that we know, the multi-layer campus design, and obviously in the upcoming section we'll discuss more about the upcoming technologies. So we know that we have our core layer, distribution layer, and access layer. And again, I have slides for all these layers, so we can go and discuss there, but everything is going and connected to the core, and then core is taking decision that how to send and where to send the summarized routes, etc. So here you can see this core is connected with the devices again at the distribution layer, and then you have the access layer where we have the WAN, where you have the internet, means you may have hybrid topology where you're connecting with the WAN, internet, and you're connecting with your data center as well. Again, this is one of the campus design, and maybe at this point of time 80 to 90% of campus design is like this only, because now we are slowly moving to the DNA. The adoption rate at this point of time for DNA or SD-Access is not that huge, but we are expecting that it in coming 1 to 2 years, or maybe 2 to 3 years, we'll see much more adoption for SD-Access. Okay, so this is the core that you have, the core, distribution, and access layer. And again, if you split this diagram, you'll find that you should have, say, structure, modularity, and hierarchy, that you have the core, access, and core, distribution, and access layer, and where you are going to connect your MPLS circuits, where you are going to connect with your internet, where you're going to connect your IP telephony services, etc. Okay, so let's quickly check that all these layers, what they are offering, what exactly they are looking for. So here you can see the diagram left and right. You have the boxes and how it look like. So you have the core, distribution, and then you have access, like that you can think. We have dedicated slide for all these layers, so better we'll check all these slides one by one. So what's the use of the access layer? What access layer is doing? You have L2, L3 features. You can go and use the high availability security QS, IP multicast, etc. You can go and use QS. You have IGMP trust boundary. You have broadcast or multicast boundaries as well. If you want, you can suppress those requests. You can go and use various type of optimization method for loop prevention if you are using L2 methodology. If you are using L3 methodology, you can use routing protocol like EIGRP, OSPF, etc. If we are doing high availability and redundancy, we can use PAGP, that very less guys are using Cisco proprietary port aggregation group protocol. Generally, we are using LSAP, link aggregation control protocol. If you have, if you are using UDLD or flex link, etc. Okay, so this is something where you have your trust boundary, where you want to protect your network. Obviously, you want to protect your network to all the places, but this is the place where the endpoint will come and connect. So at this point of at this particular level, you want higher security, you want segmentation, you want MACsec, BPD filters, filter guard, etc. Correct? Now, next you have the distribution layer. Distribution layer is there. This is the second type of backbone or second level of backbone we have, where you want to apply some more mature policy and high availability features. So that's why we have the high availability load balancing QoS. We can do the aggregation of all the access at the level of distribution, means you have less number of devices that is there in the distribution label at compared to the access layer. Even in access layer, you can use 2K series or 3K series switches. In distribution layer, you can use 4K or maybe a 6K. Now Cisco is requesting everyone to use 9K model of switch, so you can choose those recommended or the supported models in terms of hardware capability. They can do the route summarization, fast convergence, and HSRP GLVP. That we have separate section for first hop redundancy protocol, HSRP GLVP BRRP in upcoming session. So we'll discuss more in the upcoming session about that. Core layer, obviously it's the core. This is the backbone. You want high availability and the scalability for the core layer. They are the aggregator point for all the routes. And again, if you go and refer this diagram, this particular diagram, you can understand that things are converging towards core layer, and then from core layer, you can distribute those routes to the other locations as well. Again, here you can see in this diagram how it look like. So you have layer 2 access, you may have routed access, you may have virtual switching, etc. Then you have the distribution level switches, everything is coming to the core, and then it is going to one of the branch or the data center or other branches. So this is the network that we are very much familiar. And again, with respect to design, you'll find that there are variations that we need to consider. Obviously, there is the evolution for the hardware. For all the devices, there is evolution or there is upgradation for the software also for all these devices. So how much virtualization these devices are supporting, uh, how much hardware, again that depends, means how much throughput as a customer or as a user I want from these infrastructure. So according to that, the hardware can be implemented, and it's recommended that even if you have this network and you want to upgrade the switches in this network, use Cisco 9K switches. So in future, if you want to migrate to DNA, you have some sort of switches where those are supporting DNA. That's a strategy nowadays all the company are using. So they are not ordering for the legacy or the old hardware, rather than they are going for the new hardware. So in future, if they want to migrate, they can use that strategy. Again, as per design perspective, here you can see that you may have layer 3 distribution interconnection, or you may have layer 2 distribution interconnection, means you want to stretch the boundary up to distribution layer. So this red color wire that you're seeing here, those are L3, and this bluish color connection that you are seeing, those are L2 domain. And that's why it is telling that what you want layer 2 access. So obviously in the bottom, in the access switch, you have the VLANs. You want to do inter VLAN routing. You have the obviously by default the STP will be running there. You have the HSRP or GLBP. You want some ether channel, you have some BPD guard, etc., etc. So all type of prevention you have. Some of the companies they are using layer 2 boundary up to the distribution layer. So here you can see the difference. Let me quickly show you the difference. So you have layer 3, this red color link in between the distribution switches. They are using a routing protocol to forward the traffic, and that's true actually. If you see any of the upcoming network or any of the SDN solution, you'll find that even for layer 2 carrier or even for layer 2 also, we are using routing. So what does it mean? So for example, if you go and check Cisco ACI, application centric infrastructure, where you have leaf and a spine, they are connected behind the scene, but they are using layer 2 type of routing strategy. Means MAC addresses also can route. That you can check. Well, that's true. uh, that the routing is better than that we are doing in terms of switching for high available network or for a scalability reason, and that is again one of the design aspect we have. So suppose if you have two different fabric, a stretch fabric, you don't want to extend the L2, although you can extend the L2, but routing is always preferred uh, on top of the L2 tunnel. So for example, the L2 tunnel is not preferred over L3 routing tunnel. All right. In short, routing is preferred design rather than stretching the L2. This is also supported model. This is not for the reason that we are talking that L2 is supported model or L3 is supported model. This is something that which is giving the capability of, say for example, VSS, virtual switching system. So uh, there are parallel enhancement in the network. Suppose if we have switches, if we connect, obviously you know that as per their priority and MAC address, they will choose who is the root switch, who is the secondary switch, etc., etc., all priority and everything. Now, what you can do in this case that you don't want these triangles in a network. What you want straight line. So you collapse these two switches inside one unit, and then the bottom switches also, they can think. So this diagram will be like this, or maybe this diagram will be like this. Means two switches, they are connected back to back. Physically they can be like this, but logically they will be like this. That's the overall idea if you are using this type of technology. And then that's the evolution you have. If you see the data center evolution, you'll find that it started with 6500, then it moves to Nexus 7K, then Nexus 9K, and then now Nexus 9K CI. So started with normal this type of network, then moved to, for example, VSS, then moved to VPC, then moved to leaf and spine, and then leaf to spine ACI. Okay, so evolution is there. Up to you which network or which type of a standard network or design you're supporting. You will find this type of network as well. You'll find this type of network as well. Both are supported in an existing model we have at this point of time. So you can have these devices in same unit, these distribution devices. So you have, for example, one control and two data channel, and these devices, they are working as a MEC, like multi-chassis Ethernet, etc. Means you are eliminating the L2 loop rather than you have a straight line in the network. All right, so this session is actually becoming lengthier. Let me stop here, and next section will continue from here. Let us continue the previous section, and we have seen that we have option that we can use L3 distribution link, or we can use L2 as a distribution link in between that. If we are using L2 capability, we have option that we can go and use virtual switching system, where we want to reduce the number of triangles in a network. Now here you can see the convergence time with respect to RSPBST or RPBST plus, then the routing protocol like OSPF and EIGRP. And that's the thing that we are considering, that when we are using the routing protocols, their convergence is faster. They are not using the blocking interfaces, like if you are using L2 interface, then STP will run automatically and 50% of link will be unutilized. So those things are not there. That's why always this routing design will be preferred with the switching design or L2 design. How it will be looking like inside the DNA, that we are going to discuss in the upcoming session. But if you see this diagram, from this diagram, let me try to explain a few of the things. So here you can see that you have border router. So for example, BR, then you have edge devices. Maybe they can do switching and routing both. So you have the edge devices as well. Now, with the use of these edge devices and plus this APs that you are seeing here, that they are near to the end point. So now these routers or now these edge devices, they are not learning the entire routing table, entire topology table, not everything, but they are knowing that what is connected to them, and then they are sending those information to MSMR. So we have this resolver, or we have the servers where they are pointed to, or they are sending all the information to the global routing table. Like that, you can think. You have one DNS, and that DNS having the information from where to where I have to reach. So those all information that DNA has or having. Then you have the access point that you can see, and then you have the WLC, that all the access point control information, or all the access point, those are managed via the WLC. We are going to discuss this also. So we have the underlay architecture or infra, we have the overlay architecture and infra, and this underlay and overlay in conjunction, they are working for SD-Access. Here you can see that the ID challenge, new services, you have the mobility services, scalability, flexible and programming infrastructure. Those are the things that you will find inside DNA or SD-Access. We have the controller, we have the control plane, and this thing we have discussed. We have the policy plane, that is the ICE, identity services. With help of control plane and policy plane, or with help of the DNAC plus policy plane, we are going to manage the DNA fabric or DNA center. So you have the endpoints, and the way that these endpoints are thinking now, they have offloaded the load that we have in the existing campus area network, or in existing enterprise campus area network. Correct? So these are the things that is going to be new thing, or these are the new innovations we have from the existing campus area network. So now if you see this existing network, and again you can go and refer this MPLS WAN technology design guide, you will get a nice document from Cisco. Now if I go here and highlight you certain things, so here you can see that you have your core, then you have your campus area network where you have the distribution switch. You may have one building with one switch, other building with one switch where you have connected the access point. Here you can see you may have one floor where you have much more number of users. So then you have the endpoint, IP phones, you have wireless access points, and you have roaming users, etc. So you have the access layer endpoints, maybe you have IoT devices as well in the existing network as well. Then you have the distribution, and then you have the core switch. Now here you can see that your core switch, one portion is going towards the WAN, and maybe this is my data center or main location. One portion it is showing that it is going to data center. So you have the Nexus switches where the core switches are connected, and then you have Nexus 5K, then you have MDS and your storage network and your application servers, etc. So you have your data center. Here you can see that you may have CE to PE. So suppose this is your CE, customer is, here you have PE, somewhere you have the MPLS backbone, that you have the P devices, so PE and P devices. So here also you can see that your core switch is connected with the core router, and then it is going to be terminated to the WAN. Here you can see that you have the VPN endpoints for the remote users, or suppose if you are using DIA or maybe DCA, direct internet access or direct cloud access, then your traffic is going via the firewall to the internet where you have IPsec tunnel for the remote users, or maybe those users who are connecting with IPsec. So either teleworker, mobile worker, or the remote user. So maybe in few of the branches they are using internet and the WAN, both means they are using the hybrid type of branch, or they are the hybrid type of branch, or maybe we have the dedicated MPLS type of branch. So that's the reason everything is shown in this particular diagram, and this is one of the validated campus area network. In this particular curriculum, you will not study this data center portion, but you should know each and everything that is showing here in this diagram with new format, with SDN format. And that's the overall goal with the CCNP enterprise network, that you should know the DNA and SD-WAN, but you should know the core as well. Again, the same thing here. You can see that how the core distribution, and then again you're going towards dual MPLS or dual carrier. Maybe you're going towards layer 2 WAN. Maybe you have some internet and you're creating IPsec tunnel, and then you're going to the internet. Okay, so all the summary routes, they are coming and collected to the WAN distribution layer, and then it is going to the core. Now this slide is also very important, and this is equally important for SD-WAN as well. So whenever you are doing the migration or the new SD-WAN deployment, at that time you have to mark the site. So you may have sites, say for example, gold, silver, you can mark it. It's just the name, and maybe bronze. Now gold means that you are using uh, uh, say for example, you have dual devices and dual ISP, that is your core, this type or maybe this type, that is your high available network. Silver may be that you have only one device but you have two ISP link, either two MPLS or maybe one MPLS, one internet, or dual internet. Correct? And bronze means that you have one device, one connection, one device, one connection. So as per the type of branch, you can categorize the branches or branch type, and then you can create the templates, and then you have to push the templates, or you can create the configuration and then you have to manage them. So for that, you should understand that what type of remote branches will be there. Now once you identify your remote branch, that one part of this course, the other thing that you should know, that what is behind that. Correct? So once you know that the WAN part, you should know the LAN part, and then that will become the enterprise network. Correct? So for that reason, you may have multiple options, but I'm going to show you that a few of the examples. So maybe you have shared LAN, maybe you have L3 connection with the switches that is behind this edge devices, or maybe you are using some sort of highly available and redundant design, or maybe ether channel, multi-chassis, or stack of switch. Actually this is the recommended way, and suppose if your WAN is your internet, so obviously you have to put the firewall as well in between that. Correct? So these are the design options we have. The last recording and this recording, actually it's very important. You can, I'm going to upload this document so you can have the reference, whatever we have discussed in the previous section and this section, and these, actually these sessions, these slides, these recordings are the fundamental of how we are going to design what is in the existing, what is going to come in the DNA and SD-WAN. Inside 1.1b, we have to understand or discuss about the high availability techniques such as FHRP and SSL. So let's discuss one by one. FHRP is nothing but first hop redundancy protocol, and how it is working And what are the flavors you have? You can see that we have HSRP, that is the hot standby redundancy protocol. Then we have VRRP, that is virtual routing redundancy protocol, and then we have the gateway load balancing protocol. Now, VRRP is the industry standard. This HSRP and GLBP are Cisco proprietary. Mostly, we are using VRRP. This VRRP and HSRP both are very much similar, but this GLBP is different, and we can discuss that how different this gateway load balancing protocol is. Basically, what is happening in all these gateway first hop redundancy protocol or gateway load balancing protocols are that, say, these, suppose if we have two routers or maybe switch, and these switch, they have the common interface going towards the LAN, and suppose you have one PC here. Now this PC can have gateway here or can have gateway here, but the common term here is, or the technology here is, that we are not giving gateways, so for example .1 or .2 for this particular IP who is .10. Rather, we are giving the gateway to some virtual IP, and that is glued with this device and this physical device. So what is the benefit? The benefit is that, for example, this particular device or router, so for example, this is router A, this is router B, he is working as an active member and B is working as a standby. So that means that packet is forwarding in this direction, and suppose if the link going towards the WAN or going towards outward is down, or the device is down, automatically the packet get gateway from this direction. Okay, so that's the term, and that's the mechanism, some sort of high availability mechanism, we can say, that if one of the device is down, or maybe if the link that you are tracking is down, you can go from other direction. Again, if this device will come back online and you have set some prompt, then again the traffic will go in this direction. Okay, so that's the thing that we are using with VRRP and HSRP. GLBP is bit different, because now if you see these terms or technology, you'll find, oh, so is it like a spanning tree or something that all the time one of the member is active and other is working as a standby, means 50% of the resource utilization we are doing? The answer is not exactly what we can do. So for example, for certain VLAN 10, 20, for example 30 and 40, if I have these four VLAN, for VLAN 10 and 20, as per high priority, here higher is better, you can set priority 200 towards router number A. So suppose this is router A and this is router number B. This A is for active, is for standby. A and B is the name of the routers. So for 10 and 20, he is the active member, and so for example 30 and 40, this B is the active member. So that means that they are using some sort of active mechanism to send the traffic, and obviously you have different virtual IP for all these different subnets. This way, in case of HSRP and VRRP, you can achieve active type of load balancing. GLBP is a bit different, that is doing the load balancing by default. So let me show you this in the diagram. You can see that when you have the distribution layer, here you can see that you have the first hop redundancy protocol. You can go and use first hop redundancy protocol. So used to provide a resilient default gateway. These are the technologies. They are providing millisecond of convergence time, means if one of the active member is fail, it can go to the standby or the backup. BRRP, if you need multi-vendor interoperability. VRRP is nothing but the industry standard that we have already discussed. GLBP facilitates uplink load balancing, and the name itself is Gateway Load Balancing Protocol. Preempt is there to avoid the backhauling of the traffic. Means preempt is something that if your device will go down and if it will come back up, again it will become the primary member of the active member. Okay. Now here you can see that how they are working. So they have these devices, they have their IP, they have their MAC, then they have their virtual IP, they have their virtual MAC. Now this virtual IP is shared, so you can think as you have some ghost router in between, and that is glued with these two devices. So when the traffic is coming, here you can see, and if he is the active, the traffic will forward it in this direction. Okay, so traffic will come, it is going in this direction because he is the active guy as per the priority. And here you can see the example for all the IP, the MAC, the gateway. Gateway is the virtual IP, and the ARP entry. Now this is the standby or active and backup. If this will go down, obviously it will reroute it to the other direction that we have discussed. That's the mechanism, 100% same with HSRP and VRRP. But if you go and check the VRRP methodology used in SD-WAN, that you can go and refer the SD-WAN course, you'll find that there is customized VRRP inside SD-WAN where we are tracking the OMP, we are tracking the prefixes. So track OMP, track prefix. Rather than here, if you want to track the interface, you have this option that you can go and track the interfaces as well. So what I'm telling that, suppose if you have WAN and you want to track this interface, you can track it. Suppose if this will go down and its priority is 200, its priority is 150, automatically you track the interface and decrement the priority. So this priority at the moment the link is down, this will become 200 minus 100 means 100. Now 150 is higher, so traffic will go in this direction. So that's the tracking thing we have. And again, the preemption option we have, you can preempt it. So if the device is down, the traffic will go in this direction. When it will come back up, then again it will go from the primary member, from the active member. Same thing we have in the VRRP, so that's why I'm not discussing here. Same methodology we have, because VRRP is open for all the vendors. It's a multi-vendor support. Rest of the things are almost the same. Now, next we have the GLBP. So let's quickly discuss about GLBP. GLBP is doing some sort of gateway load balancing. So here you can see this IP, MAC, virtual IP, and virtual MAC. Now you have virtual MAC here, and here you have two different virtual MAC. So what will happen that sometime traffic will go in this direction and sometime traffic will go in this direction. That's why you can see that both the direction we have the traffic flow. Although I haven't seen much of the customer using this methodology due to some internal load balancing issues related to MAC addresses. But yeah, we have this option that we can go and use the GLBP as well. So where we don't have to group the VLANs that we have discussed earlier. So you don't need to group the VLANs, but they will do the load balancing at their own level. So they can do their MAC address based load balancing. And here you can see that how some of the traffic is going via B, some of the traffic is going via A. One is the active virtual gateway, one is the active virtual forwarder, like that. Okay, so this methodology that they are doing the MAC based load balancing, this methodology you can create some sort of VLAN based load balancing. So some traffic will go via the gateway 1, some traffic will go via the gateway 2, and as a whole unit they are working as a active load balancer. All right, so let's stop here. Let us continue the previous section and discuss about the other high availability features that we have. So we have SSO, that is the stateful switch over, and how it is helping to provide high availability in the campus architecture design that we are going to discuss. Now here you can see that we have two different type of network design. We have layer 2, layer 3 topology. We have multi-tier layer 3 topology. Here you can see that this blue interfaces or this blue lines are a layer 2 interface, and then this red one, red color connectivity lines are L3 interfaces. Here in this diagram you have L2 plus L3 link. Here in this diagram you have everywhere the L3 link. So either it's L2 L3 topology or complete L3 topology, we have option to do SSO. We can do stateful switchover. Now, what does it mean and why this is important? You can see here that you have two use cases for this. Either you have a big catalyst chassis box where you have active and a standby supervisor engine, or you have a stack of switch. Now suppose if you want to upgrade the image but you don't want to take the maintenance window. So you don't want to tear down, or you don't want to stop the production traffic, and then you want to upgrade the image. That's the one of the use case with we have with the SSO. In that case, we can go and achieve this target with help of SSO. Now, when we are using SSO, there is one problem that uh, suppose you are doing iOS upgrade and you have this SSO feature enable. You have active supervisor engine, you have a standby supervisor engine. The problem here is that if you do the switch over, that will not be a stateful. Now to do this a stateful switch over, you should have the common database between the active soup and the standby soup. Here in the diagram you can see clearly that their active and their standby supervisor engine, they haven't synced their routing database. So particularly with respect to routing database, they are not doing the stateful switchover until unless you go there and enable one of the feature that is nothing but NFS, non-forwarding, non-stop forwarding. So here you can see that if you go to these protocol like OSPF, BGP, etc., and you have to enable the feature called non-stop forwarding, NSF. And for that, you should go and check the dataset that which particular version or hardware or model that is supporting NSF, non-stop forwarding, which is not supporting. Okay. Apart from that, it's okay that we have this SSO. We can go and use SSO with NSF, and then they will do the stateful switchover. That's the one very important point we have. The other point is that suppose if we are using ISSU, that in-service software upgrade. Now in that case also, you should know that which particular supervisor engine, which particular image, what is the hardware platform that you want to upgrade. Suppose if you want to do the major upgrades, so for example 6.0 to 7.0, it is recommended from Cisco TAC or Cisco that you do not do in-service upgrade, or you do not do inline upgrade. Rather than you take complete maintenance window, take complete downtime, and then you do the major upgrade. Now these SSO and these ISSU or these fast upgrades, whatever we have, for these upgrades we can go and use this SSO, and it is quite a bit handy. Okay, so that's the feature we have with the SSO. All right, so let's stop here. We have completed 1.1 and now we are inside 1.2. In 1.2, the topics are that what is the principle for wireless LAN deployment, the wireless LAN deployment, and the services involved inside that. So let's first try to understand the design and deployment option for the WLAN or wireless LAN. We have controller based architecture, we have mobility architecture, how it works. So here you can see that what components we have. Components we have the wireless LAN controller, we have the access points, and actually if you compare these technology with the SD-WAN, so we know that we have the evolution of SDN technology or SD-WAN or any type of SDN, SD-LAN or ACI. Now in that, what are the things we have? We have something called control plane and we have the data plane. Now, if you think WLC, wireless LAN controller, as a control plane, you can think access point as endpoint devices. They are working as a data plane. Means these access points they are dependent upon their control plane or the controllers. Then you have the management plane. You can use Prime Cisco Prime infrastructure, or you can use Epic EM or DNAC DNS Center. We have the mobility service engines as well, MSE. So here you can see that you have the access point and they have to join. First of all, they are forming some sort of cap WAP tunnel, and that is the industry standard nowadays with the control plane. So you can think that the data plane, they will join with the control plane. The data plane is nothing but the AP. The control plane is nothing but the WLC, and then they are working accordingly. So once they join, then they are getting the configuration pushed, kicked from the controllers, and then they are up and running, or they are ready to run. Now, when we are talking about the centralized wireless LAN architecture, here you can see that you have your access point and they may be spread across the geographical location. You have the controller. Now you have to think, or you have to check actually the data sheet, that how many access point that a particular controller can hold, and according to that you have to go and check the capability of the controllers, and actually when you are designing the network, how many access point and how many users you have. So those capacity planning we have to do. All right, so here you can see that in this design that you have the cap WAP tunnel, and this cap WAP tunnel, that is the industry standard. It can be for control plane. So here you can see that when they are forming the control plane, they have the DTLS tunnel. Even in the SD-WAN also, when we have the vSmart as a control plane, and we have the vEdge or edge devices as a data plane, they are forming some sort of DTLS or TLS tunnel in between to send and receive their OMP traffic or the control plane traffic. For data plane, they have the DTLS, that's the optional. But for data plane, we know that in SD-WAN we have IPsec tunnel in between that. So there it is different, but most of the things means logically, if you try to analyze, you'll find that yeah, WLC is an old technology, means wireless LAN control is quite a bit old in the market now. SD-WAN is also become older, but they have introduced this control plane and data plane feature long time ago. Even if you go and check the catalyst switch where you have the supervisor engines, so supervisor engines and the line card, so you have the soup engine and then you have the line card, they are also very much have the concept of control plane and data plane. So this control plane and data plane feature is not something that is 100% new in SD-WAN, but somewhere they got inspiration and then we are working inside the SDN. So now we have the cap WAP tunnel, and one note is that cap WAP is not supported on the layer 2 mode. Okay, so this is the thing, and let us continue. Here you have one graph where you can understand that your AP access point will boot. They will discover the wireless LAN controller. They will form the control connection that TTLS will set up. They will join the WLC. If you want, you can reset as well. They can check, WLC can check the image as well. From WLC, they can push the configuration and they are up and running. They are ready to run, correct? Again, very much similar to the SD-WAN steps. They are using the plug and play feature as well. The SD-WAN is also using either plug and play in case of C edge, that is the ISR devices, and they can use ZTP, zero touch provisioning, in case of V edge. All these things are explained with the lab in the SD-WAN course, so you can refer that. Now let's see and compare the plug and play option or feature here. Why we want plug and play? You want plug and play that, so for example, in remote sites, you don't have the IT management staff. So what you can do, simply someone at the remote location, they can connect the interface and that's it. Once they connect the interface, rest each and everything can be done remotely. So they can reduce the cost, they can reduce the complexity. You have the high level of security. Why? Because you are forming the DTLS tunnel with the controllers and the time and productivity. So that's the reason actually we need or this plug and play or this ZTP are very popular nowadays. So you have IT staff sitting somewhere in some location and he can manage n number of sites with the feature of PNP. How this PNP process is working, here you can see that obviously they have to resolve the DNS, they have to get the IP via DHCP, then they try to initiate the traffic, they try to build a web tunnel with the WLC, that's a discover phase. Then they can go and check cloud related features. Actually, what is happening in this at this point of time, that while they are discovering the AP, they should they have to form the DTLS tunnel, and for that DTLS tunnel there are chances that you have your in-premises certificate or you are using some other cloud hosted certification features. So cloud redirection will happen for these APs, and then finally they can go and join. These steps are very much similar in the ZTP process or PNP process in Cisco SD-WAN as well. So you can go and compare these two features. What you can do, that you can check the PNP process for the AP, and then you can go and search over Google the PNP process for SD-WAN or the ZTP process of SD-WAN. You'll find the steps will be similar. Obviously, the way that we are doing is different, but overall the steps are very much similar. So what will happen here you can see the summary slide we have, that AP will boot, it will discover the WLC, they will form the DTLS channel, they will join the WLC, and then WLC will push the configuration, and then the AP will be up and running. Now here you can see that now you have the three different tier. You have the management plane, either you are using prime infrastructure or DNAC, and that is solved or resolved inside DNS Center. Then you have the control plane, that is nothing but WLC, and then you have the data plane, that is nothing but the access point. These access point can sit anywhere remotely, and you are using the feature called plug and play. So from the prime infrastructure, you are using WLC to the methodology is plug and play to install all the remotely hosted access points to reduce the complexity, to reduce or to enhance the productivity as well. Okay, so let's stop here. Let us continue our discussion. We have the controller-based architecture and the mobility-based architecture. Now this term mobility and the roaming both are different. Mobility means you are providing the mobile features. Roaming means the user can roam from one place to other place. He can associate and de-associate with a different type of access point. I can show you the diagram here. You can see this user, this laptop that you're seeing here. It can associate and de-associate with different access points, and that's the feature roaming. Mobility is providing you that capability that you can roam. Now the next important thing we have is to understand that what are the WLC or which type of WLC is there and what is the capability. Again, you can go and refer the Cisco dataset. There you will get much more information about the capabilities, features of the WLC. So for example, we have the Mobility Express who can support 52,000, 50 APs, 1000 clients, 100 AP, 2000 clients in these series. As you can see, they are supporting up to 100 AP. Then we have mid-size enterprise level WLC, say 3500, Cisco 5520 series. There you can see that how many APs, clients, and what is the overall throughput. How many is APs client and what is the overall throughput for this 5520. And for the large enterprise, we have 8540 WLC that can support 6000 AP. Even the rake unit, you can see it's bigger. So this WLC, that is 5520, is one RU, one rake unit. This 8540 has the highest scalability, for redundancy and scalability. Stability is again the different thing. Scalability is different thing. Higher availability and redundancy is again the different thing. So we can achieve all those targets, but this 8540 has the highest scalability, means it can support up to 6K, 6000 access points, 64000 clients, 64K clients. The deployment models, we have centralized, Flex Connect, and Mesh. More and much information related to this WLC and their operations and all, you will get inside CCNP WLC course. There is separate CCNP course for wireless LAN controller, or we can say that for wireless. Not only for LAN controller, but for complete wireless, we have separate course as well. But here also you will get the core knowledge, means what is AP, what is WLC, their association, de-associations, and their design related stuffs as well. So now when you are grouping the mobility engines, when you are grouping the mobility devices, here you can see that you can go and group this mobility devices. The mobility group name is a mobility group everywhere. They have their own MAC address, say 1 for this mobility device or the controller, then 2 for this controller, and then 3 for this controller. So that means his neighbor is 2 and 3. So 1 has neighbor 2, 3, 2 has neighbor 1, 3, 3 has neighbor 1, 2. And now this client, if you check this client, he is roaming from one place to other place, and because all these controllers, they are part of one mobility group and they have their own DTLS channel in between them. So for any user perspective, they don't have much issue to roam from one place to other place. Obviously, behind the scene, they are doing this control plane and data plane message exchange. So we have the cap wrap tunnel and we have the join. We have all those things that we have discussed initially, and then they can associate and dissociate the SSID or the access point. Now again, you can see that you can go and group the mobility group. So if you want 24 WLC and 72 WLC inside the mobility group, you can go and group them. You should go and check the mobility group, say for example 8.0, 8.2 and 8.3. Even if you go and check the latest data sheet, you will find some new addition, some new revisions. So according to that, we can go and design our mobility groups. Okay, so let's stop here. Let us continue and discuss the best practices. We should do the RF planning. We should do the RF optimization, means we should categorize the data, voice, video, traffic, and location and client density. We should have the optimized gig Wi-Fi as a primary and gig Ethernet as a fallback. We should have high redundancy, and we'll see in the upcoming slide that what does it mean by SSO in terms of client, AP, and WLC. And then we have AVC, application visibility control. That means for mission critical traffic or application, how you are categorizing the application, correct? So you are giving priority to one traffic over other. And that's why we have actually AVC. They can recognize the application with the metadata, and then obviously we can put the rule for that. Now here you can see that we have three SSO. We have client SSO. That means that if in case of any type of failover, the client state remain active. There is no problem with the active client state, in other words. Then we have the APSSO, means suppose if you are failovering from one active WLC to other, still your AP, they don't have disruption, they have stateful switchover. And finally, you have the cluster of WLC. So one is primary, one is backup, standby, etc. Like that, you have the redundancy in terms of WLC as well. So here you can see that box 1-to-1 means 1-to-1 availability. One is in active state and other is hot standby. I will show you that you can connect this via dedicated link in the upcoming slide. Let me quickly show you this. Here you can see that you have the redundant port in between two WLCs. Here you can see the redundant port in between two WLC. Correct? So like that, if client sessions are active, those are client SSO. If AP sessions are active in case of failover, those are AP SSO. There is timing in between that. So suppose AAP, which has joined the WLC, and then he is actively tracking the active WLC. Suppose this active is gone, then he will send some probe and he'll wait. He will not get any response from the active. That means he will go and work with the standby. Okay, and it's a very normal situation you have. Say for example, here you can see that downtime during failover reduced to 5 to 1000 millisecond depending upon failover. In case of power failure on active WLC, it may take 350 to 500 millisecond. In case of network failure, it can take up to few seconds. And we have the SSO support for these models: 3504, 5500, 7500, 8500, and Wisdom 2. You can group these WLC, how you can make primary, secondary, and tertiary part of one group. For that, you can go to the high availability section. There you can see that you have the backup primary controller IP, backup primary controller name, because everything we are going to do via the GUI. So it's actually very easy to create the or have the redundancy from the main or the active configuration GUI dashboard. And here you can see that you have the redundant port that you can go and connect these redundant port for SSO. And again, we have 13504 pairing device. So pair of devices, here you can see you have two devices, and you can see the RP ports where you can go and pair or make this as a part of redundancy. All right, so these are the things related to redundancy of WLC. I hope you understand up to this point, because next section again we have some summary slides, 2-3 summary slides, and then we'll move to other section. So let's stop here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's a very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main players at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now let's start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see, that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers, correct? Now, what type of terms we are going to use? Um, Overall, if you see that how the technology fits in, actually it is simple, and that's the reason that AWS and other cloud service provider, they have gained their popularity. So it's simple to implement, and it's very easy to use, and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router, I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct? So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider, they also uh, programmed, or in the same way they have written their code, so they can connect either with Cisco or Juniper or any third party or any networking domain companies, correct? Because any of the companies, they can use the cloud hosted applications, not only Cisco, correct? All right, so these are the terms that are going to be used, and when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this Google, GCP, AWS, and Azure, so these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, is still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them, so we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer, correct? And then per project service requirement, again this depends upon the service. Now when we are extending the private network to the public domain or private cloud, say for example at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity, available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, 1 virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage, there are n number of things. All different cloud vendors are providing. Now, how this topology look like? Again, private network extending to public network. I'm using BGP as an overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications. Correct? Now, in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router. And then same way, they can exchange the routes as well. All right, so let's just stop here, and in next section we'll continue from here. In 1.3, we have to understand the on-prem versus the over-the-cloud deployment. And actually nowadays it's a very popular term that you have something on-prem, you have something over the cloud, or you have mix of both. So you are using on-prem and then you are using multiple cloud. Now we have three main players at this point of time when we are talking about the cloud service provider. We have Amazon, one of the major stakeholder for cloud services. We have Azure from Microsoft, and then we have Google as well. Google is also gaining popularity, and then they have done a huge investment in the cloud domain. Now let's just start this section and try to understand that how these terms fit together when we are talking about on-prem and over the cloud deployment. So when we are talking about hybrid cloud networking, here you can see, that means that you have on-prem and you have a single public cloud provider. When we are talking about multi-cloud networking, then you have on-prem and you have multiple cloud providers. Correct? Now, what type of terms we are going to use? Overall, if you see that how the technology fits in, actually it is simple, and that's the reason that AWS and other cloud service provider, they have gained their popularity. So it's simple to implement, and it's very easy to use, and it's highly available. So these are the key pillars upon which these services depends upon. Now, for example, I'll skip this slide. I'll come back to this slide. So for example, I'll show you an example here. So now I have my private network, and inside that private network, I have one virtual router or maybe physical router. This router, I am creating gateway with Google VPN. It may be AWS gateway, it may be Azure gateway. Everywhere you have same type of feature and capability. Maybe the name and the terminologies will get changed. So then you can see that I can reach to the Google Cloud router, and this can work as a gateway for the application that is hosting behind this router. Correct? So you have multiple application hosted here, and those application have gateway as a cloud router. Then I have the VPN connectivity in between public and the private cloud, and then maybe I have a user hosted behind this private network. Okay, so this way actually the flow will work for all the cloud providers. So let's try to understand these terms. So obviously you want to create the IPsec or IKE version 2 or IKE version 2, 1 and 2. So I think 2 and 2 twice, but yeah, you have option. Some of the cloud provider, they are supporting version 1, some of them are supporting version 2. You have SSL, you have PKI infrastructure. Then routing, it is supporting a static BGP, OSPF, EIGRP as a IGP. So you have to redistribute IGP to BGP. BGP is one of the standard protocol, and BGP is used everywhere. We have the tunneling methodology as well, like IPsec tunnel mode, GRE, MGRE, MPLS, etc. So bottom line is that whatever things that we have learned in Cisco, whatever technology that we have learned in Cisco, the same way these cloud provider, they also uh, programmed, or in the same way they have written their code, so they can connect either with Cisco or Juniper or any third party or any networking domain companies, correct? Because any of the companies, they can use the cloud hosted applications, not only Cisco, correct? All right, so these are the terms that are going to be used. And when you create the tunnel in between your private and the public cloud, obviously you have the VPN gateway one place, you have the VPN gateway at the cloud side, and then you can form the tunnel. For routing purpose, you have BGP who can take all the routes from one place to other place. If you want to learn more about this, Google, GCP, AWS, and Azure. So these are the links that you can go and verify. Now, why we are using multi-cloud or multiple cloud? Because obviously different, if you are use different vendors, so they have their own availability. If one of the vendor go down, is still the other vendor is up and running. So the reason is high availability. We have all these actually cloud providers, they have some unique features in them. So we can use one feature from one cloud provider, other main core feature from other cloud provider, and we can mix and match our requirement as a customer, correct? And then per project service requirement, again this depends upon the service. Now when we are extending the private network to the public domain or private cloud, say for example at this point of time to the public cloud, then Cisco has their cloud service router, and obviously they have the compute requirement, so they have the route process, and along with other services it can be installed over ESXi. Here you can see the list of the minimum requirement. So for example, performance elasticity, available licenses, we have 10 Mbps to 10 Gbps. We have the CPU footprint, 1 virtual CPU to 8 virtual CPU, and the licenses. So you can install the CSR over any of these compute. Once you install this, then you can form the tunnel from your private to the public network. And here you have the list of all the dashboard of different type of cloud provider. Most of the cloud provider trainings are having very less cost, or it's free. You can create your, at least you can create the account over any of these cloud provider, and you can go and check the features. So for example, I can go and open Amazon, aws.amazon.com. I'll get the dashboard, and from that dashboard I can go and check n number of features they are providing. So you want to do compute, you want to do networking, security, storage, there are n number of things, all different cloud vendors are providing. Now how this topology look like? Again, private network extending to public network. I'm using BGP as an overlay protocol. I have tunnel in between my private network to public network, obviously for security sake. And then even you can see that I can redistribute IGP over eBGP. BGP will carry those prefixes till the Google Cloud, and then it will reach to the gateway router, and then it will reach to the applications, correct? Now in case of physical routers, that capability is also there. So I can create the IPsec tunnel between the physical router to the Google VPN, and then it will reach to the Google router, and then same way they can exchange the routes as well. All right, so let's just stop here, and next section will continue from here. Let us continue our discussion and add more complexity into the design. So now we know that we can have the interconnectivity between the private network and the public network. So here you can see that your private network, you are creating IPsec tunnel. You have the IPsec IKE version 2 tunnel mode. You create a tunnel up to these VPN gateways, and these you're reaching up to these routers. These routers are actually the gateway for these virtual private cloud. These are some of the compute thing where you have hosted your applications. So these application having these gateways, and from here it is reaching to this point, and here you may have your user. Okay, so this is one of the deployment model, but we have others as well. So let's see that how DMVPN is taking role in this. Before coming to DMVPN, here you can see in the diagram that you may have interconnectivity in between clouds. So here you can see that from AWS cloud to Google Cloud, I have this VPN tunnel, and then these maybe you have the users here and you have servers here, etc., etc. There may be chances, but these compute network can communicate across the cloud as well. Now, if you want to make this arrangement little more automated and much more meaningful, then Cisco has given the solution. We can integrate with DMVPN, dynamic multi-point VPN. Now this dynamic multi-point VPN or DMVPN, what you can do, that you can define the hub, and then you have the spokes. So here you can see you have the spokes. So this will work as a hub and a spoke methodology, and depending upon which particular phase of DMVPN you are using, it may be hub and a spoke, it may be a spoke and a spoke as well. If we are using, I think, DMVPN phase 3. Again, if you want to add much more redundancy as per your design requirement, still we have the option that we can add primary and secondary hub, and then we have the spoke. So now you can see that we have the redundancy in terms of spokes, or even for few of the spoke is primary, for few of the spoke is the primary. Like that we can do some sort of load balancing as well, and this will give us the perfect design related option. Same thing here, you can see that for one of the cloud, he is, or the first router is the gateway. For other cloud, the other router is the gateway, but they are working as a primary and secondary. Now at this point of time, you may be thinking that then what is the role of SD-WAN when we are integrating our existing WAN with the cloud? Now role here is that you should go at this point of time and can search SD-WAN infra as a service. In that case, even this is much more automated. You can go to vManage. You can have your images. Obviously, you need the images to spin up. Even from vManage, we can manage the ISR as well. We have the virtual edge as well. We have ISR virtual as well. So you can manage n number of devices. You can create the template for those devices, and then you can push the configuration from vManage to the edge devices. Not only you can track the on-prem devices, but you can track the devices that will be installed inside the cloud. Okay, and that's the true power we have when we are using the vManage to manage such type of requirement. So it will give you great visibility, and the use of access or ease of access, or the ease you can access the network and monitor the network, it's really amazing. So you can go and check that how we can achieve the same target With help of vManage, obviously the way of doing things will be different, but we are going to achieve the same target in much more simpler way if we are using the SD-WAN, and then we are integrating with the cloud. Let us start with section 1, where we have to understand the architecture and various components. What are the topics we have inside the section 1? First of all, we are going to discuss about the architecture and component. Then we have to understand the components of the controllers. We have the orchestration plane, management plane, controller plane or control plane. Then we have the data plane devices. Inside data plane device, we have various things like what is TLOC, how they are forming the IPsec tunnel, what is Viptela route, what is the BFT, bidirectional forward detection. Now there are some common terms that we are going to use. So in terms of data plane device, we have V-Edge or Viptela Edge routers. We have C-Edge, that is nothing but Cisco ISR/ASR routers or router. Those are nothing but SD-WAN router. Then we have the controller. We have vSmart controller, that is nothing but your control plane. We have the orchestrator plane, that is the vBond. And then we have the management plane, that is nothing but vManage. Now this small v is not virtual. This stands for Viptela, because Viptela was the parent company who has introduced SD-WAN. Now the overall solution will look like this, although this diagram will find little bit busy, but once you understand all the components and the hierarchy, then it makes sense. Now starting from the orchestrator plane or the orchestration plane, you can see that you have a couple of vBond, and those vBond are identified as a DNS or a URL. They may be inside the DMZ zone. So one of the interface is towards the private data center, or one of the interface is towards the data center. Other interface is facing towards the public interface. So you have the orchestration plane, then you can see that you have the management plane, that is nothing but vManage. It is recommended that you should have cluster of vManage, means three manage or three servers inside same cluster. Now it's actually very big, and here you can see in the slide that it can be in multi-tenant mode or dedicated, means dedicated to one customer or group of customers having multi-tenancy, or maybe one company or organization having multiple sub-organizations. So any possibility will be there, but this is the management plane from where you can manage entire fabric. This is the one common place from where you can manage everything. So here you can see that from this management plane, I am managing control plane devices, plus parallelly you can push the configuration template to all the devices. Correct? All the devices in the data plane. Not only in the data plane, but in the control plane as well. So the usability of this is huge, and we'll see some of the use cases of the vManage, but vManage is there. From there, you can do the monitoring, troubleshooting, configuration, in short, everything we can do from the vManage. Then we have the control plane. That may be inside containers, or we have the VMs that you can spin up over the hypervisor. Now, recommendation for control plane that they should also be in group. So maybe you have two vSmart in one group, two other vSmart in other group, but they should have the same configuration. That means these are my control plane devices. They should have the same configuration, or they should have the common configuration. Otherwise, there may be inconsistency in the network. Now, in terms of control connection, whenever the data plane devices, they are forming the control connection, they can form the control connection with one group of vSmart as a primary, other group of vSmart as a secondary, but in any case, all the vSmart, they should have the same information. Then finally, you can see that you have the data plane devices in the bottom. So irrespective of transport, either it's internet, MPLS or 4G, they have the IPsec tunnel among with other devices. By default, they have full mesh type of setup, means all the devices have the IPsec tunnel with all the other data plane device, correct? They can be physical, they can be virtual. Okay, so now here in the diagram, you can see if I draw it. Let me try to draw the diagram so you can understand. Here you can see that this link, either this can be DTLS or TLS, and here also it can be DTLS or TLS. In vBond also you have the control connections, so vBond to vSmart, like that. I'm not drawing all the connections, but this is always, actually vBond connections are always DTLS. Now what is DTLS and TLS? TLS is nothing but your SSL, secure socket layer, plus TCP, TCP based SSL, and DTLS is nothing but your SSL plus UDP, UDP based SSL. That is nothing but your DTLS. Okay, some space, less space is there, but you can understand. Now you have a control connection like that, and then you may have the data connection or the IPsec connection. So how it will look like, let me quickly draw here the data connection as well with some other color. So now from device to device, you have the IPsec connection. By default, it will be full mesh. So here it's not in a bundle, but single. They have the IPsec connection, that is the data plane connection. So obviously the traffic will move only from one data plane device to the other data plane device, and from the control plane, that is your vSmart, you are sending the updates. The controller, that's the vSmart, they can send the update with help of OMP protocol, that is the overlay management protocol. They can use or they can send actually different type of control messages related to routing updates, security key exchange update, related to policy exchange. Okay, so that's actually the role of the controller. Now here you can see that this is the overall overview, or this is the summary of the architecture that we have inside the SD-WAN. Now why it is very interesting and important, because Cisco SD-WAN, they can scale. So here you can see, if I start from the bottom, any location, branch, co-location, cloud, any transport, satellite, internet, MPLS, 5G, LTE, any service. They can use branch security. We have cloud integrated services or security. We have the application quality experience for SaaS application, voice collaboration, cloud on ramp. Means you can integrate with any type of service in the SD-WAN. And then we have any deployment. Any deployment means on-prem, cloud, multi-tenancy, even MSPs like managed service providers, they are also offering these services. So you can see that how open and secure our network is. Open, that we can go and we are very much near to the cloud integration, or we are near to the cloud. Even we can install everything over cloud as well, either it's a controller or data plane device. You can integrate with any services. It's so flexible. You can run the application over broadband or internet as well, because anyways they are forming very high level secure tunnel in between data plane devices. So adding all these points, you'll find that the SD-WAN is highly secure and desirable solution at the moment. And I think almost all the customers, they are going for SD-WAN deployment. Now again, you can see the SD-WAN deployment architecture. You may have your branches spread across geography. You may have your physical branches. You may have your virtual branches as well. And then you can see that you can use software as a service. You can use DIA, directly use those services. The good thing about this, that whatever place you have your services or application, you can track each and everything from your vManage dashboard. So you have single GUI, single dashboard. From there, you can manage or you can track all the applications. Okay, so not only you can track and manage the application, but you can do the configuration and changes, etc., etc. There's so much tunable options are there. So here you can see that software as a service, or it's a VPC, virtual private cloud, or it's enterprise controllers, or it's a private cloud. Everything, each and everything we can go and integrate with our SD-WAN fabric inside that architecture. Let us talk about the controllers. We have three different type of controller. One is the orchestration plane, that is nothing but the vBond. Management plane, that is nothing but vManage. Control plane, that is nothing but vSmart. So vBond, vManage, vSmart, or vManage, vBond, vSmart, etc., etc. Now here you can see in the bracket vBond and comma NAT and vSmart comma OMP, because actually these features are very important to understand. And we should understand these features. So for example, vSmart. vSmart is your control plane. And among vSmart, suppose if you have 2-3 vSmart, so among vSmart, they are running OMP. And from vSmart to edge devices or vSmart to branch edge devices, again you have OMP. So we have overlay management protocol, that is nothing but your control plane. So for example, if your OMP is down, your control plane is down. So that's the importance we have. Let's learn one by one what are the baseline features with these controllers. Say, for example, we have the orchestration plane. What are the characteristic and what is the use of the orchestration plane is that they are used to do the secure bring up. So to bring up your Viptela fabric, first of all those devices, they are going to, or they have to go and they have to contact with the orchestration plane or the vBond. So what is happening? So suppose that's your day 0 deployment and you want to deploy one of your edge device. What will happen that first of all, this edge device, they will go and contact the vBond. So let me draw here and let me try to explain. All right, so let me redraw here. So what will happen that these devices, they will go and contact first of all the vBond. Now what vBond will do, he will check what is the serial number, what is the chassis ID of the edge devices, and this edge device, they will go and check the organization name, org name of the vBond. Now once this vBond will satisfy, because they are doing some sort of whitelist modeling, they have the list of all the devices that is going to be part of the fabric. So once the vBond will be satisfied that, oh, the request I am getting is legitimate, they will form some sort of temporary, they will never form the permanent tunnel, temporary DTLS tunnel, because remember, vBond understand only DTLS. So they will form the temporary DTLS tunnel, and then he will offer this edge device what is the vManage and the vSmart IP addresses. Now next time these guys, they will go and contact the vManage and the vSmart, and the same process will happen. vManage will go and check the serial number, chassis ID of vEdge. vEdge will check the org name. That's a part of certificate. That's a part of licensing certificate. Then again, the vSmart will go and check the serial number and the chassis ID, and then the vEdge will check the org name of the vSmart, and then what will happen? What will be the end result? The end result is that the edge devices, so here let me try draw with other color. So they will form the permanent either TLS or DTLS connection. They will form the permanent connection with vManage, with vSmart, and your temporary tunnel will tear down. Okay, so here you can see the nodes. Let me try to read out the nodes here. We have the nodes that is telling that the orchestration plane is there to do the secure bring up of the all the component, so securely bringing up the devices in the fabric. Orchestrate control and the management plane, first point of authentication, distribute list of vSmart and manage to the edge devices or routers, facilitate NAT traversal, require public IP, could sit behind one-to-one NAT, highly resilient, multi-tenant or single tenant. So that's the use of the orchestration plane. Its use is defined, their role is defined, and these are the main points. Now you can go and install this over the compute over ESXi or hypervisor, and here you can see some of the important points that they should internet reachable, they are doing the orchestration, they are securely bringing up the fabric. Now the next very important piece we have is the management plane. This management plane will go and integrate with third-party APIs, and it is there to do, you can see, to do day 0, day 1, day 2 operation, means all the day. You have to bring up first of all your vManage, and then you have to add vBond, vSmart. You have to do at least minimum configuration. You have to do the licensing process. Once your controllers are up and running, then only can add the data plane devices. And for that, you have to start with vManage. This is centralized provisioning. It can be multi-tenant or single tenant, where you can build the policies and template. You can do troubleshooting, monitoring, software upgrade, GUI with RBAC. It can be integrated with third-party tools for APIs and programming. This is also highly resilient. Now this is also a software, so you can go and install the cluster over the compute, either ESXi or KVM. Used for centralized management, API, configure, monitor, and management. These things then can be done via the vManage. Finally, in the controller section, you have the vSmart, that is the actual brain behind the scene. Now, with help of this particular vSmart, what you can do, that it will provide you the intelligence. So you can do app route policy, central policy, you can do any type of service insertion, chaining, whatever, all policies, IPsec key exchange, overall routing management, everything is done with help of a vSmart. That's your policy engine. That's your brain. Okay, and this is also a software, and you want to operate this vSmart in a redundant manner in a group. So you can have group of 3-4 devices. You can have other group in other data center or other zone with 3-4 devices. Only thing is important that all those vSmart in a single fabric, they should have consistency. They should have same database. That's the important thing. So here you can see routing information, encryption key propagation, policy management, service chaining, traffic engineering, and so many things that we can do and achieve with respect to vSmart. All right, so that's the main thing we have with all the controllers. Next, we have the data plane device, and you'll find so many interesting things inside the SD-WAN data plane devices. Not only that they are doing the actual movement of data within the IPsec tunnel, but whatever existing WAN features we have, say for example, we can do VRRP, we can do OSPF, we can do BGP, we can do EIGRP, etc. So all the traditional routing protocols they are supporting. We have advanced features as well, like zero touch deployment or provisioning. They have the physical plus the virtual form factor. So these things are there, that is there in the existing WAN as well, except this zero touch provisioning or plug and play options. Even plug and play option is there in the intelligent WAN or iWAN as well. But what new things we have? It can do application recognition. It's a huge feature. Now, so for example, in Viptela devices can go and they can do The application recognition, they have something inbuilt DPI, Deep Packet Inspection Engine. In Viptela, that is COSMOS. Again, I'll repeat, COSMOS. In Cisco devices, we know that's very popular term as a N-bar, that is network-based application recognition. Now Cisco has introduced new VM as well, and they have enhanced the N-bar. We have something called AVC as well, application visibility control, enhanced version of N-bar, you can say in other words. But yeah, you have the application recognition engine. So your devices now, the SD-WAN devices now, they can understand the application metadata like Palo Alto firewall or firepower firewalls can do, or you can say that next generation firewall, they have this capability to understand the application or recognize the application, and then as per the policy, they can take the action. That's the same thing we have in the application aware routing feature. Okay, and that's one of the major advantage we have. Not only we can do the app aware routing, we can do app aware firewalling as well. Now apart from that, the edge devices and the control plane devices, that's the vSmart, they are forming the OMP session. Means we have the routing peer with my control plane devices, and then I'm exchanging all my routes. Either it's a Viptela route or TLOC route. Later on, we are going to discuss about these things like OMP, TLOC, and etc. etc. So either it's a security route or service route, it's a Viptela route or OMP route, or it's a TLOC route or next hop route. All these things you are sending to your controller, because we are dealing with the SDN solution, your controller is working as a route reflector, RR, and once they receive the route from one of the branch, they will reflect to the remaining branches. And that's the whole thing. Now, if we compare this particular solution with, say, for example, ACI leaf and spine, what leaf are doing? They are sending their endpoint uh, registration or their endpoint information to spine. Spine is working as a route reflector. He can reflect to everyone. Likewise, here also you can see these are your leaves. You think that these are your endpoint. These guys, whatever they are learning, they are sending to vSmart, and vSmart is reflecting to everyone. In between, the underlying protocol is OMP. And again, it's a huge, OMP can carry so many things. But the overview or the top view is like that. Then obviously these are the data plane devices. So let's go and see that what are the variants we have in this data plane devices. You can see that there's a number of devices that is supporting for SD-WAN. We have enterprise network compute system, say ENCS 5100, where you can go and integrate, or we can go and deploy the SD-WAN images, the third-party firewall, load balancer, etc., etc. It's a very capable devices, and so many customers they are using ENCS devices. You can see overall throughput as well, 250 to 2 GB. As per your scale will increase, your compute, your memory, your RAM, etc. increase. That means they will support more throughput. Now we have both the form factor. We have hardware, we have software. Here you can see the Viptela devices. In Viptela, you have a small end devices like VH100, then 1000, then 2000. Very much it is looking like Cisco device. Cisco maybe 1800 or 2800 type of hardware. Then here you can see that you have iOS XE image. Now this is the thing I want to explain here, because I found some of the confusion around the community. See, we have SD-WAN, Cisco SD-WAN, and you have two type of operating system. One, iOS XE with something 16.10 or more, maybe 16.11. You can convert or you can upgrade the image of iOS XE. Inside iOS XE image, we have SD-WAN code written. So it will support features, SD-WAN features. But there is one native operating system that is nothing but Viptela OS. This Viptela OS, actually the evolution of this Viptela OS was due to SD-WAN. So SD-WAN was the core in the brain, and then evolution happened. Now this Viptela operating system, it is coming with vEdge, Viptela Edge, but Cisco has introduced the same image you can run. Here you can see vEdge next generation ISR platform. You can use Cisco ISR platform to run Viptela OS as well. And that's a huge advantage we have with Cisco. Means you have the best operating system for SD-WAN, and then you have the best hardware for branches. You can integrate both, and they will do all the features, that whatever features we have in the SD-WAN and whatever features that is going to come in the SD-WAN, everything will be going to be supported. So that's the good thing we have. Okay. So apart from that, as per the scale, you can see we have the ISR. We have the ISR 4000 up to 2 Gbps speed. Then we have the aggregator routers, ASRs, that having up to 200 Gbps of speed. So if you are looking for the speed and throughput, you can go and choose your branch devices. I have few slides for edge devices. You can see 100 and 1000. How behind the scene this vEdge is looking like, very much like Cisco device. You have the management interface, you have the serial console, USB, LEDs, you have the fixed 8 gig Ethernet SFP port. Why I have added this slide? Because I want to tell you one nice thing about these hardware. These hardware, they are coming with TPM chip. Now this trusted platform module or chips, they have anti-counterfeit and secure authentication. Means what is happening, that OEM, Cisco is the OEM in this case, they are adding or they are putting the RSA keys inside this TPM chip, those preloaded certificates or CSR, certificate signing request, they are shipped to the customer. So what customer has to do, at the moment they connect their WAN interfaces to the WAN, or they should be VPN 0, we'll talk about this later on, but at the moment you connect your interface to the WAN, they will do the auto authentication, or automatically they will get authenticated from the controller devices, because you have the preloaded certificate inside the TPM chip. Now considering the fact that the edge devices, they are coming with the secure image or secure boot image, Cisco devices also coming with secure image. Cisco devices, they are using TAM module, Trusted Anchor module. I will show you this in the next slide. And the edge devices, they are using TPM. This TAM module, you can check, this is there in the UCS boxes as well. You can go and check. So how it is secure, you can see you have the anchor module that is very near to the hardware anchor, microloader, and then bootloader check the operating system, and the OS get launch. So it's like internal integrity checked by the anchor module, and then it will load up. Likewise, you can see that you have the common features between TAM and the TPM. So they are anti-tamper protection, non-volatile storage, policy and configuration. They have crypto services like key store, random number generation, and crypto image. Now all these features that you are seeing here, this is belonging to certificate plus to secure your hardware. And that's the power we have. And even the provider of SD-WAN, they have thought of all these things before putting or before giving the SD-WAN solution. So all these features we have inside the data plane devices. This is the last video in section 1.4. This is 1.4b, traditional WAN and the SD-WAN solution. Now, what exactly inside SD-WAN solution is that, so this is your existing WAN. Whatever things that you can't do in the existing WAN, or it's very difficult to do in the existing WAN, that I can go and do inside the SD-WAN. So the term is simplified solution, the scalability, inbuilt secure fabric. Those things are by default there inside the SD-WAN. That is although not there in the in the existing WAN, but you can achieve with certain number of codes. One of the major drawback we have in the existing WAN is that its visibility is not that much. And suppose if we have to create IPsec tunnel, now if you use DMVPN, that is very much the case we have inside the SD-WAN, is still that DMVPN or any type of IPsec VPN that we have, in SD-WAN you will find that it is 100% optimized. So at the moment you bring up the control plane, now the control plane, now I'm seeing that most of the customer, they are taking the control plane from Cisco. So you may have over the cloud control plane. So I have this cloud hosted, say for example, cloud hosted control plane. So my control plane burden is gone now. Now I am only worried for the data plane devices. Now these data plane devices, what are the major things they will do? They will do routing, they will form IPsec tunnel, they should do data plane policies, or they should do data policies, not data plane policy. But inside data plane policy, you have so many things actually. You can refer my SD-WAN course where I have explained this, and we have so many things to consider when we are talking about policies. But in short, what I'm telling that what are the capabilities you have is the routing, you have the IPsec, you have the app, say for example, app aware routing that is falling under data plane policy or data plane or data policy, etc. So routing, IPsec, data policy, and plus cloud integration. These things are the nature of SD-WAN. They are evolved with these capabilities. Although, in other hand, if you go and check the existing WAN, so you will find that for each and everything you have to write the code. So, for example, if you want to form IPsec tunnel, you have to plan, and that DMVPN planning for hub and spoke and redundant DMVPN design itself is time consuming, and it should be constant throughout the devices. Correct? Means you should use some sort of a standardization for the configuration. On other hand, when you have the IGP and when you have the BGP, so those configurations should also be um, good, although the routing capability of Cisco devices is the best, and Cisco is very good in the routing at least. They are very good in other features as well, but routing is the fundamental and core of the Cisco networking. Even Cisco is very good in switching and in data center and other domains as well. All right. So the thing is that you can do all those things, but it's restrictive. You have to write n number of line of codes. It's not that much scalable. You can integrate with API, which is very difficult. You have to uh, check what are the alternates there in the market. So you can use Ansible, Playbook, etc., to do full automation for the existing WAN, and it's a time consuming. So you don't have full visibility, and its evolution is not that by default it can scale in terms of routing, security, cloud integration, etc., etc. Correct? So that's a major uh, differences we have in the existing WAN and the SD-WAN. Is still, if you go and complete that SD-WAN course, you will get the complete picture of SD-WAN, because already at this point of time we know whatever network we are working is the WAN. One portion of that network is the WAN infrastructure. So we know about the WAN, and once you go and complete the SD-WAN course, then you will understand about the SD-WAN course, and then you will be at the better position to compare with the SD-WAN features with the existing WAN feature. All right, so let's stop here. Now we reach to 1.5, and in 1.5 we have to learn and understand about software defined access, SD access. The common term is DNA. Here we have to understand that what is SD-Access and what does it mean by control and data plane. And some of the examples also I'll add. We can uh, correlate this, or we can differentiate in a manner that what is the existing campus and then how it will look like inside the DNA or SD-Access. All right, so we know DNA, and what DNA is going to add value in the market is that we have the full automation engine, we have the analytic engine. Actually, we have NDP, network data analytic engines. What is happening here is, and I have explained this earlier also, that now you have management plane, you have control plane, you have data plane, and you have policy plane. Now this management plane is nothing but your DNAC engine, DNA controller. From DNA controller, you can write the policies, you can do the orchestration. It is open for the API. We have full automation support. We have full analytic engines. We can do the programming. We have the virtualization support. We'll see that. What does it mean by network virtualization? And then obviously we have this cloud integration and support as well. In short, whatever required for SDN, everything is supported in this particular module, in this particular feature. So this is nothing but the SDN type of LAN or campus area network solution. Now, why we are getting such type of enhancement in the existing campus network to the DNA is because now we have the full support from the hardware, and then we have full support from the programming as well. Full support from the hardware means now we have the programmable ASICs. ASICs where we can write the program, they can understand the program. They have the analytics, means they can understand the analytics as well. They can understand the programming as well. We can do full automation in that. So here you can see that due to the evolution of ASIC, either it's a wired or wireless stacking, trustsic SDN, they can do programming. They are flexible. Recirculation will be less. We have integrated stacking, visibility, security. Means we have mature and very extensive hardware, and that can be easily integrated with the programming. So whatever programming that we want to do, or in future we want to add it, that will be fully supported with the hardware. Generally we are using Catalyst 9000 switches for DNA. I will see that later on in this session, and I will point you to the URL where you will get the list of all the supported devices. So not only the switch, but routers, WLCs are also there for DNA. Now let's try to understand that what is fabric, because this fabric is a common term. Either it's a ACI fabric, application centric infra in a data center, or SD-WAN fabric, or DNA fabric. So everywhere you used to get the term fabric. What is fabric? Fabric is nothing but the overlay. So that means we have underlay as well, and the answer is yes. We have underlay and then we have overlay. So whatever connectivity, whatever physical connectivity you have, that is nothing but your underlay, correct? And then if you abstract this physical connectivity as per your networking, as per your topology, that will be the overlay. And different abstraction can be different virtual network or tenant. So tenant 1, tenant 2, tenant 3, these tenants are nothing behind the scene. They are the overlay or instances of the physical infrastructure or the abstractions, correct? So the overlay that we are using at this point of time is not a new concept. We know that we used to use Lisp, OTV, DFA, ACI is new, but CAP, PAP tunnels, IPsec over DMVP, and MPLS, GRE, these are actually the old terms. So what Cisco has done nicely in DNA is that they have use the old mature technology only. So for example, Lisp and VXLAN, we are going to use inside DNA, and with that, we have the SD-Access, this DNA, a campus area network, that is software-defined access network. Again, we have some slides that just to differentiate inside the underlay and overlay. So with one particular fixed underlay, you may have multiple overlay. So you can create overlay for tenant 1, tenant 2, tenant 3, or customer 1, 2, 3, etc., etc. Correct? And that's the true power you have. So now you have fixed your physical devices and connections and interfaces and wiring, and then you can abstract that. Now, if you do this overlay, or if you are in the fabric, then what features you have? You can do the mobility, scalability, programming. Now you have all sort of flexibility with you. Correct? Again, one more example with the overlay, and this is actually specific to the DNA. In upcoming session, we'll go and learn about DNA terminology, and then you will find that you have terminology used, say for example, edge devices. So you have edge devices, then you will go and learn that you have the border devices as well. You have edge devices, border devices, and then edge devices and the border devices. Then again, we'll see in upcoming slides other terminologies as well that you can abstract inside the overlay. So you may have multiple overlay with the fixed underlay. So you have underlay and then you have overlay. For underlay also you have the control plane, overlay also you have the control plane. Just an example, underlay control plane may be VXLAN, overlay control plane may be Lisp. Okay, we're going to discuss about Lisp also in the upcoming session. Maybe after this, we have session for Lisp. Even if you go and check the syllabus, you'll find that section 2.3 is for VXLAN and Lisp. So after this section, when you go and start your section 2, that is for virtualization, there you will find the topics related to VXLAN and the Lisp as well. Now there is some best of both in the world. So L3 and L2 overlay examples, and VXLAN you can think as a, even VXLAN is used for L2 and L3 as well. But at this point of time, you can think that VXLAN can be used as a L2, and then Lisp can be used as a L3, although VXLAN can be used for both. Generally it is used as a L3 overlay, this VXLAN. All right, so what type of planes we have? We have control plane, we have data plane, and we have policy plane. And one by one we are going to learn actually in section 2.3. I think A and B, you can go and refer. We have VXLAN and Lisp. And then you have the policy plane. These are the key components of SD-Access or DNA. The differences: L2 plus L3 overlay versus L2 or L3 overlay, host mobility with Anycast gateway, VRF and NZT. We have topic related to VRF as well in section 2 in the virtualization, virtual tunnel endpoints, no topology limitation. Why, if you have any limitation, not in DNA? Because we are going to use the scalability method with respect to Lisp, locator separation protocol or locator ID separation protocol. We'll see that. We have complete things related to that. We are going to check that. So what are the terms we have in DNA? You have control plane, that is a Lisp map server. You will find this term MSMR, map server and map resolver. Then you have the edge node, they are Lisp tunnel router. So XTR, it may be inward and outward. We'll see that. So you have tunnel router as a edge node, and then you have proxy tunnel router PTR as a border node. I will go and refer this topology. And then we have the intermediate nodes as well. These terms we are going to use so many times in the DNA. The fabric domain is FT, that is the Lisp process. Virtual network, we have the VN or the VRF. We are going to check this, and these are the loose term. So VN is the loose term for Lisp instance, is the loose term for VRF. Endpoint ID group or EIG is a segment that can be used inside the TrustSec that we can check. Host pool is the dynamic endpoint ID or VLAN plus the IP subnet. So these are the terms actually are going to be used inside the DNA. All right, so I hope you understand that's overall DNA term. At least three planes are there. Three things are there: Lisp as a control plane, VXLAN as a data plane, and ICE actually is for policy plane. We have very important topic now is the Lisp. Lisp is the control mechanism or control protocol for DNA. This is nothing but the locator ID separation protocol. Means how you can differentiate or how you can separate the identity and location. We'll see that what is the mechanism and what are the technical definitions or technology behind the Lisp. Correct? So let's try to understand this fabric and this DNA piece step by step. Now here in the diagram, you can see that you have edge devices. These are actually the edge devices. You have three components. You have edge, then you have border, then you have control. One by one we'll go and discuss all. But these edge devices that you are seeing here, actually the endpoint identities are connected with them. Here you can see EID. So this edge device specification is that one portion is connected with EID, but one portion is inside the fabric, correct? Now inside the fabric where you are running the Lisp protocol as a control mechanism, now this Lisp protocol has a R locator, means router locator, and then inside that you have one database. So that means that whatever edge devices you have, they will map to the RLock, and that EID to RLock mapping will be stored inside the database. And that's the case we have. It is doing like this. Now we have the other components as well. So let's try to understand all the terminology, and then I'll come back and connect all those pieces. Now, if you use Lisp, what will happen? Say you are storing or you are preserving the identity. So suppose if you move the system from one place to other place, before Lisp, they have to change their identity. But if you are using Lisp, you can see they are preserving the identity. So that's why they are supporting the mobility feature. And this mobility feature is huge in the campus area network because all the time users are moving from one place to other place. Now, how is Lisp used in the campus fabric? Let's try to understand this. In campus fabric, you have the a controller router, you can say at this point of time. So you have one controller router, and then you have the edge devices that is connected with EID. You know that they will use R locator, and here you have the database who will store EID to R locator. Now what will happen? This EID has the database /34 for IPv4, /128 for IPv6 or MAC addresses. So at the moment you are part of Fabric or you want to become the member of Fabric, you will send all the prefixes to the controllers or to the control plane. Now this controller, what he will do, that he have his database. Next time, suppose this is A and this is B. Next time, suppose the B wants to communicate with A and he don't know how to reach to A, he will go and contact the controller. Hey controller, I want to reach to A. Now since controller know that this request is for A, why? Because he has the EID to R locator information, so he can tell, okay, this is the way that you can reach, and later on they can go and communicate directly. Okay, so it is working, you can think at this point of time as a proxy, but that's true. why it is working in this way and what's the benefit we have, I will show in the next slide. But this is the mechanism behind the scene, correct? And you can read out these points as well. Now here you can see that you have the edge node or edge device. Now the Lisp term is Lisp tunnel router. So these are the Lisp tunnel router because they are going to do the mapping for EID to R locator. And again, this term is also huge. So provide Anycast L3 gateway for connected endpoints. So whatever EID to R locator, obviously R locator will be fixed for the EID, but they are going to check who is the group to near, who is the nearby endpoint, and then according to that, he has to store the information. Again, in the big fabric, you have or you should have multiple control nodes. Now, those control nodes, which particular group of endpoint is near to that control node, so there this Anycast will come into the picture, correct? All right, so you have the EID. They have to register to the control plane or the controller, and then the controller will have the database for EID to the allocator. Then again, you have the border node as well, and they are termed as a Lisp proxy tunnel router. So you have Lisp tunnel router and then you have Lisp proxy tunnel router. Why? Because if you want to go to Lisp to non-Lisp domain, or who will be your entry or exit point, so these border nodes will work like that. So here you can see the nodes. Connects traditional L3 network, that means non-Lisp domain if you want to go, where two domain exchange endpoint reachability and policy information. They can have VRF and security tagging group or group tagging. We'll see that these things are possible when we are talking about Lisp. The two very important feature of Lisp is one is the mobility, other one is the virtualization, or they are supporting VRF. Okay, provides a domain exit point for all the uh, edge nodes. So that's the usefulness of the border. So now we have three terms. We have edge, we have border, and we have control. Border is the entry point, the exit point for all the edge devices. Plus, if you want to communicate from Lisp to non-Lisp domain, this border will be getting used. This control plane or the controller device is to have the database for EID to R locator information, correct? And these are the terms actually. Apart from that, there is one other term as well, that uh, transient devices. So in between, if we have non-Lisp devices, so that is also supported. So it is not mandatory that inside the fabric you are running Lisp to each and every devices. All right, so we reached or we understand up to this point. Let's understand few more slides. What benefit we have, and that's the main thing. So I'm going to use Lisp, then what benefit that Lisp will provide to me. Now here you can see the benefit. First of all, mobility and then the virtualization. Both features are there, means devices can move from one place to other place, but they still have their actual identity. Why? Because they're responsible to manage their identity. That's it. That's it. They're not there to manage the entire topology table or entire database, because for that you have other devices in a network. Apart from that, these Lisp, they are fully supporting virtualization. So for virtualization, there are some code for VRF and all, but they are fully supporting virtualization. Now, before moving further, let's try to understand about this location and identity term. You have location and identity. You have the identity of yourself. So that is nothing but the endpoint route. So you have endpoint route, and then you have this color red is topology route. Now you can see in a big network, the topology route will be very big. And why you want to have the topology route and unnecessarily you are utilizing your tables, your CPU and processing, etc. Rather than you offload this. You offload this topology route to some database. Whenever you want to need it, just contact to the database and that database will provide you that information. So rather than adding or rather than putting extra burden to all the devices, you can put that in a centralized location like this. So now you can see that the efficient utilization of the CPU, they are not overloaded because you are storing the topology table to the central location, and whenever they need, they will go contact there, they will get the answer and then they can communicate directly. That's the overall idea. So now you can see the scalability feature, the better utilization of resource feature, and they are supporting mobility and they are supporting virtualization as well. So routing scalability is there, mobility is there, and virtualization is there. With help of Lisp, we can achieve all these target. Finally, we have the Lisp mobility in the campus fabric. We have the host pool. Now, this is nothing but you are preserving the VLAN and the IP subnet. So now you are creating the VRF, for example. So VRF A, VRF B, VRF C. Later, we'll go and study about VN, virtual network, associated with VRF. So different network or instances you can create, and once you have those instances or network, they are associated with VLAN ID. Everything will happen dynamically here, and they will manage the network. So you have the resource, but you are doing sort of virtualization in terms of VLAN and subnet. You are preserving the VLAN and subnet, and then you are doing the communication. That term is host pool. So host pool is based on IP, subnet, and VLAN ID. Okay. Again, these are the features we have inside the Lisp, but the core fundamental is the same. That means that you have to register somewhere. Where you are registering, he has the information of all the topology inside the fabric. You have local responsibility. Now you can think like this: you have local responsibility, and someone has the global responsibility for all the devices who has their own individual responsibility. Whenever one responsibility wants to communicate with other responsibility or who has the responsibility, so at that time they will consult the global member and he will provide the path. Obviously this will not having the lag, this will be very faster. Okay. Finally, the Lisp is supporting the virtual networking or VRF, and you can by default that will be VRF 0, but we have option. We can go and configure VRF 1, 2, 3, 4, etc., etc. So different fabrics we can create, or you can think like different overlay you can create inside the fabric. This overlay is nothing but the virtual network. This virtual network is nothing but a tenant itself. So tenant, overlay, virtual network, all together they are the same term or the same thing. Alright, so final thing is that how Lisp is working. Already we have discussed that you have one centralized database. So whenever your edge device who has the uh, identifier or edge endpoint identifier, they will go and register to the control plane or the controller, or basically we are telling this as a control router. Sometimes it is referred as a MSMR, map server, map resolver. So bottom line is that once you are inside the fabric with help of RLock, so EID to RLock mapping is happening, and then you have the entire database is stored at this guy. You can think this as DNS as well. So you may have local DNS, you may have global DNS, like that you can think. And whenever you require, you are resolving like DNS. So these guys will resolve like DNS. They will send their query, and finally they will get the response, and then they will do the communication. So very much like how the DNS is working, the same way the Lisp is working. If you want to learn more about this, you can go and check these links. Plus, you can go and check, there are so many good documents in Cisco Live as well that you can go and refer. Previous session we have discussed about a Lisp, that is the control plane for DNA. The data plane for DNA is a VXLAN, and let's learn about VXLAN. So now here you can see the header formatted. That before going that, let's try to understand that what type of headers information we have inside VXLAN and Lisp. So normal IP packet will be looking like this. You have the payload, you have IP, you have Ethernet. But if you go and check Lisp, Lisp is actually the L3 overlay, but VXLAN is L2 plus L3, means it supports both L2 and L3. Lisp is referred as, you can see here, this is something IP in IP, and VXLAN you can think as a UDP in IP. So you have IP packet, even you have Ethernet packet, and then you have the UDP encapsulation, and then you have the outer header format as well. We have the document, we have the slide actually, that is referring some of the points. I'll come back there as well. So MAC in IP, but you can think VXLAN as a UDP in IP as well. And here you can see Lisp as IP in IP. Okay, so VXLAN as per Cisco, you can refer as MAC in IP, and Lisp you can refer as IP in IP. All right, so here you can see that you have the header format for VXLAN. You have your IP and payload up to this point. Then you have VXLAN encapsulation. Then you have you have the UDP encapsulation, and then you have IP and Ethernet. These are the outer header, and then these are the inner header. Now, knowing up to this point, let me go back to the actual header format, and we have those in detail as well. Let's try to understand this first, and then I'll go and cover the next header format as well. So now here you can see that you have the actual payload, then you have the IP header, you have MAC header, you have VXLAN header, you have UDP, where you have the destination port as 4789. Then you have outer IP header and the outer MAC. Now in outer IP header, it's important that you have the source IP as a source RLOC related to Lisp, and then the destination is destination RLOC related to Lisp. That is the fabric outbound and inbound IP addresses. The rest of the things are very much similar, that how the VXLAN used to work. In UDP, you will see that your source port is the hash of L2, L3, L4 headers. Your destination port is UDP 4789. Okay. Now, if you go and check the VXLAN header, you'll find that you have the segment ID that is going to integrate with ICE security group tagging. So you have 64K possible segments. Then you have this VNID, VNID, and this is actually 16 million. And actually 16 million is not supported, but yeah, it's very much and more than the VLAN ID. VLAN is actually, we know that we have only 4K VLAN, and that's the restriction we want to overcome inside VXLAN, that we have 16 million of possible VLAN if we are using L2 VXLAN, VRF if we are using L3 VXLAN. Okay. Although this diagram is very busy, you have to take your time and at least draw the VXLAN, UDP, and outer IP header. These three are important. Now VXLAN, once you understand VXLAN, these are the fixed thing. Then UDP header, it's easy. Source will be the hash value, so you can do the ECMP. Destination will be fixed 4789, and then the outer IP addresses are the Lisp-based inner and outer IP. That is the RLOC, correct? Now we have one more diagram here. Let's try to understand parallelly Lisp header and the VXLAN header. Lisp, we know that IP in IP, so that's why you have the inner header as a IP. Then you have the Lisp header. You have one field here, that is the instance ID. This instance ID is the criteria for the virtualization. So if you want to do a Lisp virtualization, you have to put instance ID apart from 0. 0 will be the default. By default, all the configuration has 0 as a Lisp ID, but for different VRF, you can put different instance ID. Then you have the UDP destination port and source that will be randomly generated. Then you have the outer header. Outer header, we know that what will be the outer header for the Lisp packet. So you have the destination routing locator, you have the source routing locator. UDP protocol number is 17, like that. So we have referred the diagram, and here you can see the same thing. You have inner header, then you have Lisp header, and then you have the outer header, correct? Like that. Better you refer this rather than this. All right. Now, when coming to VXLAN, here you can see that you have inner header. So you have the payload here, and you have the Ethernet as well. Then obviously you should have IP as well. So once you have the IP, then you have the VXLAN. Here you have the VNID or VNI. You have L2 and L3 VNID. You have some reserve bit as well. Then you have the UDP encapsulation here, where the destination port is 4789. Source will be the hash of different values. Then you have the source routing locator and destination routing locator. And then you have this is actually your outer header. So you have outer header, your UDP, your VXLAN, your Ethernet, your payload, and optional things. Okay. So this is the way that you can understand VXLAN, and actually we have covered the detailed comparison of VXLAN and the packet format. Now we have one more slide here, that is that how this data plane is working. Obviously it will do the decapsulation and encapsulation at the edge point or the edge node. So if you have two edge node inside the fabric, they will do the encapsulation and decapsulation. So if I can draw and explain here, I have one device here as edge, and then I have EID. I have other device as a edge, so suppose edge 2 and edge 1, and then I have EID. When the packet will come, it will resolve the Lisp. It will go and contact with the control device or MSMR, where it should know that how to reach to the destination. Then the dynamic VXLAN tunnel will form. In that dynamics VXLAN tunnel, the source and destination outer header will be the RLOC source and destination IP. Correct? So that's the thing written here. The underlay address, advertisement, and mapping. This is your underlay, and this is your overlay or fabric. Correct? So this thing will happen. Then automatic tunnel, so your VXLAN tunnel will form automatically. Then frame decapsulation between routing locators. Obviously encapsulation and decapsulation will happen. So once you are sending the frame with VXLAN, it will do the encapsulation, and once it will reach to the destination over the tunnel, he will do the decap. So encap and decap will happen. Lisp is IP in IP, VXLAN is MAC in IP, and then we have some of the Lisp control events as well. So this was the detailed explanation of VXLAN, and I hope you understand the format, the encapsulation, the packet format, and how it is working. So in next section, we'll go and learn that what type of products supported inside DNA. Although there are links where you can go and check the list of product, and there's a huge number of products that has been supported inside SD-Access or DNA. This is the last recording in section 1.5, and we are going to study about which type of devices supported inside DNA. Plus, I'm going to do the summary as well for section 1.5. We know that we have three variants. We have the edge node supported devices here you can see, and we can go and check the data sheet as well, which is the hardware and which is the software supported for DNA as edge node. Then we have the border node. Here you can see that 3K, 6K, ASR 1K, ISR 4K, Nexus 7K, they are supported as a border node. Again, these are the old iOS XE and iOS images. We can go and check the latest image, latest plus the stable image for SD-Access. And finally, we have the control plane devices as well. So we have the Catalyst 3K, 3850, 6K, 6800, and ASR 1K and ISR 4K. You can see here that in the border node and the control plane node, devices are common as well. So there are devices, they can work as a border and they can work as a control plane node as well, that will be there in the fabric. Now if you want to check the new and the latest number of devices and how many devices are supported, you can go and check this particular link. There you will get the Excel sheet, and in that you will get so many supported devices with different product ID, different devices and their hardware capabilities as well. If you want, you have to go and check the data sheet. All right, so let's summarize that what we have a study. We know that we have the management plane, we have the control plane, we have the data plane, we have policy plane, and we have a WLC as well. So in the DNA or SD-Access, what are the key components we have? We have the DNAC server who can do the automation, assurance, plus management, correct? Because he has a full visibility, because the telemetry is supported inside this, so that's why he has the full visibility. He can do management, automation, and the assurance. That policy plane is ICE, so we can create Pixie grid feature and the ICE. So from ICE they can send the input to the DNA center, all the contextual information, and DNA center can analyze those and then it can give the output. But the policy plane is ICE. Then we have the edge node here. You can see the edge devices where you have EID connected, endpoint identifiers, and then those will be registered inside the control plane nodes. Then we have the border node to do the communication with non-Lisp environment. We have the wireless controllers. The APs are not shown here in the diagram, but yeah, APs and wireless controller, they can use Fabric to build the tunnel to do the communication. So this is the overall picture of the DNA, where you have single unified fabric that will be controlled and managed from the DNA center or the DNAC. Okay, and finally, this is the overall thing that we want to achieve. So we want to do the we want to achieve actually virtual network, or we want to achieve the overlay. Beginning of this section we have discussed that yeah, you have fabric, you have underlay, fixed hardware, and then you can abstract that as a virtual network or the overlay or tenant. So here you can see that you have the fixed hardware connection, where you have the border node, edge node, intermediate nodes, etc. And then you have multiple instances as a virtual network A, virtual network B, virtual network C, up to N, etc. Okay, and that's the overall goal we have with the fabric, and this is the thing that we can achieve with SD-Access or DNA. 1.6 is again important section where we have to learn about quality of service, both related to wired and wireless. Apart from that, We are going to discuss about QoS components and the policy in detail as well. Now, why we need quality of service? We know that if we have congestion, if we have bandwidth issue, at that point of time you need QoS. Even if you have bandwidth issue and still you need QoS, means if you have sufficient bandwidth and still you need QoS, because how you're classifying the traffic and which traffic you're giving the priority, that's important. In the next slide, I can show you here. So here you can see that there are chances that you have uh, high sender, slow receiver, and vice versa. So at that point of time, you need a quality of service. Suppose you have 10 gig, 10 gig. So let me highlight here. Two interfaces with 10 gig, and then here you have uh, only one link with 10 gig. So suppose 10 plus 10 become 20. So with 20 Mbps or 20 gig, you are sending the traffic, but the receiver having a speed only of 10 gig or maybe 10 Mbps. So in that case, you have 2:1 of oversubscription, and this is the classical case of high sender and slow receiver. Obviously, in that case, although whatever speed or bandwidth you have, still you have to categorize the traffic, classify the traffic, and then you have to map with the certain hardware queues inside different type of Cisco platform. So why we need QoS? Because the primary role of QoS is to manage the packet loss. There are traffic, they are very much delay sensitive. So if much more delay and congestion there to deliver the packet, uh, they will lose their meaning, and it's actually very difficult for those packets to do the reassembly. So first thing is that manage the packet loss. The second thing is that obviously the end-to-end delivery should happen, and for that you have trust, classify, and the policing. In this section, we are going to learn uh, all these things with respect to all the hardware. Now, when I am talking about all the hardware, we'll see in the next slide that which type of hardware it is expected to learn about QoS. Before going there, we should know our tool. So we should know the hardware we are going to work on, what is the CLI command or the GUI command, or what is the software or syntax, what is the global setting to that hardware, what will be the default setting to that hardware, where you want to set the trust boundary, where you want to apply the QoS, either it's a physical or logical interfaces. You should understand this NBAR, network-based application recognition protocol. This is not very new thing, but Cisco has done so much innovation inside NBAR, and now this NBAR along with DPI, Deep Packet Inspection Engine, they are working inside SD-WAN images or SD-WAN devices as well. So for example, Cisco ISR, they have NBAR 2, so they can do deep packet inspection. Somehow they come to know about the metadata of the protocol, and according to that metadata protocol inline, so packet when it is coming to the ingress going to the egress, at that point of time you can go and apply app route policies and different type of policies as well. So NVAR is important. Who is going to do the uh, application discovery? Once you discover the application, then you can apply the policy for that, and they apply policy either ingress and egress as per requirement. Now let's quickly see that what type of hardware we have in this. We have hardware 2960, 3560, 3750. They are very much similar type of hardware, and by default QoS is disabled. You have to go and write a code MLS QoS. Then the QoS will get kicked, it will get a start. MLS is nothing but multi-layer switch QoS, MLS QoS. Okay, so here you can see this is one type of hardware. Now the second type of hardware you have is 3650, 3850, where you can go and use modular QoS CLI command. Modular QoS is very much iOS XE. Images are using, even the Cisco routers are also using MQoS format of QoS or syntax. QoS is enabled by default. You can go and allow this, means apply this QoS. Okay, we'll see later on that what are the syntax and what are the queues, etc., etc. Then you have 5006800 modular chassis switch. Again, you can see, so here you have MLS, here you have MQC, and then in these chassis you have C3PL, Cisco Common Classification Policy Language QoS. Now here you can see that QoS is enabled by default in SUP2T, Supervisor Engine 2T, and 6T, disabled on by default on SUP720. So even the common hardware is still different. Supervisor engines has different type of setting, and that's the thing, that when you're using QoS, you have to learn the QoS for all different type of hardwares. Okay, all ports are trusted at layer 2 and layer 3 by default. C3PL presents queuing policy similar to MQC. The good thing is this, that C3PL and MQC format will be similar. Only difference is there that you have to use the type of policy. Likewise, we have Nexus 7K 7700 Nexus, where QoS is enabled by default. All ports are trusted at layer 2 and layer 3 by default. NXOX queuing policy similar to MQC, but as defined type and with default class names. So again, here also you have to learn the QoS policy syntax. Different hardware, different type, different way to write the policy. Good thing is that MQC is very much common for all the platform except the access layer type of switch like 2960, 3560, and 3750. Now let's quickly discuss about the trust boundary, where you want to put the trust boundary. And when we are talking about QoS, remember that you have layer 2 QoS, that is class of service. You have layer 3 QoS, that may be type of service, and we'll see that how we are going to map costs with DSCP, layer 3 DSCP marking bit. Okay. So here in the diagram, you can see that you can set the trust boundary for Cisco phone, for telepresent system, IP camera, media player. Your trust boundary may be at the level of switch also, or you're not using any type of trust. So that's one thing, that you can go and use the trust boundaries for QoS configuration. Suppose if you want to map your COS to QoS, so here you can see that you have 8 COS and then you are mapping with 64 DSCP bit. Now in very easy term, how it is that actually you have 8 bit, and let me try to write, say 1, 2, 3, 4, 5, 6, 7, 8. Now last two you can reserve as ECN, explicit congestion notification. Then first these three, and again you have to count from here. So these three you can think as that can be used for DSCP, or actually there are complete list of AF, assured forwarding, and hence. Then you have the first 3 bit, actually those are used for COS, class of service. So that means you have 000, 001 up to 111. So that's why the number will be from 0 to 8, because these you can read as 2 to the power 1, 2 to the power 2, and 2 to the power 3. So 1, 2, 3, like that. So binary to the decimal conversion, etc. So that's why here you can see that you have COS bit like this, and then you are mapping with the DSCP, and inside DSCP you have 64 values. You can map like this. Now again you have to understand, and that will come with experience, that which is your high priority traffic, which is your low priority traffic, mid priority traffic, default traffic, etc. So when we are using COS 0, generally the COS 0 marking will be for default. If you have high priority traffic, So here you can see that you have high priority traffic where you are using COS 6 and 7. These are for control plane traffic. These are for network control traffic. So for example, OSPF is there, or STP is there, or any type of control message exchange. These queues, even these are reserved for that. Then you have EF, explicit forwarding. This EF or expedite forwarding, these EF are for voice type of traffic. Then you can have this is, say for example, high priority traffic, mid traffic, and default. Like that, you should categorize all these things. But never mind, we have the slides in the upcoming session that we are going to discuss about that. Here again, you can have the trust boundary, and boundary doesn't mean that you are going to apply the policy at that point of time. So you have trust boundary here to mark the packet for the VoIP or for IP phone. Now for this particular IP phone, the policy may apply it at switch level, it may apply to the router level. This PEP is nothing but policy enforcement points. So it doesn't mean that if your trust boundary is there, you are going to apply the QoS policy at the same point. You can change the policy enforcement. Now, when you are applying the QoS, here you can see that you can apply per port QoS, you can apply per VLAN QoS. When you apply per VLAN QoS, whatever interfaces inside that VLAN, that will come into the picture. Correct? So policy map is applied to the logical VLAN interface. You can go to the VLAN, you can apply service policy input marking, and then you have, because suppose if this is 2960 switch, so you have to go and use this command mlsqs VLAN west for all the interfaces, and then over the VLAN you are going to, or you are applying the policy. Now if it is per port QoS, so you can go to all the ports and then you can apply the QoS service policy input marking. Correct? So these are the starting point of QoS. In upcoming session, we are going to learn more and more about QoS. Before winding the session, I have given one extra slide here for N bar. N bar, they are using UADP chip. This is nothing but the ASIC. And due to this ASIC, we have that much capability to understand the metadata, or to understand 1400 plus applications. So with help of this unified access data plane chip, if we are capable to understand the application, and once we are able to understand the application, then we can create and put the policies. Correct? Everyone knows that Cisco is one of the best company who's making high quality hardware, and N-bar 2 embedded inside the hardware, providing very nice application recognition features. All right, so this is it for the introductory session. Let's stop here, and in next section we are continuing from here. Let us discuss about QoS design and implementation for these hardwares or for these platforms. So we are going to start with 2960 and we'll see the QoS design. Later on, we are going to discuss about remaining hardwares and platforms and design. Before starting anything, we should understand this chart, because all the time you are going to get too many things. Actually, you are going to get different type of code words. Say for example, COS, DSCP, TOS, AF, IPP, IP precedence, CS, class selector, drop probability, and ECN, explicit congestion notification. Now I already told you that you have to focus on 8-bit. So 1, 2, 3, 4, 5, 6, 7, 8. Last two you can exclude because they are used for ECN, explicit congestion notification, but these 6 you can consider. So now if you see this particular table here in your right hand side, from here you can easily figure out that what is the cost value and how we are going to map with the cost to DSCP. Again, this particular diagram and slide actually is important. First of all, we have the category of application from high priority to low priority. So here you have high priority and then you have low priority traffic, correct? So you have routing and control. So for example, control information, or you have control packet. For that you are giving class selector 7 and class selector 6. Now the first column that you are seeing is COS, class of service or IP precedence. Starting from 0 going to 7, that means we have 8 option. So here the option number 8, that is 7, and option number 7, that is 6. The 7 and option 8 is for the control traffic. You can think for this point of time that is reserved. That is reserved for the system. Correct? Then you have high priority real-time traffic. Oops, let me clean this. So we have the high priority real-time traffic, and for that high priority real-time traffic, we should go and classify and do the marking. So let me go back. So again, you can see in this particular chart that you have class selector 5 EF, that is for voice. Likewise, class selector 4 and then AF, assured forwarding 41, 42, 43. So 41, 42, 43 means these are the high priority. So actually this chart is from high priority to low priority traffic. Likewise, you have the streaming video, mission critical, call signaling, class selector 3 starting from 31 to 33. Likewise, you can read this. Now, if you want to convert this in terms of bit, so here you have to go and check the bit. What you can do here, that here you can see that you have the DSCP. So obviously the first one is the default, so everything is 0. But the second one, that is the scavenger traffic, CS1 class selector 1. Again, you can see that one is for class selector 1, AF11, AF12, AF13. 8, 10, 12, 14. How you are getting this number? So you are getting this number starting from bit 3. So 1, 2, 3, 4. That means this is 2. It will start like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And since these bits are 0, 0, 0, so that's the reason you have 2 to the power 3 means 2 into 2 into 2, 4 into 2, that means 8. So that's why this is 8. Now how it is 10? 1 0 1 0, we know this binary will be 10, and then again 8 plus 4 will be 12. Likewise, suppose if you want to go and calculate this EF, how is this EF is 46. So that calculation here you can see that you have starting from here 1 0 1 1 1 0. So that means you have leave this. So you have 2 4 8 16 32. You are not taking this 16, so if you add this, 32 plus 8 is 40, 40 plus 4, 44 plus 2, 46. Like that you can check this, correct? This is the maths. You can pause the recording here and you complete this mathematics. Otherwise, whenever you want to write the code, you can go and take the snapshot of this particular slide and you can refer it all the time, correct? Or you can make your own slide like this as well. All right. What is the best practice? The best practice for QoS is that if you have QoS in hardware and software, you prefer QoS in hardware. First thing. Second thing, classify and mark application as close to their source. So do the classification and marking nearby the source, because it is easy to classify and mark nearby the source. You polish unwanted traffic, and if it is unwanted traffic, put into the default queue. Then enable queuing policy at every node with the potential for congestion. If you see that congestion is there you can go and enable the queuing. Correct? So very straightforward. Suppose if you are seeing congestion on all these three switches, you can go and enable that QoS there. Now this slide you can see that you have trusted port. So all these yellow color are trusted. Then you have conditional trusted endpoints. So you have IP camera or IP phone, etc. Those are the conditional trusted endpoint. And then you have printer you don't want to trust. Okay, so you can classify, you can mark in terms of trusted or untrusted. Here also, you can see that you can have yellow ones as trusted, then black one is not trusted, then green is conditional, and then this red one is the classification and marking. So what is the summary for these things is that you should know that where you have to trust, where you have to do classification and marking, where you have to apply the QoS policy, either ingress or the egress. Correct? Now suppose if you're dealing with the hardware type of QoS, and that QoS type with that particular switch model is 1P, 1P stands for priority, 3Q and 1 threshold. So in that case, you have one priority queue and you have 3 queue. So priority queue, obviously you are going to put the voice traffic or real-time traffic, and then you have 3 queue. In these 3 queue, you can go and classify your traffic. We'll see that in upcoming 3-4 slides. You'll see that how it can be utilized. So again, here you can see it's just next after this. We have, so for example, one priority queue, 3Q and 3T. Now this example is for one threshold, but here we have the three threshold values, and that's why you can see T1, T2, T3. So all the queues you have 3 threshold. Anyways, whatever number of thresholds you have with the queue, that is not a big thing. How you can apply this? Here you can see that you have the classification of traffic. So that's fixed thing you have, classification of traffic for a scavenger, for bulk, for network management, for transactional data. Remember, this thing again mapped with QoS, how it is. So here you can see that scavenger, bulk data, you have CS1, AF11, 12, 13. Low priority to the high priority, and a related DSCP marking or DSCP table is 8, 10, 12, and 14. Okay, so while you are doing this, you should know the calculation. So for example, this is say low priority to high priority in this diagram, and in the last diagram that is up, actually this is low priority up to high priority down, and here it is a high priority up to low priority down. Okay, all right. So now here you can see that you have different classes. Obviously you have one priority queue. So let me show you that which particular category is falling inside priority queue. EF, CS5, CS4. Now here you can see that where is your EF is VoIP, CS5 is broadcast traffic, and then CS4, here you can see CS4 is real-time traffic. So these traffic are falling inside this. Then you have 3 queue. So you have queue number 2. I can see queue number 2 here. You have queue number 4. And suppose you are using one queue as a default queue. Okay. So this is your queue number 3. So I have Q2, Q3, and Q4. Now Q2, I'm using CS2 up to CS7. Now again, it depends that inside Q2 you are putting threshold 3 as CS7, CS6, and then CS3 as a threshold 2, and rest of the AF assured forwarding 2, 3, 4 inside Q2 T1. Then Q3 you are using 35% as a default, and then finally you have Q4 you are using as AF4 and CS1. Now AF1 sorry, AF1 and CS1. You can go and check. This is used for scavenger. So I am giving 5% of traffic to Q4 for default traffic or for scavenger. AF1, here you can see the bulk data. So bulk data and scavenger, we are using 5% only. Means after that it will do the tail drop. But what is there in default queue? So here you can see that inside default queue, we have the default traffic. Default traffic I am using for default queue. So Q3 and Q4 actually is used for default and scavenger and bulk data. For that, I reserve 40% of traffic. Remaining 60% of traffic we are using for Q2 and priority queue. Okay. So this is the thing that you have to design the QoS before doing the actual implementation. Now, when you are doing the implementation, we know that this is MLS, multi-layer switch queuing methodology. So you have to go and enable the queue. You have to go and enable the trust model, conditional trust, service policy model, and then you have to apply it. Correct? So we have policy map, marking, mapping table, and weighted tail drop. How it look like? The first step for 2960 series switches are that enable QoS with command MLS QoS. Then the good thing that you can go and use COS DSCP, or directly you can use COS as well. We know COS, we know DSCP, both have mapping as well. So here you can see that COS mapping. If you have any doubt to understand this mapping, what you will do, you can go and check the reference slide. So where we have the reference slide, the first one here. So here you can see the COS to DSCP mapping, the column 1 and column 3, and actually technically column 2 and column 4. So 0, 8, 12, 0, 8, 10, 12, 14, 16, 18, 20, 22, etc. If I go here and see, I can clearly see that 0, 8, 16, 24, 32, 46, 48, and 56. That's the marking. If you are using the DSCP model, we can simply go and use MLS QoS trust DSCP. You can go and trust different type of Cisco devices like Cisco phone, CTS, IP camera, a media player. So this is the way that you can go and do the enable the QoS and do the DSCP marking. Again, here you can see that you can go and enable the DSCP marking. Now the next phase is that how you will go and enable the policy. You have to create the class map and policy map. Class map will be called inside policy map. So here you can see that I have class map called VoIP, media, signaling, transactional, bulk, and scavenger. Once I have all this class map, then I am calling this class map inside policy map one by one. So policy map VoIP set, again you can see we are setting the DSCP bit. So we are setting the DSCP EF for VoIP. We are setting for multimedia AF41, and again class signaling CS3, transactional data AF2. And when you are doing this thing, mapping, then this diagram will come into the picture. So according to your classification, your marking, you have to go and apply the policy. So obviously you have the classification of traffic, and then you are doing the DSCP marking while you are putting the policy. Now once I have complete policy, then I can go to the interface and then I can apply it like service policy, input marking policy, and that's it. Okay. Now it seems little bit complex if you are new to QoS, but if you go a step by step that whatever we are following here, then you will find it that it's logical, and after few practice, or if you do little bit of practice, you'll find that QoS is a interesting topic to learn and do the mastery for. In this section, we are going to discuss about 3650, 3850, and 9300 platform. Here you can see that we have the trust model, means which particular interface is connected with what type of device you want to trust and you don't want to trust, or you have any conditional trust. Now in case of 3850 or 3650, we have these steps to follow. So when we are doing the ingress QoS model, we have trust DSCP/CoS model, conditional trust service policy model, and finally for the egress queuing, that is the hardware queue, we have 2P, 2 priority, 6 queue, and 3 threshold. So let's understand that ingress trust model. We can go and go to the interface, and then we have the CLI command, trust device, Cisco phone, CTS, IP camera, etc. Or we can use conditional trust. Example here, you can see that you can go and create the class map, say voice, whose cost value is 5, signaling, cost value is 3, and then you can go inside the policy map called Cisco IP phone, where you can call the class whose cost is 5, and then you mark the DSCP bit as EF. Likewise, you can call the class signaling, and then you can mark the DSCP as CS3. Obviously, then you have class default, set DSCP as a default. Then you can go to the interface and you can apply this policy. So we have option that which particular methodology we want to use for the classification, or at least for the trust model. Now, in the upcoming slides, I'm going to show you that how you're going to create the policy and apply over the hardware queue or over the queue model that we have is 2P, 6Q, 3 threshold or 3T. We know that we have the N bar supported in these hardwares, and N bars can have 1400 plus application recognition. When we are supporting N bar, at that time how we can create the class. So I can go and use, say for example, class map voice, and then I can match the protocol. That's the keyword, match the protocol, Cisco phone, Cisco Jabber, link audio, Citrix, etc, etc. If you go there, type match protocol and question mark, you will get a long list of application that is supported to that particular platform that you can match it. Apart from that, we can go and create other classes as well. This protocol is related to NBAR. So again, you can see that you have the broadcast video, match protocol, Cisco IP phone. You have the real-time interactive, the protocol is telepresence. Call signaling, the protocol is skinny. Telepresence control, the protocol is Citrix, SA, etc, etc. Okay, so we can do the classification of the traffic with respect to N bar, and then the next phase is to call those class map inside the policy map. So I can go to policy map, and then I can call the class voice. Now voice will call all these 4 protocols, and I'm setting the DSCP as EF. Likewise, we can create all this policy, and then we can apply over the interface. Correct. Now N bar, which is supporting 1400 plus application, and it is supporting 12 class model, and this is one of the reference we have. So here you can see that we have class voice, broadcast video, interactive, multimedia conferencing, multimedia streaming, signaling control, management, transactional data, bulk data scavenger. So 1 2 3 4 5 6 7 8 9 10 11, and let me show you the last one as well. So while you apply inside this policy, you can see that you have class voice, video, and all up to 11, and last is the class default. Okay, so you can have protocol matching with all of these classes, and then you can go and do the DSCP marking. Correct. So this is the way that we can efficiently use this N bar feature inside 3K platforms. Again, marking and policing, how we can do. So here you can see that the configuration related to marking and policing. So for example, I have class VLAN VoIP set EF, set DSCP as a EF, then police 1 to 8K, confirm action transmit, exceed action drop. So what is it? What does it mean? Again, the concept of policing you'll find at each and every point. So what you can do here, that you have, say for example, B sub C, confirm burst, and then you have B sub E, that is excessive burst. So what you want to do at this point of time, if you have confirm action, you are doing the transmit. So you transmit it, and then you have certain buffer. Exceed action, again exceed action, you have option that you want to transmit or drop, but in this case, say for example, I'm dropping. So B sub C, transmit, and excessive burst we can drop because we are using the policing. Likewise, you have all the policies, correct? So here you can see all these policy in the list for all the class of the traffic. Then for transactional data, you can see confirm action, exceed action, set DSCP transmit. DSCP table is table map. Then class bulk data and set DSCP transmit DSCP table as a table map. Then you have the table map, that is map of DSCP table. And here we can see that you are mapping 0 to 8, 10 to 8, 18 to 8, etc. Now, if you see this diagram in this slide, you'll find that how it is called. So here we have the table map for 18 to 8. Then you have table map for 10 to 8. And then finally you have the table map from 0 to 8. Okay, and obviously you have the class default, you have class scavenger, you have bulk data. For those, you are using the table map as well. So this is the way that we can use the policing as well. Let me quickly go and show you the full policy configuration. In case of per port per WLAN policy, we have WLAN. So for example, match WLAN 110. Class map is DWLAN, that is 10. Again, you can go and call these class map inside the policy. Now what we can do, that rather using all the features that we have, we should standardize the configuration. Like we should create the class map like this, and then policy map like this, and then we should apply it. Okay, obviously if you want to do the policing, you can do the policing as well, and that's very much required as well. So let me quickly show you that how this queue look like and what will be the final configuration. Here you can see that because this is two priority, so you have priority queue 1 and priority queue 2. Then you have 1, 2, 3, 4, 5, 6. 6 queue with 3 threshold. And how we can map the traffic, this slide can be your reference slide, that how you are mapping your 2 priority and 6 queue. So for example, I have priority queue 1 and priority queue 2. Here you can see, let me try to highlight here. So here you can see that you have EF and the priority queue level 1 EF for VoIP, and then you have CS5 and CS4 for broadcast video, and then for real-time interactive. So you are using your priority queues 10% and 20% here. Then you should use your AF4. So AF4 is used for multimedia conferencing, where we are using the bandwidth remaining 10%, and then the weighted tail drop is in conjunction with both. Then we have AF3 for multimedia streaming, where bandwidth remaining percent, DSCP based weighted tail drop. You are using the tail drop, means whatever left over, it will start dropping. Then finally you have the transactional data. Then you have AF1, means you have bulk and scavenger. So like that, you can use all your queues in this manner. And if you draw the configuration, how it will be looking like. So here you can see that you have voice priority Q1 matching DSCP EF. So when you are creating the class map, you are matching the DSCP value. So you have class 1, 2, 3, 4, 5, 6, 7. 7 class plus 1 is default, so you have total 8 class. Now how you are utilizing those classes? So for example, policy map, the name of policy map is this, for example. Then class priority Q1, priority level 1, percentage of bandwidth 10. Then Q2, priority level 2, percentage of bandwidth is 20. This is very much like this, correct? So once you do that, then you have the other class, that is control management queue. If you go and check you have control management queue where you're mapping this high level class selectors. What you are doing for that, you're giving bandwidth percent remaining 10, and you are giving the buffer as well 10%. Now you are moving to the standardization. If you go at this point of time and if you check the SD-WAN quality of service configuration, you'll find they have structured in this manner, means even better than this, because same place you are getting all those things, and even you can do the configuration with GUI as well. Then you have the conferencing queue 10%, buffer, queue limit DSCP, remaining percent, 80%, 90%, etc. So the configuration, although here it is using the strict priority, the remaining bandwidth percent, the tail dropping, etc. So whatever you are seeing here, all the configurations you can drill down and you can check the same way we have the configuration here. So finally, for bulk data, we have bandwidth remaining percent 5, the queue buffer ratio is 10, queue limit DSCP is 80%, AF 11% is 90, means for the scavenger traffic. So when you have the scavenger traffic, you are using the DSCP based weighted tail drop, correct? So that's why you have the DSCP based weighted tail drop 80 and 90. So after that particular limit or point of time, they will start doing the tail dropping. And finally, you have this class default where you have the bandwidth percent remaining is 25%. So here you can see this bandwidth remaining percent is 25%. So this is the way you can design the policy. So first of all, do the classification, then design the policy and you can apply it. Correct? So do the classification, create the policy, and before applying, suppose if you want to use the shaping as well, so you can do a nesting of policy as well. I can go and create one parent policy for 50 Mbps traffic, and I can map inside class default, shape average. I can give this particular subline CIR for shaping, and then I can call my child policy inside the parent policy, and then the parent policy I can apply over the interface. Okay, so this is the standard way of doing the MQC, modular QoS CLI configuration, or even most of the iOS XE platform. We are creating the policies and applying the policy like this only. All right, so let's stop here. Now we are going to discuss rest of the platform. We have 4500, 6500 and 7K and 7700 platform. Whatever knowledge that we have gained so far, those knowledge we are going to use in these platform. So we need not worry to relearn all those things. Now directly here you can see that in case of 4500 platform, we have, so for example, one priority, 7 queue and one threshold. So overall we have 8 queue, out of that one is priority queue. And if you have 12 class model, here you have 12 classes. You can see that how these classes are mapped. So priority queue is mapped with EF, CS5 and CS4. And then here you can go and check what is CS5, what is CS4, what is EF. Likewise, then you have queue number 1, 2, 3, 4, 5, 6 and 7. So here you can see that Q1 is starting with default queue 25%, Q2 is bandwidth remaining 1%, Q3 bandwidth remaining 4%, Q4 remaining 10%, 5 10%. Like that we have all the queue to class mapping. Correct? So this is about the 4500 QoS design. Now inside 6500 and 6800 QoS design, you can see that again you have 12 class model and you have say 2 priority 6 queue, means you have 2 plus 6 queue plus you have 4 threshold. Here again you can see that Q1 up to Q6 and then 2 priority queue. So first of all you can figure out that how you are mapping priority queue level 1 and priority queue level 2. 1 and 2 we are using EF, CS4 and CS5. Then rest of the queues here have been used. Now for example AF4, which is using multimedia conferencing, it is used for multimedia conferencing queue where 20% is bandwidth remaining, and then we have a DSCP based weighted random early detection. So if you want to do congestion avoidance, you can use either tail drop or you can use a random early detection method, that you start discarding the packet before you reach to certain threshold value. In AF3 also we have 20% bandwidth remaining plus weighted random early detection. In AF2 also like same, but in case of bulk data you can use 5% of bandwidth remaining percent, because you don't want to give more bandwidth for bulk data, or maybe in case of a scavenger as well. Okay, so this is the model. This is actually the standard format, but if you want to change anything you can change as well. Okay, then finally we have the Nexus platform, and inside Nexus platform you can see that you have 4Q1T. Now this dual class model, again you have the costs. So for example you have 8E4 4Q 8Q in 1Q1 like that. Actually if you go and log into the Nexus platform, you'll find that you have so many inbuilt QoS, and it is recommended that do not change it until unless it is required. So how the mapping is, here you can see that you have Q1, you have Q2, you have Q3 and Q4. Q2 is used as a Q default, correct? So Q1 it is matching cost 567. Q0 obviously it is for default. Q3 is mapping cost 234. So if I start with cost 1, so cost 1 for Q4, and again you can check the subsequent mapping. So cost 1 is mapped with bulk data and scavenger. Best effort is mapped with cost 0, that is your default queue. Then here you can see that you have Q3 mapping with cost 2, 3 and 4. 2 is transactional data network management. 3 is, so here you can see the 3 is multimedia and signaling, and likewise all these queue have been mapped. So once we know this mapping and this queue methodology, obviously we can then go and write the syntax, write the software commands. That is again it's easy. Again here you can see that you have 4Q1T, 1T, how it is mapped here. Apart from this mapping, we are giving the bandwidth percent and the queue limit as well, bandwidth percent and queue limit as well, because we have one threshold as well. In 7700, where you have 8 queue and one threshold, it's very much that we have 6K design where you have 2 priority and 6 queue. But anyways, you have 8 queue, and how you're mapping the 8 queue. So first of all, you can go and check your priority traffic. Priority traffic is cost 5, 6 and 7 used for priority, and here you can see the cost values. Then you can see the queue 2, 3, 4, 5, 6, 7, and then you have one default. All these 12 classes model, how they are mapped with Nexus 7700 F series line card. So this is the way that all these wired QoS can be used and mapped, and we have discussed a lot in detail each and every component and things inside the QoS. Now next section onward, we have to study QoS for wireless network or wireless infra as well. Last topic in section 1.6, we have WLAN QoS. Now WLAN QoS may become the weakest link in the chain, because there are some, you can see that actually there are 3 primary reasons for that. Means there are some issues, or there means these WLANs are not that efficient that we have the wired LAN. So that's one of the reason. So here you can see the primary reason are typical downshift in speed and throughput. Here you don't have any dedicated pipe. You have some sort of shared media. Here you can see in the diagram, and all the mobile devices are devices who are using WLC, SSID, etc., they are using the shared network. One thing. The other thing here you can say that shift from full duplex to half duplex. So these are the issues, these are the constraints we have that may be causing the weakest link in the chain. The other important thing here to understand is that wireless LAN supporting 4 level of services. So if you have wired LAN, you have to map your, say for example, 8 class of wired LAN to 4 class of wireless LAN. So that is also one of the limitation you have. Now, because the wireless media, they are going to use a CSMA CA, that is collision avoidance mechanism. So there are chances, we'll see that in upcoming slides, that you have to wait for some period of time or a small duration of time, but that is a small fraction of time also can cause trouble. So for example, voice, if we have 15 millisecond jitter versus 5 millisecond of jitter, the improvement is 300%. So for example, transactional data, 14 millisecond latency versus 2 millisecond of latency can have 700% performance issue or enhancement in performance. Both ways we can think. So these are the things that is considered for wireless media, and for that obviously we want to apply QS as well. What are the tools we have? We have the user priorities, and later we'll see that how we have to map DSCP to the user priority. We have access category, we have arbitration, inter frame spacing, we have contention windows. We'll see that AIFS and CW in next slide. What does it mean? But they are associated with some sort of collision avoidance mechanism. Then finally, you have enhanced distributed coordination function. We have to map the DSCP with a user profile. You can define the trust boundaries. We have discussed about policy enforcement points earlier. So you have PEPs, and obviously the WLCs, they are supporting AVC as well, application visibility and control. Now here you will understand about AIFS and contention video. Since we are using CSMA/CA, that is the collision avoidance technique, uh, if you compare with the LAN technique, that is CSMA/CD, collision detection. So if collision will happen, then the algorithm will start recalculating the refresh interval, and then next time they will avoid. But here, this is by default, they will wait until they will find that the link is okay or the transmission is okay, means I can do the transmission if it's ready to send, right? So it's something like collision avoidance, and that's the reason that the sender have to wait for fixed amount of time, and that is nothing but AIFS. Correct. The other waiting time you have is the random amount of time, that is the contention window. So not only that you are waiting for fixed amount of time, but you have the contention window as well. And then finally, this AIFS and contention window timers vary by access category. So here you can see that you have access category as defined by voice, video, best effort, and background. Now this access category, you know that you have high priority to the low priority data, correct? And according to that, your access category in conjunction with AIFS, in conjunction with contention window minimum and max, everything will work together. So for example, here you can see in the diagram below, the background having the longest contention window plus the longest AIFS, rather than the voice has less contention window plus the AIFS, etc. So voice and video AIFS is same, but contention video for voice and videos are different. Let me quickly show that how these models are going to map. So you have 802.11 access category. You have access category for voice, video, best effort, and background. Likewise, wireless media mapping, you can see that you have voice video best effort background. If you are using Cisco AirOS WLC, you have this category like platinum, gold, silver, and bronze. Let me show you much more information related to that. So we know and we have a study about this model. This is our RFC 4594 based DSCP based model. Now, how you are going to map all these classes or traffic classes with the IEEE 802.11 model? You can have a reference for this particular slide. So in future, if you are designing the wireless QoS, you can map in the same way that you are seeing here. So for example, CS1 is mapped with UP1, AF1 is mapped with UP2, UP user priority 0 is mapped with best effort. So like that, you can go and check each and everything. Then we have the high priority data as well. So for example, multimedia conferencing or voice plus DSCP admin. So here you can see that voice plus DSCP admit is user priority 6, and this multimedia is user priority 4. So like that, the mapping should be happen. Now the next question here is that how the 3-bit user priority can map with the 6-bit DSCP. So in that case, when you have user priority to DSCP default mapping, here in the diagram you can see that you will map 3-bit and rest 3-bit will be zeroed. So they will mark as a 0. So in that way, the frame will processed, and obviously your actual header or actual DSCP marking will be kept inside the IP packet. So whenever you are marking your user priorities, that is going inside the cap map tunnel from your access point to the WLC. So here you can see the marking will be like this, and they will mark only last 3-bit. So user priority has 3-bit, that will be marked with the 3 last bit of the DSCP. Okay, and in this way the flow of frame will happen. Now, if you want to learn more about the QoS related to WLAN, you can go and check this RFC 4594, and also you have the Cisco validated design as well. So you can go and refer the design document from Cisco as well. Finally, we reached to section 1.7. This will be the last subsection actually of section 1. And what are the topics we have in 1.7? We have to understand about hardware and the software switching mechanism, how CEF, Cisco Express Forwarding working, what does it mean by TCAM, MAC addresses, and FIB versus RIB. So all these things we'll study step by step, and before coming to 1.7 A, B, and C, I just wanted to explain you about hardware architecture of 9300. Although we have a study in our QoS section that in Cisco, we have long list of switching platform. Obviously in routing platform is also there, but we have long list of products. Now, because this core exam and upcoming exams, Cisco keeping track, or they are thinking that in future people will go and in enterprise network they will use DNA, they will use SD-WAN. So when we are coming to DNA specifically, in DNA we should use DNA ready hardware, and that's the reason in the hardware section I just wanted to focus on 9300 hardware. Now this 9300 catalyst switch is security integrated, means you can enable MACsec and other security related things. Whatever there in the switch generation related to security, you'll find inside 9300. It's a mobility ready, it's a IoT ready, because we know that IoT is a big topic nowadays, and it's a even bigger topic in Cisco DNA, and it's ready for the cloud as well. So here you can see that you can connect with SDA, you have web UI, you have patchability, etc. So let's understand this 9300 and at least 3 to 4 very important features related to 9300. Now here you can see the family. So we have 1G data, uh, 9300 specifically. Even you can go and refer the data sheet as well. So you have 24 plus 48 port, then you have 1G unified PoE/PoE plus 24 port 48 ports, and then you have M gig UPoE switches. So first of all, at least one thing we can understand here, that they are PoE ready, and not only they are PoE ready. So here you can see that line rate on all port. They will give you line rate throughput on all the ports. All the ports are PoE ready. So you can connect in any port you can connect the uh, IP phones or Cisco phones, so it will get the power. Then you have 24 multi-gigabit Ethernet ports. Here you can see you have 10 gig, 5 gig, 2.5, 1 gig ports available. So you can see that port availability, PoE, line rate, everything is enhanced here. Now, which type of SFP models they are supporting? Here you can see that you have uh, online insertion and removal SFP supported, like 4 into 1 SFP or SFP/SFP plus. You have QSFP as well, that is 2 into 40. Then finally you have the copper support as well. So 4 by 1, 2.5, 5 and 10 gig. Correct. So all sort of SFP, SFP plus and copper interfaces are supported. Now here you can see that we have the power capability, means what type of power modules you have. You have 350 watt AC up to 1100 watt AC. It's very much similar to Cisco 3850 switches. And then we can do the stacking as well. So a stacking capability is also there. When you are doing the stacking of the switches, then you can stack up to 8 members in a switch, and in that case obviously when we are doing the stacking, they have active and a standby feature. So someone is active and who is taking control for all the switches. So from there you can go and log into all the switches, and from active you have to configure the active, and rest of the members are supporting the active configuration. So that means we have the centralized control plane, we have distributed data plane, and that's the power of stacking. We have one-to-one stateful redundancy, and again, we have discussed this earlier, that we have a stateful switchover SSO, plus we have NSF, non-stop forwarding as well. So you have a stateful switchover, you have NSF. Let us continue our discussion about the innovation inside Catalyst 9300. Here you can see that it is built in RFID. Uh, apart from that, apart from uh, regular Catalyst switch like 3850 or any other platform, what extra you have? We are going to check and discuss about what extra capability we have inside 9300. At this point of time in the overview section, you can see that you have RFID, and I want to highlight this extra capability that we have in terms of ASIC. So here you can see, let me try to do a spotlight. We have flexible ASIC UADP 2.0, and that's the extra thing we have inside this 9300. Due to the ASIC is it's quite extensive, high performance, programmable, and it's actually amazing innovation from Cisco, that this unified access data plane ASIC, we have 3-4 slides for that we are going to discuss more about this. So here you can see that you have extensible ASIC, you have RFID capability, and then you have the line rate capability. So let's move on and see that what other features you have in terms of hardware. Obviously, we have discussed about the stack. So we can have a stack of 8, and we have NSF and SSO supported. That's okay. Now let's try to dig deeper inside the switch, and let's try to understand the core difference, that where 9300 is standing and moving onwards if we are comparing with the other catalyst switching platform. So you have this UADP. Rest all the things you will find same, like redundant power supply, power stack connection, fan FRU, back stack connection, USB. Rest everything is okay, but you have this UADP. That's the ASIC. Now let's discuss about this ASIC. Before moving to that ASIC, you can see that you have x86 CPU who can support different type of programming options. So they can host Puppet, Ceph, Wireshark, Ansible, iPerf, Kibana, Perf, Sonar, etc. So they have this debugging options, and they can integrate with any third-party vendor for API integration or programming. Yeah, so we are waiting for this ASIC study, and now you can see that we don't have the traditional ASIC where things are monolithic. Although this new ASIC, this UADP, they can understand different type of encapsulation as well. Say in traditional ASIC, if you put load on the frame, means if you are doing some encapsulation, you have VXLAN encapsulation overhead, GRE encapsulation overhead, etc. Those are not supported because they are doing a normal lookup related to MAC, IPv4, ACL, QS, etc. But in the new UADP, you'll find that it is supporting most of the things. So here you can see that you have the architect, you have the RTL design, synthesis, floor planning, fabrication, etc. Everything is there inside this new chip, and this chip is looking like this. So you have UADP, Unified Access Data Plane, which will provide you high performance, flexibility, and programming. So we have PFP, performance, flexibility, programmability, and that's the reason that it is used inside Cisco DNA. It has investment protection, universal deployment, enhances scaling, and it can have 7.46 billion transistors. It is using 28 nm technology. This is actually very much related to the hardware features, correct? But yeah, the summary is this, that because we have very high capable data plane related ASICs, that's why the capability is very much good, and you can think this 9300 as a next generation catalyst switch. Apart from that, we have some key features that they have flex parser, programming pipelines, recirculation capability, micro engines, adaptable tables. Okay, and no compromise on performance. Although they are giving you lot of features and capability, but there is no compromise on performance. Finally, let's quickly see this architecture. So for example, we are seeing 930024 port layout. How it look like if we are new to this hardware type of a structure. So how we can understand and read this, obviously you have IO module, input output module, means you have to give something in the input, correct? So maybe the end machine or PC, anything is connected. So let me try to mark here. So you have your PC and it is connected, or maybe you have some other switch and it is connected. So where it will be connected, obviously to the port. This is 24 ports, so 12 plus 12 port, it is divided like this. Then you have octal physical connections. So that means the ports are mapped to the octal physical. Obviously you have the network interface, then you have the forwarding controller, packet buffer. Now all these things, suppose if you have a stack of switches, then you have 480G stack interface, but all these things are mapped with the ASIC, and then you have your quad core CPU, you have your flash memory, USB management console, etc., etc. So you can study or if you want to understand this design, go from bottom to top, and then you can understand more about this. Now quickly let me show you this multi-gig Ethernet or multi-gigabit 9300, and here you can see this capability is even much more enhanced. So now you have 12 port unified PoE, and you have multi-gig quad physical. Multi-gig quad physical. You have core 0 and core 1 inside ASIC. You have core 0 and core 1 inside ASIC 0 and inside ASIC 1. Obviously, these are mapping with the unified access data plane. Here you can see this overall clock cycle. Then you can see this quad core CPU 1.8 gigahertz, and then you have a rest of flash memory and USB management, etc. Okay, so these are the hardware level details of the switch platform. I have covered 9300 because that's the catalyst switch that we are looking for in upcoming networking technology, and that's the innovation we have. Next topic we have traditional MLS, multi-layer switching, and SEF Cisco Express forwarding. So what's the fundamental here? The fundamental here is route once and switch many. And again, if you correlate this with the SD-WAN, means you have the control plane and data plane. Control plane who will take all the decision, and then the data plane, it will forward the packet. Correct? So here also you'll find that you have the control plane called route processor or RP, and then you have the data plane that is the switching engine, that is the SE. Route processor will take the decision, and then it will program the switching engine that now I have taken the decision, this is the source, this is the destination, and you need to forward the packets. This is the way that the forwarding will be very fast, and this is the way that the multi-layer switch or switches, they are providing the line rate speed. Correct? Now Cisco Express forwarding, how it is working and what are the key components we have. Again, the core of Cisco Express forwarding is take the decision once, and then everyone will follow that decision. So route once means that you have the brain, and in the chassis type of architecture, the brain is the supervisor engine. So either we are using the Catalyst 6K or 4K or 4500 series switches. We have the supervisor engines who will take the decision, and then they will program the line card to forward the packet. If you have the fixed type of switch, so for example 3850, 3750, etc., so there also SIF can be enabled in the hardware. Okay, so SIF is the feature. Here you can see in the diagram and understand more, that will provide you the fast forwarding of the packets, because all the time the request is not going to the CPU. CPU will take the decision once. So you are punting the packet to the CPU, who is building the routing table and the ARP table, but they will program the switching engine, or they will program the line card where you have the dynamic engine called fib, and then you have the next hop adjacency, or you have IP to next hop mapping, from where the packet will move to the destination. Correct? So here in the diagram clearly you can see that the different rows of all these components. Routing table, it will build the routing table, that's the route processor, and then you have the ARP table, that's the L3 to L2 mapping, that will resolve the MAC address. Now you have the dynamic entry, that's the fib table, forward information base, and that fib table will be arranged in a way that you have the longest prefix match to the lowest prefix match. That's the beauty of this fib table. And then finally, this fib, whatever information they have taken from the ARP table, so now you have IP to next hop mapping, or you know that who is your next hop agency, and then you can forward the packet as per layer 3 forwarding engine. Actually, this is the mechanism that MLS is using. So now you have different type of terms. You have routing information base, who will form forwarding information base in terms of longest prefix match. So that is the LPM. And then you have the ARP table that will do the L3 to L2 mapping, and then you have the adjacency table that will be used by the fib. Okay, so I have put all these points here. If you want to read these slides, you can read it, but whatever we are discussing, the same thing here also. Now, once you have your rib, once you have your ARP table, once you have your fib, once you have your adjacency table, if you want to verify, you can go and verify like show IP CEF. And if you want to check the CEF entries in detail, you have that detail option. So you can come to know that who is the network you are looking for if you want to check that particular network. So we have option that we can go and check the particular destination network. So for example, show IPsec prefix IP, and then if you want to check the longer prefix matches, because this fib entry or the CEF entry, they will be in a manner that they will have the longest match and then the least match. It's like that. Obviously, if you have the longest match, then only the fib entry, that will be the natural choice for the fib entry, that you have to check the next hop for the longest match, correct? All right, so in this way, this fib entry will come into the picture, and when you check the fib entry, you can see that you have multiple next hop like attached or in the same network in the other network. Again, it depends that who exactly is your next hop. According to that, they will build the table entry. Now, again, if you want to see this in detail, so you can go and check show IPsec, the network and detail, where you will go and get the detailed information about the agency, about the next hop, dependencies, etc. Okay. Now the next important thing we have is the agency table. So we know at this point of time that you have the fixed components. So for example, rib table, and then you have the ARP table. Now you have the dynamic entry as per the longest match, that is the fib table, and then you have the agency table. Now this agency table obviously will be taken from the ARP table. So ARP is doing L3 to L2 mapping, and then when fib, they are looking for their next hop entry, they are contacting the adjacency table, and then as per the longest match, they can get the next hop. Okay, so that's the thing we have, that's the important we have in the agency table, but there are so many other stuffs as well inside the agency table. If you want to check that, you have this option show agency table. You can go and check that. You have the summary and detail option as well. The agency table will be look like this. So first, you can see that first few numbers belonging to MAC address, and then rest of the keywords are there. But what is important there in the agency table is to understand a different type of keywords. So while you are checking your agency table, you will find that you have null agency. Now what does it mean by null agency is that used to switch packet destined for null interfaces. The null interfaces always is defined on a router or switch. It represents a logical interface that silently observes packet without actually forwarding it. So you may have null interfaces. They are not actively forwarding the packet from one place to other places, but they are silently uh, absorbing the packet. Then you have the drop agency. Obviously, drop agency, as name suggests, that they are going to drop the packet, and the reason may be you have encapsulation failure, unresolved address, unsupported protocols, no valid route presents, no valid agency, you have checksum error, etc. Now, if you want to go and check this drop agency, you have this option. You can go and type show CEF drop, and then you can check encapsulation failure, no route, etc., etc. Okay. Then the third one is discard agency. Discard agency means your next hop is discarded by some blocking rule, ACL rule, etc. Then finally you have the punt agency. Punt agency means that you don't have your adjacent table, You don't have your next hop, and directly you are forwarding the packet towards the CPU or towards the route process. If you want, you can go and check show CEF no safe switched, means they are not safe switched, rather than they are CPU or the RP switched or RP processed. So according to that, you can go and check these important keywords. So here you can see that you have null urgency, you have drop urgency, you have discard and point urgency. Finally, when everything is happen and the packet is ready to go, so at that time the rewriting of packet will happen in the egress or when it is leaving to the switch or the router. So what are the things they will change? They will change the layer 2 destination. Obviously the layer 2 destination will be the next hop MAC address. They will go and change the layer 2 source address. That will be the egress MAC address of that particular interface. They will go and check the TTL, means they will go and decrement the TTL by 1. They will go and check the layer 3 IP checksum. They will go and check layer 2 checksum as well. So these are the things that the switch will check before actually sending the packet to the egress. Finally, SIF will be enabled. Nowadays it is enabled to all the routers, all the switches. But suppose if you want to disable SIF on certain platform, you have option. You can go and type no IP SIF. In some platform, we have to write no IP route cache or maybe both. Okay, so in this way, we can disable the SIF. So obviously everything will be handled from the CPU or from the routing process in this case. And this is not the recommended way, but sometimes for the sake of troubleshooting or some other reasons, we used to do this. All right, so let's stop here. This is the last session in section 1. We are going to verify the SIF and we'll see the TCAM as well. Let's discuss or start with the SIF verification. So first of all, what you can do, you can go to the CLI and you can run the command show IP interface VLAN and show IP interface and the interface name. Suppose if it is a VLAN interface, you can go and give the VLAN and the number. Here you will see that SIF is enabled. So that means this particular interface SIF is enabled. Although you have other important informations as well with this command. So this is very simple and easy to run command, and you'll get a lot of information related to that particular interface. To understand the SIF or to verify the SIF is enabled or not, to run the SIF command, we have show IP SIF command. If we run that command in the next hop column, you can see that you have receive, attach, and other information. So what does it mean? The first entry here, you can see that you have 000/32. This is nothing but suppose if you don't have the adjacency table, if you don't have next hop, then the packet will be pointed to the CPU or the route process. That's the first entry you have. Then suppose you have 192.168.199.0/24 and attached as a next hop. That means that this is your interface. That's why it is showing attached. Then again you can see that you have 199.0/32. That's the network. This network and this network is receive. So that means that obviously your network, but the thing here is that this is a reserve entry. Here you can see the more explanation. So if it is .0/24 and if it is attached, means it is connected interface. If it's .0/32, that means it is a reserve for exact network or network address, and this is used to contain adjacency for packets sent to network address. If the network is not directly connected, in this case there is no adjacency and the entry is marked as a receive. So I think you understand that .0/32, this is for network. Then you have .1/32, and this is also a reserve entry. This is very much like host route /32 host route. So you have network route or you have network, you have host route, reserve entries. Then again you have .2. Dot 2 means that you may have dot 2 as your neighbor switch. So you are connected with your neighbor switch whose IP is dot 2. And then finally you have 255 /32. That is nothing but the broadcast address, and that is also marked as a receive, and this is also a reserve entry. If you want to know detail about CIF, you can go and check show IP CIF, and then the detail will get the detailed explanation. Now finally we have to understand about the TCAM resources. So here you can see that you have forwarding resources. Inside that you have MAC, host route, IGMP routes, LPM route, multicast route, SCT. Now this particular output or this particular reference is belonging to 9300 catalyst switch. In 9300 catalyst switch, you have output like this. Then in the TCAM resources, you can see that you have security ACL, QoS ACL, service ACL. Inside that you have PBR, NetFlow, SPAN, MACSAC, SecCop, Tunnel Lisp. And even you have the entities for NetFlow as well. Now here you can see the exact partition. So for forwarding resources, we have 32K reserved, the host route 24K, IGMP 8K, longest prefix match 8K, multicast route 8K, SDT 8K. And then again you can see and have a reference for the feature resources for TCAM entries as well. In bottom you have the NetFlow entries 64K ASIC as well. If you want to see this in detail, so you can go and run this command in Catalyst 9K show platform hardware FED fed switch active forward ASIC resource TCAM utilization 0. And here you can see that unicast MAC addresses, max value, use value, IGMP L2, directly or indirectly connected states, and all those informations we have in this particular output. So if you run this output, if you want to see the detail of this from the CLI, you can go and execute this command and get it. Finally, just for the reference, you have the default STM template network interface. You can see the forwarding resources and the TCAM resources and the reserve entries. All right, so let's stop here. In our enterprise core curriculum, section 2 is belonging to virtualization and the percentage is 10% weightage. Here you can see the topics related to little bit of VMware type of thing. Like you have to learn, understand hypervisor type 1, type 2, virtual machine, virtual switching. What I have done that I'm going to record small 14 videos, and I'll go a little bit beyond whatever there in syllabus just to our knowledge and study purpose. So you'll find it very informative, all these 14 videos that will cover actually not only the Cisco aspect of hypervisor, virtual machine and virtual switching, but the VMware aspect as well. So I'm going to touch both. Then we have 2.2 where we have to learn about VRF, GRE and IPsec tunneling. And then 2.3 we have Lisp and VXLAN. Now for Lisp and VXLAN, I'm going to upload the same video that we have done in section 1 for Lisp and VXLAN. So one video for Lisp and one video for VXLAN. So here 2.3a and b you'll find some sort of repetition in terms of just section 2.3a and b that we have already done inside section 1. Okay, so this particular section you'll find that it will go over very quickly, and you'll find this section also is very informative and it will add up your skill set and knowledge base. Then what is server and operating system? What's the basic definition of server? Server means that someone who is hosting services, someone who is providing services. But you can see that server, they have various components, and these servers, they are taking requests from the client. They are processing those requests and providing certain services. Now the server consists of the CPU, the internal storage, main memory, interface card. Means there is various input and output uh, processing. There is various components inside the server. uh, After processing those servers, they are providing the services, correct? Now, what is the main component, and to be very precise, what is the main software component we have inside the server is nothing but the operating system. Now, the operating system is someone who is the brain, and you can see the definition of operating system. A very standard definition is that operating system can define as software that control computer resources and provide common services for other computer program that run on top of it. So for example, in my laptop I have Windows operating system, and once I have Windows operating system, then I have different applications. So for example, I'm using Gmail, I'm using web browsing, I'm watching YouTube, I am uploading courses to Udemy, watching courses from different vendors, uploading courses to here and there, doing some chat, playing game. Means all those applications that is hosted and that is actually connected with the operating system. So operating system you can think as a boss who is providing the time slots, who is providing the instructions. So you can think that operating system in the core and a small programs, they are connected somehow with this main program, this operating system program, and then operating system, they have their own mechanism to provide time slot, to provide space, to provide computation, everything that is provided by operating system. So you can think this is the heart inside the server, and which is responsible for all to run all the other programs. Main vendors: Microsoft, Linux, FreeBSD, Apple, Android, Cisco iOS, Chrome, etc. Some of the operating system here, you can see the difference that they are used inside the laptop or server, etc. But some of the operating system, they are used inside the networking devices like routers, switches, firewall, etc. etc. Correct? Now here you can see the view of the operating system. So you have the kernel space, that is the low level programming, and that is the program that is associated with operating system. And then maybe I have user space and various applications like email, chatting, online, um, video game, etc., etc., etc. And these applications, that is program, these kernel programming, that is again the program, they are associated, and again these hardwares that you are seeing, so for example RAM, NIC, disk, they also have their own programs. So actually behind the scene, all the programs from high level language to low level language, they used to consult to each other with different type of messaging bus in between them, and they are providing the output as requested as an input. So we are giving some input, processing happening, that is the program is happening, message bus, they are receiving the instruction, and then they are providing the output. So that's the basic of the operating system. Next section we'll learn about that how this hypervisor operating system works, and they are helping us to reduce the overall cost, reduce, or we can say the more efficiently we can use the different type of hardware component or resources with help of emulated uh, features that we have inside the hypervisor program. What is virtualization? And with help of virtualization technique, what we are going to achieve? Last section we study about the servers and the definition of server and operating system. You think virtualization is a type of emulation where you have fixed hardware. On top of that, you can use some emulated program, and then you can install various operating system. So what is the traditional way to install an operating system? Say I have my laptop, I can go to my laptop. In that laptop, that is my fixed hardware inside that laptop, I have fixed CPU, memory, RAM,
etc. So I have my laptop, and on top of my laptop I can install operating systems. So for example, I'm using Windows operating system. Now think like this, that you have the hardware. So I have the hardware. On top of that, so let me write here hardware. On top of that, I can install some sort of emulated software. So I can install emulated software. This is actually termed as a hypervisor. So I can install a hypervisor on top of hardware, and now whatever, say for example, RAM, CPU, network interface card, memory, etc. you have, those fixed hardware they can use, and they can think that I have my own RAM, CPU, network card, memory, etc. I can install operating system 1, operating system 2, operating system 3. Obviously there should be some limit that how many operating system you can install. I'll write here N on top of the fixed hardware and the hypervisor. Now if we use this particular emulation or emulated way to install the operating system, actually this is termed as a host. So on top of host, and in this course we are going to study about VMware hypervisor, that is nothing but ESXi. So on top of host I am installing a various guest operating system. So these are nothing but guest operating system, and in this way we can save a tremendous amount of hardware resources, and that's the term actually, something termed as a server virtualization. Now there is difference between the server virtualization and hardware virtualization, and you will understand this thing coming forward or going forward. So for example, when you perfectly use the hardware resources, that is nothing but the server virtualization. And suppose if you know the term, so for example, unified computing system inside Cisco. So you have unified computing system. Inside that you can install so many servers with server profile, etc. That is one of the example of server virtualization. The other example, just now we have seen that you have one big hardware resource, and then you are installing some sort of hypervisor emulated software on that, and then you are installing the guest operating system. So that is the example of server virtualization. When we are talking about network virtualization, now it is everywhere. So this network virtualization is used, say for example, SDN solution. So for example, my SD-WAN is a type of network virtualization, or inside that I have network virtualization. So for example, Cisco application centric infrastructure, VMware NSX, these are using network virtualization concept. Uh, Easy example, can I give the easy example? Yes, the easiest one is the VRF, virtual routing forwarding. This is again a type of network virtualization. Okay, so virtualization technique means, now here you can see this is the example of server virtualization. You have, suppose if you have one hardware, one operating system, that is we are not using any type of virtualization, but you can use in between the hypervisor or the virtualization software that is known as a host. On top of host, we can have n number of operating systems. So here you can see OS, different operating system we are installing, and then on top of that we are installing the applications. So in this way we can reduce the cost, and it is actually quite efficient. Almost all the companies are using that way, this method only. Again, here you can see that you have multiple ESXi, so you may have host 1, host 2, host 3, few of the host having a few of the operating system or guest operating system, few of the host having few of the guest operating system. And suppose if you want to manage entire infrastructure, later on we'll see that how to manage the hypervisors, cluster of host, data center, etc. So we have one VMware popular tool or popular software or suite of software protocol suite, whatever you tell this is, you have one management layer, that is the vSphere server and vSphere client. And in our lab also we are going to use the vSphere client to manage. So here you can see that you have the server and here you have the client, and with help of one web browser, one application, you can manage the entire big infrastructure. So now you can see the complexity has been reduced, the overall virtualization of hardware has been enhanced, and in this way companies, they can save lot of money. So now what is the hypervisor? The definition of hypervisor is, a hypervisor can be defined as a software that can emulate the hardware like CPU, memory, RAM, storage, etc. for the installation of guest operating system. In the context of server technology, a hypervisor is essentially a program that allows creation of virtual server. So whatever we have discussed, the same thing. Again, if you want to see this diagram, you can see that you have your server, your hardware, you put your operating system and the application. But in this way, you are not using the virtual way or you are not using the hardware resource efficiently. Instead of that, what you can do, that you have your hardware, put the host or the hypervisor, and on top of that you put operating system and application. So easily you can enhance the performance, reduce the cost, better use of the hardware resources, single plane of management for different guest operating system or application, etc. Again, we have one more diagram here. You can see that you have one big framework. You have fixed hardware, the 86 architecture. You have your virtualized software here, and on top of that virtualized software, you are installing operating system application, operating system application, operating system application. Now all these CPU, RAM, NIC card, disk, whatever you're seeing here in the diagram, actually those are termed as a virtual RAM, virtual memory, virtual NIC, etc. So you have your real CPU, memory, NIC, disk, and on top of that you are using everything as a virtual. And that's the power of the hypervisor we have. In this course, basically we are going to focus on the VMware ESXi, but there are so many good vendors. There are vendors like VMware ESXi is a hypervisor, Microsoft Hyper-V. These are the popular vendors. Then we have the Linux KVM. These three are the topmost trending hypervisor. Apart from that, we have the Red Hat Citrix Zen Server. This is also very popular, Citrix Zen Server. We have Oracle VM. Then we have, we'll see later on that we have two type of hypervisor as well. Then you have Microsoft Windows Virtual PC, Oracle VM VirtualBox, Pallor Desktop for Mac. You have these many vendors who are providing these hypervisor softwares. So I hope you understand that what is the meaning of hypervisor, why we are using the hypervisor, and in long term how we can go and manage them. Let us quickly discuss that what type of hypervisors we have and what is the benefit we have with the hypervisor. So clearly you can see that in case of physical server, you have your hardware, operating system, and application. In type 1 type of hypervisor, you have your bare metal, your server. On top of that, you are installing the hypervisor, and then you have the guest operating system and the application. In type 2, you can see that you have the bare metal, or you have the server, operating system, and on top of operating system, you are installing the hypervisor and the operating systems, like the guest operating system and the host operating system. Now, this type 1 is actually popular and it's quite hardware efficient. So this is the preferred hypervisor technology that we have, and most of the places that companies, they are using the server. So you have the hardware, you have the host operating system, that is nothing but the hypervisor, you have guest operating system, and then you have the application. Now doing so, we have benefit. Let me quickly show you the benefits. We can reduce the capital and the operating cost, minimized or eliminated downtime, because in this case you may have redundant host. So suppose if one host go down, still you have your different host and your VM can move to that particular host. So that's why it is redundant, means you have the redundancy in terms of host, in terms of guest operating system, plus the application redundancy. You will see the design and architecture of virtualization with respect to, say, for example, VMware, and you'll find that the downtime is reduced. Obviously, if your operation cost is less, your downtime is less, it will increase the productivity, efficiency, agility, and responsiveness. Faster provisioning of application, yes. We'll see that how easily you can install a guest operating system on top of host. It's very easy. You can do with few clicks. It has greater business continuity and disaster recovery. We have some mechanism, we have some methods that we can do the disaster recovery, and it will simplify the data center management, and that's the key. So when we are simplifying the things with higher efficiency, agility, more productivity with lower cost, that's the goal of all the businesses nowadays. Let us discuss about the virtual machine and try to understand that how we are going to install over the hypervisor. We'll see the installation lab in upcoming session, but here we'll try to understand that how it will be emulated over the hypervisor or over the ESXi. So now what is happening, that we know it is clear up to this point that I have the server on the top of server. So I have server. On top of that, I have ESXi or the hypervisor. And on top of that, we are going to install the operating system. Those are nothing but guest operating system. Now these guest operating system, whatever actual hardware is there, they are sharing. So inside that guest operating system, they have shared, or you can say that they have shared actual physical hardware in terms of virtual CPU, virtual RAM, virtual hard drive, virtual storage, virtual NIC. So everything is virtual. Whatever actual we have, all those emulated virtual hardware they have. That's the first thing. The second thing, and very important thing we'll see in the upcoming slide, is that everything is in form of folder. Okay, so here you can see I will log into the vSphere client and I'll show you that you'll find that the CPU is virtual CPU, virtual memory, virtual hard disk, everything is virtual here, correct? So I will log into that vSphere client. I'll show you. The next important thing here you can mark or highlight is that everything is in the form of folder. We'll see that. I'll show you that database and the folders inside that. But now let's see the terminology and the extension. So we have .vmdk extension. What is this? This is nothing but your internal storage. So your virtual disk internal storage having extension .vmdk, correct? Obviously VM is for virtual machine disk, that is internal. Then you have the swap memory, that extension is .vswap swp, and that is used for what? So here you can see that is used for virtual memory whenever the process running on the VM reaches the VRAM predefined limit. It's nothing but virtual memory. Virtual memory is swap, vswap. Virtual storage is v.mdk. Then you have the log. Why? So there in the .log extension, all stuffs related to troubleshooting purpose they will stored. So the file store all the information a VM produces for troubleshooting purpose. Then configuration, that will be stored inside .vmx. So here you can see .vmdk, .swap, .log, .vms. Why I am explaining this thing? Because when I log into the vSphere client, from there you can go and check these folders and extension. So once you are seeing .vmx, that means it is there for virtual RAM size, VNIC information, and other references for the other files. Then we have non-volatile RAM, that is .nvram extension. Again, the use of non-volatile RAM, here also the use is same. Correct? So these are the important extensions we have, but apart from that also you will see further more extensions. I took the snapshot from there from the file system, and here you can see that .nvram, .vmdk, .vmsd, vmx, .log, etc. Okay. So what's a virtual machine? Virtual machine is nothing but a machine which is installed on top of hypervisor as a guest operating system. They are using the virtual resources. Actually, they are using the actual resource in terms of virtual resource to run their operating system, or you can not or but and you can install the application on top of operating systems. So let me quickly go and log into the vSphere client. From there I will show you the virtual machine, how it looks like, and the various type of file and folder system. Here I'm inside the vSphere client, and we'll see later on that what are these entries or items inside the dashboard. So think this is a vSphere client dashboard where you have host and cluster, virtual machine template, the storage, networking, content libraries, global inventory system, and other stuff. So we'll see that these things later on. At the moment I am focused upon only on the VM virtual machine. So what you can do, you can go and click VM and template. Once you click, you can see a list of VM over the ESXi over the hypervisor. We'll go and check ESXi and their architecture as well later on. But suppose this is the tiny Linux, and I want to see the summary, what type of virtual hardware it has, what type of emulated hardware it has. So here you can see the list of hardware, the VM hardware, the CPU, memory, network card. I will discuss more about network card later on, video card, VMCI, and the other hardware related stuffs. Storage area, memory uses, and CPU info, the IP address and the hypervisor. ESXi02 acorp.local. It is having 32-bit of Linux operating system. The hypervisor is ESXi 5.5. These are the tools that is running. Okay, so this is the hardware. Now if I want to see that their file and folder structure, I can go to the data store. It is attached with this particular data store, and I am very much looking for my tiny Linux file and folder system. Here on the top you can see you have this expand button. If you go and expand that, you can see it is coming up, and now if I go and click to tiny Linux, the folder will open, and inside this particular folder you can see all the extensions that we have discussed: .nvram, vmdk, vmx, log, etc. Correct? So this is the way that we can go and check few of the things inside that. Later on we'll study more and more about this, and we are going to learn each and everything. Let's go through the hypervisor architecture of VMware ESXi. Now in the diagram you can clearly see that there are multiple ways actually to do the management of the hypervisor and the associated guest operating system, etc. So suppose if we have cluster of hosts, say ESXi 1, 2, 3, and I will log into the vSphere client, and I'll show you that from one particular management plane, and that is nothing but a web browser, from single web browser with help of vSphere server, with help of vSphere client software, you can actually manage, or you are able to manage, the entire VMware infrastructure. That's the overview or the top view of the architecture of the VMware. This is the VMware client, that from where we are going to manage everything. This is the web browser, and here you can see that vSphere Web Client is a web browser based application that you can use to manage, monitor, and administrate the objects that make up your virtualized data center. And that's the key. See, from one application, I am going to manage the entire virtual data center. And that's the power we have from the VMware. And that's the reason that VMware increased so much in terms of software defined data center. So from a single software, you can manage the entire data center objects spread across the globe. Now here you can see that what are the things that we can do from the vSphere client. We can go and check the health, the status, performance of the objects. We can do the management and the administration commands from the vSphere object. We can create, configure, provision, and delete the vSphere object. So think everything that whatever guest operating systems we have on top of host or maybe cluster of host, everything can be managed from one application, and that application is nothing but vSphere Web Client. So vSphere Web Client, it's very popular in terms of vSphere client. So we are not telling okay vSphere Web Client, but vSphere client. From vSphere client, we are going to manage, monitor, organize, check the health, and there are so many things. Plus, we have so many added new application. From there, we can actually go and add certain new capabilities inside this management plane, inside this management web application. Correct? So once you log in, how it look like, here you can see that the first, this is the navigation tree or the navigator. Then the second is the main content area. So what's the inventory list, host cluster, VM, storage, networking, content libraries, vRealize orchestrator. So many things we can go and check from here. Then on top you have the search bar. Now my login will be a little bit different because again we are using some new or the latest version of vSphere client. But more or less you can see that you have work in progress, you have alarm, you have recent task, etc. It will look like that. You can go to the home button where you will get the list of all those objects or all those operations that you want to check. Once you click the global inventory list, it will give you the inventory list related to data center, host, cluster, network, storage, virtual network. So all the objects associated with these variants or these operations you will get from the global inventory list. Likewise, I can go to the home. From there I can go to virtual machine. I can go and log to a individual virtual machine. I can go and check their summary, their hardware, their capabilities. You can see I can go and check their hardware things. If I want to add any new vNIC or the NIC card, I can go. You can see 1, 2, 3, all these things I will show you in the lab as well. So I can go click and I can add one new NIC. Once you add a new NIC, what will happen that you will find that that particular NIC, once you add, you can see the work inside the recent task and the progress also you can go and see. So work in progress, all those things you can go and verify. So let me quickly log into the vSphere client and let me walk you through all those things that just now we have seen. Alright, so I logged in inside the vSphere client, and here you can see the task, the navigation, the task here, the main content page, the navigation, the search, all those things. The home button also here in the menu is little bit different than what we have seen, but more or less is the same thing. Now what I can do, I can go click to the menu, I can go to the inventory list. Here you can see the objects related to a resource related to data center, host, cluster, resource pool, data stores, data store cluster, network, virtual distributed switch or port groups, etc. All those things we have here. Here I have the task and the alarm also. So I can see the task, I can see the alarm, and all right. So what I'll do, I'll go to the host. Once I am inside the host, actually I want to go inside the virtual machine. So let me go like this. You have multiple ways. You can click to the menu, you can click VM template, you can reach here, or you can click here. You can go to the global inventory list. Once you are inside the global inventory list, you can see your hosts are there. Once you are inside the host, likewise you can go one by one. Inside the host also virtual machine, I can go here. I have the tiny URL. I can go back. That's the power we have with this management. I can tell this is the management plane, or I can tell that this is the management web client URL from where we are going to manage, or from where we are going to give the instruction to all the objects inside the VMware data center. Think like this is a data center. We are managing a data center from a web application. All right, so I want to go to the this Windows client, and let's see what is here inside this particular hypervisor. Remember, when I'm going to global inventory, host is nothing but the hypervisor. Inside this hypervisor, I have the guest operating system. So how many guest operating system you have? You have two guest operating system, Tiny Linux and the Windows. I want to go inside the Windows. Once you are inside the Windows, you can go and click here. You can have the summary. These are the hardwares. I want to add one of the hardware here. So I can go click edit setting. Once we are inside the edit setting, I want to add one network adapter. So let's add one of the network adapter. And here I'm not getting the network adapter in the bottom, but here you can see on top you have the add new device. So this is actually a little bit newer display we have. So you can go click add new device. What you want to add? You want to add the network adapter. Once you click add network adapter, you can see the new adapter option came up. I want to select that. What is your network? So it is asking about which particular distributed switch, and let's add this one. Once I add this, and this is showing the connected as well. Connected on power on, yep. And then what we'll do, simply click OK. And if you click the recent task, here you can see that task is on. Let me show you this 6 millisecond, and this is related to Windows. This is the way that you can actually go and see the recent task. So task is going on with the Windows 10. We have added one of the NIC card. Task is completed. So let me quickly do one more thing. Let me do one more time so you can understand. Add new device. Add one more network adapter. And VM reason 1, something like that will add. So I will go here and I'll click browse. VM reason 1. Okay. And see the task queued, completed. Have you seen that? It was queued and now it is completed. So now we have the 2 tasks. Here you can see in the taskbar. So this is the way that see how easily we have added one of the hardware component, one of the networking component. Like that, it's very easy. Just with help of few clicks, you can manage, operate, check the health. You can do each and everything from this particular vSphere client. In this section, we are going to install one virtual machine over ESXi. You can see the steps. You can go to the home, click VM and templates, then go to the data center. From there, in the bottom, you can go and select create new virtual machine. Then you will get one page where you have to follow the steps one by one. So you have to go and check that select a creation type. It's a new virtual machine or deploy from template, cloning, etc. Then you can go and check the name and the folder, what's the compute, what's the storage. So let me show you one by one all these things. So I'll go and give the web server 01 as a name, select which is the data center belongs to. Then you can go and give what's the compute. Say for example, this is belonging to ESXi 1 or 2 or 3. Then I can go and give the data store, say DSISCSI. Then a few of the other things that the check and the compatibility, etc. Once you do up to this step, then finally you have to go, and here you can see some of the slides are overlapping. So from here, from point number 2C, you can go here and see 2C. For example, I'll select this DSISCSI01, and then in my case, my ESXi is 6.7. So I can go and select that. Then I'm going to use the same guest OS and the guest OS version. Once I do that, then I'll go and select the new CD and DVD drive as well. And then all the steps you can see 1, 2, 3, 4, 5. Once I do ready and complete, finish, that's it. Then once my web server will be showing there, what I will do right click and then I'll power on. So let me do one thing. Let me quickly log into the ESXi or the vSphere client, and from there I'll show you that how you can follow all these steps one by one. So let me quickly log in there. Alright, so I logged in inside my vSphere client. I can go to the menu, and here you can see VM and templates. Here also you can see the VM and templates. We have the shortcut key as well, Control Alt plus 3. Once you are here inside the client, if you go and click to the data center, and let me scroll down, let me expand this first, and here if I do right click here, you can see you have option to create add host, means you want to add new ESXi, you want to add new cluster, you want to create new folder, you want to create distributed switch. Later on we'll discuss about this. You want to create new virtual machine, or you have the OVF template. So here we want to create new virtual machine, and now you can see all the list and questionnaire we have. So create a new virtual machine. Yes, I want to create this. What's the name? So let's go here and give the name, say for example web server. So I'll give name as a server 01. What's the location? Here you can see I can go and check the location. That is nothing but site A data center. Next it is asking about the compute. I have a 1A and 2A. I will select 1A for the moment. Then the storage. Now I'll select the first one, that is the ISK01, and on top you can see that we have option data store default, vSAN and vVol, no requirement policy. So we'll leave this as default. We'll go next, and then the compatible 6.7, and later we'll use 6.7 at the moment. We'll go and click next. Now select a guest operating system. What type of operating system this is? This is a Linux, and I want to use OS 64-bit. So this is the family, this is the version, correct? We'll go next. Now the customized hardware, it is asking me that this is the hardware details. You have the CPU, 1 core, memory 2 GB, new hard disk 16 GB, ISCSI controller, new network connected. Here I want to add this new CD drive, DVD drive. I want to add this, say for example, data store ISO. So suppose if I add this, it is coming here, it is asking that what image you have inside the data store. You can see that you have Tiny, Linux, etc. In NFS, what images you have, in VM image, what images you have, correct? So actually I'm looking for that photon image. So I'll do one thing, I'll do cancel here, and let me try to check what is there in the content library ISO. Inside content library, you can see that I have Photon 2.0, and I will save this. Means I will select this and click OK. I'll make this as a connected, and rest of the options also you can see here. You can go to VM option also, you can see all those options. So we are almost done with the installation of the VM, and let's click finish it. Once you click finish it, you can go and check the task as well. So here you can see the task is going on, and you can see that you have the VM server, web server 01, that is at the moment powered off, and you have this launch remote console as well for this server. But before that, what I'll do, I'll go here and I'll do power on for this server. Once I power on, I can go and click launch remote console just to see that how it is working behind the scene. So now you can see that the install option has came to install from the CD DVD that we have attached. So let's quickly go through it. All right, and now you can see that it is in progress. You accept this, yes, and then the virtual disk is 16 GB. Okay, I am just pressing enter. This will erase the disk. Are you sure? Yes. We'll wait for a few seconds. I want to install this Photon minimal. Yes. Hypervisor optimize. Yes. And then it is asking about the host name. So I'll give the host name as a, for example, web server. So web server 01 is the host name, and then I should give the passwords. So let me give the password, a long password. Let me try to retype this password and confirm password. Now the installation is in progress. You can see all the installation steps is going on. Congratulations, Photon has been installed in 20 seconds. Press any key to continue to boot. So I'll go and press enter, and now it is booting up. We'll wait, and here it is. Alright, so here you can see that now I have the username and the password. So I'll go and give the username and the password that I have set earlier, and now we are in. So now we have the web server 01, and if I see the IP address, because it is connected with the DHCP, and if I know what's the outside IP address, so let me try to ping from here. Say the IP, I know the IP from the outside is 192.168.1.0.10, and this command is not found in this Photon. Now because we have done this minimum configuration, so that's why this ping by default is not installed. So let me try to install this ping feature, IP utils. Let me try to do that. Just in this case, what we have done, that we try to do the minimum installation, because our goal was to install a particular VM, and in the minimum install for the Photon, the ping was not supported. So I have used this tdnf install IP utils and just to install this feature, and let me try now. Still the ping is not there. So never mind. What we can do, that we can do the full install, and in the full install this ping will work. So our task is done, that our installation is successful. Let me minimize this and let me show you here. So let me go out from here, and now you can see this is power on. We have launched the remote console as well to verify this, and now it is up and working. Alright, so we can stop here now.
This particular session is very important because we are going to start virtual machine networking, VM networking, and there are so many nice terms that we should learn and know. So let's start this. Now you can see that what's the problem we have. So once you have the host and once you have the hypervisor, so we know that we have the say for example host, and on top of that we have operating system or the guest operating system. So I have server, host, and the guest operating system. Now problem here is, so let me try to draw here. The problem here is that once you have host and you have operating a guest operating system, the first problem is that which software element should control the physical network adapter drive. So here you have your physical network adapter in the server. Who will control that? The hypervisor or the guest operating system? Obviously hypervisor has to control, but how? That's the first thing. The second thing, that how should communication occur between VM and the external resource. So now in this diagram you can see that you have your VMs and you have your server as well. Now these servers may be connected with switch, so for example L2 or L3 switch, and then you may have a router or you may have external world. So now this VM, how this VM will come, because this VM has their virtual NIC. So the virtual NIC adapter will come to the server and then it will go to the outside. Here we have the diagram. In this diagram you can see clearly that how these VMs will go and communicate to the outside. This is nothing but south to north or north-south traffic. So how this will happen? That's the second point, second challenge. The third challenge is that how the host will communicate to each other. So inside that I may have, so for example 25 VMs. So how this east to west traffic or east to west communication happen, and who has the control over this communication? Correct? So those are the questions. The solution that VMware came with in early 2000, that once you install this particular host, this particular hypervisor, at that time you have network standard switch. So you have host standard switch or vSphere standard switch, VSS. Now once you have the VSS, that means this particular VSS, obviously they have the VNIC from the vSwitch. You can think this as a switch in between. So now this is the switch, and then this switch will control the east to west or north to south or south to north traffic, etc. Now once we have this particular standard switch or the standard switch in terms of vSphere or network standard switch, we'll see the problem. Further, we have some problem. So before going to that particular problem, let's see this particular diagram here. So here clearly we'll see that you have your physical infrastructure, and if I try to analyze this with a switch, you think like you have one switch and here you have north. Just to analyze this particular diagram, here you have south, means here you have server, virtual server. So here you have virtual server, and here you have, for example, outside world, a router domain. Now we can think like this particular standard virtual switch or virtual standard switch, that in Cisco domain we used to study about access port. So access VLAN 10, access VLAN 20, access VLAN 30, access VLAN 40, etc. Then you have one interface that is going towards the router, that is nothing but trunk. So you can think at the moment this trunk is nothing but your uplink going toward the external router domain, and then you have this access port. These access ports belonging to certain VMs, you can think this as a port group. We'll learn about port group in the upcoming section, but you think this as a port group, and you may have certain specific port groups as well, certain specific VM port as well, that may be used for management traffic, that may be used for fault tolerance, that may be used for vMotion. So here you can see that
the blue color is nothing but complete VM related ports, and there you have the uplink or your physical interfaces. So here you have port group related to management, port group related to vMotion, maybe port group related to fault tolerance, etc. Then you have port group related to test, port group related to production, and this is over one host. So this is nothing but host 1, and same type of thing. That's a problem here. So if you want to scale up same type of port group with the same name, everything, you have to create across, say for example, if you have 25 hosts, 25 ESXi servers, then you have to go and create the same name throughout. And that's why we have evolved to the distributed virtual switch that we'll discuss later on. But yeah, here you can see the production, here you can see the test, the port group. So the attributes having common properties or common properties inside the same group, a group of common properties, anything you can tell, that's a port group. Then you have the vMotion, you have the management. So here you can see the uplink and you can see the downlink, or you can see the VM link. So this is nothing but my VM link, and this is nothing but my uplink. Everything is defined inside the port group. Common property, attribute group, or grouping of common property or common task things. So clearly you have, say, VM1, guest operating system 1, guest operating system 2, 3, and 4. 4 VMs. 2 of the VM, they are part of, for example, sales. 2 of the VMs, for example, they are part of HR. So they belong to HR, they belongs to sales. Like that, you can group the ports and you can connect with the virtual machines. Alright, so you can analyze like your normal Cisco world also like this, but again now at this time we should understand that virtually how they look like, correct? We should understand that those terms. Now what is the issue we have when we are using the standard switching system? In that you can see that the standard switch is created. So at the moment you will install ESXi, you have your VSS up and running. Now the problem here is each switch on every ESXi must be created and configured individual. So you have to go create, etc. This can be time consuming, although we can do some sort of automation, but it is taking some time to do this. The second thing, one important note when using vSphere standard switch and some of the high availability features with vCenter in the standard switch must be named. You have this naming convention. So your naming should be common throughout the vSphere domain. Okay, and then also note that the features like input out network IO control, LLDP network health check, and the backup and restore means some advanced features, they are not supported in the standard switch. So these are the issues we have, and that's why we want to use the distributed virtual switch. We'll see in upcoming sections. In this important section, we are going to study about a VMware vSphere port group. That's the port group and the standard switch or the vSwitch. So what is port group and what is the significance of the port group? Now in this section, we'll understand 100% about the port group and the standard switch. Next section, we'll go and perform the lab task. So what is happening? I'll give you one example. Suppose you have one VM, virtual machine, and it has the VNIC. Now likewise you have other VM, say VM2, this is VM1 and VM2. This has VNIC. Now what you can do that these particular interfaces, virtual NIC, you can connect with a port group. Now again, what is the port group? So port group having common properties. Port group having common policies. So suppose if these VMs related to HR, so you can go and set common properties, common attributes inside the port group,
And whenever you are associating different VMs to this particular port group, they are part of same port group. Okay. Now, one interesting thing, suppose if you know ACI, application centric infra inside Cisco ACI, inside that we have concept of endpoint group EPG. So suppose if you create VMM domain and then if you go and create endpoint group, this endpoint group inside ACI is equal to port group as well. Now the concept of endpoint group is also same. You may have common EPG. So for example, EPG related to web or HR or sales, etc. Now those common EPGs, that means here uh, part of port group or the port group is equivalent to endpoint group. Okay, so VMware port group and then Cisco has evaluated their endpoint group. Both are actually same. Common attribute, common properties. You can common properties interfaces or interfaces that you are going to connect with the common properties. Those are nothing but the port group. Right, so what's the definition here? Let's see. So definition of vSwitch connectivity policy, which essentially define how the virtual device handle traffic that belongs to group of VM. In case of VMware vSphere, this policy is called as a port group. So you have one group where you are collecting all the ports and this group having the policy that will be applicable to all the interfaces or all the ports connected inside this group, like that. Alright, so later I will log into the device and I'll show you how we can select or deselect the port group. With respect to this particular image that is here, you can see that I have, this is the vSwitch. I will log in and I'll show you all the properties in 6.7 vSphere client, and you will find the display is a bit different, but these policies or the properties will be the same. We'll see that in the upcoming recording. So they are belonging to, say for example, WLAN 105, then you have the security policy, traffic shaping, and the teaming. If I go back in the slide, so let me go back in the slide, here you can see that, let me go back one slide back. So here you can see that your vSwitch having security policy, traffic shaping, failover policies, and the WLAN tagged with that. We'll see that. We'll see that you have VM port group belonging to 100, and how we can we'll go and connect all these things. We'll see. So at the moment, just think common properties interfaces grouped inside a group, or common interfaces grouped together with the common policies and properties of the port group. I'll show you. I'll log into the VM, I'll go to the network adapter, and that network adapter I'll connect with the port group. This network adapter is nothing but virtual interface, VNIC. Alright, so we have already discussed that once you have the standard switch, at that time you have issues. What issues you have? That suppose if you have same type of port group, you have to go and create those port group in all the host. So host 1, host 2, host 3. Suppose you have HR here as a standard switch, you have to create here, everywhere. That's the problem. Means you can think like Cisco access switch. So all these VSS standard switches are working as a Cisco access switch, but again all the access switches are going to be connected with the distributed switch, and that's the term that we'll see later on, that what's the use case of the distributed switch. I have complete set of slides for that. We'll discuss inside that. But yeah, for the operational efficiency, to support new features, you need a distributed virtual switch, and inside that also you can go and attach the port groups. So port groups belonging to distributed switch we'll see later on. Alright, in this section mainly we are going to focus inside the standard switch. So how I can go and add the standard switch, I'll go and I'll show you all these steps. Now there are multiple ways to create the standard switch. First of all, we'll go to the host and see that do we have
do we have a standard switch already? If not, then we'll go and add that. This is one of the way, but we have multiple ways. I'll show you different ways to go and add the network. So you can right click to the host, you can add the network. Once you go inside that, you'll find that what you want to add: VM kernel, physical network adapter, or virtual machine port group for a standard switch. Now VM kernel, clearly you'll see here that it belongs to vMotion. So vSphere, vMotion, iSCSI, NFS, FCOE, FT, that is the fault tolerance, and virtual SAN if you are creating the VM kernel. I'll show you all these ports, interfaces, port group, and switch, or the standard switch, in the upcoming recording. Then you may have the physical network adapter. A physical network adapter handles the network traffic to the other host on the network. Then you have the standard switch, and then we have the group for a standard switch. We'll see that. So suppose if you select the third option, then you will get the option either you want the existing standard switch or you have the new standard switch. You can go and add the adapters. So you can click on use adapter, click plus sign, then you will get the option for the physical network adapter. You can use one adapter, two adapter. Once you have one and two adapter, you can use this up and down arrow. You can set the different networking parameters or the properties of the adapters. All these things I will show you. And finally, you can see that this network having label network label, and the VLAN at the moment is untagged VLAN 0. That's it. So this way we can create the standard switch. Now suppose if you want to go and edit something, I'll go and log in and I'll show you that you can edit the vSwitch also. Obviously you select the vSwitch, you have the pencil button here for the edit. You can go and edit. So you can go and change the properties. So for example, if I go and select, it is asking about what's the MTU, what's the security policy, what's the traffic shaping, teaming, and failover. All those things we can go and select one by one. But it's still, just for knowledge purpose, we are studying that, okay, we have the standard switch option or vSwitch option, but later and in the production, generally we are using the distributed virtual switch. So this is also an option we have that we can go and check. Likewise, in the next section, in the lab section, I'll go there and I'll show you that you can go and select the physical adapter as well. And this is the way I'm going to show you. So I will go to the dashboard first. From there, from the dashboard, I will go to the ESXi. Once you go there, you have this networking option. So you can go and check the virtual switch, VM kernel adapters, physical adapters, TCP IP configuration. Once you are inside the physical adapter, here you can see you have the add network options. You can go and check all these things. I will show you one by one, all these operations. Yeah. So what is the takeaway from this particular section is, the takeaway is that what is port group. You should understand what is port group, irrespective of virtual switch or a distributed virtual switch. The significance of port group is there. Means you are going to connect the interfaces or VNIC interfaces having common attribute properties with a same type of port group. Once you have the port group, that's the first thing that we study, the port group. Second thing we are going to study, or we have studied so far, or we have seen the slide says, how to create the standard switch. And then again, a few of the slides you can see that how you can go and edit the physical adapter as well. So all these things, when we see this in a lab, then we'll understand more than these slides. But still, these slides are just for your reference, that you can go and you can do any type of change. Say for example, if I understand that what's the theory behind all these port groups and the standard switch and the distributed virtual switch, then it's actually very easy and straightforward that we can use the GUI, and inside the GUI we can go and do all sort of changes. Correct? So here it is showing that how we can go and do the load balancing in between the physical adapters, say for example active or active standby, etc. Correct?
So let's stop here, and in the next section uh, I'm going to show you the port group and a standard switch, and we'll see that how we can edit, create, even if you want we can delete also. Let us perform the lab task. So I want to make this particular video very clear that you understand what is meaning of host, what is meaning of physical interface, what is the uh, virtual or VM interface. So suppose I have one host. In this case, we have host 1 and host 2. Now here you should understand, I'll go and log in, I'll show you all those things. Now inside this host, a few of the interfaces will be physical interfaces. So I'll mark this as a physical. We'll see both the hosts, they have their individual physical interfaces. We'll see that what is the physical interfaces. And these guys, they have their vSwitch, and these guys, they have their DVS. Now DVS will be common for all the hosts, correct? And that's the use of DVS. DVS having global view for all the host and the networking. But these hosts, they may have their local switch. So VSS, say for example, VS0, VS0. Now again, where we are going to use the port groups, that is also very important. So let's just understand all these things. So let me go to the host and cluster. Inside host and cluster, if I go, let me walk you all these things. So I'm inside, say, host 1, and if I go and click, say for example, you have configured. So first of all, let's start with configuration. Inside configuration, you can see you have the networking tab here. Inside networking, you have virtual switch. So what type of switch I have inside the ESXi or the host? Virtual switch, VM kernel adapter, physical adapter, and TCP IP configuration. Now this VM kernel adapter, you think this is related to control plane traffic. Control plane traffic. This physical adapter that is going outside, this is nothing but uplink, correct? Control plane traffic, it is going outside like that. You have to think now. So you have the host, you have the control plane adapters, you have the uplink, and then you have the virtual switch where you are connecting your VM interfaces or VM NIC, or generally we are telling VNIC. We'll see, we have one diagram. We'll check that. So VNIC, virtual NICs, we are in VM, we have virtual NIC, we are connecting with the virtual switch. Now this switch, this virtual switch may be a standard switch or maybe distributed virtual switch, correct? So let me go and show you that. So I will go here and click virtual switch. Once I click that, you can see here inside virtual switch you have two category of switch. One category is this distributed virtual switch. Other category is standard switch, that is the V switch. Now on the top you have the option you can add network and add those switches. We'll see later on. But because this particular section is focused on vSwitch, standard switch, so we'll explore on that. But suppose if I go and click this distributed switch, let me expand this. Now here you can see that this particular virtual switch is connected with different type of network interfaces. So we have the ESXi region, it's just the name, belonging to VM kernel. This is not attached with any VM. So you have different networking, and these networking interfaces, you can think these networking interfaces nothing but as a port group, correct? So here you can see that you have one of the port group that is nothing but a VM region, VDS.com. This is just the name. It attached with one of the virtual machine, that is Windows 10, correct? Now here you can see clearly that this Windows machine, this is a part of port group or the networking. They have their VNIC is connected here.
that is pinned towards two uplink. Now these uplinks can do the NIC teaming, load balancing, etc. etc. So many features that we can achieve with the grouping of uplink. But this uplink that is inside one of the group, one of the networking, they are part of uplink region 01 network. So you have 1, 2, 3, 4 and 5 different type of network inside this particular distributed virtual switch, and the name of this particular distributed virtual switch is nothing but region A0 VDS comp. So before showing you this section that is the standard switch, I want to show you one very important thing. So if I go here and click networking, either you can go and click there or you can go to the menu and you have this networking. Either way is fine. So once you are inside the networking, you can see here that you have the switch. This is the DBS switch. Inside that you have the groups, correct? So inside that you can see that you have different network. This is the one way to see this. You can see distributed switch. This is actually the port group network. You have some uplink. So uplink having two hosts. This is the switch, and this particular switch is combined or can be combined with multiple hosts or the ESXi, correct? Now let's go back. We'll go to the cluster here, and inside the host, again I want to show you some other things. So suppose I'm jumping ahead of the time. Suppose in this place, if I go and click network, you can see here the network. So you can see you have the network distributed port group. You can see distributed port group. Then you have uplink port group. Then you have the standard network. We'll see this also. What does it belong to? One of the VM is part of this particular standard network. This is actually belonging to our switch, our standard switch. Then you have distributed port group, distributed port group. So you have port groups. You have uplink port group, and one VM network is there. This also I can think as a port group at the moment. It's like this. Now, before moving further, let's quickly go and check the vSwitch, because I'm very much interested in the vSwitch. So I'll go to host configuration and the vSwitch, and let's see the standard vSwitch. So now you have on a standard vSwitch, you can see one uplink and one of the VM, vNIC. So one vNIC connected with one uplink. This is nothing but Tiny Linux, correct? Now if you want to see more detail about this, you can go and check the MAC address adapter type. You can go and check the properties related to that. All these properties we'll discuss in the upcoming section. But yeah, what are the things you can do with the standard switch? Now you can put the security features like promiscuous MAC address changes for force transmit. By default, you can see these are the default settings. Traffic shaping option we can do. We have the NIC teaming. At the moment only one NIC is there, so we'll not do any load balancing type of thing or teaming type of thing, correct? So here you can clearly see that you think that you have your host one. Say this is my host one. Say host one. Let me write it one more time. Host one. This host having DVS, but this has a vSwitch as well. Now this vSwitch, and obviously you have the VM as well. One of the VM, that name is Tiny Linux. One of the VM port, that is nothing but vNIC, is connected with the vSwitch 0. And this vSwitch 0, you can see that they are tied with one of the uplink as well. The uplink is nothing but VMNIC2. Okay, so first of all, let's see that this particular guy, this particular host one, having how many uplinks. So if you want to see this, you have to go here to the physical adapter. You can see that it has 0, 1, 2 and 3. This 2 is connected with this particular access switch for the moment. I'll give the name as an access switch. So this is your standard switch or access switch. Here you can see. But two other NICs, say for example, the physical link, say VM NIC 0 and VM NIC 1, they are connected with these DVS. So they are connected DVS, but still I have one VNIC that is called VM NIC 3 that is not assigned anywhere. So what I will do, I'll go and attach this guy here. Okay, so let's do this operation. I'll go and attach this leftover VNIC to the standard switch, and then we can do certain operations. Correct. But at the moment, I think that you are able to understand that how this local switching or how the access or the standard switch and DVS is working. Correct. So here you can see you have this option of add the network, but I'll go to this switch. If I'm here in the virtual switch, I can click add network. When you're adding the network, again you can see now we are going in depth. Again you can see you have option to create VM kernel network adapter that is related to control traffic such as vMotion, ISKG, NFS, FCOE, fault tolerance, vSAN and host management. Other thing, you have the virtual machine port group for a standard switch. You have the physical network adapter. Because I am focused on virtual switch, so I'll do one thing, I'll use this. Now suppose if you want to create a new standard switch, you have option here that you can use the existing. So I can go and use this guy vSwitch 0, that is my existing switch, and then I'll go next. Now the network label, I'll leave this as default. I'll leave this WLAN ID as default. I'll click next. Ready to complete, finish. Now you can see, first of all, what I have shown you here is that I simply went on and added the extra network here. So I have added, say, VM network and then VM network 2. This is nothing but a local port group. You can think this is a local port group local to this particular vSwitch. So once I have created this, then what I will do here, so now we have two port group, local port group. I can go to the tiny Linux here. If you go here, you can go here and you can click, do right click here, or you can go to the configure also. So tiny Linux and configure, I think in configure also you should get the option related to add the VM, but we are not getting it here. Configuration, never mind. You have multiple ways to do the same thing. What you can do here, let me check the action also if I get, yeah. So you can do like this. You can go to the action, you can click edit setting, or you can do right click here. You can go to the edit settings, and now if you see here, browse, you can see your VM network 2 has been created. You can add this. So this is what we have done. Now let me go back to the network. First of all, now you can see that it is connected with network 2. So let me go back one more time because I want to add two network. So for that, what I can do here, that okay, I'll roll back to VM network first. This is with the local switch, and then add new device. Let me add one more network adapter, and this network adapter, this time I will add network number 2. Okay, so now what is happening, we can go and check the task as well. So we have successfully added extra network. Now when we are talking about these networks, even we'll see later on, not with the standard switch, because we are not going to do much things in the standard with respect to a standard switch. Whenever you see the production network, you will find only distributed virtual switches, and those are heavily used. So I'm not stretching much inside this, but still you can see that you can go and add the standard network. So if I go down here, you can see that now inside that we have two network here. What about adding physical network adapter? So let me go and add the physical adapter as well. And so let's do this. I'll go to the physical adapter. I have one of the physical adapter that is unused. I can click this. I can click edit, and let's see, edit. I can simply change the speed and duplex, but I'll do one thing. I'll add the network physical adapter. Let's add the physical adapter now, and physical adapter with the existing switch. I have this V switch. Okay, we'll go next. I have this. Let's click if I have any unused. Yes, so I want to add this VNIC 3 there. So now you'll see initially in that vSwitch we have one uplink. Now you have added one more uplink, and here's the trick. So what you want? You want active standby, or you want active like this? You can see all the properties, or you want to do the unused. So for example, I want active. Then you can see you have all sort of properties here, CDP, LLDP, all these options we have. We'll check this later on, but I can go next here, finish. So once I finish this, now you can see these two physical interfaces part of vSwitch. I'll go quickly back to the switch, and inside the switch you can see now you have two. You can see. So clearly you see that how I have added the VNIC, virtual NIC, and then added one interface inside the VM machine, and both the interfaces you can see here, they are part of the NIC or the port group, and then the port group related to physical interface, but it's the physical interface. Use as active. You have option, you can use this as a active standby as well. You can go and check the settings. So I hope you understand how we can do the operations related to networking. Now on the top you can see manage physical adapters, add the networking. So from here also you have the option. So multiple options you have when you are adding the VM kernel for this particular switch. So that option also you have. Okay, existing standard switch, if you are adding the VM kernel name, what is the IPv4 address, what's the use of this, it's the vMotion or whatever is the management interface, obtain IPv4 address automatically, or you have any address that you want to put, you have any subnet mask you want to put, you have the default gateway and all. I'm just showing it for an example. So enter a valid subnet mask. So I'll do one thing, I'll give 24. I'll do this thing, we'll use this notation, but it is not telling you that in which format you have to put, etc. And finish. This will fail because this is the wrong address and all, but let's see what error we are getting. So we can go and check the alarm and events as well, that what errors we are getting adding this particular VM kernel NIC. Occurred during host configuration, and we have error because that IP is not existing and the other stuff. But I'm just showing you that from here also you can add. If you want to edit anything, you can go and do the edit. So with respect to vSwitch, I can go and change the properties. I can go and change the security setting like MAC address changes, force transmit. We'll see all these things later on. What does mean? What is the overall? So for example, use of this and the definition of this we'll see in the upcoming slides. Load balancing method, you can see you have plenty of load balancing method like IP based, MAC based, virtual port, etc. Fallback, notify, and the failover order. Then if you want to click manage, you can do up and down. So this is actually all the operations related to local switch. And this actually we are not using much, but it's good that we understand that how we can add, delete, change, modify, etc., etc. So how we are doing n number of operations related to this. But our more focus will be on the distributed virtual switch. So let's stop here, and upcoming section will again learn more about the virtual networking. Let us discuss the port group properties. Here you can see that we have the properties, security, traffic shaping, and the teaming and the failover option. When we are inside security, we have promiscuous mode, MAC address change, and the force transmit. And the order that we can select, or the options that to select, is accept or reject, correct? So let's see one by one. In case of promiscuous mode, if it is uh, chosen as a reject, that means there is no effect. But if you accept this mode, that means you are detecting the frames with respect to whatever policy you have configured for that particular port group, or for that particular adapter inside the port group, correct? So if it is accept, that means you are detecting all the frames passing through the vSphere standard switch. You can see the default setting here. The default will be like this: promiscuous is reject, MAC address change, and the force transmit is accept, accept. So let's see what is there in the MAC address changes. In MAC address change, one thing to note here, that the vSphere, that is inside the VMX configuration file where they are storing the MAC address. So suppose if they see that any change inside the MAC address, means if you make this as a reject, if any change in the MAC address, they will start dropping the traffic. Rather, if you make this as a accept, that means in that case they will allow those frames. So what is happening here? Changing the MAC address from the guest OS has the intended effect. Frames sent to the altered MAC address are received by the virtual machine. So even the MAC address change is there, the frames will be passed. Force transmit, reject means, again, force means someone is doing some sort of spoofing in case of MAC address. So here what will happen, and this is again applied to the outbound frame. So any outbound frame with a source MAC address that is different from the one currently set in the adapter is dropped. So if while doing the transmission of the frames, it will see what's the source MAC address, what is set in the adapter, and if it is reject, it will drop that. If it is accept, it will allow that. So it depends that what security policies we have. According to that, we can accept or reject. Alright, traffic shaping, it's very much like Cisco configuration, Cisco traffic shaping, or the QoS configurations. What is happening here, that you have, say, average bandwidth, then you may have certain peak bandwidth, so say peak, and then if you are going or for some slice of time, if you are going little bit up, then you have burst traffic. Okay, so these are the normal actually option inside the Cisco QoS as well. What is the standard, what is the peak bandwidth, and how much you want to buffer in case of the burst. Okay, all right. Then we have the important thing, that is the load balancing option and the failover in case of teaming. So here you can see that we have multiple options. I think we have 6 load balancing options here. So let us see all those load balancing options one by one. So first load balancing option, here you can see that route based on the originating virtual port. Now what will happen, that the select an uplink based on the virtual port ID on the switch. So once they select the uplink, then they will stick some sort of pinning type of option. You have 2 or 3 uplink, you select one of the uplink and you are sticking with that. That's the default load balancing option we have. Then we have the route based IP hash and the MAC based IP hash. This is very much like if you are comparing this with the LACP port channel. in switch when we are creating the ether channel. So at that time they can do route based, they can do uh, sorry, they can do IP MAC based, they can do IP MAC port address based. Means there are also so many load balancing methods in case of LSCP and PAGP, that is the Cisco Ether channel term. There are here also you can see that you have a route based IP hash, means you are checking the hash value of the source and the destination IP, and then you are sending the frames over the uplink. Then same thing with respect to MAC also we have. Then we have the load balancing option with respect to NIC load. So suppose if we have two NIC, one of the NIC having load 30%, one have 10%, automatically load will shift to the other NIC. So this is also a nice feature. Then we have explicit failover order, means according to the high interface number, suppose this is number 2, this is number 1, you are always pinned to number 2. So what is happening? Let me read. From the list of active adapters, always use the highest order uplink that passes the failover detection criteria. And this is no actual load balancing is performed in this option. Obviously, this is something like user defined. You can go and define the load balancing method. So once we have the load balancing methods, then what options we have? Rest of the options you can see we have the network failure detection, link status only or beacon related. Then you have notify switch and fallback. Link status means it's very flat. If link is up and down, it will tell us, oh, this particular link you are sending the traffic is down, use the other link. Then you have the beacon probing. This is a smart, intelligent way to detect the link status. So 1, 2, 3, whatever number of links we have, we are sending the probes after every 1 second, and we are checking that okay, link is up or not. And then if it is not up, obviously the traffic will go to the some other direction. Very much like we are doing in Cisco also, but generally we try to check the ISP link. So we have some sort of IP tracking SLA type of thing in Cisco. So you are checking one link up to with respect to other link, sending some sort of IP, ICMP, unreachable type of beacon or probes, and you're checking that link is up or not. If it is not, if it is unreachable, after every 1 second, you're sending the probes with, say, for example, hold down timer of 3 seconds or 5 seconds. If it is not responding, you can go to the other direction. Notify switch. We have this option, specify where the virtual switch notify the physical switch in case of failover. So if any failover, it will notify the switch. And then finally, you have this failover option. This is also very logical. Failover option, you have the fallback is set to yes if fallback is set to no. So suppose if you have two link and fallback is set to yes, suppose this link is down, this will become active. Suppose if this link will come back, this will become active standby in case of active standby. So whatever original state of the link was there, once it will get recovered, it will start forwarding the traffic. And that is not the case in the if the fallback is set to no. So what will happen, that two links are there, active standby, this is gone, this standby become active, or maybe active. So now he is the primary who is sending the traffic. Now suppose if this link will get restored, still it will sending the traffic until unless something will happen here, and then it will become active and sending the traffic. So these are the failover fallback options we have, and these are all the options we have inside the vSwitch. You can see still we have multiple options related to security, traffic shaping, teaming, and failover. This recording session is going to be very small. We are going to understand about a distributed virtual switch. And now suppose if you see this diagram, now this diagram is a little bit confusing, but let's come back to this diagram after this. So now if you see this particular diagram, you can see that the distributed virtual switch having host wide visibility. So all the hosts, they can connect with the distributed virtual switch, although these hosts, they have their own standard switch. This particular own standard switch, you can see that they have a VM kernel NIC, they have uplink, these are nothing but a physical link, you can think VM NIC as a uplink, and they have a VNIC, that is VM hosted NIC. So if I draw this diagram, you can understand, say you have guest operating system. This is nothing but the guest OS and hosted over the host. So you may have multiple guests. All these multiple guests, they may be part of this vSwitch. Here you can see, just for an example, it is shown like this, and they may be part of DVS. But what is interesting and important to note here is that you have VM kernel NIC, you have VM NIC, you have VNIC. So you have three different type of NIC. You have NIC for management, you have NIC for uplink, you have NIC for virtual machine, correct? And the difference here is that this distributed virtual switch has a global visibility. So it will be visible for all the hosts. Now here you can understand this diagram now. So let me change the color of my pen. Now here you can see that you have the physical interfaces here. Now these physical interfaces are nothing but VM NIC. So you have VM NIC 1, VM NIC 2, here you have VM NIC 1 for this, VM NIC 2 for this particular host. Like that you can think. And you can see the uplink. Now you have the VM. So this particular VM, what is the name? This is nothing but VNIC. So they are VNIC, they are VNIC, VNIC, VNIC. So they are VNIC, they are VNIC. Now you have the distributed virtual switch. Here we have the port group A, B, C, D, etc. Now in the diagram you can clearly see, suppose this A belong to HR. A is a placeholder for HR. So these two VMs, they are belonging to HR group. So these two guest operating system, they are, for example, HR server 1 or HR server 2. Okay, or generally we are giving this name like web server 1, web server 2. Okay, then you can see that you have VM, and here it's showing like this, but you have VM with multiple VNIC. So here I have VM with two VNIC. They are part of, for example, this is app server 01. Then you can see the other host inside the cluster. So they may be, all these hosts are part of DC cluster 01. So other side that VM, they have their VNIC. This guy having the VNIC, they are part of one of the other port group, that is nothing but DB. So this VM name is, say, DB, I'll write DB server 01. This is DB server 02. So now you can understand that you can group all those different VMs as per their attributes to the same type of port groups, and then you can apply certain rules, certain policies over the distributed virtual switch inside the port groups, and those will be applicable to all these endpoints or all these VMs. So here you can see the endpoint is nothing but your virtual machine. So either the traffic is going to east to west, or traffic is going from south to north or north to south, but when it is going outside, it is leaving the cluster, or when it is leaving the vSphere, at that time they are using the physical interfaces. So this is actually the important analogy, and I hope that you understand that. You please pause the recording and then you can check these definition. Whatever we have discussed so far, you'll find the same thing written here. Let us do the walkthrough of the distributed virtual switch. So we have one distributed virtual switch. I can go here, I can show you that what's the summary, how to do the configuration inside this distributed virtual switch. So I can go here, I can select configuration, and then we can check the properties. Now here you can see clearly that you have properties related to general properties, advanced, discovery protocol, some sort of administrator contract or contact, sorry. These are the properties we have. I'll log into the switch and I'll show you all these options. Then you can go and view the topology. You can create the private VLAN. You can do the configuration related to net flow, port mirroring. You can go and do the configuration related to health check. So I'll show you all these options one by one. Suppose if you want to set some of the properties. So what you can do here, you can click to the configuration and then you can go to the properties. You can click edit. Once you click edit, then you will get the option general and advanced. In general, you can go change the name, you can go and change the total number of uplink ports, your IO control, you can make it disable, enable, you can put the description, correct? Then what is the meaning of uplink? You can add more number of uplink, you can add more number of ports, you can give this enable or disable for the IO control, you can put the description. Then suppose if you go inside the advanced option, here you can see the options related to MTU, multicast filter mode, discovery protocol, administration contract. Now MTU we can go increase or decrease, means depending upon the use case. But in multicast filter mode, you can see that you have two mode, basic and IGMP MLD snooping. Basic means from the IPv4 address, it will make out what is the MAC address, and then it will forward the traffic. In case of IGMP or MLD snooping, as per their IGMP membership, they will forward the traffic. Discovery protocol, we have two options, CDP, LLDP, and disable also. So suppose if you are using CDP, Cisco Discovery Protocol, you can see here the CDP, LLDP, and disable as well. So if you are using CDP, you have option that you are the listener, or you are advertising, or you are listening and advertising both. We can go to the health check and again we can click edit. Once you click edit, then you get the option related to VLAN and MTU. What is the state? What's the interval? These intervals are in minute. The teaming failover, what's the state? What's the interval? If you want, you can change those values, correct? So what I'm going to do before moving further, let me go log into the vSphere client and I'll show you all these options where we'll find. All right, so I logged in inside the vSphere client. What I can do, you have option. You can go to the menu. You can go and select the networking. From here also you can see the networking. So let's go and go inside the networking. Inside network, I want to check this switch. Inside switch summary, you can see that switch detail. So how many network you have? This is nothing but your port group. How many hosts you have, how many virtual machines are connected, how many ports are there. Then if you have any nodes, then if you have any tag, what features you have, we'll go and see all the features. So IO feature, net flow, you can see all these features are supported. Net flow supported, LLTP supported, link aggregation control protocol, that is basic support, port mirroring supported, IGMP MLD snooping supported, health check supported, and then you have the custom attribute. So how you can go and configure this, go and click to the configure. We are inside the setting and properties. If I go click edit, here you can see that I can go and change the name. I can change the number of uplink ports. I'll leave this as 4. Then you have the IO control. You can enable, disable. If you want to put any description, you can put the description. Then we can go to this advanced option. We have the MTU option. Here you can see the multicast option, either the basic or IGMP MLD. Then the discovery protocol, we have option LLDP, CDP, disable. Then the operation, what operation you want. You want listen, advertise, both. We can go and give the administrator contract name and the other details. Apart from that, you can see inside the setting, I can go and check the topology. This thing actually we have checked earlier. So earlier, uh, previously we went here and we have done the walkthrough. We have seen the port groups and the VM. Basically, they are nothing but uh, VNIC and VM kernel interfaces, and these are nothing but the uplink interfaces that's belonging to the physical interface. So you have the topology. Then if you want to create the private VLAN, like in Cisco, we have private VLAN type. So for example, a community, isolated, promiscuous, etc. So I can go and create VLAN inside VLAN that will work as a second. Here clearly you can see primary VLAN, secondary VLAN, VLAN type. So we can go click edit and we can define that. What's the primary VLAN you want to add? What's the secondary VLAN you want to add, etc. etc. Correct? And you can see the type is by default promiscuous, but here you have options. So let's see that the options that we have, it is creating. So once I click here plus, you can see I can go and change the number, say for example 30, and this is the secondary VLAN. What's the VLAN type you have? So if you click here, by default it is taking promiscuous, but I'll not go deep inside this. I will leave this at the moment as it is. So I have primary VLAN, I have secondary VLAN. You can see primary VLAN, secondary VLAN, both are 30-30 like that. Then we have the net flow, very much similar to the Cisco configuration of net flow, who is the collector IP, collector port, what's the domain, switch IP address, and then you have the collector sampling, inactive or active timers, etc. Then we can do the mirroring. This is nothing but the span or ER span like in Cisco we have. So if I go and check the options, you can see clearly here that you have the port, distributed port mirroring, remote mirroring source, remote mirroring destination, encapsulated remote mirroring source. So we have all those options related to port mirroring. Finally, you can go and check the health alarm. So VLAN and MTU, teaming and failover. So I can go and check this health check, the state for VLAN and MTU. You can go and enable. This is for 1 minute teaming failover state. You can go and enable, you can click OK. This is the setting that we can go and do inside the vSwitch. Later on we'll add the rest of the things as well, but you can go log into the vSwitch, you can go and check most of the features, and here you can see the difference now with the standard switch and the distributed switch. In the distributed switch you have so many added features. So you have private VLAN, you have net flow, you have mirroring, health check, etc. So that's why this distributed virtual switch is actually important and popular in the production network. Now we are going to learn that how to create the distributed port group. It's actually very easy. I can go to the distributed virtual switch, right click, and then I can create this distributed port group. So I have that option. I can go and give any name. I will give any logical name. Then we have the configuration setting. What's the port binding option? It is static or femoral. What's the port allocation option? Is it elastic or fixed? Then number of ports, then the resource pool, VLAN, some advanced option. So what does it mean by port binding? Here you can see the first option is port binding. Either we can use a static, so statically the VM interfaces or VNIC, I can go and attach with the distributed port group, or there is no binding, that is the femoral port. Then in the port allocation, you can see you have the elastic option, you have fixed option. Elastic means that is the default option. By default, you have 8 port assigned. If that 8 port will get assigned, it will create again 8 ports. Fixed means the default number of ports is set to 8. No additional ports are created when all the port will get assigned or exhausted. The number of ports, we can go and give the number of ports. Then we have the option related to network resource pool. Why we are using this network resource pool? If you have created a network pool to help control traffic, you can select this. Just for the control traffic, we have this option. Then in bottom, you can see you have the VLAN type. So VLAN type may be none, uh, trunking, private VLAN, etc. So whatever option we have over the interface to the VLAN, we can go and assign it, very much similar to Cisco interfaces where we have switchboard mode, access, trunk, and add some uh, VLAN over the trunk, etc. Then we have the private VLAN option also in the switch interfaces. So we have all those options. Then finally, you have the advanced option. Select this checkbox to customize the policy configuration for the new distributed port group. So if you want to customize, I can go here and use the advanced option. Here you can see advanced, check this, customize default policies configuration. So like that, we'll go and create the port group. Once you create that, you can go and check inside the VM networking. This new port group will be created. Now next, what we can do, we'll go to the topology section and we'll see that where exactly this port group is. You can go and check that port group. Not only you can check the port group, but what I will do in the activity that some of the VM with the VNIC I will assign with this particular port group, and then we can see that the VNIC, how they are mapped with the VM NIC or the uplink. Correct. So those things we can go and see. Also here you can see in the diagram that you have the VM kernel ports. You have the VM kernel port with the different port groups as well. All right, here you can see this tiny URL is the VNIC is mapped with the VM NIC. So let's log into the vSphere client and let's complete this task. All right, so I logged in inside the vSphere client and we are inside the VM network. We are inside the network option. So here you have the network. Here you can see that you have the distributed virtual switch. Simply go and do the right click. You can create the distributed port group. Yes, I want to create the port group, although I have option to import the port group, manage the distributed port group. So I don't want that. I can give the name, say I'm going to use this as a, say for example, I give name as a tiny web server group. Okay, location is this particular switch. That's okay. We'll go next. Then you can see the option. You have the port binding, a static or ephemeral, that is no binding. So static and binding, you have elastic and fixed option. By default you have the 8. After that it will go and add. Network resource pool for network control traffic, we'll leave it. VLAN type, I'll leave it as a none, but you have the VLAN trunking, and the private VLAN option. Customize default policy configuration. If you enable, then you can see that you have traffic shaping, teaming failover, monitoring, miscellaneous. All those customization option will get appeared. So I'll make this on, so we'll understand, we'll see all those options as well. We have already discussed about promiscuous MAC address and the force transmit. And let me go back. All is reject, reject, reject. I'll make this as a accept for the moment, as we have checked in our last section. Then the traffic shaping, at the moment I'll leave this as it is. Then you can see that you have 4 uplink, all are active. The default is route based on the originating virtual port. That's the load balancing default method. Then you have the network failure, link status. You have probe also. We have study about this. Notify switch, yes. Fallback, yes. So it will restore the original status of the interface if it will get fallbacked. Then monitoring, I will not use NetFlow at the moment, but if you want, you can go enable and then you can use it. At the moment, I'll make this as a disable. Then you have the miscellaneous option. Inside miscellaneous, block all ports. Option is yes or no. We'll leave this. Next. So now you have your distributed port group with all those options. And now here you can see that you have tiny web server. This is attached with 2 hosts, that is 2 hypervisors. Network protocol profile is not there. Rest of the things are not there at the moment. So here you can see that it is attached with two hosts, but suppose if you want to attach the host here, we'll see that. I'll show you that how to do some sort of manipulation later on. At the moment, what I want to show at this point of time is that once you create the distributed port group, first of all, I want to go to the switch and I want to show you, let me go and show you the changes that happens. So if I go here, now I can see this that the network is 6. So 1, 2, 3, 4, 5, 6. 5 plus 1, initially it was 5. Rest of the things will leave this as same at the moment. I can go to the configuration. Inside the configuration, I want to show you this topology option. Once you are inside the topology, if I scroll down here, you can see here. So you have this tiny web server group as per the alphabetical order they have taken. So E, S, and then T, and then V. So now what I want to show here is the few of the port groups. So for example, this particular port group, that is VM regional A0 VDS comp, having two virtual machine, Tiny and the Windows. And now they are mapped. So they are mapped from here up to this point, correct? If you want to see the setting, you can see it. So what I want to do here, that I want to remove this Tiny and I want to attach this Tiny here. So you can see that the number of virtual machines will increase, correct? So that will be the valid test. What I can do here, multiple ways we have. I can go to the host cluster or maybe VM and templates, because I'm looking for the Tiny, Linux, and the two, both I am looking for. So what I can do here, I can go to the edit setting. That's the easiest way to reach there. I can go to the network controller. I can browse this, and now you can associate with the Tiny web server. Remember, port group is the same type of attributes, same type of properties that you are connecting your endpoint or the virtual machine interface to this particular group, correct? So I have done this. Once we've done this, then I'll click OK. Then I'll go to this Tiny 2 as well, and there also we'll go to the edit setting. Once we are here, instead of VM network, click browse, and then I'll go and use this Tiny web server group. Okay. Then we'll go back to the networking and we'll go to the switch, configure, and topology. We are already inside the topology. Now you can see this Tiny URL. Two are connected, correct? To VNIC going to this particular uplink, and if you want to see this uplink and the associated host, so this host has these two uplinks, this host has these two uplinks, VMNIC 0001, like 0, 0 and 1, VMNIC 0 and 1, both the hosts having those. So like that, you can see that it is mapped. Few of the uplinks, 3 and 4, they are unused. Few of the uplinks are in use. So this is the way you can create the port group. Once you have the port group, how you can go and attach the VM interface with the port group. And if you want, you can go and verify from this particular configuration and topology option. All right. So I hope you understand up to this point. Let's stop here. Next section we'll do more lab related to this. Let us create a new distributed switch and then we'll add some ports and VM, etc. So let's try to complete this activity. So to create the new distributed switch, what you have to do, you can go to the data center. You can see I have the data center, and then I can do right click, but there are multiple ways to do the same thing. So I can do the right click here, and then I'm getting this option, create distributed switch. So inside distributed switch, we have the option to create it. Or suppose if you can import also, you can create new also. Then we'll go and give the name. We are using 6.6
and the ESXi version is 6.7 and later. So you'll get the option. What is the configuration option? How many uplinks you are putting? What is the IO control? What is the default port group? So create a default port group. The port group name is D port group. So with the switch, we are creating one default port group as well. Now, once you are here in the ready to complete, you can see the summary and then you can click finish. So now you can see how easy it is to create a DVS, distributed virtual switch. Simply we can go and with a few clicks, maybe 4 or 5 clicks, we can go and easily create a switch. Now once I have a switch, so what's the logic here now? That once you have the switch, and sometimes what is happening that we are importing that switch from the ACI. So inside ACI, when we are doing some sort of VMM integration, at that time we have that VMM. So I have created a virtual switch inside the ACI from ACI, application centric infra from Cisco. That vSphere, they will download that switch. So either that's the case, or like we have created the new switch here. In both the case, once you create the switch, then you have to add the host to this particular switch. So this is a flat switch without having any host attachment. So I can go and add host 1, host 2, host 3, etc. Correct? So once we have the switch, I want to add the host, the ESXi hypervisors. So here you can see I have a new VDS. I can click add and manage the host, add the host, manage host network, remove host. Now while you are adding the host to this particular switch, this is the switch we are going to add the host. You can see you have option that manage the physical adapter, manage the VM kernel adapter, manage the VM network, and then its summary. It's ready to complete. So one by one you go add the host. Here we have two hosts, ESXi1 and ESXi2. You can select both. You can add this with this particular switch. Once you add this switch, then you have this option called manage physical network. Now what you can do that whatever unused interfaces you have, physical interface, that is nothing but the VM NIC. We have discussed already this thing. You select this, assign uplink. So you have to select and assign as an uplink. You can go and select this. So here you can see that one of the uplink where I have the VM NIC 3 assigned. Like that we can go and assign it. Then apply the uplink assignment to the rest of the host. So this uplink will be assigned with both the host 1 and host 2. So here you can see that, okay, I'm assigning the uplink that is nothing but VM NIC 3 with host number 1, VM NIC 3 with host number 2. And that's why even in the previous section also you have seen that VM NIC 0, VM NIC 1, they are part of host 1, and similarly VM NIC 0, VM NIC 1, they are part of host 2 as well. So in this case what will happen that VM NIC 3 also part of host 1, and VM NIC, nothing but the physical interface, also the part of host 2. This thing will happen, correct? But the moral of the story is that you select these interfaces, assign it, that's it. So you have to go select it. So suppose now you are selecting the VM kernel interfaces, you select this and assign it. Then it will be attached to the host. Alright, so like that we can go and attach. Then finally you can see that migrate the VM networking. So here you can see that few of the VM virtual machine, they are attached with other host. Few of the virtual machine, they are attached to the other host. If you want to do it now, you can do it, but later also I can come back and I can go back to the VM and I can do this association. So it's very easy and straightforward. Once you do that, ready to complete, and you are done. Once you do that, then you can go and verify as well. So I can go inside the VDS and I can check the host association. If VMs are associated, I can go and check the VMs. If you have the port groups, you can go and check the port groups, like that. configuration, we can go and check the topology and all. So this is the way that we can go and create the new virtual switch. So what I will do now, that I will go and log into the vSphere, and from there we'll go and create this. Alright, so I logged in inside the vSphere client, and what I can do here, you can see that you have the site A data center, and if you go and right click here, you can see you have add host, add cluster, etc. But what we want distributed switch, new distributed switch. So click there. What's the name? I can give any logical name, so I'll give this, say for example, VMM, and with other. I can give any name, correct? Okay, what's the location? This is located as the site A data center. No problem, we'll go next. Now you can see that we have the switch version and the ESXi version. That's okay. Then number of uplinks, the IO control is enable. The default port group, we want to use this default port group. If you want, you can change the name as well. So what I can do here, I can go back, I can use this name, I can come back here, and I will make this as a VMM distributed port group, so DPG, any name you can give. Then you can click next, and now you have the summary. Very easily you have created one more switch here. This particular switch having the network, so you can see here that you have the DPG and you have the uplink as well. So it's actually very interesting to go and verify the network related to this. I'll come to this topology as well, but if you go if you want to see here, you can see that you have the distributed port group. See, they have created with very default configuration, and we have the uplink port group. So whenever you are creating the new distributed virtual switch, at that time all your uplinks, whatever uplinks, so in this case we have, say for example, 4 uplinks. All those 4 uplinks, they are part of one port group. The name is very much similar that whatever we have given to the switch, and then you can see the name as well. So you can see the VMM with other DV uplink 262, and if I want to go inside that, we'll go and check more inside this also. But what is happening here, that those uplinks, so let me show you the topology so you will understand this, what I try to explain here. I can go to the switch and the topology. You can see all your 4 uplink that you have added, they are part of this port group. This is my, for example, this is my physical interface, correct? And then I have one port group. That port group is associated with or I am going to associate with the VM interfaces. So it will be used as a VNIC, and this will be used as a VMNIC, inside and outside. Very easy and straightforward. Now if you want to do any changes and all, everything we can go and do with this particular switch. All these options we have. So if you want to change any LSCP thing, you can go and change it. There is no problem. Load balancing and all options are there. If you want to add net flow, you can go and click add net flow configuration. There is no problem in that. So that's the thing. You can see that now if you compare with the standard switch and the DBS, you have plenty of options here that you don't have inside the standard switch, correct? So I am very much here want to show you this topology because now we have the visual representation, correct? So what I want to do, I'll go to the VM and say for example Linux, Tiny Linux 2. This particular guy, if you go and check the network related to this guy, he is belonging to this particular port group, correct? Tiny Web Server group. What I want to do here, I'll right click here, I'll go to edit setting, and then this network adapter 1 I want to attach with the new group that we have created.
So what is our group name? Let's see. Here you can see that storage, tiny VM. I don't have that group here, correct? Why we don't have group showing here? Because the reason behind this, so once you created this DVS, the distributed virtual switch, and if you go to the host, you can see it is not attached with any of the host, any of the ESXi. So first of all, you should go and attach this with this host. So what you can do, simply right click here, and then you have option attach host. So let's see, we have the edit setting and all those things also, but we should get the option related to attach the host. And you can see add and manage host. We have this option. So what you want? You want to add host? Yes. Go next. What are the hosts you want to add? So go and click new host, and you can select one or both. Now with this particular switch, we are adding the host. The next option we have is manage physical adapter, correct? So what we can do here, I can click this VNIC 3 because this is free at the moment, and I'll click here, select this and click assign uplink. So if you do that, what will happen? Assign to uplink 1, both the host. So ESXi1 assign with 3 and ESXi2 will also assign with 3. So it should be like this, that both should be assigned here. If not, then you go and you select one by one like I have done. So now you can see that both the hosts are assigned. If you want to unassign, then that option is also there. So one by one, what you can do here, you select it and then assign uplink, and then scroll down and assign the uplink. Like that, we'll go next. I don't want to do anything related to VM kernel at the moment, but if you want, you have that option as well. We'll go next. Then migrate VM network. This migration we'll see later on. We'll go next, and finish. So now once I finish this, I can go and check the recent task. Now you can see the tasks both came here. Consume memory also you can see. What we can do now is that now we can go to the VMs. I'm interested to. Now you can go to the edit setting, and now you will see that port group option. So I'll go here and I can see this VMM with DPG. Click OK, and once you click OK, click connect. So let me do this. You can go and check the recent task. It is completed. If it is completed, then we will go back here and let's go back to the networking. So I can show you the topology option. Now here, if you go and check the configuration topology, now you can see that you have the VM that is connected here, and if you want to see the uplink attached, which interface, so here you can see. Okay, so you're seeing this option. Now from scratch, we created one distributed switch, and then we have created one port group, attached this port group with the VM. We went here, we have attached the uplinks here, and you can see how it can be done. Previously, we have studied that how to change the settings with the uplink, how to change and play around with these port groups as well. So this is a way you can see that plenty of options are there related to this, and we can easily create and manipulate the distributed switches. All right, so let's stop here.
In 2.2 and 2.3, we have to learn about VRF, GRE, IPsec tunneling, Lisp, and VXLAN. So let's start VRF, virtual routing and forwarding. what is the use of VRF? When you are creating virtual routing and forwarding instance, so at that time you can segregate or segment the routing table. So for example, you have one global routing table, and then you may have a routing table for segmented, or for example, you can think like for customer A, you have one, customer B, you have one, customer C, you have one, like that. So it's like segmentation in routing. And what's the use case for that? So you may have business VPN services, network segmentation, data center access, etc. Now, this term that VRF that we are seeing here is actually layer 3 virtualization in terms of routing. But if you see and verify that, do you have any layer 2 virtualization technique? Yes, we have VLAN, virtual LAN, as a layer 2 virtualization technique where you have, say for example, every VLAN having their own spanning tree instance. Every VLAN has its own MAC forwarding table. Likewise, if you go and check VRF, you'll find that all the VRFs, they have their own CIF, they have their own routing processes. Means most of the routing protocols, they are supporting VRF. And in the diagram, you can see that you have one global table, and then you can have VRF. So what we are doing that we are creating a VRF, and then we are associating that VRF to one of the L3 interface. So that means that one L3 interface, or one interface specifically, can have only one VRF. And later in the lab section, you'll come to know about this. Now we have various techniques related to VRF to provide fast switching or fast pathing. VRF Lite and then MPLS. MPLS is quite a bit popular. So what's the idea behind this is that you may have end-to-end segmentation. So suppose if I have diagram, so here you can see that maybe you have one end where you have VRF A and VRF B, and then you want this segregation, or you want this virtual routing forwarding instance to propagate throughout the network, means end-to-end routing instance or end-to-end segmentation. Now, if you go and use VRF Lite, so in that case, whatever devices you have in between, here you can see, although you have only one switch in between, but it is showing green and red, means you have two VRF, two routing forwarding instance, two inside process, or two virtualization inside one box. We can think like that. So the idea here is that if you are using VRF Lite, then you have to go and enable VRF Lite to all the devices. And that's the problem, that VRF Lite, although they are very easy to use, but they are not scalable. So that's the reason we are using MPLS, multi-protocol label switching, where again you are using LDP as a protocol to create the labels and then to exchange the label. Okay, so this is one of the use of the VRF. Although we are going to have, so we are going to perform one lab, and in that lab you will see use of this VRF or front door VRF with IPsec and with the tunneling method. So we have that lab. At this point of time, VRF is a technique where you can create or where you can divide a global routing table into a small independent routing tables, and all these VRFs, they are holding their own forwarding table and the route process. Okay, if you want to propagate it end to end, you can use VRF Lite, but in that case you have to enable VRF Lite and those VRF to all the devices in between. One other thing here, you can see that this VRF, they are supporting encapsulation as well, that is 802.1q. All right, so this is the things related to VRF. We can stop here, and in next section we are going to learn about GRE. Next topic, we have generic routing encapsulation. What's the use of generic routing encapsulation is that you can create the tunnel from one place to other place with the use of GRE. Now, the interesting thing about this GRE is that as long as you have IP reachability and you don't want to expose your intermediate devices, you can create a GRE tunnel from one place to other place. Now, maybe we can think at this point of time, okay, I'm creating the GRE tunnel, so what about security? Now, we can integrate GRE with IPsec as well. We can integrate GRE with IKE as well. So in the lab section, I will show you that not only that will create the tunnel in between two endpoints, so whatever intermediate devices we have, uh, we are going to create tunnel on top of that. The source and destination tunnel will be the endpoints of the source and destinations egress interfaces. In this case, what we are achieving is, first of all, that we don't want to go hop by hop and take the routing decision, although we are directly reaching from one tunnel endpoint to the other tunnel. So we are creating the tunnel. Then for security reason, for security purpose, we can integrate our GRE with IPsec as well. So both the things or both the features we are achieving here, we are doing the routing, we are doing the IPsec as well. Originally, it was developed by Cisco, but later on, it becomes industry standard. And later on in this session, I'll show you the packet format as well. Here you can see that the usefulness of GR is that you can integrate with IPsec for security reason, first thing. Second thing, one of the great advantages of GRE is that it allows routing of IP packet between private IPv4 network which are separated over public IPv4 internet. So that is also very interesting use case we have, that you can create the GRE in between the private and the public network as well. Okay. Now this GRE also supports encapsulating IPv4 broadcast and multicast traffic. So these are the high level features we have for GRE, how this packet format will look like, taken from the RFC 1701, this GRE header. So here you can see that you have certain flags. Let me quickly go and highlight those flags. So we have flag says C, checksum, route, key, sequence, source route. Then we have this recurrence is something like a recursive route. So it is written in short like recur, but this is for recursive route. Then you have the flags, you have version, what protocol type you have. So for example, if you are using IP packet, then what will be the protocol type? Checksum. Now interesting thing here, so that's the reason I'm highlighting this thing, that this checksum, if you have checksum, this field will become 1. If we have routing, this field will become 1. If we have authentication key, this will become 1. If we have GRE sequence, this field will become 1. Okay. Although I have the explanation in the upcoming slides, so let me quickly show you that. You have the checksum, see routing present, that will become R. So here you can see R and routing. Means if your flag is 1, that means you have the routing. If you set the key for authentication, then key flag will become 1. If you have the sequence number for the packets, then this S flag will become 1, and here you can see the sequence number for the GRE packets. Correct. Again, if you have a strict source route, then the small s will become 1. For recursion, control and version number, generally they are set to be 0. A protocol type for IP field, it is set to 0800. Means suppose if you are doing the packet capture to understand that what type of packet is it, if you are getting 0800, that means it's GRE IP packet. Then the checksum, then the key and the sequence number, same that we have discussed. All right. So let's finally discuss the packet format, the normal packet or original IP packet, how it look like, and then when you are doing the GRE encapsulation, how it look like. So once you do the GRE encapsulation, here you can see that your original packet, so you have the your original IP, TCP UDP application layer. On top of that, you are putting the GRE header, and then you have the outer IP header. Okay, so now you can think like this, that you have the inner header, and then you have the outer header. Inner header, that's your actual IP and your payload, and the outer header is the encapsulation with GRE with the tunnel IP addresses. All right, so let's just stop here, and next section we'll start IPsec. Next topic we have IP security. Nowadays you will see that almost all the companies, they are using IPsec, because nowadays we are sending our corporate traffic over internet or public media. So at that time we have to take security measures, like we should provide the authentication, confidentiality, integrity, key management, etc. Now the popular term is CIA, C for confidentiality, I for integrity, and A for authentication. Confidentiality means that your data packet is not seen by other. You are sending encrypted packets. So if someone is still, if they are spoofing the packet, or somehow they have those packets or those files, still they are unable, or it's very difficult to decrypt and get the value of that data. Integrity means it is not altered by others. So whatever you are sending, whatever data you are sending, that other side, they are getting the same information. Authentication means you have the valid source, and maybe you have the valid destination as well. Means two parties, they are authenticating and then they are exchanging the data. Now here you can see in the diagram that you may have two types of IPsec. So IPsec actually has two flavor. One is a remote access VPN, where you are putting the VPN client inside the machine, or maybe it's a client or less, or maybe client full, or you are using site-to-site VPN. Now this site-to-site or point-to-point VPN may be point-to-point or slash point to multi-point. So either it's a IPsec, or it may be DMVPN, or any other type of advanced IPsec methodology. What's the fundamental behind this? That any case you are doing the encryption, you are doing the authentication of the packets, and then you are sending the data from one place to other place. Now IPsec is actually a suite of protocol. It's not an individual thing. It is an umbrella where you have so many other things as well. So you have IPsec here, but you have ESP, or authentication header. ESP is nothing but encapsulating security payload, and the supporting things, we'll see that you have, say for example, phase 1 and phase 2. In phase 1 you have ISA-KEMP policy, say Internet Security Association Key Management Protocol, and phase 2 actually you have IPsec itself, and we are telling it as a transform set policy. You'll see that. So you have phase 1 and phase 2. Inside phase 1 again, you have so many things that you can do in transform set, where actually you are moving the data with help of either ESP or authentication header. Here also you can put various security parameters that I'm going to show you in the coming slide. So let me quickly go and show you phase 1. What are the things you can put? Say for example, in phase 1 you can put the encryption, either days, triple days, or AES. Again, AES having bits, say AES, advanced encryption standard, etc., where you have bit either 128 or 192 or 256. Again, tighter the security, tighter way or tighter encryption methodologies we are using. You can use hash MD5. You can use authentication either pre-share or you can use certificates as well. Then you have the group, Diffie-Hellman group, and inside Diffie-Hellman group, again you have options to choose. All right, so this is phase one where exactly you're building the framework, and then you have phase two, that is the IPsec transform set or IPsec transport, where you are sending the data with the header, so ESP header, and again you are doing the combination of encryption, you are using MD5, HMAC, etc. So phase one and phase two, if you go and check the IPsec there, you will find that not only you have the phase one and phase two. So suppose you have completed ISA camp, and suppose I have two devices. In between, I want to create IPsec tunnel. So you should know, first of all, you should have IP reachability in between these devices. And suppose outside IP here is 111 and here is, for example, 11.1.1.1. So these outside interface should ping to each other, and over these interfaces, you are going to create, or we are going to apply the IPsec policy actually. So phase two is IPsec, for example. Then you have to create the ACL. So what type of interesting traffic you have that you want to put inside the IPsec tunnel, or for that you are creating the IPsec tunnel. Then fourth number, that you have to go and create the crypto map. Inside crypto map, you can define the ACL, you can define the peer, you can define the transform set, correct? And finally, you have to apply over the interface. So these are the steps, but the phase is phase one and phase two. All right, so let's quickly go and check other theoretical aspect. So you have security architecture. Inside security architecture, you have two security header, AH and ESP. We'll go and discuss more about those parameters. Then you have the security association. All the tunnel, they are associated with security parameter index, that is SPI. But this security association having three component: SPI, destination address, and security protocol. Okay, and now this security association have a database of security association, determine IPsec processing for sender, determine IPsec decoding for destination. Essays are not fixed, generated and customized per flow. So per flow, you will find, if you go and check the security association for phase one and phase two, uh, actually for phase two, you can go and check show crypto IPsec essay. We'll see that later on in the lab section. You can check that SPI indexes. Now they can up to 32 bits large, and according to the agreement with the header, what are the things you have inside security association? Inside security association, you have SPI, destination IP, IPsec protocol, either AH or ESP. Correct? So that's about security association. Now let's quickly discuss about AH and ESP, authentication header. It is used for data integrity. Entire packet has not been tampered with authentication. Can trust IP address source. Use MAC to authenticate. Symmetric encryption like this. One-way hash also. They can use anti-reply. They can use integrity check values as well. So what does it mean? Let me quickly show you here in the diagram that this is the actual IPv4 packet. Now you have two mode to use IPsec. You can use transport mode, you can use tunnel mode, correct? Now transport mode is that you are not changing the IP. So whatever IP you have, you can see the packet is going with the original IP. So what you are doing, that you have data, you have TCP field, and then you are putting the authentication header. You are sending with the actual IP, correct? But in case of tunnel mode, and that's the preferred mode, we should use tunnel mode, that cover entire original packet. So here you can see in the diagram, we are covering entire packet Then we are putting this authentication header, and then we are sending the new IP header. That's the difference, but still you can see that we are doing the authentication for packet. So that's why the need of ESP, encapsulating security payload, that will provide message content confidentiality. Uh, Again, this is coming with the encryption. So we are putting extra thing, that is the encryption. Provide limited traffic flow confidentiality, can optionally provide the same authentication header service as AH, support a range of ciphers. So they are robust than AH. They are supporting DIS, triple DIS, RC5, IDEA, CAST, etc. A variant of DIS most common, pad to mid block size for traffic flow. Now here you can see original data, then transport and the tunnel mode. And you can see that we should use this tunnel mode, because when we are using the tunnel mode, then we are changing the IP, means we are protecting the IP as well, because whatever actual payload we have, so here you can see that you have the payload and original IP, and then you have the ESP header. So up to your original IP you are doing the encryption, and up to your ESP you are doing the authentication. Correct? So here we are providing both the features, encryption and authentication, and that's why the ESP is the preferred way that we can do in the phase 2. All right, so remember that we should use the tunnel mode because we want to use uh, gateway to gateway, or we want to encrypt our IP from one gateway to other gateway. We are in the lab section. What we have to do in the lab, you can see the topology diagram here. We have 3 routers. Router number 2 will work as a transit router. So what I'm going to do here is that I'm going to provide the IP addresses over these physical interfaces, and then router 1 and router 3, I'm going to create first of all normal tunnel with respect to front door VRF. So we are going to learn about VRF, about how to create the tunnel. Once we have the VRF, once we have the tunnel created, once we have the IGP up and running, after that I will go and add the IPsec configuration. So whatever we have studied in these sections, these sections like VRF, GRE and IPsec, everything you can see here in this lab section. So let me go and log into the devices. Alright, so we have 3 routers here. You can see router number 1, 2 and 3. And let me show you the IP addresses over these interfaces. So I can go here and type show IP interface brief, and you can check that. So what I have done, that I have created one interface as per the topology and assign the IP. Let me quickly go to the loopback 0 and assign the IP address there as well. Say for example 10.111.10.10.1/24, and you should give like the subnet mask. Alright, so we have the IP address assigned here over the loopback interface, over the physical interface. Let's do the rest of the configuration. So what I want here, first of all, I want to create one VRF. Say name of VRF, I am giving say front door VRF. So front door VRF is the VRF. Now if you go inside that, you can see that you have options that you can define: export, import, route distinguisher, route target, etc. At the moment, what I want to do, that this particular VRF I want to assign to the physical interface. So what physical interface we have here? Now here you can see that we have physical interface gig 0/1, and we have assigned the IP address as well to that interface. Now if you go to gig interface 0/1, And if you assign this, say for example, IPVRF forwarding front door VRF, so FVRF, you will see that it will erase the IP address over that interface. So that means you have to give that particular address one more time, correct? And that's the important point we have. Now if I go and check show IP interface brief, and if I check show VRF, so now here you can see that you have the VRF, and we haven't defined any import export RD route distinguisher or any other things on this. All right, so these are very basic and very initial steps that we are doing at this point of time. So what we have done, that we have created the VRF name called front door VRF or FVRF. We have assigned to one of the physical interface. We have one loopback interface as well. Next, what I want to do, that I want to create one tunnel. So let me quickly show you the diagram. We have this topology, and I want to create one tunnel interface as well, and I'll give the IP 192.168. So let's go and create one tunnel, say tunnel 0, and the IP address is 192.168 1.1 255.255.255.0. This is the tunnel source IP actually. Now over this tunnel, what I want to do, that tunnel source is obviously my physical interface. And what's my physical interface? Gig 0/1. And what will be the tunnel destination? Now tunnel destination I haven't assigned yet, but if you go to R3 and if you check the tunnel interface, that is 222.3. That's the tunnel destination for router number 1. So this will be the tunnel destination, and tunnel VRF is front door VRF. That's the name actually. All right. Now once I created this tunnel, I can go and check the tunnel configuration. This is the tunnel configuration, and then you can go and check the tunnel interface. Now if you go here and check the tunnel interface, the loopback is tunnel, and tunnel protocol is, here you can see that protocol is GRE and transport is IP. So by default, whenever you are creating the tunnel, that will be GRE. Okay. All right. So once we have the interface configured, once we have the tunnel configured, then we should give the routing as well. For this routing protocol, I'm going to use, say for example, EIGRP in this case. So I'll go and start EIGRP. What network we have? We have one network, say 10.10.10.0, and I can give the wildcard like this. Then I have other network 1.0, and I'll give the wildcard like this. I'll do not assembly. So one last thing I have to do, that for front door VRF, I should create a route for that as well. So I'll create one static route for my front door VRF, FVRF, and that is default route pointing towards the gateway. Okay, so here you can see section IP route, or I can go and do include IP route just to check the IP route command, and then we can go and check the GRP as well, and then we can go and check the tunnel 0 configuration as well. So these are the configuration that we have done for router number 1, that is source of the tunnel. Likewise, I'll go and configure the router 2, that is going to become the transit. So here if I come and if I check show IP interface brief, this is a transit router and we have already assigned the IP addresses, so no need to do any further things to that. Now we'll go to router number 3 and we can do the same thing that we have done for router number 1. So here we can follow the process or follow the steps. IPVRF is the name, and then obviously I'll go to 0/1 and then I will forward to front VRF. Then I'll go and assign the IP one more time. And we can verify that. So this is the step number 1. Then in step number 2 that I want to create a tunnel. So interface tunnel 0, IP address for this tunnel as per our diagram. Say IP address is 192.168.1.3.255.255.255.0. Now once we are inside the tunnel, I can give tunnel source as gig 0/1. Tunnel destination will be 1111, correct? That is router number 1 physical interface. And then finally, tunnel VRF is FVRF, and we are very much done. So this is step number 2. I can go and check interface tunnel 0, and here you can see this configuration. Likewise, here you can see the configuration. So we have almost same identical configuration matching. I'll quickly go and enable the EIGRP process. We know the network here. So what network we have? I have network, say 192.168.1.0.000.255. That is one network. And other network is that I want to give this loop back. That is 30.30.30.0. If you go to router number 1, here you can see that you're advertising your loopback, you're advertising your tunnel. Alright, so we are very much done, and next thing we have to do that we should create one default route for the transit router. So that is IP route VRF, front door VRF 000, and what will be the IP for these interface? That is this IP. Alright, so we have created this tunnel. I can see that tunnel is up and we are getting the agency as well. So if we go and check show IP EIGRP neighbors, show IP route, and we are getting the routes. Likewise, if I go here and check show IP route EIGRP1, you can see that they are receiving the route. So this is the very first basic step that we are doing here. We are enabling the VRF, and then we are checking the GRE as well. So you can go and check show interface tunnel, and here you can see that your encapsulation is GRE. This point you can see the source and destination as well. So let's stop here, and in the next section I'll go and add the IPsec configuration in this. We can continue our lab, and now we can add the IPsec profiles in this. So let's start with router number 1. What I can do here, first of all, I'll go and create the keyring. So here you can see that you have crypto and you have this keyring. I can give the name for this as well. So GRE IPsec is the name, and VRF is front VRF. Okay. What's the key you want to give? So pre-share key, and the address for the destination is so 2.2.2.3, and the key I will use, for example, Cisco. Okay, great. Now once we have this keyring, then I'll go and create the SICMP policy. So let's go and create that. Alright, it's a bit slow. We can wait here. Alright, it's back. So now what we can do, that we can go and create the SICMP policy. So for example 10, and then I can go and use the authentication as pre-share. Okay. Now once we have the keyring, once we have the SICMP policy, next I want to create the profile for the SICMP. So let's create the crypto SICMP profile, and the name of profile I want to give, say, GRE IPsec. Okay. So a profile is deemed incomplete until it's matched the identity statement. So we'll go here inside the profile and we'll give the keyring. So keyring is GRE IPsec, and then match identity for the address 222.3, that's the destination address, and then 255.255.255 for front door VRF. So what we have done so far, let me quickly show you that we have created SICMP configuration, and we have created the keyring as well. So better I will use crypto. From crypto you can see everything that we have created. So first of all, we have created this keyring, then we have created ISACMP policy, and then we have created ISACMP profile. Correct. Now these commands we can copy and then we can reuse inside R3 as well, and we can change the address and we can use it. So let's complete. So now we have the ISACMP policy. Next we know that we should create the transform set. So we can go to crypto IPsec transform set, and this also I can give the name as GRE IPsec, but we can give different name as per the standard. I can go and use, say, ESP, and what options we have, say for example DES, and we can give the mode as well. At the moment I'll use mode as a transport. Now we have phase 1 configure, now we have phase 2 configure. Finally I'll go and create the profile for IPsec as well, because this profile I'm going to map inside the tunnel. So crypto IPsec profile, and name also I'll give the same, GRE IPsec. What are the things we can set here? So transform set is GRE IPsec, and then the SICMP profile is GRE IPsec. We are very much done. Let's quickly check the configuration, show run, and then section crypto, because everything is starting with crypto. Here it is. So we have created the keyring policy, then ISACMP profile, then transform set profile, and then obviously the IPsec transform set profile. So this is the configuration. Finally, what we need to do here is that we should go to interface tunnel 0, and inside interface tunnel 0 we can go and match this. So I can go here, use tunnel protection. Once I'm inside tunnel protection, then I can go and apply it. Tunnel protection, and then you can see IPsec profile, that is GRE IPsec. Okay, so I'm not using shared at this point of time because this will solve my purpose. Great. So what we can do here, that now we can go and use this section crypto. What it is telling, this log here, you can see that you have this GRE. You are sending some encrypted packet, but you are not receiving, etc. Because one side you have uh, created this configuration, but other side you haven't done anything. So what we'll do here, we'll go and open the notepad, and we know that other side the IP will be 1111. Rest everything will be the same, correct? So we'll copy and paste this configuration to here, and we'll go to interface tunnel 0, and here also we'll run this tunnel protection IPsec profile GRE IPsec. Alright, so this is the way that we can go and do the configuration. Now you can see this, we are getting the up message. So we can stop here, and next section we can do, or we can run few of the verification commands. Let us run a few of the verification command. So first of all, I want to ping from here to the source or to the other side of the tunnel, and behind the tunnel we have some loopback. So I want to ping that loopback address. My source is loopback 0 itself, and now you can see that I'm able to ping from this source to this destination and vice versa. Let's go and check the phase 1 security association, and you can see that we have QM ideal, that's correct. And now I want to check the phase 2, that is the IPsec SA. Now here you can see that you have tunnel, actually you have two tunnel, inbound and outbound. First of all, you can see that you have the local ident, you have the remote ident, so you have this source and you have this destination. Actually the front door VRF IP addresses it is showing. We have some allow flags, origin in is ACL. Now here you can see that in-cap and decap packets, almost same number of in-cap and decap. That means the transmission is happening properly from both the ends. You can see this local endpoint and the remote endpoint. Few of the policy we haven't set here, so that's why it is showing none. PFS is showing no, etc. Now we have learned about the SPI index. Here you can see that you have the inbound SPI index, and then you can see that you have the outbound SPI index as well. Right? Now here also everything is okay and correct. The final output that you want to check is the crypto session, and here you can see the port number and the protocol number. Everything is working up and fine. So this is the minimum basic configuration, that once you do the configuration you can go and verify from the show command. The best thing or the best command to verify all of your crypto configuration is show run section crypto. So if you run this command, you'll get whatever crypto related command that we have run, it will show. Okay. So this is the baseline verification that we can do once we complete our lab section. What I'm going to do here, that I'm going to save the configuration. Topology obviously will get with the slides. This configuration I will put there in the slide as well. So if you want to practice, you can practice from your side. Either you can use GNS or you can use Viral. In my case, I am using Viral. In section 3.0, we have infrastructure. That weightage you can see that is 30%, and the topics that we have is belonging to layer 2. So here you can see the layer 2 important topics. Say for example, trunk, WLAN, Ether channel, and RSTP and MST. In layer 3, we have to learn important protocol about EIGRP, OSPF, and BGP. Then wireless, and finally we have IP services. So let's start with section 3 and with layer 2, that is 3.1. So agenda here is that to learn about the WLAN, trunk, and various troubleshooting options that we have. So let's start 3.1, that is the 3.1a belonging to layer 2 troubleshooting, trunks, etc. Let's start 3.1a, where we have to learn about layer 2 technology and few of the troubleshooting steps. So before starting 3.1a, I just wanted to quickly revise about WLAN and trunking protocols. So here you can see in the diagram that when you have two switches, and when you're connecting two switches, obviously you want to allow different WLAN inside that. So that's why the distribution layer switch and the access layer switch, we have 802.1q trunk. Now what is trunk, which type of trunks we have, that I'm going to discuss. So let's first understand that what is VLAN and why we need VLAN. Say, what is the default nature of a switch? We know that by default, whenever a switch there and whenever it receives a frame, so for example, you haven't enabled any type of VLAN, or you're not working, created any VLAN to the switch. So whenever the frame will come and hit to the switch, it will broadcast that particular frame to all the available interfaces, correct? And in this way, number of collision domain or number of collision will increase. Rather than, what you can do, that whatever switch you have, you can divide that switch into a smaller group, and that smaller group is nothing but the virtual LAN. So this LAN segment you're dividing into a smaller group, that is, if for example VLAN 10, VLAN 20, VLAN 30. Now in that case, when a request will come, it will only broadcast it to that particular group, because different VLAN, they have the logical boundary. So VLAN is nothing but a logical boundary to reduce the broadcast domain. Plus, when we are creating the VLAN, by default, we are providing some more security as well. So VLAN 10 and VLAN 20, they will not communicate until unless we have a router in between, that we can use router on a stick concept, or maybe the switch, they are supporting SVI. So they need some sort of gateway to communicate across the VLAN. So here you can see in the diagram that you have VLAN 100 and VLAN 200. They are purely in different IP subnet. So two different IP subnets or two different broadcast domains, they will communicate only if they know how to reach to the gateway, or they have to cross the gateway or the boundary. Now how to create the VLAN, it's very easy. You can go to the global config mode. You can give VLAN and the number, and then you can define, then you can give the name. So VLAN number and name, you can define like that. Now here you can see that we are supporting although up to 4K number of VLANs, means we can create up to 4094 VLAN starting from 1. VLAN 1 will be default, but this number 1006 to 4094 will be supported in transport mode, means they will be supported inside extended VLAN range. You can go and create up to 2005, where 1002, 3, 4, and 5 they are reserved for token ring and FTDI purposes. Okay, so we can go and create the VLANs. It's very easy to create. Let me quickly log into the switch and let me show you that how you can create the. So here I am inside the switch, and what I can do, I can go and create, say for example, VLAN 100, and then I can go and give the name as, say for example, servers. Then we can check the VLAN. So here you can see that you have VLAN 1 by default, and all the interfaces by default they are part of that VLAN. Then you have the reserved VLAN 1002 to 1005. But again, you can go and create the VLAN. So for example, I have created the VLAN 100, and I should exit, and then we can go and check that VLAN. So here you can see that now you have the VLAN 100 created here. I will not add any interface, but if you want, you can add the interface as well. So for example, any of the interface, show interface brief. Let's see that what available interfaces we have. To this particular switch. These are the interfaces that I can see here, and if I can check the interfaces and the summary, so now you can see that you have these interfaces because this is the virtual switch. So you are seeing less number of interfaces, but I can go to any of the interfaces, for example, 1/1, and then I can go to switch port mode access. We'll discuss about this mode access and trunk, and then I can go and assign switch port access VLAN 100, and then I can go and check about this particular interface, that is show interface E11, and we have this option of VLAN. Even we have option for the trunk as well. So this mapping will not work, but if we go and check show interface E11 and then trunk, so here you can see that the encapsulation is negotiated. This is non-trunking. What is trunking, what is non-trunking, we'll see. The number of VLAN allowed over this interface is VLAN 100 that we have created. So like that we can go and check it. So here you have the command, and you can check show VLAN that just now we have checked. Now if you want to assign that particular VLAN to the interface, you can go and use switchport access VLAN 100. Again, you can go and check show VLAN. So 100 is assigned to this particular interface. Now, what type of ports we have that we can assign to VLAN? We have access and we have trunk. So what does it mean? It simply means that suppose if we have switch, and that switch is connected with the terminating device, means where you are terminating the network. So that particular interface you can put inside access VLAN. Say maybe access VLAN 100 or 200 or 300, etc., etc. And that's the reason in corporate network we are creating certain type of VLANs. So for example, VLAN name data, VLAN name wires, VLAN name sales, HR, etc., etc. So terminating devices generally we are assigning to the access port, but where you want to connect the other networking devices and you want to extend that access VLAN throughout the network, or you want to propagate that VLAN throughout the network. So whenever you're connecting a networking device to other networking device which is non-terminating, that you want to extend the network. So at that point, you want to create the trunk. So trunk simply means that can allow multiple access VLAN, or that can allow multiple VLAN. Access means they are part of only one VLAN. Later on, we'll see that we have different type of trunking protocols. So here you can see that rather using three different cables over one interface, once you enable the trunk, you can allow different VLANs over that. So for example, VLAN 100, 101, 102. We have trunking protocols. We have ISL, that is Cisco proprietary inter-switch link, and then we have industry standard, that is 802.1q. Now in this diagram, it is quite clear that if you have terminating devices, so these terminating devices, they are part of same VLAN or a VLAN. Here you can see VLAN 100, here you can see VLAN 200, here you have VLAN 200, like that. And suppose if you want to extend, or you want to pass multiple VLANs over the trunk link, then you can go and allow those VLANs over connecting networking devices. Correct? So either we can use ISL, or we can use 802.1q. Here we have dynamic trunking protocol as well, which is something you can think that this is uh, dynamically negotiating the trunk, or dynamically negotiating two switch properties, although we have option to do this configuration manually as well. So how we are going to do this manual configuration, how we are going to do it dynamically, I'll show you in upcoming slides. Now the characteristic of 802.1q, that is now the standard, and even Cisco also uses 802.1q, is because this is lightweight rather than this ISL that is encapsulating entire frame. 802.1q, the feature or the improvement it has is that they are embedding. So here you can see that they are embedding 4-byte VLAN tag. So they are adding some tag to the frame, and once they add the tag, then the default size of the frame will increase up to 1518, because they are adding 4-byte of frame, and then it is supporting maximum 4096 VLAN. Now how it look like? It look like this. So you have the frame. When you add 802.1q VLAN tag, inside VLAN tag itself, you have VLAN ID 12-bit, and that's the reason it is supporting 4096 VLAN, because 2 to the power 12, if you check this number, then you will find it will be 4K, correct? So 2 into 2, if you do 12 times, we know that uh, uh, you can do the math, so you'll find that it is 4K. Apart from that, we have priority bit, we have the protocol tag, we have some bit as well, that is the canonical format bit. Okay, so we have just a overhead of 4-byte, and it is propagating the number of VLANs through this tag. So let me quickly log into the switch, and I'll create a VLAN 200, and then in between two switches, I have switch 1 and switch 2, I will enable the trunk. So let's do that. Mode trunk. And now it is telling that, see, this command is rejected because the trunk encapsulation is auto. If you want to do it manually, you have to do switch port trunk encapsulation. And here you can see that you have .1q ISL negotiate. So I'll do .1q and then switch port mode trunk. Okay, and what type of VLAN you want to allow? Switch port trunk allowed VLAN, say 100 and 200. Although I haven't created the VLAN 100 and 200, I want to create 100 and 200, and I don't want to add this VLAN 10. So I can do remove 10. Okay. Now we can go to the interface, say E0/0 and even 0/1 as well. So what command we are using? We are using switch port. First of all, switch port trunk encapsulation .1q. This is that manually I am telling that encapsulation is .1q. Switch port mode is trunk and we are allowing VLAN 100 and 200. Now same thing I can do to this side as well. I can go to interface range E0/0 to 1 and then now we can go and check show interface E0/1 trunk. This is one very good command. So allowed, here you can see that over E01 the allowed VLAN is this and this. The VLAN allowed over certain interface is this. We can go and check show and interface E0/0. So this is the command that we are working at the moment. I haven't created VLAN 200 to other switch, so I should create that also, but just for demo purpose. This is solving the purpose. So this is the way that we can go and create the VLANs, and then we can create a manual trunking, or we can do manual trunking as well. Next, we have to understand about the trunk and dynamic trunking protocol, DTP. We know that we can create the trunk or to pass multiple VLANs across two different switch or inter-switch link, we can create the trunk. We have option that we can do it manually, and then we have option that we can do or we can use dynamic protocol as well. So for example, if you have an interface 2/24 and if you run this command switch port mode trunk, first of all, it will throw an error. It will tell you that first you do the trunk encapsulation protocol or run the trunk encapsulation protocol, either ISL or .1q. So if you do that, and suppose if you have two switches connected back to back, say I have one switch here, another switch here. Here if I do ISL inter-switch link and here I do .1q, then obviously they will not form the trunk. So both sides we should give the same protocol, same encapsulation in other words, and then only they will form the trunk. So for example, if I give same encapsulation, so for example 8.1q or 802.1q or .1q, etc., then they will form the trunk. Now here we have the option. Either we want to do it manually or we want to use the DTP, dynamic trunking protocol. So for that case, what you can do that you can go to one side and you can do encapsulation negotiate. The full command is switch for trunk encapsulating or encapsulation negotiate, but they will prefer ISL. They will not prefer 802.1q due to these other Cisco switch. So they are going to prefer ISL. Better we can do it manually as long as possible. Now, once you have multiple VLAN and you want to allow it, you have option switch port trunk allow VLAN, and then you can give number of VLAN or range of VLAN. If you want to remove, you can remove that also, that we have done in the previous section where we have removed one VLAN, we have allowed certain VLANs. Now with this TTP dynamic trunking protocol, that is again the dynamic way to create the trunk. Again we have options. So this DTP has two modes to dynamically decide whether the port become a trunk or not. We have dynamic desirable and then we have dynamic auto. So here you can see if I go to certain interface and if I type switch port mode dynamic and question mark, I will show you in this in the switch as well. So then I have option dynamic desirable, dynamic auto. Now we have one long list that if two different switch, what mode they are running in and how they are going to initiate the trunk. So for example, you can do manual, you can do with help of DTP automatically. So manually, if you are making trunk, obviously they will form the trunk. One side trunk, other side is dynamic desirable. Dynamic desirable means you are sending the packets to form the trunk, means you are sending the negotiating packet. But dynamic auto will not send. So we'll see that. One side trunk, other side is dynamic auto. They will form the trunk. If one side you have dynamic, say desirable, other side dynamic desirable, they will form the trunk. So all these cases, they are forming the trunk. And suppose if you have dynamic desirable and dynamic auto, they will form the trunk. But if you have dynamic auto, they will not form the trunk, because both these sites, they will expect that they are ready to listen the frames, but they are not actively sending the frames. So that's why they will not form the trunk. Now suppose if you want to disable DTP, you have option switch port, no negotiate. Correct. So in that case, we are not using this DTP to form the trunk. And again, you have the summary slide, whatever we have discussed here. Now, what are the troubleshooting option we have? Suppose if you're forming trunk and this trunk is not coming up. So you should check these things like what's the trunk mode, ISL versus 802.1q with respect to frame tagging protocol. So this is trunk mode will be, you should check what is the mode of the interface, say access or trunk, etc. Then the tagging protocol is ISL versus 802.1q. Then do you have a native VLAN mismatch? Suppose one side you are allowing 100 and 200, other side you are allowing only 200. Do you have any VTP domain configured? We'll see that VTP in the upcoming section. And that is only true when you are using DTP to negotiate the trunk. So these things one by one, you should go and check. Then we have one very important command here. Here you can see in the bottom that show interface name and switch port. This is actually very important command included with show interface trunk. So these two commands are there for verification, and both side you can go and run, means both side means both the switch. You can go and run this command and you can check that which VLANs are allowed, which protocol is running, what is the mode of trunk, etc. So let me quickly go and log into the switch and we can do some of the verification commands. So I am inside the switch, and if we go and check show interface description, we are just checking that switch 1 and switch 2, which interfaces they are using. So E00 and E01, these are the interfaces that is connecting to switch 1 and switch 2. And if you go and check show interface trunk, one very important command. So here you can see that E00 and 01, they are allowing these two VLANs, although the management domain it is showing only 100. Why? Because if you go and check show VLAN, you have only one VLAN. So what I'll do, I'll go and create VLAN 200 as well, and name I will give, say for example, clients. Now if we go and check show VLAN, we have server and we have client. Although we haven't assigned that to any of the interfaces, now we can go and check interface trunk, and now here you can see these VLANs are coming. Okay. All right. Now the status, you can straight away see that 00 and 01, they have status of trunking. Native VLAN is VLAN 1. The mode is on. Okay. Now show run interface E0/0. This is the configuration we are using. If I go to other side, so interface and then trunk 100, 200, because we haven't created any of the VLAN, so it is not showing anything. Mode is on, encapsulation is 802.1q. That's okay. Then I can go here. Also, I can create VLAN 100, name servers, and then WLAN 200, name clients, and then we can go and check show interface trunk. So you'll get the same result. Now next very important thing that we can check, show interface E0/0 and then the switch port. This is actually a nice output that will give you detail about VLAN and trunk. So administrative mode is trunk, operational mode is trunk, encapsulating 802.1q, negotiating of the trunk is on, access mode VLAN, that's the native VLAN, is 1, that's okay. Tagging is enable, voice VLAN is none. We are not using private VLAN at this point of time. Trunking is enabled, we are passing 100, 200. Pruning is there, means there are some default options as well. All right, so what we can do now at this point of time, we can check all the DTP option. So if I go to interface E0/0 and once I am inside switch port, you can see that what options you have. So you have a no negotiate if you don't want to, or if you want to turn off DTP, you can use no negotiate. Then if you want to check mode, and then you have this dynamic, you can see auto and desirable, and we have seen that list. So DDDD one side and DDD other side, that will form the trunk. If you have auto both the side, dynamic auto, they will not form the trunk and vice versa. Okay, so this is the way that we can create the trunks and we can verify as well. All right, so let's stop here. Next we have VTP, VLAN Trunking Protocol. And what is the use of VTP? We'll see that. This is something that we want to replicate or propagate the VLAN dynamically or automatically. And this will be useful for the large infrastructure where you don't want to create the VLAN switch by switch or hop by hop. So in this case, we can use VTP as a feature so that can replicate the VLAN, or in terms of the VLAN database, from one switch to the nth switch, correct? So how we are going to do this, what are the terminologies used and all, we are going to discuss and learn all those things in this particular section. So you have this VTP, and VTP, they have their own features. So what features they have, we'll see that. First of all, they have versions, say version 1 and version 2. Version 2 is quite a bit popular, although we have version 3 as well, which has again some added advantage. So let's focus on version 2 and we'll see what features we have in version 3 as well. VTP version 2 that can do VLAN consistency check. They are domain independent, transparent pass through. Means there are some, you have some added advantage in version 2. And in version 2, we'll see that how we can configure it. In version 2, what are the key component we have, that we'll see in the upcoming slide. Now what important thing we have in version 3 is that not only version 3 can replicate the VLAN database, but they are able to replicate the other databases as well, such as MST, multiple spanning tree protocol. Apart from that, version 3 can have support up to 4000 VLAN. They are supporting private VLAN. They have improved authentication. Whatever issues you have in version 2, and we have one issue in version 2, that suppose that you have switches and you brought new switch inside the VTP domain, by mistake, if the domain name is same, and suppose if the revision number for that new switch is higher, so whatever database that new switch has, they will go and write those databases or those VLAN to all the switches, and you can understand how big that issue is, how big outage it will be. So there is no database protection mechanism that we have in version 2 that is there in version 3. So here you can see that protection from accidental database overrides by using VTP primary and secondary server, ability to enable VTP on per port basis. Okay, what modes we have for VTP? We have three modes. Actually, we have four modes. Let me show you here in the diagram. So here you can see that you have server, you have client, you have transparent, you have off. Server means you can create the database, and from there with the revision number it will go and write to all the client who is listening those and updating their database, transparent who is simply passing that information. So here in the diagram you can see that you have server who is sending the information, because this switch is in transparent mode, so he is passing that to the other client who is learning that new information. Likewise, here you can see that server is sending to the other client. If the VTP is off, so they will ignore the VTP update. So in a switch where you don't want that VTP update, you can turn that off, so that particular switch will not get the VTP updates. Correct? So the same thing you have explained in this diagram, and then you have the notes that you can refer. We have version 1 and we have version 2. In version 2, we have added advantages and feature. One of the very interesting thing and important thing we have with respect to troubleshooting as well is the revision number. Now in the lab section, we will see this revision number, the format of this revision number as well. Not only the format, but uh, when you go and check show VTP status or show VTP, you will find that you have the revision number. So at the moment you will add the VLAN, the revision number will upgrade, and then since he has the higher revision number, he will send the advertisement to the other peer switches or downstream switch to update that database that you have added inside the server VLAN. Correct? So that's the reason the revision number is important, because it is one of the component of the VTP advertisement. So here you can see that if you want to change this revision number, because accidentally you don't want to connect any switch by default in a network who has higher revision number, if because by default the switch mode is server. So if revision number is higher, it will start sending the VTP advertisement, and other switch they will think, oh, his revision number is higher, so I should overwrite my database as well. So you don't want to do this. So in that case, the safe thing is that you change the mode to transparent and then change it back to the server or client. So if you made that to transparent, what will happen that they will change their revision number to 0. And this is particularly for the new switch. The other option is that change the VTP domain name and then change it back to the original name. So you can change the domain name and change it back. The best option we have is the option 2, that change the mode to the transparent. Okay. Now we have already discussed about VTP version 3. They have this protection mechanism because they have VTP primary and secondary server. What type of messages we have inside VTP? We have summary advertisement, we have subnet advertisement, we have advertisement request. Summary advertisement, here you can see that it is sending the VTP version, domain, configuration revision, timestamp, and MD5. Correct? So suppose if two switch, their domain name is not the same, means if they are not in the same domain, obviously they will not read those databases, or they will not override those databases. And same is true with the MD5 digest as well. They should have common password so they can replicate the database or understand the database and override it later on. So a switch is sending the summary advertisement and the subnet advertisement. In both the summary advertisement and the subnet advertisement, you will find that you have configuration revision number. So here you can see inside the subset, not subnet, it is a subset advertisement. Inside the subset advertisement, again you have the revision number, and revision number simply means that if you are getting some information from higher revision number, you have to overwrite it. Now suppose um, here you can see that there is one use case of advertisement request. What it is that if switch receive a summary advertisement with a revision number higher than its own. So suppose I am getting a update with revision number 3, but mine is, say for example, 2. so I am lower in the revision number, then I will send the advertisement request that, hey server, my revision number is lower. You write all the VLAN information and update my revision number. So all the devices in a network should have the common revision number. Okay. All right. So how we can do the configuration? It's very easy. You have to do at least two things. Domain. So you have to go and define the VTP domain and then VTP mode. You define the VTP domain, VTP mode, even we have to define the VTP version as well. So you do VTP domain, you do VTP mode, you do VTP version, and if you want to do the protection, you can use the VTP password as well. So it's very easy to configure if you follow these configuration steps. So it's easy to do the configuration. How we can verify it? You can go and check show VTP status. So here you can see that its VTP version is 2, configuration revision is 42, maximum VLAN supported 1005, number of existing VLAN is 7, the operational mode is server, the domain name is my domain, the pruning mode is disabled at this moment. We'll see that what does it mean by pruning, and this MD5 digest is also there. Again, we can go and check the VTP counters as well. So now here you can see that we have the VTP pruning. What does it mean by VTP pruning? Pruning means simply that you cut off unnecessary information. That's the prune. Now VTP pruning means that you don't want to propagate unnecessary information to the switches. So here you can see in the diagram. So suppose if switch B will advertise the VLAN information, he will send switch C VLAN 100, 200. That switch C anyways is not going to understand. And switch A, he will advertise VLAN 300. Again, he will not understand because he don't have that. So in that case, what you can do, that simply you can cut off these information to advertise in first place. So here you can see that you can go to the switch globally, you can enable VTP pruning, and then once you enable that, then you can go to the switch interface where this inter-switch link is connected, and you can do switch port trunk pruning, and you can prune those VLANs. Apart from that, you have other options as well, like VLAN add, remove, etc. All these options we have with the normal trunk as well. So we can prune those unnecessary VLAN to propagate from one place to other place. Correct? Now, if you want to do the optimizing convergence, already we have studied about the DTP in the previous section. All right, so this is the VTP pruning, and this is the VTP. If I want to summarize this, how I can understand VTP. So we can think like this, that VTP, if you want to configure, you have to configure actually minimum 2 things, but 4 things are required, like VTP domain, VTP version, VTP mode, and password. VTP has version 1, 2, 3. 2 and 3 is most popular to use. Their modes are client server and transparent. Transparent means that simply bypass the advertisement. Server who is creating, client who is receiving. And the common factor in all these modes and things are the revision number. So if the revision number is higher, he has the authority to update the database to the other devices. Correct? And then we have seen that we have the advertisement like summary and subset. And if your revision number is less, you will send the advertisement request to update that revision number. How we are going to configure it, we'll see in the next section. Let us perform the lab task. So we have this arrangement where we have switch 1, switch 2, and switch 3. Let me quickly draw the diagram. So I have switch 1, and then it is connected with switch 2, and then it is connected with switch 3. 1, 2, and 3. Even switch 3 and switch 1 is also connected back to back. But we will make this interface as off, or we'll disable these interfaces. All right, so switch 1, 2, and 3, what interfaces they have? say 00 and 01 in between that, and here you have 02 and 03. So it is connected like that, and here it is say 00 and 01, and here it is say 02 and 03. I'll shut down these interfaces, so I don't want any cross communication in between the switches. So this is the topology, and we want to run this VTP. So what I will do that switch 1 I will make, or switch 101 I'll make as a VTP server. So let's do this. I'll go and create VLAN 10 to 20, and here you can see show VLAN. So now we have the list of VLAN. A few of the VLANs we have created earlier as well. Then I'll go to the interface range E 0/2 and 3. So E0/3. Even I can go and give the hyphen as well. These interfaces I will do this shutdown because I don't want switch 1 and switch 3 do the communication. Alright, we can go and check show CDP neighbor, and we can check what switches we have in communication. So here you can see that I can directly communicate with switch 102 or switch 2, and that's the agenda we have. Alright, so let's go and create the VTP, say domain. I'll make this as a my domain, then VTP version. Here you can see that we have the syslog message telling that the domain name has changed from null to my domain. Version is 2, and then VTP, what options we have. Here you can see that we can give the mode, we can give the password, we have the pruning option. We'll see that. So now I can go and give the mode as a client server transparent and off. So this is the server. By default it will be the server. I'll go to the other switch here. If you check number of VLANs, so it is replicating. Why? Because if I go and check show VTP status, so here you can see that this version is version 2. It is running version 2, although it is able to understand 1, 2, 3. The domain is my domain, and by default you can see that this is also server. What is the configuration revision number it has? That number is 4. Number of VLANs is this. Let's check this in the first switch as well. So means that by default the VTP is on the switches. So I'll go back to switch number 1, and inside switch number 1 we can check the VTP status. Let me run the command show VTP status, and here you can see that you have version, you have mode, and you can see number of VLAN supported. So everything is perfect and correct. There is no problem here. Now if I go here and create one more VLAN, say for example VLAN say 55, and now if you go and check the status, you can see that number of VLAN become 19. The revision is 5, and the same thing should be replicated to the other switches as well. So the revision from 4 it become 5, and now if I go here and check the VTP status, now you can see 19 and 5, although the mode is server, that I will change it to client, and we'll check the transparent as well. Here if I go and check show VTP status on switch number 3, so let's check that. Now this is also server, and number of VLANs is 5, configuration revision is 0 and he is not able to get the information from switch 1 to switch number says 3, because switch 2 and switch 3 even they are not forming the trunk. So what I will do, I'll go quickly here and we have one interface here, interface E0/2. I can go and manually assign the trunk, or we can do this dynamically as well. That's the DTP. So I'll do this thing, switch port and then trunk. You can see that you have uh, encapsulation and you have native pruning allowed as well. What I want to do switch port mode, and that's dynamic. We have desirable option. A switch port mode dynamic desirable, and then switch port mode trunk. Now the flip side of this is this, that if both side you are enabling this, they will go and execute ISL instead of .1 queue. So the recommendation is that we should do the .1 queue, correct? So that's the reason. Let me quickly go and do this switch port trunk encapsulation .1 queue, that because that's the standard, correct? So what we have done over show run interface E0/2 is these commands, switch port trunk, and then I don't need switch port mode dynamic desirable because I can go and make switch port mode trunk. But anyways, let's go here and run these commands here as well. Interface E0/2. So interface E0/2, then we can check show VTP status. Now you can see that they have formed the trunk and now multiple VLANs are passing. Next thing, what I want to do here is that the VTP mode I want to change as a client. Okay, and then we'll go and check the show VTP status. Then here I will go and create some more VLANs, say VLAN 6270, and then we'll check the status, show VTP. What options you have, you can see that counters device interface status and the password. So now total is 30, revision number is 6. We can go ahead and check. Total is 30, revision is 6. Now I can go here and check 30 and 6. So still we can see that the client is sending some information to the server as well, and he is updating his database. Now what I don't want to do this thing. Rather what I want here is that the VTP mode is client first of all, okay, and then I will go and create some more VLAN just to verify, say VLAN 8290, and we can go and verify the VTP status on switch number 3. So now this is 41 and 7. Now in between the switch, I will go and make this as a VTP mode transparent, and then we'll check the revision. Now you can see the revision number become 0, although they have this 41 VLAN that they have already learned. So now if I go here and create some more VLAN, say for example 100 to 110, And if we go and check the status, now this is 8 and 51. Here you will see this will become 0 and 41, but it should become 8. Now here you can see that the status is the same. So as per the transparent mode, it should pass the information. Although you can see that revision number is still 7 and the number of VLANs are 41. That should be 51. So clearly we are seeing that they are not updating the revision number in between if we have the transparent. And this is the issue with the virtual devices, but ideally, as per the theory, they should update the database. So I'll do one thing, I'll go back to switch number 2 and I'll make this VTP mode as a client one more time. And now we should see here. Now they are replicating in the client mode. So server in client mode is working perfectly. Transparent mode, although they are changing the revision number, but they are not propagating the number of VLANs, correct? Now if I go to VTP mode and then I can make this off and we can check the status now. So now revision number becomes 0 and whatever number of VLANs I have, they are learning that. Obviously, if revision number is 0, that means that they will not learn those data in case if it is off. So now if I go here and create some more VLAN, say VLAN 150 to 160. So we can go and check the revision number 9262, and here also we can go and check the revision number 9262. Here this is off. Okay. The last piece that we have to learn and understand here is the pruning method. So if I go here and first of all I should enable VTP pruning globally. Once you enable that, so cannot modify pruning unless the VTP is in server mode. So that's the restriction. First of all, the pruning should be inside the server because the server has the authority to create the VLANs and then it is replicating the database. So VTP pruning is on. Now what we can do is that we can go to switch port and let me go to the interface. The interface is 0/0 switch port trunk, and then you have pruning, and then you can use VLAN, and you have add, accept, remove, none, etc. Okay. Now we can go to the switch port interface E0/0 and we can check the switch port related to E0/0. Here you can see that the mode, the encapsulation, the trunking, and you can see the pruning VLAN is enabled. We have made that as a none, so that's why it is showing like that. Okay, so this is the way that we can create the VTP and we can do the verification as well. 3.1 we have Ether channel configuration. We know that Ether channel is something that we can bundle the interfaces to overall increase the throughput. So here you can see in the diagram that you have core, distribution, and access layer. Generally, where we want to do this bundling or aggregation of the port or interfaces, they are at the level of core and the distribution layer generally. That doesn't mean that we can't do at the access layer. We can do as per requirement. So what we are achieving with Ether channel or the port bundling, that that we want to give much more throughput whatever we have at this point of time when you are connecting the interfaces back to back. That simply means very simple term that suppose I have switch A and switch B. So let me try to draw here. Say for example one switch here and one switch here. If I have 1 gig interface, then obviously the overall throughput is 1 gig. But you can take, say for example, 4 interfaces and you can bundle and they can work as a 4 gig interface. So overall throughput obviously will increase, will become 4 gig. Now the important thing here is to understand is that this 4 gig interface is per application. Means suppose if you have only one application and you think that one application is getting 4 gig of interface, that's not true. The algorithm or mechanism behind the scene is that suppose if you have two interfaces, they will do the load balancing. So 1 gig and 1 gig will get load balancing or get load balanced per application flow. That's the key thing we have here. Whenever we are doing the port bundling, that doesn't mean that this become one 4 gig pipe and all the applications are getting 4 gig of speed. It's not the same thing. All right, so we have different type of methodology behind this, and we'll see that we have LACP, Link Aggregation Control Protocol, and we have Cisco proprietary, that is the PAGP, Port Aggregation Protocol. But moral of the story is same, that you are aggregating the port for higher throughput. Now we have to go and check that how we can create this Ether channel or bundle. We have option, we can do it manually, we can do it dynamically as well. Manually when we are talking, so for example I have two interfaces, I can go and I can use this command interface range and then channel group 1 mode on, or maybe you can use some other number like 10, 20, 30, 40, etc. So when you are using mode and on, and we have multiple option, so for example in LACP we have option related to active, passive, and on. So for example, if you are using on, this is a manual thing. Manually, you are turning on this LACP protocol or channel protocol. Okay. Now, once we are running this command, what is happening behind the scene? Automatically, port channel interface 1 will get created. Now, this port channel 1 interface that you are creating, here you have to go and write your logical configuration, or you have to do the coding. So for example, if I have two interface 23 and 24 and I want to run commands related to switch port mode trunk and allow certain VLAN, then I do not have to run the command over the member interfaces. Rather, I have to do it inside the logical interface. So we should understand some of the technical term here, that I have a switch and I have two member interfaces, so for example 23 and 24. When you bundle these interfaces and you are using manual method turning, so for example LACP on, so at that point of time, so for example the group you are using is 1, so you are going to create interface port channel. Here you can see this port channel 1, and whatever configuration you want to put over these interfaces, you should put here over the port channel. The switch port mode trunk and allowed VLAN we should put there. Suppose if you want to create a layer 3 port channel, then you can go to the port channel, you can do no switch port, and then you can assign the IP address as well. Okay, so this is the manual way to do the configuration, although we have the automatic way as well, and we have the protocol as well to do this. We'll see that in the upcoming slide. One important note here, that whenever we are creating the port channel among 2 or 3 or 4 switches, obviously these are point-to-point configurations. So in between two switch, whenever you are creating the port channel, So at that time, your speed, duplex, and other hardware related properties should be the same. So what I am telling here, that you are creating port channel here, no problem, you can create it. Like that, you can create other port channel here. So for example, number 10 and 20, etc. So these interfaces, so for example, speed, duplex, should be same, correct? Otherwise, they will not form the port channel, and constantly they will throw an error as well. All right, so next we have the dynamic way to do the configuration. We have a link aggregation protocol, we have port aggregation protocol. Uh, Now everyone is using LACP, and even in the syllabus also, um, it is recommended that we should learn, understand LACP. Although if we learn one methodology, the second will come automatically. So I'm going to focus on LACP, link aggregation protocol. This is the dynamic way to create the bundles. We have mode for LACP is active and passive. If both side of switch is active, they will form the port channel. Both side is, say one side is active, other side is passive, again they will form the port channel. If both side is passive, then they will not form the port channel, because no one is sending the LACP control packets. So obviously both are the listener for LACP, and they will not auto negotiate the ether channel or the bundle. So here you can see that when you are doing the LACP negotiation, means when you are doing this automatically, so you can go to the interface, channel protocol you can define, then you have to go and give the channel group name, mode active. So suppose one side I am using active, other side I am using passive, so they will go and form the port channel. It's very easy and straightforward. There is no much thing behind this. Now we have some important thing related to LACP, that we can have 8 interfaces inside group, and 8 interfaces we can work as a backup. So 8 plus 8, they are supporting total 16 interfaces that can form LACP, but these 8 interfaces are working as a backup. Now who will work as an active? That depends upon port priority. By default, that will be 32768, and lower is the better. Okay. Now apart from that, we have other variable as well. Other variable is system priority. So suppose if you have two switch, and which switch will take the active role and which will work as a standby or secondary role. So who is the primary, who is the secondary? So that depends upon the system priority. By default, that is also 32768, and lower system priority is better. So suppose this is 500 and this is 32768. So obviously he is the active initiator and he has to take the decision. So by default both will be the same, so that again if you have the tiebreaker, so in that case always the lowest MAC address will be preferred. So whoever switch having the lowest MAC address, he will take the decision, because by default we are not changing the port priority, we are not changing the system priority. So as per the MAC address, in terms of system priority, lowest MAC address will win. In terms of port priority, lowest port number will win in case of tiebreaker. Now once you do the configuration, you can go and check show ether channel summary. That's the nice command. There you have the legends or flags. So for example, D for down, P that they are in the port channel, I for a standalone, S for suspended, R for L3, S for layer 2, etc. So you have the legends and you can check the status. So these devices, S stand for layer 2 and U stand for port channel in use. So this port channel is successfully formed. This is layer 2 and up and running. Okay. On Cisco Nexus switch, the syntax is a little bit different, obviously, in the Catalyst switch and the Nexus switch, but the concept behind the scene is the same. So this way we can go and create the port channel. Here you have some difference, means what is the difference between port aggregation protocol and link aggregation protocol. In port aggregation protocol, we are using the mode as auto and desirable. Desirable is equivalent to active, and I think there is some typo here. So desirable is equivalent to active. Okay. All right, so it's not a typo mistake, but in the diagram, there are different use cases. So manually, you can do on, either it's a PAGP or link aggregation protocol, they will work. Now, on off, one side on, other side off will not form the channel. That's true. Then one side auto, other side desirable, they will form the port channel. Now here you can see that you have auto. So let me write here auto, and then you have desirable. This auto is passive for LACP, so for example PAGP, and this desirable is active. So if both side is desirable, they will form the port channel. Both side is auto, they will not form the port channel, and same is the case with LACP that we have discussed earlier. So these are the use cases, these are the scenarios we have that will work here to form the Ether channel. Let us perform the lab task here. In our lab, so for example, we have switches, and these switches, so for example, switch 1 and switch 2, their interfaces are 0, 0 and 0, 1 both sides. So we'll go and form the LACP port channel. First, we'll try to form with the manual method. Manual method means you can make this on, and then we will use the LACP as well. Even we have option for PAGP as well, but we'll focus on manual and LACP. So let's go and do this. First of all, what I will do, that I will do the default for the interfaces that we have E00 and 01, because we have done some configuration earlier and I don't want to do that here again. Means I don't want to have the old configuration, so I can go and default the old configuration. Now once I delete this, then I can go here and I can take the range of E0/0 and 1. Let me type it. So 0/0 and 1. And then we have this option of channel group. So for example, channel group, you can see the number is from 1 to 255. I can take 100 and then mode. Mode on means we are making this on, we are turning this on. So now here we can see, because this is the virtual device, so maybe we'll get some error. So port 100 invalid group slot number, etc, etc. Let's go back and try to make this 10. Okay, so this is the problem with the virtual switch itself. This is not the problem with the actual hardware. So if I use 10, it took the 10, and likewise I can do one thing, that show an interface E0/0. Let's copy and paste this configuration other side as well. So here interface range E0/0 to 1, and then I can paste the configuration, or we can go to channel group 10 or whatever we have. Let's see that we have created 10 and mode on. So 10 mode on. Now once we create this Ether channel, then we have option that we can go and check show Ether channel summary. Now here you can see that S stand for switched layer 2 and U stand for up. So we have this is up and running, and ports are in bundle. Now, if you want to know detail about this, so we have option of ether channel, and then you have this option of detail. Even you can go and check the load balancing method as well. So I can go here and check this detail as well, and in detail you can check this information in detail as well. So here you can see all these detail options that we are getting. Now this is the manual method. Now suppose if I want to do this with the uh, automatic, or if I want to use any of the protocol, so in that case I should go to the interfaces first. We have the interface range, and then you can go and define the protocol. So this channel protocol is either LACP or PAGP. That's a Cisco proprietary and the industry standard. Now because they are already in bundle, so we are getting this error. What I'll do here, that I'll exit here and I'll remove that group, or maybe we can go here and then we can remove that statement. So I'll do no here, and then I'll go and remove that statement from the other switch as well. So let's go to the range and paste this configuration, removed. All right. Next, what we can do here, that we want to give this channel protocol as a LACP. Then I can go and define the channel group, say for example 20, and then you can see the mode we have is active and passive for LACP, auto and desirable for PAGP. But I want active, say for example active this side, and other side I can go here, and there again I can go and type say channel protocol is LACP, then channel group is 20, mode is passive. So either it should be active active or active passive, so it will form the port channel. Now if I go here and check show ether channel summary, I can see the ether channel summary. I can see that now we have this, and they haven't negotiated everything, so that's why it was showing as suspended state. Let's see what is the actual code here. So waiting and S and N. So here you can see that you have layer 2 not in use and waiting for aggregation. So still the LSCP was not negotiated, and that's why it was showing that it is waiting. Now you can see that 20 has been formed and it is working properly. Correct. So this is the way that we can go and bundle the ports. If you want to see more things related to this, so still we have the option that we can go and check the protocol and then enter. So here you have the LACP protocol, you have group 20, you have that mode is on. So like that we can go and check this. Now suppose if we have some issue that is keep coming and coming and coming, so you have the option to do the debug for LACP. Once you do the debug for LACP, then you have to check that who is the sender, who is the receiver, etc, etc. Okay, so you need to understand that this debug how it is working. And if you go here and oops, so I can go here and I can debug LACP events here as well. I can go to conft and monitor, or let's see if I can monitor over the screen, otherwise I have to go and check the logs. If any problem will be there, it will start sending these LACP related negotiations problem that we can go and check. So I think terminal monitor is the command. Console already monitors. All right. Now if I go here and do any type of if any type of issue will come, so let's see. And channel protocol is PAGP. So if we create any issue here, and then if we verify this, we can see some problem. So I'll do one thing, no channel protocol LSCP, and then you can go and check the debug. So this is the way that we can go and verify the debug as well. Remember that whenever you are creating the debug, it's not recommended that you should do in the production network. You should have the maintenance window, or if the issue is major, you can take Cisco TAC online, and then you can do the troubleshooting, deep dive troubleshooting. In 3.1c, we have to configure and verify RSTP and MST. So let's start with RSTP, that is Rapid Spanning Tree Protocol. Now it's very good that if we know the other spanning tree protocols as well. So for example, it's good if we know STP, PVSTP, PVSTP plus, and then RST, and then RSTP, and then MST. But I'm going to revise those spanning tree protocol, at least the core behind the spanning tree protocol methodology. What exactly happening when we are talking about the switching network or switching architecture? So in that case, to prevent from the loop, we are running actually STP. So suppose if you have three nodes connected like this, like a triangle, suppose switch A, B, and C. Now here you can see that if you build your network like this, obviously uh, you will find the loop. So frame will be looped across this triangle. So uh, now again, you may think that why we are creating network like triangles or looped network. The answer is for redundancy. We are creating such type of network so that can provide us redundancy. So for sake of redundancy, we are creating such type of network. So for example, if one link is down, still you have one backup link, or maybe you have other links as well. So two links is down, still you have one link, etc. So for sake of redundancy in a switched network or in layer 2 network, we are creating loops, or we are at least creating such type of network design. Now the question here, second question may be that, okay, since we are creating the loop, then what is the loop prevention mechanism? And then the STP is the answer. Spanning tree protocol is loop prevention mechanism. What it is doing, that as per the priority, one of the switch will become root, and then obviously you have second root and non-root. But what is happening, that whatever interfaces that is going towards the root, they are termed as a root port. So you have a root port, and whatever interface you have in front of root port, those are termed as a designated port. So you have DP, and then you have RP. Now what about those switches where you have least priority? They are not root, they are not secondary root. So in that case, they will go and check the priority. If priority is same, then they will check who has the lowest MAC address. So one of the interface will treat as a blocking, BLK, say BLK as a blocking, and other will treat it as a designated port. So this is the blocking port, and then you have the designated port. So the summary of this explanation is that since you have such type of arrangement, So one of the interface is working as a blocking port, and suppose if your main interface is down, so still the traffic can go from this direction, because from blocking it will move to listening, then it will move to learning, and then it will move to forwarding. Okay, so it will take some 30 to 50 seconds to converge, and after that period of time the traffic will go from the blocking, because finally it will become the forwarding port. Okay, now here that's a problem, that we don't want to use STP, rather than we want to use rapid STP. We don't want to wait for this time to converge the network, and that's the solution is to use the rapid STP. So let's see that what are the things we have in the rapid STP. This is under 802.1W, or rapid spanning tree protocol. It's similar to STP, but there are dissimilarity as well. There are differences as well. We'll see that what are the differences we have. So BPDUs, here also you have bridge protocol data unit. These are the, you can think these are the control type of messages upon which the switches, they are building their STP, or they are building their RSTP. Here also they will select one root bridge as per the lowest bridge ID, that will be 32768. We'll see that in the next slide. Then the root and designated ports are elected and functional identical to STP. These are the similarities. What is not similar? You can see that here you have root port, alternate port, designated port, and backup port. In other hand, in STP you have root port, designated port, and blocking port. So let me show you in the diagram. It's always easy to understand with respect to diagram. Here you can see that you have the lowest priority, so priority 100, who will become a root bridge. So this guy, and this is with respect to STP, and this is with respect to RSTP. So this guy is the root. Whatever going towards the root bridge is root port. There you can see these are the root port, and then as per the high uh, priority, one will become block, one will be the designated port. If you have any issue in this direction, then it will move to the forwarding state and packet will flow like this. Correct? On other hand, you can see that in RSTP, he is the root bridge, for example. So these are the root port. We have the designated port, same like STP, but instead of blocking, here you can see that you have alternate port. Correct. And if you have two link, so one link is designated port, other one is the backup for the designated port. So instead of blocking, we have alternate port inside RSTP, and that is one of the reason for faster convergence, but there are other reasons as well. Here you can see that instead of blocking, listening, learning, and forwarding, we have discarding, learning, and forwarding phase. So we are not waiting for that particular amount of time, rather than we are moving to the forwarding state as soon as possible, as quickly as possible. Now, initially, a switchboard starts in a discarding state, obviously, then he has to start his learning. Now, a discarding port will not forward frames or learn MAC addresses, as the name suggests. A discarding port will listen for BPDUs. Alternate and backup port will remain in the discarding state. So you have your alternate and the backup port. They are still listening, but they are not actively participating. So they are listening. Otherwise, if failure will happen, how they will start forwarding the frame. So they are not they are not in the forwarding state, but they are still listening the BPDUs. Now RSTP does not need a listening state. Instead, if a port is elected as a root or designated port, it will transition from discarding to a learning. So here you can see that now if you have root selection, then in that case the port will move from discarding to the learning state. Now what will happen in this case? A learning port will begin to add MAC address to the CAM table. However, a learning port cannot forward frames still. So here you can see that you have three state. In discarding, you are listening that. In learning, you are start learning the MAC address, but in discarding and in learning, still you are not forwarding the packet until unless you reach to the forwarding mode. Finally, when you reach to the forwarding state, then it will send and listen for BPDU, learn MAC address, and forward the frame. Root and designated port will eventually transition to a forwarding state. Okay, so once you have the selection of the root, selection of the ports like root port, designated port, alternate port, etc., they will move from discarding learning to the forwarding state. Now the main question here, that why RSTP has faster convergence? And now you will see the core difference between STP and RSTP. Why? So BPDUs are generated by every switch and sent out as a hello interval. Switches no longer required artificial forward delay timer. Now what is happening in this case, that all the switches, they are generating their own bridge protocol data unit and they are forwarding to their peer switch. Okay. Now what is happening in STP? STP code is 802.1d. Now in STP, BPDUs are generated by the root bridge. Now, if switch receive a BPDU from the root bridge on its root port, it will propagate the BPDU to the downstream or its neighbor. This convergence process is slow and STP relies on forward delay timer to ensure a loop-free environment. So now you can understand that rather in RSTP, switches, they are generating the BPDU and sending to the neighbor. But in STP, that is 802.1d, you have one root port or you have one root bridge election. One switch will become the higher authority and then he will generate the BPDU and all the downstream switches will listen as per their delay timer or as per their timer. So you can see here that the default nature of STP is slow rather compared to RSTP. Now in RSTP, switch will handshake directly with their neighbors, allowing the topology to be quickly sync. This allows port to rapidly transition from discarding to the forwarding state without delay. So you have one-to-one handshake, and then from discarding it will quickly move to the forwarding state where they want to forward the packet. Now again, we have some port type in RSTP. We have edge port, and suppose if you know at this point of time about port fast. Port fast is one of the very popular term that whenever you are connecting the switch with the terminating device, say for example server, so you don't want to send the BPDU. So I don't want to send BPDU or I don't want to send STP control packet to the device that is non-switch, which is not a switch. There is no meaning of that. So that's the reason this particular interface, we are making this interface as a port fast, means quickly it will go to the forwarding state. Likewise the edge. Now this edge port is working as a port fast, immediately it is going to the forwarding state. So there is no listening, learning, forwarding like STP, or there is no discarding, learning and forwarding like RSTP, but directly it will move to the forwarding state. Now second port type, we have the root. Root ports are connected with other switch and has the best path cost to the root bridge. Obviously we know that root port is there. That is one side you have root port, other side you have designated port, so you can reach quickly to the root bridge. And then finally you have point-to-point port. What this point-to-point port is doing, that port that connect to other switch with the potential to become the designated port for a segment. So it can become DP. And now if you go and refer the actual diagram that we have here, so you will understand. So you have root port that is going towards the root bridge, and here you can see the adjacent to root port is the designated port. Designated port adjacent is root port, but here you can see that you have designated port and backup port as well. Alright, finally we have some important notes here related to RSTP. So let me quickly cover this. Now if edge port receive a BPDU, it will lose its edge port and status and transition normal through the RSTP process On Cisco switch, any port configured with port fast become the edge port. We know that. Say edge port, I already explained this, is port fast. Quickly move to the forwarding state. That's the summary for the edge port. Now the RSTP converge process is below. So let's quickly understand the convergence process of RSTP, why they are converging so fast, and we have discussed this in the earlier slide as well. So let me quickly revise this. Now switches exchange bridge protocol data unit to elect the root bridge. This is valid for all the spanning tree protocol. Now edge port immediately transition to forward state because they are nothing but the port fast. All potential root and point-to-point ports are start with the discarding state. So this is actually important. By default, the ports will start with a discarding state. Correct? Means they are actively listening the BPDU. They are not learning the MAC addresses. They are not forwarding the frame. They are learning. So you can think behind the scene. It's not learning actually. They are listening. So you can think this as a listening active listener. Then if a port receive a superior BPDU, it become to a root port and transition immediately to the forwarding state. So obviously once you learn the BPDUs, then you will move to the forwarding state. Superior means that suppose if you are getting one BPD, because in this case what is happening, all the switches, they are generating their own BPDs and they are exchanging it. So suppose this switch has low priority, say 32768 the default priority. Suppose this has priority 32769. He has 68. 69 is not a valid number, just for example. So obviously when he receive the PPTU, he will understand, oh, I am getting this with the higher or the superior switch, and then this will become, so this particular point-to-point interface will become the forwarding state. Okay, for point-to-point port, each switch will exchange a handshake proposal to determine which port become the designated. Obviously, you can do the handshake and you have to define who is the designated. It's okay. Once the switch agrees, the designated port move immediately into the forwarding state. So here you can see the convergence is like little bit different than STP. So ports, they are starting with the discarding state and then they are moving to the forwarding state. At the moment you get some superior BPDU, it will become the root port. So again, remember, if he is the root bridge, that means that you are the root port and he is the DP. Okay, so if he is sending the BPDU, it will be superior BPDU. Correct? And when he is sending the BPDU, he is not superior BPDU. So that's why it is telling that it will move to the forwarding state, because you have only one blocking type of a state, that is the discarding. So either you will be at the learning or you will be at the forwarding and you will be at the discarding, but there are less chances that when you have the superior BPDU, you are in the discarding state. All right, so this is the summary for the RSTP convergence. Now every switch will perform this handshake process with each of the neighbors until all the switch will get sync. Complete convergence happen very quickly within the second. So all the switches, they are sending their BPDUs, and then switches, they are calculating on basis of BPDU and the superior BPDU. Now, whoever is sending the superior BPDU, he has become the root bridge and his interface will become the designated port. The adjacent port will become the root port because he has to reach to the superior bridge, and according to that all the switches will converge. Once they converge, once they sync, then RSTP will up and running to all the switches, and then it will take a few seconds, and that's why it's TCN in STP and RSTP both have different way. TCN is nothing but topology change notification. Now what is happening in STP, say in case of when the switch move to forwarding state, or in a state of when they are going to blocking or down state, at that time they are generating the TCN, particularly in STP, that is 802.1d. Now that TCN bit will go to the root bridge because we know that root bridge has to take a decision. Now what root bridge is doing now, that now if they are sending the BPDU, they are setting the TC bit, that is the topology change bit, and then they are forwarding this to all the downstream switches. So all the downstream switch will come to know that the port is going to the forwarding state, or switch interface is going to the forwarding state, or blocking or down state. Correct? Now again, this is little bit time consuming process. Rather than in RSTP, what is happening, first of all, only non-edge port when they are moving to forwarding state. So we know that this edge port are working as a port fast, or they are equivalent to port fast. Directly or quickly they are going to the forwarding state. So only non-edge port, when they are transitioning to forwarding state, they are generating the TCN. Now good thing about RSTP that all the switches that they can generate the BPDU and send the BPDU. So in this case, what has happened, that they are not waiting for the root bridge to understand or recognize that particular change or that particular topology change notification, and then it will send to all the downstream switch. Rather than the switch, whenever he got that change notification, he will update the other switch. So that's the reason this process is faster. So here you can see that any switch can generate the TC BPDU, allowing the topology to quickly converge via the handsets. Now, a switch receiving a BPDU will flush all MAC addresses learned on designated port except the port where they are receiving the TC or topology change BPDU. So again, the core thing behind the scene is that all the switches in RSTP, they can generate and send the BPDU, and they can sync the RSTP database, or they can sync the RSTP states. Correct? Rather than they will wait for some max edge timer to be expire, or some edge timer to expire, or rather than they are waiting for some central authority, say for example the root bridge, to send the updates, to send the updated BPDU to all the downstream switch in the STP. All right. So here again you can see that we have some flavor of RSTP, and next section we are going to do the lab related to that. We'll learn on more on that. Now here you can see that not only the RSTP, their convergence is faster, but they are taking care of two failure. So either it's a direct or indirect failure. We know that the optimization of STP, if you read that STP, you'll find that you have certain mechanism that you can optimize the STP, like uplink fast, backbone fast, port fast is also one of the optimization technique. So port fast is already taken care inside the edge, or the nature of STP, or the edge port. Edge port is working as port fast. Then for direct and indirect failure, this is also taken care inside RSTP. So we don't need to optimize because these features are already included. So in case of any direct or indirect failure, the alternate ports or the backup ports, they will not wait. Rather than they will move to the forwarding state. Okay. Now we have two implementation of RSTP. One is rapid per VLAN RSTP, that is the Cisco proprietary. So because we are going to run the RSTP on a Cisco switch, so we will go and use this spanning tree mode rapid PVST. And the other one is the multiple spanning tree that we'll study in the upcoming sections. Okay, so we have our lab setup. Let me quickly show you this lab setup and what we are going to do here. So for example, this is the topology diagram that we have. What I can do in this, that, so for example, I have switch 1 and switch 2 and switch 3. So here I'm going to run the RSTP in between switch number 1, 2 and 3 like this. At the moment, I'll not use all the interfaces, all the switches, but this will solve our purpose if we run the RSTP in between that, and then we'll go and run few of the verification commands. Okay, so let's stop here, and in the upcoming section, we have a lab related to rapid PBST or rapid STP. Now we have the lab section. So what we are going to do here, I'm going to run the RSTP in between switch number 1, 2, and 3. They are actually 101, 102, and 103. So here you can see in the diagram that we have the ports that is connected like this, say 1, 2, and 3. So here we'll run the STP, and then we are going to verify that. Here are the interfaces E00 from switch 1 to 2, and then 1 to 3, and then 2 to 3. I'll figure out in the with help of social DP neighbor, and then we'll run that. So what I'm going to do, first of all, I'll go and create a VLAN to all the switches. So let me quickly go and create the VLAN. So for example, VLAN 10, because we know that all the VLANs, they have their own STP instance. So I can go to this script, and then I can select all. I can go to conf t and VLAN 10, and then we can exit. All right, so send this script to all the switches. All right, now once we have this, and we can go and check show VLAN. So we have VLAN 10. Now we can go and check show a spanning tree. And for spanning tree, we have a few very important and interesting commands that we used to apply all the time, or we used to run all the time, like show spanning tree detail, show spanning tree summary. So here I can go and run the show spanning tree summary. Here you can see this summary of all these instances. Here you can see that blocking, listening, learning, forwarding, etc. Now we know that by default we are running STP, so that's why you're getting this result. We haven't enabled rapid PVST. We have to change the mode for that. We'll do that. Then you have the detail command. In detail command, you'll come to know most of the things like the topology change, notifications, the timers for STP, etc., and etc. So here you can see that we are dealing actually with switch number 1, 2, and 3. I don't want to add other switch and the interfaces, but we have so many interfaces that is coming here. So let me try to run few more commands, and then we have, say, interface. This is also very important command. So for example, interface 0/0 and enter. So now with this command, I can see that this particular interface is in forwarding state. The role is designated, and like that, I can go and check. So basically, say for example, I have 3 switch, and in this switch, I want to know that who is my root. So suppose I have switch 1, and then I have, say for example, switch 2 and switch 3. They are connected like this. So let's try to figure out first of all who is the root. Okay, so for that I can go again back to the show spanning tree detail, and here we'll see that who is the root for VLAN 10. I am not considering VLAN 0, so let's leave this VLAN 0. Everywhere we are seeing this VLAN 0. So let me quickly go and check that do I have VLAN 10 everywhere. So I can see I have VLAN 10 here, and then I should have VLAN here. So I have all the VLAN, although I haven't added any interface inside the VLAN 10. So what I will do, that I'll move some interfaces inside VLAN 10. So let's do that. I'll show CDP neighbor. Let's check that who is connected with switch number 2 and switch number 3. So here you can see these are the interfaces. I can go here, interface range E0/0 to 1, and this is switch port access VLAN 10. Likewise, I'll go and select the range that is from, here you can see 0/2 to 3, and this is also I'll make as switch port access VLAN 10. Okay, I'll go to switch number 2, and here also we'll run sociodp neighbor conf interface range E. Let's see. So we have 0, 0, 0, 1, 2 until like that it is connected. So from 0, 0 to 0, 3, and finally we'll go to switch number 3, and we'll check that neighbors for 1 and 2. So these are the ports. So I can go here and do interface range 0/0 till 3, switch port access VLAN 10. Alright, because we want to verify this only for VLAN 10. So show spanning tree VLAN 10 and then detail. So now here you can see this is telling you the information about VLAN 10. That's okay. And if I go inside VLAN 10 and if I go and check who is the root, so here you can see that the root port ID is this, the priority into the MAC address. So let's verify that this MAC address belongs to which particular switch, correct? So now if you go here and check, your MAC address is AABB C006500. Now if you see this particular output, and what is the priority? 32778. Why this is 778? Because 32768 is the default priority plus the VLAN ID. So that's why it is showing like this. So everywhere you will find that the priority is 32778. So whoever has the lowest MAC address, that switch will become the root, correct? Root bridge. All right, so let's continue this. All right, so we can verify like this, and because we have two interfaces connected, so you are seeing interface E0/0 up to 0/3. Although if you go to any of the port and you'll see the detail, you can see clearly. For example, E0/2 for VLAN 10 is the designated forwarding, that is the DP. Whose cost, whose port priority, port identifier, you can see here, they have the priority of 32768 plus 10, that's the VLAN number, and this is the address. Now the designated bridge has priority this is the MAC address, then again you can see the port priority and all other data. Now the question here is that in this scenario, who is the root and then who is the non-root, or maybe who is the root and then what about the designated port and the root port and blocking, etc. Because we are running this spanning tree protocol at the moment. So for that you can go and check show a spanning tree, and then bridge means yourself. So we have two options here. One is the bridge option, that is my, and then what about the root? So I can go and check the bridge address and then the root address, and here you can see that bridge address for VLAN 10, we're focusing on VLAN 10, and root address for VLAN 10, both are same. So that means that this particular switch is the root. Now since this is the root, I want to know that what is the port status. So now if you go here and check, say for example WLAN 10, and say we have option for interfaces as well. Interface wise we can go and check, say E0/0, and then I can check the state as well and detail as well. So interface wise also you can filter. So for example 00 is the designated port. So if you go and refer the topology diagram, we'll find that we have different port from switch that is going to switch 1 to 2, say 00 and 01, and here also you have 00 and 0/1. So this is a DP. That means if you go and check here, this must be RP, correct? Again, whatever we have a study, we are following the same thing. So now if I go and copy this command here, you can see here this is a route forwarding. That's correct. So DP and RP, like that we can go and analyze. Now what we want to know here, I fully want to know the root address and the bridge address. So root address we know that will be 6500. And now again if you go and check the bridge address for this particular switch, what is the MAC address? Because priority is the same. Likewise, if you go and check the MAC address for this particular switch, you'll find this is 6700. So as per the lower MAC address, switch 1 is the winner. Now if you go and check this particular interface, that the interface between switch 2 and switch 3, here you will find this blocking. So spanning tree WLAN 10, say for example detail. Now for WLAN 10, you'll find that few of the ports, so this is root, it's okay, 00. You'll find blocking, and you'll find ports here in switch 3. A few of the ports are in blocking stage. Okay, so this is related to STP. All these commands related to STP. So what are the big commands we have, or important commands we have? Show spanning tree summary. It will give you the summary, the spanning tree, and for that particular VLAN, you can check the detail like this. Then you can check, so spanning tree. So for example, sometimes we used to use filters as well. So for example, I can go and check include, and then um, we can filter certain things here. So for example, designated, or then I can add here designated, and say for example other also if I have. So everything is designated forwarding because of this is the root. So here you can see all the ports, they are coming like this. Yeah, so we have option, we can filter, we can add multiple filters as well. Here you can see that we have only 2 port address designated. All right, but what we have to do in this lab, that we have to go and run the RSTP. So I'll go to the switch and we have to change the mode. So spanning tree mode is, and if I type question mark here, you can see that you have mode MST, PVST, and rapid PVST. Now, if you are changing the mode for rapid PVST, you should do this to all the switches, correct? So we'll go here and paste that command to all the switch. Then these switch will get converged. Once these switch will get converged, now we can go and check show a spanning tree, and you have the same options here, correct? So here you can see that for MST you have some other option, but show a spanning tree, and then we can go and check detail. Inside detail you can see that VLAN 1. I don't want to check VLAN 1, but still VLAN 1 is executing RSTP compatible spanning tree protocol. You can check this. Better I can go and run the command show spanning tree VLAN 10 and then detail. So we can check only VLAN 10 commands. Now we will see that the port role will get changed. So DP will be DP. There is no problem on that in switch number 1. But if you go and check this in switch number 2 and 3, as per the rapid STP, the designation will get changed. So this is root, it's okay, designated forwarding, designated forwarding. Now here you can see this alternate blocking. So now you can see that the designations are getting changed. The role of the port is getting changed. So VLAN 10, so spanning tree, VLAN 10 and detail. Now here also you can see this is the forwarding, alternate blocking, alternate blocking. Alright, so this is the way that we can go and run the RSTP and then we can verify that. Alright, so we can verify like this. Again, if you want to check more options, you can go to show spanning tree VLAN 10. If you want to check root and then other options, here you can see that you have options related to priority, port, hello interval, details, cost, etc. etc. Then if you want to check some other stuffs, here you can see if I go to a spanning tree, again if I want to check the bridge and then the protocol, and if I press enter, so here you can see it is running in RSTP. Same thing that we have in STP, there is no much change, slight change in the configuration, but the verification options are the same for STP as for the RSTP as well. Next topic we have multiple spanning tree, MST. Now why we use MST, and it's very interesting that we should go and check the generation or the evolution of a spanning tree protocol. We have three different types of spanning tree protocol or STP. We have common spanning tree protocol where you have a single instance of STP for all the VLAN. Then to optimize that, we can use PVST or PVST plus, that is per VLAN spanning tree. Say when we have single instance for all the VLANs, so for example, I have VLAN 10, 20, 30, 40. At the moment you enable the STP, you'll find that that STP is running for all the instances of VLAN or all the VLANs. Rather than we can go and optimize this behavior with PVST, PVST plus, but still further we can go and enhance this process with help of MST. Because the problem with PVST or PVST plus is that you have to maintain a separate STP instance, and that will be overhead in terms of CPU and memory for the switch. So if you have, say for example, thousands of VLAN, so at that time it's actually very difficult for switch resources to manage that much amount of databases. Now what we can do in multiple spanning tree is that multiple VLAN instances can be mapped with one STP instance, or multiple VLANs can be mapped with one STP instance. By default they will be mapped with MST0, but we can create from 0 to 15, means total 16 instances of MST is possible to create. Now here you can see that each MST instance, that is MSTI, builds their own RSTP topology database, including electing its own root bridge. Now the selection of root bridge and the various parameters are almost exact that what we are doing in the STP. Only the way that we are going to configure is different. So how we are going to configure the MST? First of all, obviously, we have to change the mode of a spanning tree to MST. Once we change the mode, then MST further separates the STP topology into regions, means we have to define the regions. All switches in region must be configured with identical MST parameters. So what are those parameters? We have 32 byte of configuration name, 16 bit of revision number, and then we should do VLAN to instance mapping. Now what all these things you can see here in the configuration, even in the lab also you can understand more about all these terms and terminologies. Now here you can see that important information that if two switches are configured with different MST parameter, they belong to different MST region. We can have up to 16 MST instance, 0 up to 15. So suppose if uh, I just started MST, so what will happen? Obviously, everything will be fault inside MST 0. So if you do not do any configuration, simply you enable the MST, they will fall under the MST 0. We have this internal spanning tree is responsible for maintaining the topology for the entire region and all the MSTs. Only the IST can send and receive BPDU and encapsulate the MST information within the BPDU as an MST record or M record. The IST is always mapped to instance 0. So we have internal spanning tree as well, who is going to map or manage all the record inside the MST0. MST is compatible with other implementation of STP, and MST region is uh, obfuscated from non-MST switch, which will see the entire MST region at STP or RSTP switch. So it's not that, say, once we have multiple VLANs, so for example, I have VLAN 10 to 20, 21 to 30, I can map with MST instance 1, MST instance 2, etc. But still, they are compatible or backup compatible with other MST as well. Okay, and those information will come as a non-MST region. So it's something like you have MST, STP, and then you have non-MST STP. They are compatible. Alright, how we are going to configure? First of all, we need to change the mode, and then we have to go inside the spanning tree configuration. We can give the name, revision, and then we have the instance to VLAN mapping, and that's it. Once we do the instance to VLAN mapping, we can go and check the pending. And earlier I told you that the way that we are configuring the STP, like how you're creating the primary or secondary or root or etc. Likewise, we have to do the things in MST as well. Okay, so the commands are very much similar. Instead of VLAN instance, they will be the group of VLANs or the instance mapping. Okay, so what we are doing inside MST is that we are mapping various VLAN to one instance. So instead of running the commands over VLAN, that is the default nature of traditional or the STP 802.1d, we are running the command with respect to instance. Now, where this instance is pointing to, it is pointing towards the group of VLAN, right? So this is the way that we can utilize the resources efficiently. If we have the VLANs, we can group those VLANs, we can map with the various instances of MST, and then behind the scene MST will work with those groups, and the overall performance for the switch, say for example the resource utilization, the CPU capacity, memory, etc. will be efficiently utilized. Alright, so let's stop here, and in this section we'll perform the lab task. Let us perform the lab task related to MST. So first of all, what I will do that I'll go and create say VLAN 10 to 100, because we are going to map these VLANs with MST instances. So in all the switch, I'll go and do the same. So now we have VLAN 10 to 100. and we can go and verify this VLAN. I can see that you have these many VLANs that I can map inside the MST instance. So what will be the command number one? That I should go and change the spanning tree mode. So now the spanning tree mode is MST, and I should do this with all the three switches that we have. So let me go and go to the configuration mode and oops, conf t and copy paste this mode command. Again, I'll go to conf t and do the copy paste. Now what we can do, that we can go to the spanning tree and MST configuration mode. Once you are here, you can see that what options you have. You can go define the name, revision, instance. So we'll do that. First of all, I'll go and give the name. So for example, my MST. Then the revision, for example, revision is 2. Then we have this instance. So instance and VLAN, say for example, instance 1, and then the VLAN range is from, say for example, 10 to 50. Then then we have instance 2 VLAN 51 to 100 that we have created. We can go and check the configuration with show pending. So here you can see that you have a VLAN instance, and whatever VLAN that we haven't mapped here, you can see that they are mapped with MST0. Correct? So now we have two instances like this. Great. Now once we have this, then I can exit and we can run the normal spanning tree command. So we have show spanning tree MST, and then we can check the configuration. We can go and check the detail. So instead of MST, you can think like you are running spanning tree VLAN. So instead of VLAN, you think like MST. That's the command. So we don't need to memorize the commands and all. So here you can see this in detail, and the port ID, priority, and everything is in detail. Now different type of VLANs actually is mapped with the MST instance, so that's why it is looking like this. Likewise, I can go and run this command to other switches as well. So I should go and change the mode to MST, then we should go to the configuration mode and run these commands. So let's do it, and we can verify with show pending, and then we should go here and do this here, show pending, and then we can exit and exit. Now we can go and check show spanning tree MST, and if you want to check the details, we have the detail option. If you want to check any of the interface, we can check that also. If I have my MST, that's the name of my MST. So MST instance list, say for example, if I give a word, and let's verify this. So what word I have here, you can see that show spanning tree MST. You can see the output in detail, and this is the name. And if I go here and check the output, say show spanning tree MS3, this is not supported here. So if I give, say for example, number like MST1, Not like that, but we can go and give the instance list that we have. So what instance list we have created that we can actually verify in the configuration. So we have instance 1 and instance 2. When I'm giving 1, so MST1 is coming like this, and if I give 2, it is throwing error for 2. And if you go and check, so MST in detail, so we have MST0, we have MST0, we have MST1, and that's the reason. So it is showing only 2 instances. Rather, if I go here and check the instance in switch number 1, and if we go and check 2, we don't have information for 51 to 100, like MST2 is not created, but it's okay. This is the way that we can go and map the VLAN to the instance mapping, and then we can go and verify the commands as well. Now, one last thing, that if you want to change the priority, because switch 3 is having the lowest uh, it's the highest MAC address, so its priority is lowest in terms of selecting the root bridge. That's why here you can see that who is the bridge, who is the root. So root is the switch number 1 because its MAC address is the lowest, but if you want to change it, you can go and change spanning tree, MS tree, and then you can go and check the, let me quickly check the configuration. So we can do like this. If you want to change the priority, we have, say for example, VLAN 10. You can see the priority is there. Now this method is for the STP, but here we are focusing to MST, and then the instance, say for example, instance is 1, and here you have the priority. So this, we have two options. Either we can use the priority command or the root command. I just wanted to make this switch as a root, and we can go and give him a root primary. And now if we go and verify the MST command, so here you will see that who is the bridge and who is the root. So this switch for MST1. So now this priority automatically get decremented, and now that switch 3 becomes the root. Now you can see their port status is changing. Initially it was forward blocking, but now everything will become forwarding because now my switch number 3 is the root switch. Okay, and same rule is applied for STP as well. In STP you have to give the VLAN, in MST you have to give the instance ID. Alright, so let's stop here. Now we reach to 3.2. 3.2 is belonging to layer 3 technology. In layer 3 specifically we have to learn about routing protocols such as OSPF, EIGRP, and BGP. So let's start with OSPF. Now OSPF, that is Open Shortest Path First Protocol, is a link state protocol like ISIS. Now what link state protocol is doing, that instead of sending the entire topology table hop by hop, they are sending the state of a link to the neighbor device. Now how this technology is working, and let me try to draw here. So generally all the link state protocol, they are forming first of all the neighbor table. So they are sending the update to all the adjacent device or the neighbor. With help of neighbor table, they are forming the topology table. Sometimes we are referring this as a entire database as well. And finally, they ran the SPF algorithm here. From the topology table, they are going to form the best path, that is the routing table. So we have three different types of table: neighbor table or database table, topology table, and then finally the routing table. Now the mechanism behind this and the theory behind this we'll see in upcoming slides. So OSPF is entirely dependent upon areas. Generally, we are telling that we have one backbone area. So here you can see that you have area 0, and logically all the areas are connected with area 0. Now these areas are 32-bit. They can be a flat number, or you can define like in dotted representation 000 like this. Areas has continuous means area. You can see that you have area 0 and then area 1, 2, 3. Um, so maybe you can think that can't I connect area 3 with area 5 or 4? Yes, we can do that connection, but you can see that area 4 is not directly connected with area 0. So somehow I have to create tunnel, or the area 3. Uh, I have to create area 3 as a tunnel, or we have to use some sort of virtual link. So area 4 can think that is directly connected with area 0. So such type of arrangement we need to do, and then the link state advertisement will flow from one place to other place. That's the LSA, correct? Now OSPF send LSA when there is a change to one of its link, and will only send the changes in the update. LSAs are additionally refreshed by after every 30 minutes. So how we can summarize it, that OSPF is a link state protocol dependent upon area. They are sending their LSAs or their advertisement to all their neighbors, and with that they are forming the neighbor table, topology table, and finally the routing table. Apart from that, that OSPF traffic is multicast. They are using 224005 for all the routers and 224006 for the designated router. The theory behind this we can discuss in upcoming session. They are using the Dijkstra shortest path first algorithm to build the routing table from the topology table, and they are supporting the variable length subnet mask. So here you can see that first of all they form the neighbor table, then they form the database, then they do their algorithm, that's the SPF algorithm, Dijkstra's SPF algorithm. Finally, they will form the best path table, that is the routing table. OSPF supports IP routing. Their AD value is 110. Their metric is cost. They are going to form the neighbor table, topology table, and routing table. Uh, all the areas should be supposed to be connected with a backbone. That's the area 0. If we have non-backbone area connected with any other area, then you have to create tunnel or virtual link in between that. Now, suppose we have such type of topology here. You can see that I have area 0 connected with area 1 and area 2. So now what we are going to tell about these devices, these routers, router A and C, they are termed as a ABR, area border router. They are termed as a ABR, area border router, because they are in the border of different areas. Okay, and we'll see that according to that the routes are also going to get reflected. So when we are talking about the routes, you'll find that you have O routes and then OIA, that is OSPF intra area. So you have two type of route, OSPF intra area route, that is this. Then you have inter area, across the area, that is this, and we'll see that we have E1 and E2 routes as well, that is coming from the external as well. Now if you see this diagram, it's actually very simple, straightforward, that we have 2 or 3 routers in area, but assume that if you have 50 or 100 routers in area. And suppose if I have 200 routers and all the 200 routers are inside area 0. So at that time what will happen? The computation means to run that SPF algorithm becomes CPU intensive rather than if you have a small areas and then you have 50 device, 100 device and 50 device in those areas. So in that case all the areas they will run their independent SPF algorithm and then they will send the update to the backbone. So in that case, the way that we are going to run the SPF algorithm, or in other words, the process, the CPU utilization, the memory will be optimized and will be used betterly because now you are running the SPF algorithm across small areas, and then those areas are going to send their LSAs to the core or to the other areas. Correct? So that's the thing, and that when we are that's why we don't have only area 0 rather than we have multiple logical areas, and then we are going to divide the devices or the routers inside the area. Then here you can see that suppose in case that if you have device and that is not connected with the area 0, so in that case you have to create the virtual link, the device which is separating the area, they are termed as a ABR. Then you have internal router, then you have backbone router. Again, these are just the terminologies. All right, now here you can see that you may have chance that you are connected with non-OSPF protocol. So you are getting the route, say for example, from the EIGRP domain. So in that case, that router is termed as a ASBR, Autonomous System Border Router. So now here you can see that C and D, they are ABR, Area Border Router, but router G is ASBR because now the routes is coming from the other routing domain to the OSPF. Okay, so uh, here you can see that if we have any other routing domain that will term as a separate autonomous system, and then you have to do the redistribution. Obviously the router G will do the redistribution from EIGRP to OSPF when it is coming to OSPF, and OSPF to EIGRP when you are sending your update to the EIGRP domain. Now in that case we have E1 and E2 type of area. Now what is E1 and E2? Here you can see by default it will be OSPF external area type 2, that is the E2. So include only the external cost to the destination network. External cost is the metric is cost advertised from outside the OSPF domain. This is the default type. Then you have E1 that will also have the metric value, that is the cost, but this will be additive, means it will add the cost per hop per router. So include both the external cost and the internal cost. So that's why you have the external cost plus the internal cost to reach the ASBR to determine the total metric. But E2 having only the external cost, that will be constant. So in summary, here you can see that you have internal routers, that all router interfaces belong to only one area. You have ABR, you have ASBR, you have backbone router that is inside area 0. Okay, so this is the baseline summary for the OSPF routing protocol. In the upcoming sessions, we will learn more about OSPF terminologies, and we have to perform the lab as well. So what type of LSAs we have in OSPF? OSPF has a long list of LSAs. We are going to discuss the top 5 at least because these we are going to use more and more in the course. So we have LSA, here you can see type 1 and type 2. Now these type 1 and type 2 LSAs are reside within the area. They are very much area specific LSA. Then we have type 3 and type 4 generated by ABR, area border router. They can flow from one area to other area. We'll see in the upcoming slide. And then we have type 5 LSA that is generated by Autonomous System Border Router, means non-OSPF protocol. They are going to generate that. Now here you can see the detailed explanation of all the LSA. Type 1 is LSA and type 2 as well. They are within the area. Use of type 1 LSA is that they have the link, obviously, the status and the cost of all those links, and they are generated by all the routers in a network. So you can think that type 1 as a default LSA generated by all the routers within that area. Then we have type 2 LSA generated by DR in the OSPF network or OSPF domain. Again, this is also specific to the area. When we have the broadcast type of network, obviously that time the DRBDR will come into the picture. Then we have the network summary LSA, that is type 3. What it is doing, that generated by ABR, and this can be used for inter-area communication. We'll see that all the places you have this inter-area link. So you have area 0 connected by different areas, and all these AB are shown in the diagram. They are going to generate type 3 LSA to do this inter-area communication. Then we have ASVR summary. Now the next question here is, suppose from OSPF inter-area, you have to reach to non-OSPF domain. So for that reason, we have Autonomous System Border Router Summary LSA, means somehow you need to reach, or somehow we have a route to reach to the non-OSPF protocol. Then we have external LSA type 5. Now this is generated by the ASBR, and this information will be flooded inside all the areas. So all the areas, if obviously you have the redistribution, all the areas should know how to reach to the autonomous system border router or the network behind the ASPR. We have type 6 as well, that is the multicast OSPF, type 7 as well, that is not so stubby area. And this type 7 is actually very important, and we'll discuss this later on. Now here in the diagram you can see that you have area 1, area 0, area 2. So belonging to area 1, area 2 and area 0, you have this router and network LSA, means type 1 and type 2 LSA will be generated in that. Then you can see that router C and D, they are ABR, so they are going to generate the type 3 and type 4, and the router G is belonging to ASBR, he is going to generate type 5 LSA. Okay, great. Then how this OSPF is going to form the OSPF neighbor relationship. So if you go and connect two OSPF or two routers in between, so suppose for sake of simplicity, I have only two routers connected in a network. So in that case, what will happen? Suppose I have router 1 and router 2, and these two routers are connected, or they are inside area 0. So obviously these routers, because they are within the area, and suppose if it is a point-to-point network, then they will send and receive the router LSA, correct? So what will happen, that they are going to send their hello packet in the point-to-point network or in the broadcast network. This hello timer is 10 seconds and dead timer is 40 seconds, so it's 1 into 4. And in the broadcast network, actually in the NBMA network, that will be 30 seconds, and then the dead timer will be 30 into 4, that is 120 seconds. So they will send and receive, they will exchange their hello packets, and if they are matching certain criteria while sending and receiving the hello packets, then they are going to form the neighbor relationship. So here you can see that what will be what are the things inside the hello packet, or what are the fields inside the hello packet. They contains area ID, area type, prefix, subnet mask, hello interval, dead interval, network type, and authentication. Basically it is termed as that they have 8 field inside hello packet, and you should match at least the area ID, the subnet mask, hello and dead interval, authentication, etc. So some fields are mandatory that should match in between two routers to form the neighbor relationship. Okay, so here you can see that a neighbor table is constructed from OSPF hello packet, which includes the following: the router ID, the current state, directly connected interfaces, and the IP address of the remote interface of each neighbor. We'll see that in the lab section, and we'll go and we'll run the command show IP OSPF neighbor, and then we can see the specific about the neighbors. Now the next topic here is that OSPF designated router and backup designated router. So what is happening and how they are going to form the DR BDR, or how they are doing the selection for the DR BDR. Let's discuss about that. So here you can see in the diagram, first of all, these devices, they should have their priorities. So let me show you what I try to tell here. I should have slide for that. Yeah. So here you can see that these devices, they have their unique identification. That's the router ID. All the routers in a network, they have the router ID. We can configure it manually, or suppose if device has the loopback interface or they have the physical interfaces, first of all they will check the loopback interface if you are not doing it manually. So that loopback interface will become the router ID, or the highest physical interface will become the router ID. So they should have the router ID. That will be by default if you're not doing it manually. Once they have router ID, then they are going to do the DR-BDR selection, and this selection will happen only in the broadcast network. So here you can see in the diagram that if we have router ABCD connected with a shared network or the broadcast network, so at that time they will go and select the DR and BDR. Okay, now what will be the selection criteria here? The DR BDR selection are determined by the router's priority, which is configured per interface basis. The router with the highest priority becomes the DR, and the second highest will become the BDR, and the rest are DR brother, something like DR, BDR, others. Okay. Now, if there is a tie in the priority, whichever router has highest router ID, that will become the DR. Now we can go and set this priority like this also, like we can go to the interface and we can set IP OSPF priority, and then we can force to make certain device as a DR or BDR. Now, by default, the priority will be 1. So obviously the selection will happen with respect to router ID. So whoever having the highest router ID in the network, that will become DR, BDR, etc. like that, in that manner. Suppose if you don't want that certain routers or device will take part inside the DR, BDR selection, so you can go to the interface and you can set the priority as a 0. So if you set the priority as a 0, that device will not take part inside the DR-BDR. Okay, so what are the important things we have studied in this video? That type of LSA, then how they are going to form the OSPF neighbor relationship, what are the important fields you have inside the hello packet. All the devices, they are sending the hello packets to the peer devices or the neighbor devices to form the neighbor relationship. Then how they are going to form the DR-BDR selection. Again, the router ID will be important factor here, and as per the router ID, they are going to form the DR-BDR, because by default we are not setting the priority. By default the priority will be 1, and according to the router ID they will select who is the DR, who is the BDR. Let us learn more about OSPF neighbor state, and then I'm going to perform a small lab task where we'll understand more about the OSPF process, OSPF actually neighbor process, and even the baseline commands of OSPF as well. So now when the OSPF, the first stage is that they have to form the neighbor relationship. When they are forming the neighbor relationship, at that time they are exchanging, or they are going through process, or they are going through multiple steps. So what are those states we have? Here you can see that they will start with a down, init, two-way, etc. So in down state indicates that no hellos has been exchanged, but the actual process will start from the init state. Init state, the devices, they will start sending their hello packets. We know that inside hello packet we have some important fields. Few of them are mandatory, like the area, like the authentication, uh, the network subnet, etc. So few of the fields are mandatory, that two sides or the neighbors, they should match those mandatory things. Then they will go to the two-way state. By the end of two-way state, uh, the devices, if they are in the broadcast network, they have to select the DR and the BDR. And by the end of two-way state, the devices, they are forming the neighbor relationship. Okay. Then we have the external start and external exchange. Now external start and exchange is a state where the devices, they have to select that who is the master and who is the slave, so they can exchange their databases. So obviously the devices, they are sending their link state or LS information to each other to build the database. Once they have the database as per the uh, master and slave entry, as per the master and slave role, they have to exchange their LS type. Correct? So someone may sending, say, link state advertisement, someone may asking link state request, so LSA, LSR, those things are going in depth when we are talking about the exchange state. Then we have loading, where all the devices, they have to sync their database, and by the end of this loading state, the OSPF process, they are forming the topology table. Remember, we have three important table. We have neighbor table, so by the end of two-way state, they will form the neighbor table. We have topology table. By the end of loading, the devices will form the topology table. And finally, once they have the topology table, on top of that, the devices will run the SPF algorithm, shortest path first algorithm, and then they have to form the routing table. We'll see that if we have the broadcast network, then they will have the rules like DR, BDR, and DR other. All right, so here you can see that suppose in broadcast network, if we have these rules, this DR other, they will go and stop at the level of two-way, because what is happening in that situation, in that case, is that you are giving the authority to DR and BDR to exchange all the LSs with all the other, rather than all the other DR others, they are exchanging their database packets. So that means they will stuck at the two-way state, means all the DR others, they will stuck at the two-way state. They will not have the full authority to exchange the databases. Correct? All right. So we have a small lab topology. In this first lab, just to start with, what we are going to do, that we will go and initiate the OSPF process. So let me show you this. Although we have this master lab topology, what we can do as per our requirement, will go and use it. So what does it mean? That we'll go and make these devices, so for example R1, R2, and switch 101 within area 0 at the moment. So they will be the part of area 0. And this switch that you are seeing here, switch 105, that I will make as a switch only. Later on we will make this as a L3, but at this point of time, I assume that I have R1, R2, and switch 101, and the IP that I am going to use, the IP will be, say, let me write here the IPs, and according to that I am going to configure the lab. So the IPs that I want to use is, say for example, 10.1.11 and 10.1.1.2 as per the name of the devices, and here, so for example, 10.1.1.101. They are inside the same broadcast network, so you can see that they will go and form the DR and BDR. Loopback addresses I will give like 111, and then this I can give 2222 as the name of the device, and this I will give as 101, 101, 101, 101. Okay, we are going to initiate the OSPF process inside area 0, and then we'll see that how they're going to exchange all those hello packets and the important LS type. All right, so let me go and log into the lab devices. All right, I logged in, and we know that we have other interfaces and links also connected that I don't want. So this is the topology that we have. What I can do here, that I will start with 101 E1/2. So let's do that. I can go to, first of all, let's see this neighbor, and I want to shut down few of the interfaces that I don't want to use. So for example, I want to use only interface 1/2, so 0001 and 1/2. So 0001, so I can do one thing, interface range E0/2 to 3, shut down, interface E1/0, shut down, because I want to use 1/2 only. So rest of the interfaces I'm making shut down. Like that, 1 also I want to make shut down. If I go and check show CDP neighbor, so I have 0001 and 12 that I want to use. Now next I will go to switch number 2. So switch 2 is not required in this particular lab, so leave it. Then I'll go to switch number 5, and we should check this E1/2 configuration as well. So I will go here and check E1/2, and what is configured here? Nothing is configured. If nothing is configured at this point of time, at least what we can do is we can make this interface as a switch port. Okay, so here you can see this capabilities R, S, and I, and that I don't want. I'll make this as a switch port. Then we'll go back to the switch number 5. Here you can see, and the interfaces we have is 0, 0, 1, 2, 3, and 10/0. So apart from that, what I want, that I want to make other interfaces as a shutdown, and we have so many interfaces here. You can see, even we can leave it as well, just to check the configuration for any of the interfaces. Say so run interface E0/0 that is connected with router number 1, and then router 2. So these are the interfaces connected. I don't want to do anything. Rather, I will do one thing, that interface range E0/0 up to, for example, 4 maybe, and 3. I'll make this as a switch port and no shutdown. And then interface E10/0 that is connected with switch number 1. That if you see here, switch number 1, what interface we have here, let me scroll up, 10/0. Yeah, so I can go here, interface E10/0. I'll make this also as a switch port, no shutdown. Alright, so we are very much good with switch number 1 and switch number 2. Here again I can go to interface E1/2 and make this as a switch port no shut. Alright, so let me quickly see here that what I exactly required. So E1/2 should not be switch port. It should be a routed port. So I'll do no switch port and then I'll assign the IP address. So for example 10.1.1.101, and then I'll create one loopback, say loopback 0, IP address 101 and 101.101. So what I have done here, we can check show IP interface brief. So I have interface E1/2 and one of the loopback interface where I have assigned the IP addresses. Okay. All right. Great. So now we can go to R1 and R2 and the interfaces you can see here. So I'll go to R1 first and I can go to interface E0/0. I'll assign IP 10.1.1.1 and then I can do ping just to check that the far end switch is reachable or not. So it is reachable, then I'll go and create one loopback, say 0, and IP address I'll give 111 to that loopback. We'll go and check the show IP interface brief so you can see that we have the IP configured here. Now let's go to R2 and inside R2 we have interface E0/0. I can go and give the IP like this and then I'll create one loopback 0 where I can give IP related to as per the diagram or as per our schema 22222, and then let me try to ping first of all within the same network. Obviously everything is inside the same network for this example. So what I'm doing that I'm pinging to all the devices from R2. So now we have the baseline IP address connectivity connected. The thing here is that we are going to enable the OSPF to all these devices and we are assuming that all these devices are inside area 0, correct? So let's do this and let me go back to the lab. Yep. So before doing that, at least one of the device I want to enable the debug. So I want to enable the debug OSPF packets and events. Debug IP OSPF packets, and then I want to enable the events as well. Okay, let's do this OSPF configuration. So we can go to router OSPF and then you have to define the process ID, say 1 I'm giving at this point of time. Then I should go and advertise the network. So network is, I have two network, one is 10.1.1.0. I can go and give the wildcard bit inside area 0. So this is the format that we can go and enable the OSPF. And at the moment I enable that, you can see that we have event because we have enabled the debug as well. We can see that this router using this multicast address and the router ID is get selected as 11111. We have discussed this earlier. If I go and check show IP OSPF, you can see the red router ID is 11111 and we have the other information as well. Okay, so we have the OSPF configuration and periodically he is sending the hello packet. We can go and check the configuration for that, what we have done. So we have enabled the OSPF process, and then we have advertised the network, correct? So likewise, I can go here and initiate the OSPF process here as well. Then I can go and I can assign the router ID via the CLI command as well, means manually as well. But if you do not do this, automatically they will take this loopback, highest loopback address as a router ID. So then I have network 10.110.0.0.0.255 area 0, and then I have network 2222, say 0.0.0 area 0. Alright, and let me see that what configuration I have done here. Now they try to exchange this neighbor relationship. From there they will go and form the topology table, and finally they will go and form the routing table as well. Okay, so let me quickly see that what command I have given here for the network. Because we have used /32, that's why I have given 0.0.0.0.0. Now somewhere you will find that you are moving to loading to full state, and here if we can see that information in the log message. So we have enabled the debug and OSPF authentication is 0. We haven't put any authentication, so it is telling that OSPF authentication is 0. And here you can see that we have this loading to full message. If you go and check show IP OSPF neighbor, then you can see that you have DR BDR selection already happened. For router 1, he is telling that router 2 is BDR. Now if you go to router 2 and if you check show IP OSPF neighbor, you can see that he will tell who is the DR. So for router 2, this 11111 is the DR, what is the interface, what is the IP address that we have discussed earlier. Now I'll go to switch number 1, and here also I'll go and do this router OSPF say 1, and then I will put the network, for example, the loopback address that we have 101.101.101.0.0.0.0 area 0, and then I'll put the network that we want to form the OSPF relationship. So we have network and with the wildcard bit 0000 to 55. Alright, and within area 0. At the moment I'll do this, I can go and check show IP OSPF neighbor. Now you can see that he is seeing that who is the DR and who is the BDR, correct? The third device. Now if you go here and check the OSPF neighbor, you can see clearly that DR other. So now this IP is DR other. We haven't assigned the router ID manually, but here you can see that they can detect it. Means the router process can go and assign what will be the router IP or router ID for these devices. We can go and check like this, show IP OSPF, and you can see the ID. Now if you want to filter and use that, I try to do with this command. Simply you can go and check the ID. That will tell you who is the router ID. Alright, so this is the way that they are going to form the DR and BDR. And if I have one more device in the DR other, then you could find that the process will stuck as two-way state. Okay, so what I'm telling here is that if I am here and if I have one more device connected to this guy here, and that is also working as a DR other, then these two devices, they will stuck as a two-way state. They will not exchange the entire topology and database tables, etc. All right, so let's stop here. In this session, I'm going to cover OSPF network type, metric, and passive interface. And next section, we'll do the lab related to this. Now, if you go and check the syllabus, so let me quickly show you the syllabus. In this syllabus, you'll find that in 3.2, you have to learn about OSPF and you have to compare with EIGRP. So for that, what I'm going to do, that I'm going to cover EIGRP in different series of videos. So once we know OSPF, once we know EIGRP, it's easy to compare. Then in 3.2b, you can see that we have to learn, understand more about OSPF. And that's the thing we are doing at this point of time. So let's quickly understand the network type, OSPF metric, and the usefulness of passive interface. Now, OSPF is supporting a wide variety of network type. Here you can see that in OSPF, you have these many network type support. Now, how to memorize this, because you can see it's a big number, this network type. So you can think like this, that you have point to point and you have, see here, so point to point, and then you have point to point, point to multi-point, broadcast and non-broadcast, like you can think. So you have network type broadcast, and then you have network type non-broadcast, and then again if we add with point to point and point to multi-point. So now point to point, obviously we know that point to point is just point to point network, two devices are connecting with each other, it's a point to point network. Then what about point to multi-point? So here you can see that point to multi-point non-broadcast. So you can think that you have point to multi-point broadcast and non-broadcast. Okay, so that means you have 1, then 2 and 3. Apart from that, you have network type broadcast. So you have network type broadcast and you have network type non-broadcast. That means you have total 5 different type of network support. Now again, if you go and check the nature of the broadcast and non-broadcast. So if it is a broadcast, that means the DR-BDR selection will happen and the neighbor will form automatically. Means you don't have to write the manual command to form the neighbor relationship. Correct? But if it is a non-broadcast, and suppose if DR-BDR is forming, you can see that the hello is unicast multicast. When you're seeing unicast, means you have to go and use the neighbor command. So you have to manually form the neighbor. Correct? So once we know about the broadcast and non-broadcast, and again you can see the timer as well. For broadcast network is 10 and 40, and for non-broadcast is 30 and 120 seconds. Correct? Now same concept we can use here. So here you can see that point to multi-point. You can think this is a point to multi-point broadcast. So that's why it's a multicast. Hello. They will not form the DR-BDR because again it's point to point, and you have so many points to point to multi-point. You can think like this. So whenever you have point to point network, you are not going to form the DR-BDR because just two devices. Why you will form DR-BDR? Then I get point to multi-point non-broadcast. Now this is non-broadcast, so that's why you have to go and use the neighbor command to form the OSPF neighbor relationship. That's the whole summary we have for the OSPF network type. So let me go back to the theory. Now here you can see that it's a broadcast. So it will do DR-BDR selection, then it is using these multicast addresses. Because this is a broadcast, they will not form the neighborship manually, automatically they will form. Point to point, no need to define the neighbors because you have only two ends. They will form the neighbor relationship. Their timers will be 10 and 40 seconds. They are going to use the multicast address. But again, point to multi-point as well. Everything that is valid here for point to point, it will be valid for point to multi-point as well. Okay. Now Then we have non-broadcast. Whenever we are talking about non-broadcast, then you have to go and form the neighbor relationship manually. Now OSPF will elect DR and BDR, but neighbor relationship will be manual. And that's why we have this summary. This summary, it's easy to memorize, even no need to recall, but just will make a point that okay, you have point to point, point to multi-point, non-broadcast, point to multi-point broadcast, and then you have broadcast and non-broadcast network. How we are going to do the configuration? Configuration part is actually very easy. Only one command is there to define the network. You have to go to the interface. Suppose you are over this serial interface, you go to the interface and use this command IP OSPF network. Suppose if you go and type question mark, then you'll get all the options. So is it a broadcast? Is it a non-broadcast? It's a point to a multi-point, etc. Each and all these options you will get. And if it is using unicast method, means if it is a non-broadcast, then you have to go and define the neighbor. Otherwise, rest of the configurations are standard OSPF configuration. So for example, NBMA, non-broadcast multi-access. So here we are going and defining the network type is a point to multi-point, and if it is a non-broadcast, then you have to go and define the neighbor, right? So just refer this summary and things will become easier. Now OSPF is using cost as a metric. Here you can see the speed and the cost. So for example, for fast Ethernet and above, your cost will be 1, and then you can see for token ring for Ethernet, for token ring 4 Mbps, you can see the cost. Now the lower is better. So if lowest cost is there, that will be the preferred path in the route selection. How we are going to do the basic OSPF configuration, although we have done one lab, so there you have seen that you can go and initiate the OSPF process. You can define the router ID, otherwise it will take the highest loopback or highest physical interface if it is not configured. Then you can define the area, and that's it. So this is the baseline configuration. Now here interesting thing is that we are defining the wildcard bit. And now it is recommended that if you know the exact subnet, so according to that you can use the exact wildcard as well. So suppose if I am using point-to-point network, so I can use, say for example, 172.168.1.0. So here it's 17. So 172.171.0, and then I can use wildcard 0.0.0.3. So like that we can go and use the wildcard wisely. What will happen if we go and initiate the OSPF process, and once we start advertising the network, or once we put this network command, then they will send the hello packet, the neighbor relationship will start working. We know that as steps down, init, two-way, X start, exchange, loading to full. First they will form the neighbor table, then topology table, and finally they will run the SPF algorithm and we'll get the final OSPF routing table. Correct? Now the final thing here in this recording, as was the theory, the passive interface, the concept of passive interface. Now suppose if you don't want to form OSPF relationship, then you can go and make any of these interface as a passive interface. So suppose if I make this interface as a passive, then you can see that the passive means the command prevents update from being sent out or received from this interface. So if I go here in this example, it is showing this interface. So if you go and make this particular interface as a passive, or any interface as a passive, they will not participate in OSPF neighbor relationship, means they will not send or receive the updates. And that's the usefulness of passive interface. But generally how we are using this command is we will do this thing, no passive interface E0. Here you can see, first of all, we'll make all the interface as a passive. So the command one is passive interface default. Suppose if you have 10 interface, that means all the 10 interface, you're not sending and receiving the updates. And then you will go and add the interfaces one by one where you want to send or receive the updates. Okay. We have one important note here that the passive interface command will prevent OSPF and EIGRP from forming neighbor relationship out of that interface. No routing updates are passed in either direction. So this passive interface is true not only for OSPF, but this is true for EIGRP as well. So we are going to stop here, and in next section, I will show you a few of the things that we have a study here, like network type, how you can go and change the network type and you can enable the passive interface. Let us do the lab. Here you can see the topology. We have router 1, router 3 and switch 101. I'm using in between switch 105 as a L2 switch. So that means I have area 0. So this big blue circle is area 0 and the network is 10.1.1.0/24. Then I have switch 101 and 102 connected. That is inside area 2020, and the network is 10.1.102.0. So 101 is dot 1 and 102 is dot 2. I have already assigned the IP address. So what we'll do, we'll go and enable the OSPF process. Then we'll go and check the default network type, and then I will make any of the interface as passive interface inside area 0, and then again we'll verify the OSPF neighbor relationship. So let's do this. I can go to router OSPF 1, and even if we are here, we have option that we can run the script as well. So if you are doing the configuration over empty putty, you have this option for a script, say conft router OSPF 1, and then you can advertise the network as well. I can select the devices and then I can send the script. Now once OSPF is configured, then I should go and assign the, or I should advertise the network, or should I can use the network command. So what you can do here, you can go and check the IP route, your connected interface, and in the network command, actually, you can go and use it with wildcard bit, and we should check this 10.1.1.0 is part of area 0. So we know as per our topology this is correct. Then we have one loopback here that will be depend that in which area you want to put. This also I'll put inside area 0. And then I have one more network that is this guy here connected with area 20, area 20. So these are my network command. Likewise, I can go to switch number 2 and I can go and check the connected routes. I can use my network command. First of all, I'll advertise my loopback inside area 20. And then I have my network that is connected, that is inside area 20, because the bottom switch is actually everything is inside area 20. So that's why area 20, area 20. All right. So at the moment we run this command, you'll find that both the switches, they are now interfaces are part of area 20, and they will run the OSPF, and here you can see that the OSPF loading to full means all the states are completed. So I can go and check show IP OSPF neighbor. You can see full BDR and the interface as well. Then we can go and check show IP OSPF. Actually show IP route OSPF. So here you can see that you have the metric value and you have the AD value. AD is 110 and the metric is 10 plus 1. So that's why it is 11. We know that for Ethernet interface that is 10 and then 1 is for loopback. So that's why it is showing like this. Alright, here you can see the Ethernet. So for that we have 10 and then generally 1 it is using for loopback. Alright, next thing that I want to check here is that is show IP OSPF interface, and that is E0/0. Now here you can see that interface where the network type is broadcast. So what I can do that the switch is connected over E00. I can go to the interface E00 and I can make that IP OSPF network as point to point. Now here you can see that you have broadcast, non-broadcast, point to, multi-point, point to point. And if you go to point to multi-point and type question mark, you have point to multi-point. By default it will be broadcast, and then you have the non-broadcast like that. So I'm interested to make this as point to point, and both sides I should do like this. So other side also I should go, and I should go here to E0/0 network point to point. Now you can see that again OSPF process is running. It is going from full to down, and the SPF algorithm is running one more time. And then we have the new tree, SPF tree, and from there we have new routing update or routing table. Show IP OSPF and the interface is E0/0. Here you can see this network is now point to point. You can see this cost as well. There is other information as well related to timers, non-stop forwarding, etc. Alright, so we have done this task with these two switches here. Likewise, I will go and initiate the OSPF process, and I will advertise the network for R1, R2, and only R1 and R2. We don't have any R3. Alright, so let me quickly check here in switch 101 what is the complete OSPF configuration that we have done. So these three network, one network is belonging to the network that we have connected with R1 and R2, that is nothing but the area 0. And then these guys have one loopback address 111 inside area 0. And likewise I'll go here and then I will use 222 area 0 and then this. Now if I go ahead and check show IP OSPF network, here we have three devices who is forming the OSPF relation. If I go and check show IP OSPF interface, I want to check the interface E0/0. So here I can see that again the network type is broadcast. Now in our topology, either I can use network type as a point to point or broadcast, but we have seen that chart that as per the topology, suppose if you are working or dealing with frame relay, then you can use NBMA and then you have the mode for NBMA, correct? I don't want to make this as a non-broadcast. If you make this non-broadcast, so suppose if I go to R1 and R2, and I should know what is my neighbor, show IP OSPF neighbor, and if I go to interface E0/0 and if I make this IP OSPF network is non-broadcast, then I need to add the neighbor command manually. So now if you check your neighbor, you can say it's a down. Because in this case, you have to use this neighbor command. So you have to go to router OSPF1 and use the neighbor command. Who is your neighbor? So this guy is your neighbor. Then use the neighbor command. This guy is your neighbor. So manually we are adding the neighbor now. And here also it is detached. So these are my neighbors. I'll go to interface E0/0. IP OSPF network is non-broadcast. Then router OSPF1. We'll go and add the neighbor, this, and again I'll go and add one other neighbor. Then we can go and check show IP OSPF neighbor. Still this is down. Show IP OSPF interface and then E0/0. So now it become non-broadcast, but we are seeing here that the network is down because we are using the wrong network type here. If we have the NBMA type of, or if we have a non-broadcast type of network, then we should go and use here. Again, you can see this hello and dead timer is changing. Okay, so what I'll do here that I'll go and make this interfaces again backup. Interface is 0/0 and IP OSPF network is, say for example, broadcast. So one side is broadcast and other side is non-broadcast at this point of time. And now you can see it is forming the relationship with the switch 101. So if I go and check do show IP OSPF neighbor, you can see it is forming this. Likewise, I'll go here and again interface is 0/0. IP OSPF network is broadcast. And then we can go and check show IP OSPF neighbor. Alright, so now we have to test the final piece, that is the passive interface. So suppose if I go and make one of the interface over R1 as a passive, so let's do that. I can go to router OSPF1. You can see that we have this command passive interface default, and then you can go and make no passive interface. So once you do this command, all the interfaces become passive, means your neighbor is down. So here you have to use no passive interface, and that is the E0/0. E0/0 is the interface. I want to make no passive interface. And again, if I go and check the neighbor, so here you can see this is up. So that was the lab related to whatever we have studied in the previous recording. You can refer this particular lab. Next, we have OSPF authentication and virtual link. So let's start with OSPF authentication. Now, actually, it's very easy to configure and it's different than RIP and EIGRP. What we can do, first of all, we can go to the area. So here you can see I'm over OSPF, I'm inside area, I am putting area 0 authentication. Then I can go to the interface level and then I can go and give the authentication key. So we have two things. We have the plain text or clear text and then we have MD5. Now same way we can go and configure the MD5 as well. So again you have to go to area 0. Here you can see that I'm over area 0 here and the authentication message digest. Then I will go to the interface and then I can assign the message digest key. So it's very easy and straightforward. I'm going to show you in the lab section about the message digest key, this authentication. So more we can discuss in the lab. Now next thing here is what about virtual link? Virtual link is again one of the use case we have in OSPF, that for example due to any reason the customer network they are not able to directly connect with area 0. We know that all the areas should be connected with area 0. So suppose you have area 1, 2 and 3. For example, later due to some reason you are connecting area 4 with area 3, not with area 0. So in that case we can create the tunnel in between area 0 and area 4. So the router inside area 4, they will think that I am part of area 0 or I am directly connected with area 0. And that's the concept of virtual link. Again, you will see the configuration here. The configuration you'll find it's a very much like we are creating that tunnel. So router, the area 1 is working as a transit and then I have tunnel in between, say for example, area 0 and area other area. So let me go back here. So here you can see this is the classical example that you have area 0, area 1 and area 2 and then you are creating the virtual link in between that. Okay, now there are possibility that you may have area 0 and in between you have area 1 and that's again the possibility is less, but still you can create the virtual link in between that. Now once we create the virtual link, then over the area 0 we have put the message digest. So same key we can put over virtual link as well. Okay, so we have seen all these steps and let's perform the same task in the lab setup. So we'll understand more about the authentication and the virtual link. Let us perform the lab related to authentication and virtual link. I have done the change in my setup here. You can see that now we have R1, R2, and that's R2, but switch 105, then switch 101, and then switch 102. So R1 switch, and then again switch, and then the switch 102 in the bottom. Subsequent network IP addresses I have changed. So we have network 10.1.1, 10.1.2, 10.1.3.0. And then we have respective area like area 0, area 1 and area 2. Now in lab number 1, we'll go and um, create or run the OSPF in between area 0 and then we'll do the MD5 authentication. In the same lab later on we have to create the virtual link and we have to make area 1 as a transit. Alright, so let me show you this IP addresses assignment here. You can see that we have created and assigned the IP addresses only so far as per the diagram. So these are the IP addresses assignment related to R1, R2, related to R1 and all the switch. So now let's start with area 0, that is R1 and switch 105. I'll go here and enable router OSPF1. Then I have network, say for example 11111. and then I'll put this inside area 0. So let me do that. Then I have network 10.1.1.0. This also I'll put inside area 0. Alright, now we'll go to the switch, that is switch 105, and we can go and check the network. First of all, we'll go and initiate the OSPF process. Then we have one network, that is 10.1.1.0, but we have 105.105 network as well. So let me quickly do that. And 0.0.0.0.0 area 0, for example. Then we have the rest of network. So now you can see I have enabled this, or I ran this command, but still I can't see that OSPF is coming up and running. So I should go and check the IP over E00, and we should have at least IP reachability. So E00 here, it is correct. If I go and check the interface configuration for this switch, so let me try to check 0/0. Wow. So we have this command configured and protocol is up. So if I do the ping, so let me do the ping from here for 10.1.1.1. That's the router IP. And I can see that ping is working. If we could go and check show IP OSPF neighbor, show run section OSPF. So here you can see that I have this network inside area 0, and then I have my network, that's the loopback, but still I can see that they are not forming the neighbor relationship. So now what I'll do, I'll go here and make this network as a 10.1.1.0 area 0, and then I'll remove this network statement. You can see that the problem here we have. Then again I'll go back and delete this and add this. So let me try to do both at a time. In router number 1. Okay, and let's try to check. Show IP OSPF neighbor. Now they are in two-way dweller state. They're stuck in dweller state. Alright, and if I go here and check in this, because we haven't removed OSPF from here, show IP OSPF neighbor. Okay, so the reason may be now it is up. Maybe the network type that we haven't changed, but now it is showing it is up and running, so that's okay. Now we have the OSPF relationship over area 0. What I want to do now, that I want to run the authentication. So I can go to router OSPF 1 and then area 0 authentication. Here you can see that you can do plain text if you want. You can leave with this authentication, or if you want to do the MD5, that is the more secure, then you can go and use this. Now at the moment I have done this, you can see that the neighbor is up, but we are getting one problem here, that authentication key, you don't have any valid key. So now what I'll do, I'll go to 00 and then IP OSPF authentication. You can see that you have authentication and message digest option. So I can go and put the key as a CCNP. You can see here that you can go to authentication and key, and then you can see here that you have option say unencrypted. This is not that I'm looking for, so I can go and give the message digest, but I want to put the key as well. So let's see, IP OSPF authentication, and we can give the authentication if it is a plain text and authentication key. And suppose if I'm using authentication, then I have this option for message digest. Actually, that is quite a confusing option that Cisco is giving to you. So, because obviously natural thing is that we'll go and check IP/OSPF authentication, and then whatever authentication will be there. But in case of message digest, you should go and check IP/OSPF, and then you have this option of message digest key if you want to put your key. So I'll put key as CCNP, but let's see, yeah, MD5, and then so this is the long command that we need to put here. Now if we go and check show IP OSPF neighbor, we can see that neighbor is down because of mismatch of the, or we don't have the key configured to the other side. So here also we can go to router OSPF1 area 0 and then the authentication message digest, and then we'll go to interface E0/0 IP OSPF message digest key. Now we are getting this error MD5 CCNP. So now you can see that the neighbor is coming back up. So this is the way that we can go and do the authentication inside area 0. Now what I want to do here, that I should go to the I should first of all do the OSPF rest of the configuration, and then we'll create the virtual link. So let me do that. R1 is okay. In R2, let me check show IP route and what network that we have configured so far. So we have router OSPF1. We should have one more network, that is 10. Let's see the network. That's 10.1.2.0. So 10.1.2.0 0000255, and that is inside area 1. Correct. So this network is in area 1. Now we have switch number 101. So let's do the configuration for switch number 101. And what network we have? We have network 10.1.3.0, that is in area number 2. Then we have network say 101, 101, 101, 101. So for example, I'll put this in area 1, and then finally I have 10.1.2.0, that is inside area number 1. Alright, so we are very much done with this OSPF configuration. Finally, we have switch number 102, where we have 10.13.0 network. So I'll go here as well and should enable OSPF, and then we have network. Say for example, first of all I'll advertise the loopback, and this is inside area 2, And finally, we have network 10.1.3.0. That is again inside area number 2. Now here you will see that after running all these commands, if we go and check show IP OSPF neighbor, so he has neighbor that is 102 and 105. Now if you go here and check to the switch 105, you will find show IP OSPF neighbor. So he should also have two neighbor, but if you go and check show IP route for OSPF, you'll find that he is not getting 102 because it is never getting tunneled or passed through the area 1. So in this case, we should go and create the virtual link. Okay, so let's create the virtual. So I'll go and create the virtual link here inside area number 1. So first of all 105 and then 102. So already we are here and router OSPF1 area 1 and then the virtual link. What is the ID? So we know that the neighbor ID is this. You can see here that we have option for message digest key as well that I'll put later on. But that's it. Area, virtual link, and then the peer device router ID. Now I'll go to 101. I'll go here and router OSPF1 area 1 virtual link is what's the router ID you're looking for to make the tunnel. That's sorry, not this one. This is 105. Okay, so I'll go and remove this, and that's it. So once you do this, then if you go here and check the OSPF, you'll find that you will start getting the routes. Now, what is happening here in this case that since you don't have key configured, so inside area 0 we have the key configured. You should go here and give the key so it will work properly. Go here and here also we'll go and we should give the key, say CCNP, and now you will see that they will start getting the routes. So if I go here and check show IP OSPF neighbor, now show IP route OSPF, it should get 102 102 102. That will be the final valid verification for this. So after running this command, I can't see that anything is happening. And let me go and check here as well. You can see this configuration is 100% correct. You're creating virtual link with this, and in router 1 also the configuration key, everything is correct, but it's still they are not forming this. So what we can do here that we can go to router OSPF one more time. Router OSPF1 area 1, say for example the authentication is message digest. This belongs to area 1, and here also we have area 1 as well. Let's see the final configuration. SPF. Now invalid key for 10/0 that we can verify. So what is happening actually here, that if you go and check the configuration, you'll find that once you are putting the key here over the virtual link, now this belongs to inside area 1. These are the interfaces where you have to put the authentication key. So for example, as a MD5. But when we are creating the virtual link, actually, in that case, that is going to propagate area 0 only. So it's not required to put the key there. Okay, but just for the security purpose, I'll go and put the key over 10/0 and E1/2 as well. So E say 10/0 and IP OSPF, or maybe IP, yeah, OSPF message digest key 1 MD5 CCNP, correct? And then finally I can go here and interface E2/1/2. Wow. So this much configuration we have done. And now if you go and check show IP OSPF neighbor, first of all we should have the neighbor. And if I go to R1 and if I go and check show IP route, so here you can see that it is getting the route as a O routes, as it is directly connected with area 0, and we don't need to put actually authentication over the area 1 interfaces that I have done, but for sake of security we want to put the authentication key at all the places, so you can go and put the authentication keys at all these places. Alright, so this was the authentication. And the next important section, we have OSPF summarization, different type of areas, and the default route concept. So let's start and understand the summarization. Now clearly you can see in the diagram that you have area 0 separated by area 1 and area 2. And for example, if you're getting routes, say 10, 1, 0, 0, 1, 1, 1, 2, 3 up to 7, and other side you can see that is 8, 9 up to 15. Now we are sending all these routes to the core router. Here you can see all the individual route, and hence the database or the topology table of the inside the area 0 will increase. Rather than what we can do, that we can summarize the area 2 as 10.1.8.0 and area 1 as a 10.1.10/21/21. Correct? So in that case, we are sending only one update, and our routing table will be efficiently utilized. Doing so, we can reduce the load over the router CPU. So this is one of the interesting use case we have with inter-area OSPF summarization. Now what's the command? Command is very easy and straightforward. We can go to the router, and over the router you can go to the area, and then you have to use the keyword called range, and then you can use the address and the subnet mask, and then this will be done. Now there is one important point to mention, that suppose if you have some of the routes in between that is not part of subnet. So for example, if I don't have 1.5, 1.6, is still I am using this summarization, that is 10.1.0.0/21. So in that case, what we can do, we can use the concept of static route null 0, and we can point out this summary route towards null 0. So that means that anything that is not matching, that will be garbaged, that will be bit bucket. Correct. Now here you can see that note that after 12.16, and now we are running the modern or advanced version of operating system, even this command is not required. It was required for the earlier version of iOS. Now the second point related to summarization we have is, suppose if the summarization is coming from the external system, it's not related to inter-area routing, but it is coming from outside. Now at this point of time, we should go to the ASBR. Suppose router B is ASBR, who is connected with non-OSPF domain or non-OSPF routing protocol. So in that case, you can do the summarization, but syntax will be little bit different. So in this case, instead of doing area, the command is summary address and then the network and the subnet mask, means whatever network we want to summarize. Correct. So now this concept is very much like we are doing the aggregation, and we have two type of border. We have ABR and we have ASBR, and like that we can easily do the summarization. Now here you can see that we have one use case in case of ASBR summarization, that if you don't want to advertise certain prefixes, so in that case, you can go specifically to that particular network and you can use the keyword called not advertise. If you use not advertise, obviously these networks will not be advertised inside the OSPF. Okay, so this is the concept related to summarization. Now next important concept we have is the OSPF area type. Now I have one summary chart as well where we can go and summarize the OSPF area type after few slides. So here you can see that you have area type called backbone, non-backbone, stub area, totally stubby area, and not so stubby area. That is NSSA in short. So let's learn and discuss about the area type. And now starting with the basic area, that is the normal or the standard area. We know inside that area we have LSA type 1, we have LSA type 2. So here you can see that we have all the LSAs inside the standard area, the type 1, type 2, type 3 and 4 generated by ABR. Then we have type 5 as well, that is generated by the ASBR. So it is able to understand all the LSA. That's the standard area. Now the second thing here, that when you are making a stub, at the moment you will make the area as a stub, the stub will not accept type 3 and type 5. But remember, they will automatically inject the default route. Now doing so, we are not, while doing so, you can think like this, while doing so, we are cutting off the SPF calculation. And who is doing the SPF calculation? My CPU, my process. So that means that we are cutting off the intensive cycles, CPU cycles, and hence we are providing good type of optimization in terms of CPU and memory. Correct? Now what's the command? Again, the CLI command is very easy and straightforward. You can go to the network. So here you can see a router process. First go to the router process, and then you can go to area 1 stub. At the moment you do the stub, that means it will start stopping type 4 and type 5, although it will get router, network and ABR generated LSA. That is type 1, type 2 and type 3. And other thing is that it is generating the default route. Now the third concept we have is the totally stubby area. Now what totally stubby area even will do, that will accept only type 1 and type 2. It will not accept type 3, type 4 and type 5 LSAs, although it will go and generate the default route for type 3, 4 and 5 LSAs. Again, the use case is that we are saving the bandwidth, we are saving the CPU core, process cycles, etc. Now the command here is interesting, that here we have used in a stub area, we have used area 1 stub. For totally stub area, you have to add one more keyword, that is no summary. So the command is area1 stub no summary. It will stop LSA 3, 4, 5 and it will generate the default route. Okay. Now the fourth one is not so stubby area. Now, why we need not so stubby area? Here you can see that you may have chance that area 0 is connected with external network, or you may have chance that area 1 is connected with external network. Correct. So in that case, we'll see that when you have area 1 connected with external network and you want to filter some sort of LSA, you are going to use the not so stubby area. Means it's a stubby area, but it's not fully stubby area. What it will do, here we'll see that like a standard stub area, NSSA area routers will share type 1 and type 2 LSAs. Okay, they are not blocking type 1 and type 2. NSSA area will also accept type 3 LSA. So they are going to accept type 1, type 2, type 3. But NSSA will not accept type 4 and type 5. Okay. Now we are going to introduce one new LSA, that is LSA type 7, that we haven't discussed so far, but not so stubby area is linked with LSA type 7. And what's the use of LSA type 7? Now we'll see. So if an ASBR exists within the NSSA area, this is ASBR will generate type 7 LSA. Again, NSSA areas are almost identical to a stub area. If area 1 was configured as NSSA, it would not accept any external route originating from router G as ASBR outside area 1. So here you can see that they are not accepting any type 4 and type 5 LSA. Rather than we have type 7 LSA. So here you can see that it will not accept, this is the router G, it will not accept any external network, external non-OSPF domain network. Correct? Great. However, area 1 also has an ASBR within the area router A. Those external route will be flooded into area 1 as type 7. So here you can see that you have area inside area 1, you have router 1 and who is getting the external routes, and that will be flooded inside area 1. Now these external route will not be forwarded to other area as type 7 LSA. Instead they will convert it into type 5, and that's the key, and that I'm going to summarize. Type 5 LSA by area 1 ABR router C. So what is happening here when you are creating not so stubby area? In that case, you are getting type 7 LSAs, and router C, what he will do, he will convert type 7 LSA to type 5 LSA, and then it will flood it into the other area, or the other area will calculate as per the type 5 LSA update. The configuration is very simple. What you have to do, you have one keyword, go to the route process and then area 1 NSSA. Okay. All right, and final concept we have is totally not so stub area. So let me stop here, and remaining concept we'll discuss in the next recording. But here you can see the summary, and in this summary, let me try to highlight. Backbone LSA 1, 2, 3, 4, and 5. They are not getting LSA 7. Non-backbone like area 1, area 2, etc. They are also getting all the LSA. Stub area LSA 1, 2, and 3. Totally a stub area, only LSA 1 and 2. Remember, they are going to generate the default routes. The not so stubby area, type 1, type 2, 3, and type 7. This type 7 will be converted to type 5, and then it will be reaching to area 0. That's the overall summary we have with this recording. So let's stop here, and next section will continue from here. Let us continue where we have left off. Now next concept we have is not totally not so stubby area, that is TNSSA. So what is the main difference between a stub and totally a stub area? The same difference you'll find between not so stubby area and totally not so stubby area. Totally not so stubby area will allow LSA type 1 and 2, and he is going to filter type 3, 4 and 5. Here you can see the configuration is very straightforward. You can go to OSPF area and then you can give area 1 NSSA. The keyword is no summary. And here we have the summary just for your reference. Now the next topic we have is OSPF and relation with default routes. We know that when we are generating to a stub area and totally a stubby area, at that time the OSPF process, they are generating the default route. But in case of ABR and ASPR inside a standard area, we don't have default route. Now suppose you are sending LSA type 3 from router C and you are expecting that you are getting say LSA type 5 from router 1. So you are getting LSA 5 from router 1 and it will go to router C and then other areas. Likewise, LSA type 3 will go to B and A and actually B and then A and then the external network. At that time, suppose for the external network, you want to create the gateway as router A, so we can go and create the default route. So here you can see that additionally force router A to generate a default route, including itself as the next hop for the external network and injects into this inside area 1. Okay, what is the command? Command is router process, go to router process and default information originate. So this will inject the default route. But in case suppose you want to force it, so for example, if a default route does not exist in its routing table, router A can still be forced to advertise a default route using always command. So in that case, if I want to force the default route, in this section it is assumed that we should know EIGRP and then the difference between EIGRP and OSPF. So let's understand about EIGRP. What type of protocol is this? Basically, EIGRP is Cisco proprietary. It's a advanced type of distance routing protocol or distance vector routing protocol. It is using dual algorithm. Its protocol number is 88. It is forming the neighbor table, topology table, and then the routing table. It's a metric basically based on bandwidth plus delay, but there are three other factors as well inside EIGRP. So let us drill down inside EIGRP. Now here you can see we have some points. I'll go through these points and then we'll discuss about a very interesting point inside EIGRP, little bit confusing as well. We have a dual algorithm inside EIGRP, that's the diffusion update algorithm that will ensure that we have the loop-free routing environment. We have to define the autonomous system for EIGRP. The multicast address inside EIGRP is used by as again the link local multicast address is 224.0.0.10 just to form the neighbor relationship or to check the neighbors. We are sending these multicast packets and hello packets. It is using reliable transport protocol to ensuring the delivery, and it does not send periodic update. It is supporting VLSM, variable length subnet mask as well, because this is the classless protocol. All right. Other points that its AD is 90, the external AD is 170. Its metric is heavily relying upon bandwidth and delay, but if you see that metric calculation, you'll find that we have three more factors: reliability, load, and MTU as well. In some of the books, it is mentioned that MTU is not part of bandwidth, but not part of metric, but Generally, most of the time, we are going to calculate the metric with respect to bandwidth and delay. Its max hop count is 224. Its default hop count is 100. Why hop count? Because this is distance vector protocol. Distance vector protocol generally depends upon the hop counts as well. They are going to form three table, neighbor table, topology table, and from topology table, it will run the dual algorithm and it will form the routing table. In EIGRP, again, we have the neighbors, and by default, the neighbor, they are sending the hello packets after every 5 seconds. And in case of slow link, the hello packet timer is 60 seconds. Likewise, we have the dead timer as well, or the hold down timer as well. Not dead, but the hold down timer. That is 3 times of hellos. That is 15 seconds, and again 60 into 3, that is 180 seconds. We have to configure, say by default it will be like this, but if you want to change the neighbor relationship per interface, you have to go to the interface and then you have to run this command, IP hello interval EIGRP, then the autonomous system, that is 10 in this case, and 7. Likewise, I have to go there and type IP hold down interval EIGRP 10 and 21. So 7 into 3 is 21. That's the hello interval and the dead interval that we can form. Now in the lab section, I will run that show IP EIGRP command, and I'll show you this output. This is something that once you run the neighbor command, or what will be there in the neighbor table. Remember, we have three tables. We have neighbor table, topology table, and the routing table. So in the lab, we'll check all threes in upcoming section. If you want to check the logs, you have the log command as well, like log neighbor changes, log neighbor warning. So these are useful command that we can run and check. Now I told you that we have an interesting concept inside EIGRP and a little bit confusing as well. So let's try to understand the feasible distance, advertised distance, feasible successor, feasible conditions, like that. Okay. So here you can see, let me read out this and then I'll show you in the diagram that all such routes are added to an EIGRP router's topology. The route with the lowest metric to each network will become the feasible distance. The feasible distance for each network will install into the routing table, that is nothing but the successor. So we have successor, primary route, we have feasible successor, that is the backup. Again, the feasible distance is derived from advertised distance. Now here you can see that you may get the terms like, say for example, feasible distance, feasible successor, successor, feasible condition, advertised distance, etc., etc. So let's try to understand how exactly it is working. Let us continue where we left off and try to understand the terminologies inside EIGRP. Now here you can see that in the diagram, I have A, and to reach to destination network, it is going via B, C, and D. Now for B, C, D, to reach to the destination, the feasible distance is 6 plus 2, 8, 9 plus 14, 23, 4 plus 5, 9. So these are the feasible successor respective to B, C, and D. But what about A? Now, if you go to A has to add his distance as well. So if you go and add, you will find that 8 plus 8, I think I have in the next slide. So let me go to the next slide. So here you can see that 8 plus 8 will become 16, then 23 plus 4, 27, and then 11. So obviously the 11 is the lowest one. So that's why in this direction he will get his successor, correct? So now I have my successor, but we know in EIGRP if you have multiple path and if they will meet certain condition, then you have the backup path as well. That is nothing but feasible successor. So let's first understand the algorithm by which EIGRP is finding his feasible successor. So here you can see it is clearly mentioned that you have the feasible successor when if it met the condition, feasible condition. What is that condition? A route only become a successor if its advertised distance is less than the current feasible distance. Now in our case, we'll go and try to understand this statement. So in our case here you can see, and I'll write this here, the advertised distance will be less than the current feasible distance, correct? Let me erase, and advertised distance will be less than the current feasible distance. That's the statement to have the backup path. Now here, if you go and check, so already I have my successor. So it is marked as a successor. It will be installed in the routing table. Now searching the feasible successor or the backup path, if we go here and check what is the feasible distance. So here your feasible distance is 8. Here your feasible distance is 23. We are adding 14 plus 9. And what is your distance, advertised distance? So you'll find that your advertised distance total path is 11, correct? So now you can see that 8 is less than 11. So 8 is less than 11. That's the condition actually, correct? So feasible distance should be, in other words, you can tell that feasible distance should be greater than the advertised distance of your neighbor, or via which path you are going. So because 8 is greater than, sorry, 11 is greater than 8, or 8 is less than 11, so that's why this is the feasible successor. That is not true in case of this path, because this is 23, which is bigger than 11. Okay, so that's the algorithm that we can verify. I will upload this slide as well. Now the last thing here in these slides is that suppose if you have failure and if you don't have the backup path, so in that case the EIGRP algorithm reran, it will move to active state. Active means actively it will try to get the feasible successor or the backup path, correct? All right, so let's stop here. Now we have EIGRP packet types and EIGRP metric value. In EIGRP, we have 5 different type of packet types. Here you can see we have hello packet, update, query, reply, and acknowledgement. Obviously, when devices they try to form the neighbor relationship, at that time they are sending and receiving the hello packets. The mode is multicast. They are using 224.0.0.10. That's the multicast address to send and receive the hello packets. Apart from that, we have update packets, means if I discover new neighbor, then I want to sync my topology and routing table. So for that reason, I can send the update packets. Now in this case, in case of new neighbors, they are using method as unicast. But suppose if you have any change in the route metric, at that time they will use multicast as a transport. We have very important packet type, that is query. Why it is using query? Because suppose your successor and suppose your feasible successor, so both, if they got failed and you don't know how to reach to the network or you don't have the network update, so at that time you're sending the query packet that do you know this network update, and you will wait for the reply. So we have the query, means the router places itself in the active state. So I'm in the active state, I'm sending the query packet and I'm waiting for the response. Now the reply packet are sent to give the response for the query packet, and these reply packets are sent as a unicast to the querying router. Now we know that EIGRP using reliable transport protocol. So that's the reason we don't have acknowledgement for hello packet and acknowledgement itself. But for all the other packets like update, query, and reply, we have acknowledgement. So here you can see that the following packet types employ RTP to ensure reliable delivery. So that's why we have acknowledgement for update, query, and reply packets. Now we have two state in EIGRP. Active state means actively you are looking for the neighbors, or actively actually you are looking for the network, and then the passive state, that is the stable state. So once the routing has been converged, once your topology table and then your routing table they are stable, at that time that state is passive. If you are still looking for a network, if you are still having a problem in the network, that move to the active state. Now we know that in active state, when I don't have the successor and feasible successor, I have sent my query packet and I'm waiting for the response. Suppose if it will take 3 minutes to take the response back, that state is termed as a stuck in active. So you have sent your request and you haven't got the response, and for 3 minutes you move to a stuck inactive. You are still inactive. You got stuck. Now there are some solution to improve this stuck inactive phase. Either you can do proper summarization, network summarization, or you can use EIGRP features such as the stub. So means your hub and a spoke, think you are the main router hub and then you have the spoke, and those spokes, suppose if you convert those spoke as a stub, then the query will not propagate and it will not unnecessarily overutilize the bandwidth. Okay, so we'll see that concept of a stub later on. Then we have some verification command in the lab section. We'll verify. We can run show IP EIGRP topology. Here you can see the state codes are P for passive, A for active. If it is a converged, then you'll find P as a passive. You have one successor or you have two successor, etc. We can get those information. Here one important point that you can see that you have feasible distance as 2297856. Now how EIGRP is calculating his feasible distance, that we are going to discuss, and that's very interesting calculation we have for the EIGRP metric value. EIGRP uses 5 parameters to calculate the metric value: bandwidth, load, reliability, delay, and MTU. Now here you will see that in some places it is mentioned that the MTU will not come into the picture. Anyways, we have these 5K values for these 5 parameters, or these 5 you can think as a variable or the component for the metric. Now these 5 component for the metric value, we have one very complex formula. So let me show you this formula here. Here you can see the formula. That metric will be calculated as K1 into minimum bandwidth, then plus K2 into minimum bandwidth, 256 minus load, plus K3 into delay, into K5 divided by K4 plus K5 divided by K4 plus reliability into 256, where your bandwidth is 10 to power 7 by divided by least bandwidth. Now this is a really complex formula. So to make this simple, what is happening generally, most of the cases you'll find that the system using K1, K4 and K5 as 000. Then you have K1 and K3, that is bandwidth and delay. And that's the reason you'll find that the calculation for the metric will be dependent mostly upon bandwidth and delay. So again, you can see that uh, 10 to power 7 divided by bandwidth, and then plus delay. Delay will be in microseconds, and this bandwidth will be in kilobits. Okay, so kilobits, and the delay will be in microseconds. Again, uh, the bandwidth will have very huge impact in the metric calculation. So that's why you can think here with this formula that your metric value is indirectly proportional. It's not directly proportional. So sometimes if you check the calculation, that it's inversely proportional to bandwidth, correct? Because you can see 10 to the power 7 divided by minimum bandwidth. Obviously, if you have delay, then you can add that, but the major role played by the bandwidth. All right, so this is the formula to calculate the metric. Now, how you want to apply this metric? If you want to change certain parameters, so for example, we have the CLI command metric weights and 0, 1, 1, 1, 1, 1, like K1 up to K5. And suppose if you want to add any of things, say for example, I'm making K3 as 1. So here you can see K3 as 1. Then again, this formula will get changed, correct? So in my case, K2, K3, K4. So here you can see K2, K3 and K4 will be 1. Then again this calculation will get changed. Again, it's highly unlikely that we are going to change the metric value. Whatever by default is there, we are using it. But yeah, in certain cases, if you want to do some sort of traffic engineering, some sort of load balancing, some sort of change in the metric calculation, then you can go to the interface and either you can change the bandwidth. That's the normal thing that we used to do for the traffic engineering. Either we are changing the bandwidth or we are changing the delay factor. So either if I change the bandwidth or the delay factor, I'm going to change the metric calculation as well. Okay. Now, again, we have one command, IP bandwidth percent EIGRP, autonomous system and 30. By default, EIGRP is using 50% of the link bandwidth. And suppose if you want to make this 30%, you can use like this. Your link bandwidth is 64, so you are using 30% of 64. We have option that we can use 100% as well with this command. And again, if you want to change the delay, you can go and use the delay as well. So let's just stop here, and in the lab section, we'll try to understand more whatever we have covered so far. Let us do the EIGRP configuration, and after that configuration, I will go and verify first of all the basic things like how EIGRP having their neighbor table, then their topology table and their routing table. Plus we'll see the various type of packet types that they have. Then we'll go and check the other things that we have studied in the previous section. So let's start, and what I'm going to do, you can see here the diagram, R1 and switch 105. So in between that you can see the interfaces. I'm going to assign the IP address to all these related interfaces, and plus I'm going to give one loopback address as well, just for verification purpose or testing purpose. So let me quickly go and assign the IP addresses to all these interfaces. So I have assigned the IP addresses to all the interfaces. Let me quickly show you that. We can go and verify once. Show IP interface brief, and I want to include the manual. We'll go and run this to all these devices, 101, 102, 103, 5 and R1, and I should press enter, send the script. So here you can see that over R1 I have this IP address, then switch number 105, I have these IP addresses. Although I haven't pinged and verified that they are reachable or not, but I have assigned the IP addresses over the interfaces and created over the loop back interface as well as per our topology. Okay, so next task I have that I should run EIGRP. So let's go and enable the router. EIGRP, we know that we have to give the autonomous system for that. So let me show you from here, from the global config mode, router EIGRP, and then we can assign the autonomous system. For example, I'm using 10. I'm going to use no auto summary, means I don't want to do the automatic summary. So that's why this no auto summary command. Then I want to advertise the network. Now we know that what type of IP we have, and if you want to check the network, connected network, you can go and then do show IP route or show IP route, so you can get the connected network list. But because I have this network here, so I can go and use, and then we have this option that we can use the wildcard bit. Then I can go and use the other network. Oops. Then I have other network as well, that is this one. And I can go and use the wildcard bit here as well. Then the third and the fourth one. So this is my third network. And then finally the fourth one. The loopback address having /32, the CIDR. So I will go and use this 00000 as a wildcard bit. We can quickly check the EIGRP configuration. So here you can see that we have these many network. Now I should go and enable this to the other devices as well. So we have done the configuration to 101. Let me go and do to 103. So for 103 the network is, so let's go to 103 router EIGRP 10. We should have the same autonomous system, no auto summary. Then the network, we know that network is this. At the moment I enable or I run this command, you'll see that they will start forming the neighbor table, topology table, and the final is the routing table. So dual algorithm will run here. Here you can see that it is running the dual algorithm, and then we have the routing table as well. All right, so at this point of time, at least I can go and check show IP EIGRP. First of all, the neighbor table. So here you can see that this guy is the neighbor. The uptime is this many second. Rest of the things we don't have much worry. We don't need to worry about this request timeout, the queue count, sequence number, round trip timer, etc. If you have any issue at that time, you'll see that queue count is increasing, or you have the RTO value is increasing, or round trip timer is increasing, etc. Okay. So first table will be the neighbor table. Then you can go and check the other stuffs as well. Like I can go and check show IP, EIGRP, topology table. That's the database you have. Now here you can see that you have the successor, feasible distance successors, and then you can see that you have the metric value as well. So here you can see your FT values. Now this calculation, we'll discuss this in upcoming slides, or even now also we can discuss. So I need to open the mathematical calculation and the calculator. So for that we'll go and check what's the bandwidth and how this calculation is coming into the picture. That's 409600. Okay, that's the FT. Again, you can see that P stands for passive, and then you have all the codes. So let me quickly open the calculator and let's do the calculation here. So we know roughly the formula for the metric value is, the metric value is 256 into 7 divided by bandwidth in kbps and plus delay. Roughly, this is the rough calculation. So let's try to understand first of all the bandwidth for the interface. Everywhere we are using Mbps, so my bandwidth is 100 Mbps. Now this 100 Mbps, let's calculate it in kbps. So let's try to do this. Now 10 to the power 7, so 4, 5, 6, 7 divided by 100 Mbps means 100 into 1000, means we have to convert into kbps. So number of zeros will be 0, that is 100, and then 30, so that will become the kbps. So the final value will be 100 and plus delay. So I should go and check the delay over the interface. So for example, show interface E0/0. Now if you go here and you can see the delay, this is in microsecond, this is not in this is, yeah, 10 to the power minus 6, that's the microsecond we have, and that's okay. So what will be the value for this? 1000 into 10 to the minus 6, correct? Okay, and that's correct format actually. So let's see. Let me open the calculator one more time. So that means we should go and add 1000 here, and then if we do 256 281600, I can see the bandwidth in kilobits, that is showing 10 to the power 4 only. And let's go and verify that what is our metric value. That is 281600, that's correct. So yep, let me open the calculator, and here you can see you have the exact 281600, 281600. Yeah, so this is the way that we can do the calculation for the metric. Okay, so what I'm going to do here now, let's just stop here, and this lab we will study some theory, and again I'm going to build, and I'm going to continuously build this lab as well in the upcoming sections as well. Let us understand some more terminology and theory for EIGRP, and likewise we are going to continue our lab as well. So the next topic we have related to passive interface, auto summarization, and authentication features. Let's see here in the slides, we'll go step by step. Now, first of all, when you're doing the baseline configuration that we have already done, go and enable the EIGRP process with autonomous system, and then we have option to advertise the network. Now, we can go and add the wildcard bit as well, so we can get the specific network advertisement. Once we do up to this point of time, obviously we know that the hello packets will start exchange, and then they will form the neighbor relationship. First of all, we have the neighbor relationship or neighbor table, then topology table, and then finally the routing table. All these things we are going to see in the upcoming lab as well. Then suppose if you don't want to form the EIGRP neighbor relationship like we have done in OSPF earlier, so then I can go to that particular interface and I can make that interface as a passive interface. Standard format is that you deny all the interfaces like passive interface default, and then selectively you can go and add the interfaces who want to do the EIGRP hello exchange or EIGRP packet exchange. So for that we have the passive interface default, and then we can go and give no passive interface and then the interface name. Now again, we have learned this in OSPF that how we are going to do the summarization. In OSPF we have summarization, or we can do summarization over area. So we have used that command. I have shown you that how that command work, or how we can use that command, and then we can do the summarization for ASBR as well. So we can do the summarization for ABR and ASBR. Here in EIGRP, this summarization is a bit easy. So first of all, in the previous section, in the lab section, we have used the auto summarization, because if you do not do the auto summarization, so in that case, what will happen, that it can be converted to their class boundary. So for example, if you have network 10.100/16, if you do not use the auto summarization, like no auto summarization feature, then it will think that his network is 10.0.0/8, because uh, 10 is belonging to class A, whose subnet mask is 255.0.0.0. So like that, we need to use this keyword like no auto summary. You have to use this. And then coming to the manual summarization. Now the same thing that we have discussed in case of OSPF, you have to go to the interface and then summary address EIGRP, the autonomous system, and what you want to summarize. So you can do the summarization. I'm going to cover this in the lab section. We'll create some different type of network, and then we'll do the summarization, and then we'll send to the devices. Now when we do the manual summarization, at that time the AD value is 5. We know that the internal AD value is 90, that EIGRP AD value is 90, but for the summarization, our AD value is 5. Now we have one note here that as with auto summarization, the router performing manual summarization will add the summary route to its routing table with a next hop of null interface as 0. So we know that uh, you're doing no auto summary. See, that's the combination. Do the no auto summary. You're not doing the summary automatically, and then you are doing the manual summarization, and that's the reason we have this AD distance as 5. Obviously, that is more than the internal distance. Okay, so do not mix with auto summarization and use this practice, no auto summary, and then the manual summarization. Then finally, in this section, we have the authentication. First of all, we have to create the authentication key. So here you can see that key chain. Define the key 1, 2, 3, 4, 5, etc. Then key string, define the password. And then over the interface, we have to go and apply it, like IP authentication keychain, autonomous system, and then key. If the authentication or the password will match for both the peer interfaces, then only they will start exchanging the EIGRP hellos. Okay, so these are the topics that I'm going to cover. Let me open the lab section and let me show you whatever we have discussed here and what are the things that we have in the leftover in the previous section as well. As per our lab topology, what we have done that we have enabled EIGRP over 101 and 103. So now if I go here and I can show you this, show IP EIGRP neighbor, show IP EIGRP topology, and show IP EIGRP. Better I do show IP route EIGRP. That's the routing table. So whoever is your feasible successor, that you will see in the routing table as well. So here you can see that what is the network that I am learning here, and that's why it is there. Rest all the network actually is connected. So you can see all are connected routes, and then finally I'm learning one of the loopback, so that's why it is coming inside this routing table. So we should check all these things first of all. Then if you want to check the packets, so we have the show IP EIGRP, and here you can see the traffic. Here you can see that what type of packets you have: hellos, update, query, replies, acts, stuck in active. So all those packets we have. With this command, we can go and check the packets as well. Okay, and then how we can go and change the metric values, so that we have discussed in the previous section. I can go to EIGRP, and then you have command metric weights, and then you can see that say for example type of service K1, then K2 for example, then K3, K4, K5. So like that we can go and put all these values. I'll not put this value, and I'm showing you that you can go and check these values. Now let me go here and let me show you show IP route EIGRP. So here you can see that you have your AD value, you have your metric value. Now if you go to the interface E0/2 and 0/2 where it is, so we are here, that is going to switch 103, and I have this option that I can go and change the bandwidth. So if I go and change the bandwidth to 5000, and if I check show run interface E0/2, show interface E0/2, here you can see this bandwidth is 5000, and here it is 5000. Now if you go and check the metric value, because we know that the metric value will get changed, so now it become this. Initially it was, so now it is 1 2 3 4 5 6 digit, because initially I think that was 10000, I think 1 and 4 times 0 the bandwidth. Now if I go up and if I can show you the bandwidth that was before change, so 1 2 3 4 5 6 409 600, that is increase, because this increment is bandwidth and metric are inversely proportional. So if this number is increasing, that means the bandwidth is decreasing. What I am telling you, that if you go to interface E0/2 and if you give the bandwidth, say for example 1 more 0, so if this will increase, this will decrease, correct? Do show IP EIGRP, or do show IP route EIGRP. So now you can see that this is decreasing. So if you increase the bandwidth, your metric will decrease, and that will become more and more preferable. All right, so these things are related to the previous section. Whatever things we have studied now, that let's cover that. So first of all, we have a study about the passive interface. If I go here and let me do one thing, I'll enable the EIGRP over these devices as well, 101 and 105. So let me quickly go to 105 and enable the EIGRP. And before that, let me check what is there inside 101, what interfaces we have. So we have 1 2 3 3 interfaces, that's correct. And then we'll go here to 105 and we are going to add the interfaces. So we have 10120, 10130 and 1. So 1 2 and 3. All right, so let's do this. Say router EIGRP 10, no auto summary, network 10.1.1.0. Then we have 2 and 3, correct? And then we have one loopback as well, so 2, and then we have 3, and then we have network related to 105, 105, 105, 105, 0000255. Alright, so there the network we have. Now since it is not coming up, that means something is wrong related to interface is down or something that we need to check. 10120 E11 and E10/0. So if I go and check to show run interface, say to show run interface E10/0, I can see that the interface is correctly defined. Then I'll go and check to E1/2, E1/1012, and if I go and check to show run or show run section EIGRP, should have a routing for that. So I can see 10.1.2.105. Yep, some issue seems to be related to connectivity or maybe interface that we need to figure out. So here you can see the issue. My interface should have correct IP address. So IP address is 10.1.2.105, and you can see 2.1 and 1.2, how minor mistake that was, but again, we should give the correct IPs, and now it is up and running. I can go and check show IP EIGRP topology, or I can go and check show IP route EIGRP because I'm interested in that. So here you can see that it is getting the loopback 103 and it is getting the loopback 101. That's why I've given the loopback addresses. So that means I have the reachability. Now if I go to 101, because he has two neighbor at this point of time, so IPE as ERP neighbor, one of the neighbor I want to make passive interface. So for that, I can go to router EIGRP10, say passive interface default. That means everything is passive. Then we can do no passive interface E, say for example 1/2, and then I can go and do no passive interface for E 0/2. So this is the use of passive interface as well. Okay. Now what we can do next, that we have the summarization option as well. So for that I can go to, let me open this diagram. I can go to 103 and I can create some loopback addresses here. So for example 7 or maybe 103, anything. So let me go and create some of the loopback. So I'll go to 103 and I will create few loopbacks, say interface loopback 101, IP address, say for example 2.2.2.1, then interface loopback 102, IP address 2.2.2.2, and then interface loopback 3, or maybe anything, IP address 2.2.2.3, 255.255.255, interface loopback 4, IP address 2.2.2.4. Like that, I can go and create some of the loopback I want to do the summarization for. Then I can go to router EIGRP10. I can do the advertisement, say network 2.2.2.2.0.0.0.7. Do show IP interface brief if you want to check your loopback. So 3, 4, 101, 102, etc. But network is 1, 2, 3, 4. Now if I can go and check these routes here, show IP routes for EIGRP. Do I am getting the loop back? So here you can see that we are getting four network. Rather, I want to want one advertisement. So what I can do here, that I can go to the interface. So let me check what interface we have. Brief, we have interface inside 103. So let me show you this diagram here. So we can go to 103 interface 0/0 and we can do the summarization. Okay, so interface is 0/0 IP, and then the summary address EIGRP 10, and then we can do the summarization. So 2.2.2.0, and then we can give the mask, say 255.255.248. All right. Then if I go here to 105, you can see the AD value is 90. 105 is getting this single advertisement. That's okay. And if I go to, I'll cover that. So now you can see that this, once you do the summarization, the EIGRP algorithm will rerun, it resynced, and it has sent the summary. Now if I go to 102, and here if I go and check, oops, we'll wait, and let's see the final command. So what we have, show run section EIGRP, and we have done this summary. Great. So we'll go to the 102, and in 102 also I'll go and verify that what advertisement exactly I'm getting here. So we'll go here and check show IP route EIGRP. Where we are, I should go to 101 as per the diagram. We haven't done any configuration for 102. So show IP route EIGRP, and we are getting this advertisement. And if I go to 103, who is the originator, show IP route EIGRP, it is sending the summary to the null, and then it is getting advertised to all the devices, correct? Now we are going to discuss the theory of load balancing, stub areas, and authentication lab will do in the upcoming section that we have already discussed. EIGRP is a protocol that can do unequal cost equal load balancing. So what does it mean? It means that if you have feasible successor, if you have successor and feasible successor, or vice versa, so in that case, one is your primary link, or one is your primary path, one is your backup, but still with help of variance, we can make both as an active link. So that means that we know that successor only get installed in routing table. But if you use the variance command, both the successor and backup successors, or the feasible successor or backup paths, those things will get installed in routing table, and you will get, although you have the unequal path. So for example, you can see these two paths, still you will see that those things will be installed in routing table. So you have the successor and you have the feasible successor, that's your backup, but still if you send 4 packets, 2 will go via this, 2 will go via this. Just an example. The devices, they are not doing packet based load balancing, but it's something called flow based load balancing. So what's the command? Variance. We'll see that how much variants we can use up to 128. We'll see that in the lab section. Maximum path by default it will be 4. We'll see that how much maximum path load balance it can do. Maximum it will be 6, but in higher version of operating system it may be more. By default it will be 4. Next topic we have a stub. Now we have discussed this earlier that suppose if I lose my successor and feasible successor, so at that time I will send the query packet, and query packet will get propagated until unless we get the reply. Suppose if I get the reply within 3 minutes, that's okay. Otherwise this process is known as a stuck inactive. Now to mitigate or to overcome from this, that already I know that network is not after this particular hop or router, I can make that spoke router as a stub. So that means that I am sending a query packet, but you will simply reply no. You don't have your what you are looking for from this direction or from this route or from this gateway. So that the query will get answered that this is the stub. All right, what's the command? We have the command. We should go to the EIGRP process. We can go and run this command EIGRP stub, and then we have 4 options: receive only, that will not share the update with neighbor. We have connected, static, and summary options. Connected means advertise connected routes. Static means router will only advertise a static route. Summary means router will advertise only summary route. Okay, so these options we have with the stub. Then we have some verification command. We have seen this show IP EIGRP neighbor. Then we have seen show IP EIGRP topology. You can check who is the successor, feasible successor, FT and AD, those values we can check. Show IP EIGRP traffic already we have seen. Show interface, and you can go and check the interface, what is the delay, what is the bandwidth, reliability, load, etc. Show IP protocols we haven't checked so far, so we'll run this in the lab. Show IP protocol will tell you detail about the protocol. It's a very useful command. It is giving the detail structure or detailing about that particular protocol. Show IP route, we can check the routing table. Show IP route EIGRP if you want to filter it. And then finally we have some debug commands such as debug EIGRP neighbor, packet route, and summary. Remember, do not run this debug command until unless you have the maintenance window. All right, so what we can do now from this point of time, I can go and log into the lab. We can continue our lab because we have to run or we have to verify few of the things one by one. Load balancing a stub, and then we have to do the authentication lab. All right, so we are inside the lab section so far. We have ran that EIGRP over 101, and let me quickly see that if we have done over 102. 102 we haven't run, so let's go and do that. What is the network we have? We have 3 and 4. So I can go here and router EIGRP 10, no auto summary, network 10.1.4.0, and then the wildcard. Then other network we have 3.0, so I can go and do that. We have 3.0, and then we have network 102, 102, 102, 102, 0000. Okay, so here also I can see that the protocol EIGRP protocol is not coming up. Let me quickly go and check the interface. Maybe the IPs assigned are not correct. So we have 4 and 3. That's correct. Let me quickly check where it is connected. So it is connected 0/0 and 1/2 as per the diagram here. You can see that should go to 101, and seems this 0/0 may be passive interface that we have done. So I can go here and you can see the usefulness of passive interface. So I can go and check the configuration first. Router EIGRP10, I should do no passive interface for E0/0, and let's see. So now here you can see that the protocol is running. Great. From this direction it's okay. Let's quickly check 10/1. So I can go to 105 and I can check here the EIGRP protocol. Do we are running the network command or not? So I can go here and check section EIGRP. We have 10, 1, 2 and 3. Is it correct? So we have 10, 1, 10, 2, 10, 1, 3. That's correct. Let me go and quickly check E 10/1. So run interface E 10/1 and we have wrong IP. So E 10/1 IP address should be 10.1.3.105 and then 255.255.255.0. Alright, so now we can see that it is working correct. Now if I go and check show IP route EIGRP, so here you can see that you have the loopback 1, 3, 5. So we have the loopback 105, 101, 103. All these we are getting. Finally, let's quickly go here to router 1 and check do we have the configuration for the EIGRP. We don't have, and we have some configuration related to summary as well that I actually don't need. So I can go to 00 and I can remove this command. Let's do router EIGRP10, no auto summary, network 10.1.1.0, and then we have one loopback. That loopback is 0000. Now if I go to any of this switch, say for example 103 also, I should get all the loopback. So let us continue and perform the lab related to authentication, and then we have the unequal cost equal load balancing, and then we'll see that what is the command for the stub as well. So let's start this. We have the topology here. You can see I'm going to enable the authentication in between R1 and switch 105. The common interface is E0/0. So how we are going to do, first of all, you need to create the keychain. Say for example, the name is CCNP in caps, just to refer this is the name. Then key I can give one, and then I can go and give the key string, say CCNP and then key. Okay, great. Then we have to go to the interface E0/0, and then we have the keyword called IP authentication. I should give the mode as EIGRP10 and MD5. So we have actually two commands. One is IP authentication, and at the moment I have executed this command, you can see this neighbor relationship is down. Then we have the keychain option, keychain EIGRP, and then the name of the key chain, that is the CCNP. Okay, that's it. So these are the commands we need to run in order to enable the authentication. Now the same copy paste I can do to this side, and you can see this neighbor is down. I can go and create the keychain first. Then I can go to the interface, and then over the interface also we can go and run this command. So let's do this. Over the interface I have these authentication command. We can go and enable this. Now we'll see that the neighbor will converge, and now I have the neighbor relationship with the router 1, that is 10.1.1.1.0. Just now it came back up 10 seconds back. Alright, so this is the way that we can do the authentication. Next we have the variance. So let's try to understand the unequal cost equal load balancing. Now here you can see that I can go and reach via this path to R1, and then I have the other path as well. So let's try to check the loop back that we have here, that is nothing but 1.1.1.1. So how many path we have to reach to 1.1.1.1 from switch 101. So if I go to switch number 101, and if we go and check show IP route for 11111, and I should give the network. So 11111, here you can see that I have only one path to reach there via E1/2. And if you go and check show IP EIGRP topology, and then if we go and check 1111/32, so inside topology it is telling that you have 2.105 and 4.102. So here you can see that it can go via 102 this way, and it can go via 105 this way. Obviously the metric value that you can see here, the FT and AD values, those are different, but you have two paths. Now is it a successor? So we know that who is the successor. Successor is this, because obviously it has lower FT. Here you can see 435200. And if you go and check this output in this manner, just to see that to reach 11111, I have only one successor. Okay, although we have two paths to reach there. So in this case, this will be direct like this via 105. Other one will be via 102 and then 105 and then R1. So what we can do now, I just wanted to add up the value for two different paths. So suppose if I want to decrement this, first of all, let's try to understand, can I do some sort of traffic engineering that traffic will go via this direction rather than directly? Let's try. So that means I have a bandwidth here defined and here defined, and that means that I have to increase the bandwidth at 2 points over switch 101 and then switch 102, correct? Because all the links have equal bandwidth. So if we go and check the bandwidth for 0/0, show interface is 0/0, here you can see that it has bandwidth this. Now I should increase the bandwidth. So 1, 2, 3, 4. What I'll do, I'll go to interface E0/0, bandwidth is, so for example, 5, 1, 2, 3, 4. Now let's see the show IP route for 1111, how it is going. So now you can see that still it is going via 105, that is still it is going directly. Now next what I will do, I'll go to 102 and I'll change the bandwidth of E1/2. So I am here, E1/2, bandwidth is 1234. If I go here and check, so what we are doing here, that we are trying to forcing the bandwidth so it will change its metric value, and so we can see that show IP EIGRP topology, that it is going via E1/2 rather than it is going via E0/0. And if we go and check topology for 1111/32, now if you check the composite metric here and composite metric here, still we don't have much change in the composite metric. Obviously the reason here is that you are changing the metric here and you are changing the metric value here. We should change here also, that is E0/0, and the bandwidth is, so we are just forcing the bandwidth. Now if we go and check, and still we can see that it is preferring this way. So IP route, so there is no change while we have changed the metric. For 1111, it is still going via the directly connected path. Okay, still it is going via this direction, although we try to change the calculation because still it may be less than what we are getting from tooling. So for example, 102 you can see what's the metric value here, 2048000, and then if you go and check the metric value from here, so if I go and check show IP route to reach to 1111, so switch number 2 to reach to router number 1, here you can see this is the metric, and if you go here, so seems the metrics are very much same. So how these guys are reaching is that they are coming to this this point, and then it is getting advertised to these directions, correct? All right, so here you can see that in this case, if you want to do traffic engineering, it's very difficult to do the traffic engineering. But one thing that we can do here is unequal cost, equal load balancing, correct? So if we have successor and if we have feasible successor, then it will be very easy to do it. Now in this case, I don't have any feasible successor. So IP EIGRP topology. So I can see here that I have only successor. I don't have any feasible successor. If I have feasible successor, then it's easy to do, but still I can go and use the router EIGRP 10 and then the command, say we have variance. I'll give the worst case, that is 128. And then if you go and check show IP route, specifically I want to see for uh, one of the route, but here I can see that 105 now have two different having equal cost multipathing, although you can see the metric value is different. So if I go here to the topology, you can see that from switch 101 to reach to 105, and obviously you have one loop back. I have two paths, this path and this path, these two paths. You can see their metric value is different. One is 2300, one is 409, and how we are doing the calculation actually, that's 230 and 409. You have to simply divide it, and you'll find it's almost double. So the difference is of double. So what I'm telling here is that when you are using the EIGRP value, we have given the variance of 128, that's the worst. You can give 3 also. And then if you go and check the route, you'll find that they are doing the unequal cost equal load balancing. And again, if I go and check show IP route, or maybe show IP EIGRP topology for this guy, and should do this with 32. So now here you can see that you have this path that is going via directly to the switch and then loop back, and then it is going via the other switch, and then here you can see the metric value, this and this. The difference is almost double. Okay, so now we can see this, and if I go and check show IP EIGRP topology, so here in the topology you can see that it is 105. So here you can see that you have two successor. So at this point of time it is showing two successor. Obviously if you have successor, then that will be installed in the routing table, because we have done so many changes in the bandwidth also. So that may be one of the reason the metric values get very much balanced. So let me quickly go and revert back the change. So I'll go to 102 and I'll change the bandwidth for E12 and E00. So let's do this. 00 bandwidth is 1234 E1/2 1/2. The bandwidth is, because again if you change the bandwidth you'll go and see the values will get changed. So for 105 now you can see that you have only one successor, although we have used the command called variance. So if I go ahead and check show IP route for 105 there you can see that you have only one path. Okay, so this is the use of the changing the metric value with help of bandwidth, although we know that we can change with a delay as well, but I'm not showing here. We can change with the bandwidth, and then we can play around with the variance command. Finally, we have one use case related to a stub. So suppose in this case, if I got some issue, and if something will happen with my destination network, somehow if I am not able to get my destination network, so what will happen? So in this case, suppose if 105 is the hub, so this guy here is the hub and these are the spokes. So you can go to the spoke and simply you can enable the command called stub. So suppose if this link will go down, for example, just in case of example, and because this is the stub, so the query will not processed, and simply the stub will respond to the hub that, oh, you can't go beyond me, I don't have any network that you're looking for. So in this case, what we can go do that we can directly go here and we can go to router EIGRP and we can check the stub command. So if we have EIGRP and stub, now you can see that you have connected, leak map, receive only, static, summary. So we can give connected and summary. Now you can see that it reran the algorithm. So now this become the stub, and the theoretical aspect of this we have already discussed. All right, so let's stop here. In 3.2, we have to study about border gateway protocol. Although the syllabus, you can see it's very small, that we should configure and verify eBGP and do some path selection or learn path best path selection criteria. But I'm going to start with zero. I'm going to start with the beginning of BGP. So what is BGP, what is IBGP, eBGP, etc., etc. So let's start. What is border gateway protocol? The first question arises is that already there are protocols, routing protocols. There is still why I need one extra protocol. Now the answer for this is that this is the exterior gateway protocol. Means this will override or this will run on top of any of the underlying protocol, any of the underlying IGP protocol, and it will work such as the application protocol. And that's true. If you see the port number that BGP is using, this is using TCP port number 179. Generally, applications, they are using TCP port numbers, or they are using TCP or UDP. So BGP is a type of application protocol generally built to run over the over any of the protocol and cross the one or one autonomous system. Again, the autonomous system is one region, so cross one region and then it can go to multiple regions. Or if you want to control multiple region routing or the network advertisement or the routing control you want across the multiple region, then that's the protocol. Or in other words, we are telling that it's a protocol for internet. It's a highly robust protocol, and it has so many tuning options. It has so many attributes, so we can tune it, and that's the thing. So it says advanced vector protocol with high level of tunability that can go across the regions. It is a type of application protocol, and the final point about this is that it can interact, or it can hold, actually it can hold a big amount of a routing database or routing table. Okay. Defined by the AS path, we know that autonomous system to autonomous system, it has its reachability. It is a distance vector protocol. It has the autonomous system number defined here. You can see from 1 to 65K. Few of the numbers are private and reserved. Nowadays, we have dotted notations as well for the BGP. Now, here you can see that why you want to use BGP. So when you have multiple connection exist to external autonomous system, means you have multiple exit or you have multiple ISP connected with you. Either those multiple connections with the same carrier or provider but connect via routing policy. The existing routing equipment can handle the additional demands. So it is highly tunable. So if you want to do some sort of preference, path preference, some sort of load balancing, etc., etc., so those things are achievable with help of BGP tuning capabilities. Okay. Now, one very important point here is that BGP true benefit is to controlling how traffic enters the local AS, local autonomous system, rather than how traffic exit from it. So the true benefit is that how you are controlling the traffic when it is coming to you, when it is coming to local AS. Now we can have two type of neighbor. We can have IBGP or we can have eBGP exterior and interior BGP. iBGP means within the autonomous system. So in this diagram, router B, C, and D, they are iBGP peer, or they can be iBGP peer. And then different autonomous systems like AS 100, 200, 300, they can be eBGP, exterior BGP peers. Now we have options that what type of iBGP relationship I want. Do we have full mesh, or what other tuning options we have? We'll go and check later on that we have multiple options when we are talking about the internal neighbor relationship or interior neighbor relationship. Generally, when we are creating the iBGP relationship, we should create fully meshed. Otherwise, there are some other options to uh, do the advertisement for the network that one iBGP peer is getting and advertising to other devices. Now, one device can have only can be part of one autonomous system, and if you want to make part of multiple, it will throw an error. We have the AD value fixed for eBGP. For eBGP, the AD value, the administrative distance is 20, and for iBGP, it is 200. Okay, so that means the eBGP routes are preferred than iBGP routes. So 20 versus 200, lower is better. That thing we know. Now the BGP peer messages, we have BGP peer messages. What type of messages we have? So we have open message, we have keep alive, we have update and notification. Now open means that I want to form the relationship with my neighbor, and here you can see that an open message is sent between peer to initiate the session. The open message has several parameters like version, local AS, BGP router ID. Then you have the keep alive. Keep alive is something like you are sending the keep alive message to your neighbor that you are alive or not. In BGP, by default, it is sending that keep alive message after every 60 seconds. A 60 second into 3, that is 180 second, is the hold down timer. So after 3 keep alive message, if you are not getting response, that means your BGP neighbor is dead. You will mark this as a dead with help of notification message. So now this notification message is sent when there is a fatal error condition. If a notification message is sent, the BGP peer session is toned down or reset. Anyways, if your peer is down, that means you will send the notification peer is down. Then we have the update message that are used to exchange the route between the peers. Now here in BGP state machine, that is the finite state machine, we have some other messages as well. So what exactly this is, that when a BGP peer session is forming, at that time, if you go, suppose if I have two routers and I want to form the BGP neighbor relationship in between that, so you will find that they will exchange some sort of messages. Those are idle, connect, active, open send, open confirm, established. Correct? So idle means that it is initiating the BGP state. Then connect, that you are waiting for the remote peer. Active, that you are actively initiating the connection. Obviously this connection is TCP. Then open sent. Open sent means you have sent the open message. Once you send the open message, then BGP listen for a reply keep alive. So you have sent the message, you got the acknowledgement, that is open confirm, and then the finite state machine will establish the connection. Correct? So it's very easy. Idle, connect, active, open send, open confirm, and they establish. Now if peer is stuck in active state, the potential problem may be that maybe you have password mismatch, maybe ACL is blocking port number 179, maybe you have incorrect AS, maybe you have incorrect neighbor statement, and so on. So if it is stuck in the active state, that means it is not good. Correct? Then you have to troubleshoot and make this as a working. Now, how we are going to configure it? We know that one router can be part of one BGP autonomous system. Go to the router BGP, and then the autonomous system. If it is a eBGP peer, remember, if it is a eBGP peer, they have the TTL value of 1. So they are always thinking that their next hop is, or their peer is one hop away. So in that case, you don't need to modify the TTL value. You don't need to modify anything, any other thing. Means router B of AS100 and router C of AS900, they have to give simple command router BGP, neighbor and remote AS. That's it. Now, if it is a IBGP pair, then you can go and you want to update the source. So for example, generally we are using a loopback as a router ID. So in case of IBGP neighbor relationship, you need this update source loopback command, correct? And I'll come to that eBGP multi-hop option as well. Suppose if you have eBGP relationship and it is multiple hop away, then you can go and use the eBGP multi-hop. So for example, 200. So in this example, it is showing simply that suppose if you are using the loopback address instead of this physical address, if you are going to use the loopback address that is again one hop away, then how you will form the relationship? So in that case, say for example, the router C is using the neighbor 1111, and we can see that who is 1111. Obviously this router B loopback address is 11111. So in that case, that will be hop away. For that we should go and use neighbor 111 eBGP multi hop 2. So you should count how many hops away your peer is, and then you can use this multi eBGP multi hop command. Finally, we can go and use the password with the neighbor command. So for that, we have the neighbor password, and so for example, Cisco. We have other option as well, that if you want to change the keep alive timer, we have discussed this about that the default keep alive is 60 seconds and 180 seconds is the hold down timer. But suppose if we want to use some aggressive timer, we can go and use timers BGP 30 and 90. And in that case, we can go and set the BGP timers. All right, so let's stop here, and in the next section we'll perform the lab, whatever we have covered in this section. Now we have to perform the lab related to BGP. Here you can see in the diagram that I have router 1 in AS100. So AS100 and AS200 router and switch 105, they're going to form eBGP relationship, exterior BGP, and in between AS200, say for example switch 101 and 105, they are going to form IBGP relationship. Okay, so let's start the configuration for R1. If I go to R1, I can go and I can initiate the router BGP process. So for example, AS is 100. Then what is your neighbor? Now for neighbor, I can go and check the directly connected neighbor. So that is directly connected neighbor is this 10.1.1.1, 10.1.1.1.0.5. So he has the neighbor 10.1.1.1.1.0.5. And then what is the remote ACE? So we should go and give the remote ACE. Say for example 200 I'm going to configure. Then here if I go and check show IP BGP summary, you can see that state is idle, correct? So it has initiated, and if I go and do some debug IP BGP, what type of packets I want to debug. So for example, I don't want all, but if I can get events, and monitor. So I can go here. Yeah, I can see some of the messages. So already we are monitoring over the screen. It's showing some of the events. If we debug IP BGP, just wanted to see the TCP number. So all address families and import in IPv4, keep alive, don't want that, out, in, etc. Okay, if I do all, then it will be big output. Okay, now one other command we have. So here you can see that at least I'm getting this message, active went to active to idle. It's tried to move from idle to active, but it is not. And then here you can see that you have the TCB. So if we go and check show TCP, TCB, and then enter, show TCP, and if you want to see the brief, you just wanted to see the open ports if you have, and if you have any other option related to that. So you have the TCP, TCB, actually that's the command, TCP, TCB is the command, and if you know the TCB address, that will work. Anyways, so let's move on and go to the other side. Here I want to initiate the router BGP process 200, and then the neighbor is a 10111 whose remote AS is 100. That's it. So now if I go here and if we see the packet here, you can see, let's stop the screen. So here you can see that you have the open, capability is open, and then a route phrase, then open, again active, went to open send to open confirm. These exchange we have actually checked in our session, and then you can see the neighbor is up. And now if you go and check the TCP TCB, so now you're getting this established session, and you have the address as well. And let me do let me undebug, and now you can see the output for this. You can see the port number is this, so local port is this, the foreign port is this. Great. So most of the information we are getting from here. All right, so now the eBGP relationship is up and running. Now what I want, that as per our diagram, I want to create iBGP relationship as well. So for that, I know that neighbor is say 101, 101, 101, 101, and whose remote AS is the same that I have. But since I am using the neighbor command, which is the loopback address, so I want to do the update source loopback 0, and I should check show an interface loopback 0. So yeah, that's correct. Now I'll go to 101. So let's go there and let's do the configuration for this. First of all, let's enable the BGP 100 whose neighbor is 105, whose remote AS is the same that I have, and then the neighbor, this update source loopback 0. Now if you go to 103, we go to 105, you will get one message, show IP BGP summary, that you have two neighbor, both are up and running. So one is up and running, that you can see here, You have a 0 prefixes. State is up and running. Now if everything is okay and correct, in between 105 and 101, so 101 and 105, then they should form the BGP, but it is not. So let's quickly check the BGP configurations, show run section BGP. So here you can see that I am part of 200, and this is also part of 200. So here you can see that directly you can see that problem, that we should have correct configuration. This is part of 200, and now you can see that we are getting some sort of notification messages. We have seen that this is something when you have some error notification messages, we are getting some malform construct. And if you go here and you check the summary neighbor idle, like that it is coming. Let's go back and let's change the AS and we'll come back to 10. All right, so let's complete the basic lab. Now here, if we go to 101, we can see that the BGP AS is wrong. So I will go and do the changes. We'll go and change this to 200, and then rest of the configurations are correct. All right, now once we done that, we can go and check the summary. You can see this is up and running. Likewise, if you go and check show IP BGP summary, that is up and running. All right, so now once we have this, what we can do, we can check other basic stuffs as well. Now, for example, that we are going to continue the lab, plus I'm going to add few topics more in the lab section. We'll go and check the BGP neighbors once we enable run the BGP. Then we'll go and check the BGP neighbor. Plus we have one concept related to BGP synchronization. What does it mean by BGP synchronization? Although our lab setup is different, but I'm going to take same type of structure, that I have one device for eBGP and few devices for iBGP, and then already we have checked the iBGP and eBGP, how we are going to form these BGP tables. Now what is happening, that once we have the neighbor table, then it will build the BGP table, and then we have the routing table. Correct, but one of the important table we have is the neighbor table. We have this command show IP BGP neighbor, where we can go and check the BGP neighbor details. If you want to check the specific detail to a specific neighbor, then you can go and use this command show IP BGP neighbor and the neighbor address. Next we have the BGP synchronization rule. Now this is important. What is happening, that the general rule for BGP, or the golden rule for BGP, is that if your BGP is there inside the autonomous system or within the autonomous system, so you should enable iBGP rule, or you should do iBGP full mesh capability inside the autonomous system. Suppose if you do not do like this, so what will happen, say for example in this diagram, this AS wants to reach to this network. Now suppose if I have iBGP relationship here, so here I have obviously the eBGP, and here obviously we have the eBGP relationship. So the traffic or the update will come to B, and then B it can go to D, because remember in BGP the iBGP neighbor relationship, it is not mandatory that they should have physical connectivity. So these BGP relationship can form over non-connected interfaces as well. Okay, so that means that I can have the IBGP relationship in between B and D. Now then it will go and reach to E. Now at this point of time, the router C, he don't know about this network 10505 etc. 10500. Next time if the return traffic will go and hit to D, and again suppose if it will go to C, since C is not having the update related to 10500, or he don't know how to reach to 10500, he will be working as a black hole. He will start black holing the traffic. So what is the rule then? Then the rule here is that you should have eBGP relationship, should have iBGP relationship in between all the devices, correct? And that's the rule you have. You should have this type of mesh rule or the topology, and that's the reason we are using uh, some sort of other technology like configuration or route reflection, because say if you have so many devices within autonomous system, and if you go and turn on BGP, and if you do this full mesh iBGP relationship, then obviously the CPU, the core utilization, memory utilization will increase. So this is not the optimal design solution. This is not that all the routers could achieve this target, because obviously they have to think more, because they have more number of control packets to process. The same explanation here, what we can do for BGP synchronization. The local AS is not a transit, so in which case you don't need if your AS is transit, or all routers in the transit AS run iBGP and are fully meshed. Okay, so the question here is that when you don't need the synchronization rule, answer is when your AS is not working as a transit. Second, when you all the devices in the transit, they are running the iBGP rule. How you can disable the synchronization? The command is no synchronization, and you can see that 12.28T synchronization is disabled by default. So in latest code, the synchronization rule is disabled. All right. So let's stop here, and we'll go back to our lab section, and whatever small and basic verification commands are there, first of all, we'll check that before moving further. Now we are going to perform the lab task. You can see in the diagram that we have AS100, we have AS200. Inside AS200, we have devices that are going to form the iBGP relationship, and in between AS100 and 200, we have the eBGP relationship. So let me quickly log into the devices. We are going to perform some of the tasks that we have covered already in the theoretical section. So let me quickly show you that what configuration I have over these devices, and obviously let's see the IP addresses as well over these devices. So if I send this script, you can see over switch 101 we have this IP. Let me show you this diagram as well. So here you can see the diagram and the IP schema. Router 1, that is inside AS100, having loopback 1111. All the switches, they have loopback as their name. So for example, here you can see the loopback IP, then the interface IP, then the interface IP. All right, so you can refer the diagram that we have, and as per our diagram, we have assigned the IP addresses to the interfaces. All right, now next thing that we should go and check the BGP neighbor. So I can go and check show IP BGP summary to all the devices. Now here I can see that As per our diagram, uh, we have EBGP relationship and the IBGP relationship. Now, if we have this type of topology, still what you want that switch 103 and 105, although they are not directly connected, they are indirectly connected, they should form the neighbor relationship. In that case only they have the full mesh, correct? So suppose even I have the back-to-back connection here, although I don't have, but still I can go and form the neighbor relationship in between the 103 and 105 because underlay we have EIGRP up and running. So before doing that, you can see here that all the devices, they have their EBGP and IBGP relationship running on. EBGP in between R1 and 105. So 105, one interface having EBGP relationship, other one is having IBGP. Now suppose if you want to know detail about that particular neighbor, so what we can do, we can go and check show IP BGP neighbor. And first of all, let's see that in this neighbor command, let me see that uh, what outputs you have. So you can go and simply check show IP BGP neighbor. Obviously, it will show you all the neighbors. So here the neighbor ID is this, belonging to 100 as a autonomous system, the router ID, the establishment, what time the neighbor got established, what type of messages they have exchanged. Here you can see open, notification, update, keep alive, and route phrase. So like that we can get the details. Now if I am very much specific to a certain neighbor, then I can go and run the neighbor command related to that particular neighbor. So I have one neighbor 10.1.1.1 and I can run and I can verify that. Okay. So what I will do first of all, that I want to show you that we can form the IBGP relationship in between 105 and 103. So let's do that. I'm already inside 105. I can go here and router BGP 200. I have my neighbor, for example, 103, and whose remote is the same. And then for this neighbor, I can go and use update source loopback 0. Now again I will go to the 103 and we can run the same command. Then we have the neighbor, say 105, 105, 105, 105, and the remote is the same, and then the neighbor update source is loopback 0. Alright, so we can see here now show IP BGP summary that we have one new neighbor added. So not only my directly connected neighbor, but my indirectly connected neighbor is also there. That's a true power we have with the BGP because this is working as a overlay type of protocol. Alright, so once we have all this information, then what I want, so I want to have a, so for example in router 1 and 105, if you go to router 105 and you want to put the password, suppose if I go to neighbor, say neighbor 10111, and you can give the password the Cisco. So if you put password from one side, other side also you should go and check the password, router BGP 100, and just to show you that it will take some time because we know that keep alive is sending after every 60 seconds and the hold down timer is 180 seconds. So it will take some time to tear down the neighbor relationship. Still your neighbor is up and running because BGP is meant to be slow protocol due to various reasons. So if you wait, it will take some time because one side your neighbor having the password, other side we don't have the password. So I'll wait till the timer will expire and then I can come back here and I can set the password. Meanwhile, we'll go and check the other option. So we have timer option as well. So for example, I can go here to the router process and then I can check the timers for BGP. Oops, timers, BGP, and then keep alive. I can give 30 and then hold down. Suppose if I 10 and 30, keep alive 10 and hold down if I give 30. That means for all the neighbors it is true. Now suppose if you are specific and you want to change the timer for a specific neighbor, so for example 105, 105, 105, 105, then also you can do that. So where we can go and check the timers here, you can see so many options we have. So for example 20 and 60. So it is telling that you should go and specify the keep alive, say for example 20, and the hold down is 60 as a peer group. So then it will take that command. We can check later on about the peer group as well. So we can leave it, but yeah, we have option that we can go and specify over the uh, per neighbor as well. Okay, so let's quickly see this BGP configuration. So here I have the neighbor with some timer, and then if I go here and check, and we can go and check show IP BGP neighbor 10.1.1.1. So here you can see that you have the neighbor established time. It is showing that what is the hold down timer and the keep alive. Although if you go here and check show IP BGP neighbor 105 and what is my neighbor, that is 10.1.1.105, and here you can see that still is this because maybe the command that we have run is okay. So here you can see the timers and the neighbor command. When we are running this neighbor command earlier, so let me show you that we are getting some error because that was not my neighbor. So that's the reason it was throwing an error, correct? Because my actual neighbor is 10 11110 not 105 So what I'll do now, I can go here and I can do this neighbor and then 10.11.105 timers. I can specify say 10 and 30, and that's it. All right, we'll go here as well, and I can go here router BGP 200, neighbor is 10.111, Timers are 10, 30, and then we can go and check show IP, BGP, summary, clear IP, BGP, say star. I'm clearing the BGP table, and now if we go and check the neighbor table, so let's go and check the summary. Now you can see that after clearing that, we have the authentication issue because we haven't put the password for one side, and here you can see the password issue is there. So I should go and show this neighbor and with the password. So I can go ahead and give the password as Cisco. Once I do that, you'll see that it will get converged and the neighbor will come back up. Now it is up. So we know that in BGP, first of all, it will form the neighbor table. Then it will go and form the BGP table. Then it will go and form the routing table, or those things will go and get added inside the routing table. Okay. So let's stop here, and next section we'll discuss more about all these behaviors. Next topic we have BGP route reflectors, configuration, and the peer group. Now what is happening in case of IBGP relationship is that whenever IBGP peers, they are getting the update from outside. So what they are doing, they are assuming that all the neighbors, either it is physically directly connected or it's not physically connected. They assume to be in full mesh. Now, if they are in the full mesh, then all the IBGP neighbors will send the update to everyone. Otherwise, there are chances that, say for example, router D will get the update, he will send to A, but A will not send to the other router because he will think that update will come from some other way that is again connected in full mesh. Now, while we are doing the approach of IBGP full mesh behavior or approach, so in that case, what we are doing that we are using some more bandwidth. We are consuming actually more bandwidth, more processing and cycles. So why? Because we have more number of BGP neighbors, correct? So if you have more number of neighbors, more number of control packets will send and receive to maintain that BGP state or BGP neighbor tables, correct? So that's one of the thing that what we can do, that we can use a route reflector. So the idea behind this is that any of the router which is there who is working as a symmetrical device. Now what does it mean by symmetrical device? Symmetrical device means he is approachable or reachable to most of the other routers. So that particular device, we are making this as a route reflector. So when he get the update, now his responsibility is to give the update to all the other devices. And this approach actually has been taken inside software defined networking as well. How? So if you go and check software defined networking, you will find that we have clause architecture. We have leaf, spine, and leaf. And again, suppose if you have more spines, spine 1 and spine 2. So all the leaves are assumed to be connected with the spines. So what does it mean? It means that behind the scene, all these spines, they are working as a route reflector. So at the moment they are getting the update, now their responsibility to send the update to all the leaves. And that's the fundamental here in route reflector. At the moment he will get the update. So suppose if I make him as a route reflector, now his responsibility is to give the update to all the other IBGP neighbors. Rather than we have the full mesh topology, route reflector will reduce the number of code, reduce the number of IBGP pairs will drastically increase the CPU and the memory performance. Correct? Now, not only the route reflector is the technique, we have other technique as well. We'll see in the next slide. So how you can do this? Here you can see I can go to router 1 and I can tell router 1 that your router B and D are the route reflector client. So the configuration is very easy. Just use neighbor, the route neighbor ID, remote AS, neighbor ID, route reflector client. That's it. Now we have other approach as well. We can use BGP confederation to come to the same place or to achieve same target. Although the configuration look like little bit tricky, but the concept behind this is to reduce the number of IBGP pair, and inside IBGP you can use EBGP type of behavior. So what is happening in this case, you can see in the diagram that you have main autonomous system. These main autonomous system, they will form the EBGP relationship. Inside this main autonomous system, I have sub autonomous system who is responsible, and you can think that who is child of the main autonomous system. So he is the child. But now since you have two different autonomous system, so 777 and 888, they will form EBGP type of relationship. So they will send and receive the updates because there is no problem with the EBGP relationship. We have this issue only with IBGP relationship. So inside the autonomous system, although it is showing only one device, but you may have multiple devices inside one AS. So they can exchange their neighbor tables, or they can exchange their updates within the across the autonomous system. Correct? So that's one concept, that you can see that you have different autonomous system inside same autonomous system. But what about AS500? When AS500 will see, he can see only AS300. He will not see the inside autonomous system, and that's the key here. Now the configuration is again straightforward, but it's like a little bit tricky. So first of all, this 888 is part of 300, 777 is part of again 300. So here you can see that router BGP configuration identifier this, then router configuration peer is this, then neighbor this, neighbor this. So you can see this configuration. If you go and check, you'll find that inside the configuration you have to think that these are the EBGP peers, and inside that these devices can peer, but they are part of the main group, that is 300. So your 888 and 777, they are part of the identifier 300. Again, you can see that BGP configuration peer is 77. So for him, he is the peer. This is the configuration for router B. Likewise, if you go and do the configuration for router A, you have to follow the same step. So you can see that step number 1, step number 2, step number 3, and then this is the same one that we used to use, correct? And then finally, the remote AS that he has is the having the AS 500. Okay, so these are the steps that we should follow, and you can go and check all these steps. You can refer the diagram, and then you can have all these steps as well. So let me quickly go back and let me quickly show you that if we are here you can see router B is a part of EBGP. It's part of configuration group as well. So that's why you have this last line. Apart from that, you have these 4 lines. So it's tricky because see that he is part of main AS. He is doing the BGP with this AS, and he is doing the EBGP relationship. Now all these commands have been configured here, and you can understand all these steps. Now for outside device, the configuration will be straightforward, and what we have discussed earlier, neighbor and the remote AS, that's it. All right, so final topic for this session is the peer group. Why you want to use a peer group? Again, to increase the performance of BGP, to reduce the number of line, to reduce or to optimize the processor and the memory usage. You can use peer group. So suppose I have 10 different neighbors and all those neighbors has 6 command that is common. So what commands will be common? So for example, remote AS, update source, route reflector client. These things are common. And I have 10, for example, I have 10 devices. So 10 into 3, that means 30 configurational lines you can put inside the peer group. So next what you have to do, you don't have to write all these codes. Rather than you can go and use a neighbor 1111, for example, peer group, my group. Neighbor 2222, peer group, my group. That's it. Neighbor 333, that's it. So you are saving a good amount of code, and apart from that, it is effectively to optimize the process and the CPU cycles. Okay. All right. So what I'm going to do in the next lab that I will perform the task related to route reflector, and again we can go ahead and we can add the peer group as well. There are very less number of people that we know that they are using configuration. So, and even in this syllabus, it is not required that you do the lab or do the CLI configuration for configuration, but just for understanding purpose, I have given this notes and you can refer this. Okay, even in our CCNP course, it is not required to do the CLI configuration, at least for this section 3.2 for route reflector, but for future perspective to understand more about BGP and their coding and stuffs, we should understand the at least the route reflection and the peer group. Now we have the lab related to route reflector client and the peer group. Here you can see the topology diagram. We have R1 router and then switch 105, 101, 103. They are inside one AS. Already we have done the setup, like we have IGP as EIGRP running in AS200, and then we have eBGP relationship between AS200 and 100. So what I'll do here, that we have one loopback. We know that we have loopback here in AS100, and that loopback I will go and advertise. So for example, I can go to my BGP 100 and we have various methodology to advertise a network. One of the method is to use the network command and then give the exact mask. Now once we advertise this, I can go and verify this inside the peer router. So I can go and check show IP BGP, and here you can see that I am receiving this route. The next hop is 10.11111. The AS path is 100. Now let's see if you check the diagram. So 111 loopback is coming to this device, this switch actually 105. Then let's see that how it is reaching to 101 and 103. So the same command show IP BGP, that's the BGP table. I can go and check to 101. 101 again, it is coming via this next hop. It will show like this only because eBGP next hop are not getting changed automatically. We have to run a command, so they will change the next hop. Now finally 103. Again, you can see that next hop is this. Now one thing I want to highlight here is that when you go and check the output in 105, you can see that you have the asterisk and the greater than sign. This asterisk means that it's a valid, and this greater than sign is best. So it's a valid best route that it is coming to 105. But if we go and check 101 1. So it is not telling that this is the best. Even if again further down the line, if you go to 103, it is telling that it's not the best route. That's the one thing. Second thing, that since we have created full mesh IBGP relationship, so if I go here and check show IP BGP summary, so we have the relationship with switch 105 as well. So what does it mean? If I go and check the BGP configuration, and if I go and remove this configuration, that is, I don't want the neighbor relationship form with the switch 105, then obviously I should go and remove these subsequent lines. Now if we go and check the BGP, here it is. Now what I can do here, I can go and clear the BGP. Since this is a lab, so I can use IPBGP star, but be very careful if you're running this command. There are chances that thousands of route will get refreshed. So that's the reason we are using keyword like soft. So this is soft reconfig inbound and outbound, and inbound or outbound, like that we are using those keywords. All right. So now if I go and check show IP BGP summary, and we can see now that we have only one neighbor. And if we go and check the show IP BGP, that's the BGP table. So let me go and run that command, show IP BGP. I want to check the BGP table. Now you can see this BGP table is gone. Why? Because that's the nature that the BGP has. So the routes coming to this, because they are directly eBGP peers, and then he will advertise to this. But 101 will not advertise those routes to the other devices. Okay, and that's a loop prevention mechanism we have inside BGP, until unless they have in full mesh or route reflection or sub AS or this configuration. So now what we'll do, that will go ahead and make 101 as a route reflector. So let's go and do the configuration for 101. All right, so we'll go here to 101. We are inside 101. I can go to router BGP 100. Then what neighbor we have? The AS is 200 for 101. So we have neighbor. Let's check the neighbor. We have this command. We can go and check. So I have 103 and 105 as my neighbors. So I can go to the neighbor, and then we can go and use as a route reflection client. So both for 103 and 105, I want to make this as a route reflection client. So 103, I have made it. Now if I go to 103, and if I go and check show IP BGP, still you can see that they are not learning the route that is coming from 105. So what I can do, that again I will go and make this neighbor as a route reflection client. And now if you go here to 103, that's the bottom one, you will start getting the update from router number 1. So it will be like it is coming from here, and then it will go here. Since he is the route reflector client, he will reflect the route to 103. And same is true. If the routes are coming in this direction, he is getting the routes, then he will go and reflect the routes to 105. So both ways you will find that it is valid. Alright, so let's see this. Because BGP updates, they are taking some time to get update. It's taking some time. Let me quickly see this. Do I have the relationship with 101? It's there. I'll go and do clear IP BGP star. Now it is showing idle because now it is up. So I have my table that is up. Now I told you one important thing, that whenever we are getting the routes, what is happening in case of IBGP. So you got the route, you know who is the next hop. He got the route, and his next hop should be this device, correct? From where I am getting the route. But if you see it, you will find that the next hop is still 10.1.1.1.1. That's the problem we have with the uh, IBGP relationship. So what we can do here, we can go to 101 and we can make, say, neighbor. So who is his neighbor? Say 103. So neighbor, before doing that, let me quickly show you this if all the BGP configuration is correct. It's correct. So I can go to neighbor. Hey, this is the neighbor, and you know your next hop is me. Okay, and likewise this router, we can tell router BGP 200 neighbor 101, your next hop is me. So this guy, your next hop is me. Now if you do this thing, if you go to 101 and if you check show IP BGP, you will see that first of all I need the best route here. Okay, so here you can see that 105, he is telling 101 that next hop is me. Hey neighbor, this is my neighbor, your next hop is me. So that means if you go here and check, this should change. See, it's got changed. It took some time, but it got changed. Now if you go 103, you are getting the updates. Even we don't need this command here to 101. If I go to 101 and if I remove this command 200, that is no neighbor 103, I'm your next hop self. Before pressing enter, if you go here to 103, who is the next hop it is showing? It is showing that its next hop is 105. That's okay for this point of time. So I can go to 101 and I can delete this. We can clear the routes as well, but ultimately we can see here that the target is achieved. So without having IBGP relationship, with help of route reflector client, 103 is able to get the routes from the EBGP from other AS whose actual AS is 100. Great. Now the second thing that we have to do is to do the configuration related to BGP peer group. So if you go again and check the configuration, although I have one command, I have two commands, very less lines of configuration I have here. But if I go to 103 and if I go to 101, and 105. So if I go ahead, show run section BGP, I have more number of configurations, so that I can reduce. So how we can do? We can create the peer group. I can go to 200. I can make neighbor, and then you can see the name of the peer group, say um, BGP peer group, BPG. That's just the name. Then what I can do here, that I can go and give the peer group. That's it. Now next, what we can do, say neighbor BPG, and what's the remote, say remote AS 200. Actually, I'm making this just for the IBGP relationship, so that's why I'm using this. Then again, I can go to neighbor BPG, update source loopback 0. Then again, I can go and check the other commands. So let me quickly go and check show run section BGP. So I have taken this command. I have taken update source loopback command. Then I have one more command, that is route reflector client. So for that also I can use it. So neighbor m say BPG, and then route reflector client. Alright, so once we have these commands, obviously I'll go ahead and I will remove these configuration. This is not required now. So once I have these, then I can do neighbor, say this, and peer group is BPG, then neighbor, say 105, and the peer group is BPG, correct? And if we go and check the, oops, so for that, if we go and check the configuration, where we are, I think I lose this. Run section BGP. All right. So here you can see that now I have the peer group, and then neighbors are mapped with the peer group. Correct? Even I don't need this command. Say I should remove this, is not required, taken care by peer group, and this is not required, taken care by peer group. Now think that suppose if you have more number of IBGP table or relationship, still what will increase? Only this line, correct? So now you have template where at least your 3 configuration lines are constant. That will be recalled by all these peer groups, correct? So now what I can do, I can go ahead and check show run section BGP, and I have an IBGP command. So what I can do here, that I can copy and paste. So for example, these 4 lines here, and then my neighbor is this 103. Actually I don't want, because we have removed that, and this peer group is a PPG. But suppose if you have more number of uh, peers or the neighbors, then you can go and do these commands, correct? Then obviously I can go and do no for this, and finally no for the neighbor command that we have with 101. We can go and check show run section BGP. We can go and check show IP BGP summary. Seems one is gone. Show run section BGP. So here you can see that I should have that neighbor command that is not showing here. So finally what I can do, I can go to neighbor, say 101, 101, 101, 101, and then the peer group is say BPG, and we can check to show run section BPG, that is BGP. Alright, so here you can see that you have the template, and then you're calling that template with this command, and our BGP is up and running. So this is the way that we can do the peer group. This is the way that we can go and do the configuration for the route reflector as well. We have very important topic, BGP best path selection. We know that BGP has a long list of attributes, and with help of these attributes, BGP used to provide best path. So what are those? Let's understand those first, and then next we have series of lab, and we'll test all these attributes, at least the important path selection attributes in the lab section. So how BGP providing the best path selection criteria? BGP contains multiple routes to the same destination. It compares the routes in pair, starting with the newest entry and working towards the oldest. Now, if you see that how it is going to determine, so suppose if I have uh, multiple paths to reach a certain destination, and then I'm going to check, means BGP is going to check criteria A, B, C, D, etc. in order to provide, okay, if this criteria, so I have to go via this path. If this criteria, I have to use this. If this criteria, I have to use this, like that. So this is in the order. First of all, it will go and check the highest weight. Then it will go and check the highest local preference. Now the weight and local preference we'll see in the lab section as well. We have following lab with that. You'll find that weight and local preference, at least local preference, is one of the attributes that is mostly used. Now both the weight and local preference, they are dictating the best outbound path. So what we are doing, we are applying the weight and local preference, say attribute values, or these values in the inward direction. So we are going to apply to the inward direction. That's the key actually. So where you're going to apply these, and to whom he is going to affect. So we are going to apply in the inward direction, inbound, and then they are going to dictate the outbound path. So that's the important thing that I want to cover. Now here you can see the order. So let me go back. Weight, local preference, locally originated route. We know that if it's local originated route, their next hop will be 0000. That means it's a self-originated route. Then the AS path. Now AS path and MED, the metric value, both are again important. So remember, weight plus local preference, both are very much similar. Then AS path and MED. These are the attributes that is used more and more in the production network. So AS path, we know that BGP is dealing with, or BGP is a distance vector protocol, and as per the AS, so you think that one autonomous system has a router, for a moment. And then if you have to cross more number of A's or more number of hops or router, that means it is not preferred. So if I am reaching to certain destination with 3 A's versus 1 A's, that means that 1 A's means via the path I am reaching with 1 A's, that will be the preferred. So shorter A's will be preferred. Then the origin code in the number, so IGP over E, GP over unknown. Then MED, again I told you that this AS path and lowest MED, both are very much similar, and even we have lab as well for these. Then BGP route type, eBGP over iBGP, eBGP will win. Then the age of the route, who is the oldest is preferred. Then the router ID, who has the lowest BGP router ID. Then the peer address, which router originate from the router with the lowest IP. So everywhere you will see that except weight and local preference where the criteria is high. Apart from that, AS, MED, then age, everything is lowest or the oldest. Correct? All right. So here you can see that weight and local preference are applied inbound, dictating the outbound. That's the key actually. So these 3-4 lines are the key. Inbound dictating outbound path, and AS and mid are applied outbound, dictating inbound. So what does it mean? So at least in case of MED, and let me draw here. So suppose you have ISP1, ISP2, and then you have your local AS. Now in case of MED and AS path, if you want to prefer ISP1 versus ISP2, so then you will go and apply the either MED or the AS path, AS prepend. That's the key. Because you have to choose, because you are choosing the outbound, so you have one subnet XXXX and you want to prefer either ISP1 or 2, you can use this method. Now when we are going to use the local path, so in that case, say when you are going to dictate the outbound path, so suppose if you have 2 exit and you want to choose one exit via versus second exit, so that in that case you are going to apply the either weight or local preference. Obviously I'll go and clarify these terms in the upcoming lab, and we are going to check the scenarios as well. So here you can see that you have one situation, one scenario that you have one route, say for example 192.1.1.0, that router D is also getting, router B is also getting. Now what I want that route should come or should preferred via router B. So in that case, what we can do, that we can go to router A, say router A, and then we can give neighbor and then the wait command. That's the one way. The other way, nice way, is that we can go and use the route map. So then what we can do, we can create one ACL or prefix list or access list, and then we can create the route map. We can match the prefix list, and then we can set the weight, and then we can go and apply to the neighbor. So here you can see the direction is in for the outbound traffic, correct? So to reach this network, I have applied weight to my neighbor, and that neighbor, so that means router A will prefer B to get these routes, correct? Again, you have the local preference. In local preference, the same thing, only the way that we are going to do the coding will change. And here you can see that we are going to apply now. Local preference has little bit difference with weight. What is that difference? So unlike weight attribute, local preference is passed on to IBGP peers and sending updates. Local preference inform IBGP router how to exit the AS if multiple path exist. So now what we can do, that local preference, even I can go and apply to these guys. So suppose local preference here, if I put 200 and if I put local preference 100 here, obviously this path will be preferred, correct? So that's the use of local preference. And here you can see that we have the example. But here we'll check the route map way of applying the local preference. Again, you can see here the direction is inbound. So here we are at router D, or maybe at router B also, there's no problem. So what we are doing for router B and D, here you can see that B and D, lower is better. So here, if B is 200 and D is 300, obviously the traffic will come via this B, because his local preference is 200. Likewise, you can see here in the policy, we can create the policy for B and D as well in the upcoming lab section. So I have this route. Same way we have created the route map and we have applied it. I'm matching this, and then I'm setting the local preference as so for example 300. Okay, and then I'm applying in. So here you can see that is 1.2, that's my neighbor. Then I'm applying in. Likewise, I will apply with local preference of 200 to router B. So obviously router B will prefer. Okay, so here you can see there's difference between wait and local preference. The local preference is passed on IBGP peers when sending the update. So that's actually the main reason you will not find use of wait more and more, because anyway the wait is Cisco proprietary as well. So mostly you will find the use case with local preference. The same thing we can do with wait with local preference, so better use local preference. And in the lab section, so we have the lab section. In the upcoming session, I will go and perform this task of wait and then local preference, and we'll see that how we are applying the in rule to affect the outbound traffic, correct? All right, so let's stop here. We'll start the lab now. Let us perform the lab task. In the lab, what we are going to do, first of all, I'm going to show you the entire setup that we have. Here you can see that we have 4 different autonomous systems, say AS50, then AS100, AS900, and AS200. Now from AS200, you can see the iOS, the router is router 7, for example. There I have one loopback, and that loopback is loopback 7777. 7.7.7.7, and that particular network I am advertising with BGP network command. So they will go and reach to AS 900, and then it will go and reach to AS 100. Inside AS 100, it will go and reach to router number 2. So before showing a complete path and how it is reaching, let me quickly go and show you the configuration that we have. So if I go here and check the configuration, show run section BGP, here you can see the configuration, and these IPs that you're seeing over the interface, these IP addresses you can refer the topology diagram as well. So router 1, here you can see the router 1 has very minimum configuration. It has one interface, and then we are advertising one of the network. Then router number 2, you can see the BGP configuration where we are running EIGRP inside the AS, and then we have 2 neighbor peer command, router 3 and router 4, and obviously we have one eBGP with router 1. Likewise, the configuration, BGP configuration for router 3, So let me do this. So here you can see the configuration for router 3. Router 3 in the diagram, you can see that it has eBGP relationship as well. So on the top you can see eBGP relationship with AS900. Likewise, we have router 4 configuration for BGP. Then we have BGP configuration for router 5, and then you can see router 6 and 7 as well. This is router 6 configuration, and finally router 7. Now what we have done, you can see that inside router 7 we are advertising one of the loopback with the BGP network command, and then we are going and seeing that how it is reaching to router number 2. So if I go and check show IP BGP, first of all I'll show the BGP table. So clearly you can see this AS is getting prepended. So the originator for that is AS200. So here you can see this 777. So the originator, then next is 900, and then it is reaching to AS100. Now here you can see that you have valid and best path, and who is the valid and best path? So it is telling 172.1.7. Now if you go here and check 172.1.7, so this is the best path. Via this it is going and reaching here, although you have the alternate path as well, that is 172.1.6. So 172.1.6, that's only the star we have, and the star means valid. So that means if I go and check show IP route for this particular network, and let's see. So here you can see that it is coming via 172.171.2, and they have learned this is the router tag and how many hops, etc. Correct? So it is learning via this. So what I want at this point of time, that it should go and learn via this particular neighbor, not via this neighbor. Other thing that we can see here, that is this changing the next hop? So if I go here and check the diagram, so obviously whenever it will go and move to the eBGP, then it will change the next hop, correct? So from here, either from router 3 or router 4, it will go and reach to router number 2. But suppose behind router 2 you have one other router in the same AS, so at that point of time you can see some differences. So you have to do some next hop self command, correct? So suppose if I go to router number 1, and if I check show IP BGP, now since this is the eBGP relationship, so for this route, who is the next hop? So he is saying that his next hop is changing, that's okay. But if router 1 will be also inside AS100, then it will be the problem. Anyway, so what is our target here? We want to have, or we want to learn this particular route from this next hop, or from this peer. So let's use the wait attribute. Before that, I want to create IP prefix list. So IP prefix list, say loopback 777 is the name of my network. Even I can go and give the a sequence number, and then I can use this if I want. So sequence 10, and then permit 7777/32. Alright, then I'll go and create one route map. Say my wait permit 10. What I want here, I want to match. So let's see, match the, let's see what is the option we have. So match the IP address, and that is the prefix list. What is the prefix list we have created? This loop 777. All right. Now what I want to do with this, I want to set the weight, say for example 8989. Then I will give one default statement for route map where I will not match anything, say for example 100. We can go and check the route map configuration. Say route map. So what we have done, that we created one IP prefix list. We have matched with the route map. Then we have set the width for that. Now we should go and apply this to the neighbor. And which neighbor you want to apply? So you want to apply this with 172.161. We want to apply with this neighbor, that is 10.1.1.2. So I'll go and apply with say 10.1.1.2. And what's the route map we have? The route map name is my TT. Because this is weight, so I want to apply in the in direction. So here you can see that it is telling that okay, so this is not the configuration that we have done. If you go and check, we have created the neighbor with the loopback, correct? So we should apply the loopback statement. So here you can see, so I should go neighbor, and the neighbor is router number 4, that is 444, and then the route map, and that will be in the my weight in the in direction. All right, now if you go and check show IP BGP, now clearly you can see that the next hop is not get changed. So for example, that's a problem actually with iBGP, and that's just to prevent from the loop. So that's a loop prevention mechanism. So what does it mean? That here you can see when the routes are coming, say 77777, and when it is entering to this AS, they are putting their IP as a next hop. When it reaches here, it should put these IPs as a next hop first of all, correct? So we should go and do a small changes in the configuration. So let me go and do the small change in the configuration. So let's do this. I can go to router number 3, say router BGP 100. I can tell neighbor 2222222, next hop self, and likewise we can go to router number 4 as well, and then we can tell router BGP 100, neighbor is next hop self. Now if you go here and check show IP BGP, you will see that next hop will get changed. Otherwise I'll force this BGP to converge. Here you can see at least next hop is not get changed, but the priority, I can see that weight update has been done and it is going via the bottom router. So here you can see that weight has done his effect, but it should change the next hop as well. And now you can see that they have changed the next hop. That's the correct actually. Weight has been changed, next hop has been changed. So this is the way, this is the use case with the weight. Now what we want here, that instead of wait. The same thing I want to do with the local preference. So first of all, I'll go to router BGP 100 and I'll remove this command. I don't want this wait, for example. So we don't need this wait. And next, what we want, that we want to use the local preference. So for local preference, let's go and check the route map as well. Route map, because now for local preference I want to create one route map as well. Now this time I don't want to apply this policy to R2. Rather than I want to apply this policy to R3 and R4. So how the local preference is working, that they are much more intuitive than wait, and their attributes can flow inside the AS. That's the key we have. So what we can do here, first of all, we'll see that how the 777 is getting reached to router number 2. Then here over router 3, I will set the local preference as 300, and router number 4, I'll set the local preference as 150, because I want that it should go and prefer this direction. Or suppose what we can do, that I'll go and create one more network here. So for example 88888 as well. Already we have 7777. I'll create one more 8888. So 77777, for example, should go in this direction, and 888888 should go in this direction. So how we can do that? Okay, so let's think that and let's try to perform that task. All right, so the target here is that 7 should go via router 3 and 8888 should go via router 4. So primary, secondary, secondary, primary, like that. So what I try to explain here, let me go and show you here. First of all, I go to router number 7 and I'll create one more loopback and I'll advertise that as well. So I can go here and create say loopback 8, IP address 88888, and then let's go to router BGP 200, and then we have the network 888 with the mask of 255. Now if I go here and check the same BGP route here, so now you can see that 8 is also coming and getting here. Now it is coming 3 and 3. So both the update, they are coming via router 3 that we don't want. For 7, say for example I want that it should come via router 3, backup will be router 4, but 8 should come via 4 and 3. Okay, so primary, secondary, and secondary, primary, like that we want to use. What we can do here, that we can go to now to router number 3 and we can create the prefix list first. So I'll go and create IP prefix list, say loop 7777, sequence say 10, permit 777732, and then I want to create one more loopback, because the deterministic criteria, I want to put some condition inside the route map. So I can go and create the network statements like this. Okay, so I have two different IP prefix list, and even I can copy and paste the same configuration to 4 as well, just to save our bandwidth. Alright, so once we are here, then we should go and create the route map. Say local pref, what I want to this route map. Say permit 10, match IP address, and that is the prefix list 777. For this, I want to set the local preference, say for example 8888. Okay, then I'll go to the other statement, that is say for example 20, and then I'll go and match the address, that is this guy here, and then I want to set the local preference a little less, so for example 88. Okay, and then I have another default route map like this. Alright, so here you can see the strategy for 777. We have the higher local preference. Likewise, I'll go and I'll create one more route map here to router number 4, where I want to match the 888. So statement number 1, I'll go and match the IP address, that is 888, and then I'll set the local preference, say for example 9999, that is very high, and then I can go to the other statement where I want to match the address, that is this guy, and then I can set the local preference 99. So the idea behind this is that for one of the prefix lists, say for example for 888, what is the local preference? Very high. And here for 888, what is the local preference? Very low. So just the condition. For 7 we have high, for 777 we have high local preference. For 8888 we have low local preference. Here the reverse. Correct? Now we should go and apply this to the neighbor. So let me see that who is the neighbor. It's the neighbor IP, router BGP 100. My neighbor is this guy here, and then the route map is local preference in direction. Correct? Now here also I can go and check router BGP 100. My neighbor is this guy, and the route map that we are going to use is the local pref is the name, and then the inward direction. Alright, now if I go here, so for 888 the 4444 should be the best path. So here you can see, now we can see clearly that they are losing the backup. So here you can see that now the routes are converging and they are getting set with the correct local preference. But still, if you want to clear the IP BGP star, you can go and do that, and then you can go and check show IP BGP. So it will take some time, but it will build the route, and clearly whatever our target was, we are able to achieve that target. Correct? So this is the way that we can go and apply the local preference. So likewise, we can go and testify AS path prepend and MED. Now the difference between AS path prepend, MED and the local preference and the wait is that the rules for prepend and MED we are going to apply in the outbound routes that will dictate the best inbound path. This is just the reverse that what we have studied and what we have done. So now in this case, suppose if we have route 10511 and you want to select B versus D, means how it is going to reach to router C and router E. So in that case, what we can do, say for example, in case of AS path prepend, we know that AS path again is like number of hop count. So if number of A's are less, that will be preferred. So suppose if I go in router B and if I add A's prepend 100, 100, 100, 3, 4 times. So that means the same route that C will get from D, E and C, that will be AS 100 and AS its own AS 900, like that, rather than it will go and get the route with AS 100, 100, 100, hundreds multiple times. So obviously it will go and prefer and learn the route from D. So here you can see that same way we can create the access list or prefix list, we can create the route map, and then inside the route map we can go and set the AS path prepend. We can use any number, so for example 200, 200, and then we can go and apply to the neighbor that we have applied for example wait, and we have seen for the local preference as well. 172.161.2, so we are applying to this neighbor. That means we are making the path B to C as a worse. So obviously you will see that the traffic will be preferred from 172.171.1, and here you can see in the output that yes, we have the valid and best route via 172.171.1 rather than 172.161.1. Now the same methodology can be used and same thing can be achieved actually with the MED as well. MED is nothing but multi-exit discriminator. By default it will be 0. We know that metric values are lower is better. So suppose if you go to router B and if you set higher MED value, so the router D to E to C path will be preferred. Again, the same way you can create the ACL, you can go and create the route map, you can match the access list or the prefix list, and then you can set the MED value, metric value, for example 200 here. That is much more better than bigger than 0. So that's the reason here again you can see that 0 is better or lower than 200, and that's why the traffic is preferred over A to D to E. So same thing we can achieve with AS prepend, and same thing we can achieve with MED as well. Alright, so let's stop here. In 3.3 we have to learn and understand about wireless technology, basics of wireless, the AP, how the APs are going to join the WLC or the control plane, how we can do the baseline troubleshooting. So let's start with the basics of wireless. Now wireless is very different than wired technology. We know that in wired technology you have routers, you have switches, you have cables, modem, endpoint systems where you have the NIC card, you are connecting the interfaces, and this is the way that network infra built. Apart from that, wireless technology is free from media. That is not 100% true. Free from medium is still in wireless technology. You have air as a media, or you have some sort of transport, but not the physical transport. So maybe air, maybe wire. Inside wire also, the wireless waves can go from one place to other place, but that is again not the exact use case we have. We'll see later on in this course that we have different type of frequency range or different type of wavelength for different wireless frequency, and which particular range we are going to use in the LAN. So it's actually broad thing, and in that broad we are using one is small spectrum or one is small slice of that wavelength for our wireless networking or for our wireless use. So let's start with a very basic, and then slowly we'll add um, things in this. We'll add some more and more concept in this. So here you can see in the diagram that you have sender, you have receiver. That's the uh, normal way of communication. So if there is receiver, if there is sender, if they are connected, then only the communication will happen, correct? Now in case of wireless, here it is showing that you have rope in between sender and receiver, but you have invisible media, say for example in wireless, but you have the waves. So for example, I'll use the term wave. So here you can see that you have the electric and magnetic field in the diagram. You have E and M, and they are propagating inside the air. So air is the media where it is propagating. Now, if this wave is not constant, so suppose you start one pulse and stop, so that will not reach to the receiver. So that means your wave should be constant. So it should have constant height and down. So here you can see you have up and down, means the flow of the wave you should have to reach to the destination. So at this point of time, with this slide, you'll understand, okay, we have media air, and then we have the wave. That construction of wave is with electric and magnetic. So we have electromagnetic wave. Now again, you can see that you have one sender who will send, and then you have a receiver who will receive. So at this point of time, I assume that everyone knows that we have the access point. We know that you have access point nowadays in all the networks. So you have access point who will send the wireless say waves, and then you have, for example, you have laptop where you have the receiver, so he is receiving, and the access point who is sending. Okay, so in that the communication will happen. Your receiver should have capability to receive, and the sender, now the sender can send in all the direction. Later on we'll study about antennas and all, and we'll see that what what is the use case of the direction of sending the frequencies or sending the wavelength or sending the signals. Okay, so you have sender, you have receiver. All right, then what is frequency? Frequency is the up and down cycle in 1 second. Okay, so let me show you the definition. I have taken the definition as well. So here you can see that frequency, the number of times the signal makes one complete up and down cycle. So when you go up and down in 1 second, so suppose if you are making 4 up and down in 1 second, so that's 1 second, your frequency is 4 hertz. Now again, what is hertz? Obviously, Hertz, this is one of the scientists who has done research and developed or given his thesis and paper related to electromagnetic wave and wrote so many books. All right, so Hertz is the most commonly used frequency unit and is nothing other than 1 cycle per second. So now you are sending the wave. Remember, you have rope and you are sending. So you are sending the wave, and in 1 second, how many up and down you have? That is 1 hertz. And suppose if we have 1,000, or if we have tens of thousands or hundreds of thousands, etc., thousands of thousands, so that will be determined as a hertz, kilohertz, megahertz, and gigahertz. We are very much specific about gigahertz in our wireless LAN network that we'll go and discuss. So now this is the thing I told you, that we have wide range of a spectrum. So we have cosmic rays, gamma rays, X-rays. We know that some of things are coming from sun. Some of the rays are spreaded in the space. Some of the rays we are using for medical healthcare as well. Ultraviolet light, microwaves, we know all these things. But what we are going to use, here you can see in terms of gigahertz. So if you see the spectrum is starting from 0, I'm focusing upon, or I'm focusing here, let me focus the spotlight, 1 gig to 10 gig. Okay, so 1 gig to 10 gig slice that we have. So in that we have 2.4 gig wireless and 5 gigahertz wireless, and then again you have the bands for that. So we are going to focus on these spectrum, and these frequency actually we are going to use inside our wireless network. Okay, so for example, for 5 gigahertz, you can see it's starting with 515 and going to 5.825. Remember, this is in gigahertz. Now, if you convert this into mega, so that means that 100,000 megahertz, and let's make this easy. So, say for example, you have 10, then 10 3, then 10 6, and let me make this as 10 9 if I'm not wrong. So 10 6 is your mega, 10 3 is your kilo. So this is the kilo, this is your mega, and this is your gigahertz. Okay, now suppose this is the range you have. So for example, 5.15 to 5.250. So what is the difference? So difference is actually 100.100 gigahertz. And now if you convert this into meg, so what will happen? Maybe 1 megahertz, because then you have to multiply this with 1, 2, and 3. So that means I think 10 megahertz. 10 megahertz is 0.1 gigahertz, correct? All right. So that's the difference of 10 actually we have. So everywhere you will see that here you have 10 meg difference. Again, if you go and see this, so 0.100, 10 megahertz, etc., etc. Means that's the band we have. Let me show you in the next slide. We have some examples related to that. So here you can see that all the spectrum range that it is shown here, and the same thing, that's the difference in between the spectrum, and that is defined as a channel. So suppose for this particular range, that is 2.4 gigahertz, starting with 2.412 gigahertz, reaching to 2.484 gigahertz, we have 14 channels. Now for one channel, what will be the difference? So this difference will be, say for example, 2.417, although it looks very small, but the value is big. 412, that is 500. This is in gigahertz. That means that you have 5 megahertz. So again, if you multiply with 1000, you will get 5 megahertz. Okay, so these are the calculation we should know. Again, it's very much mathematical, and little bit physics is also involved. So what about the channels? Here you can see the channels and the difference in between that. Let's continue. So here you can see that you have 14 channel, and in between that gap is 5 megahertz. Now again, if you see the overlapping and non-overlapping channel, you'll find that there is one condition. So if the signal bandwidth less than, or it should be less than, the channel width. So here you can see the signal bandwidth and the channel width. If signal bandwidth is less, there is no overlapping. But if you can see that signal bandwidth is more than the channel, so in between 1, 2, 3, 4, you have a small channel width. So in that case, you have the overlapping. Okay, so these things should be considered. Again, what's the concept of phase? Phase means how much shift there in the actual cycle. So suppose in the first diagram, you can see that there is 0% shift or 0 degree of shift. So that's how the two line is showing in parallel. But suppose if you have shift of 30° or 60° or 180°, then you can check the phase shift. Okay, so again, these are purely terms related to physics, some sort of electrical and magnetic signals. Again, we are studying in the networking. All right. So what are the terms that we are going to use more and more and more? So you will find that frequency, the hertz, then the wavelength, then the channel width, etc. So one of the key term we have is the wavelength. Now what is the wavelength? Wavelength is the length for one cycle. So the wavelength measured of the physical distance that a wave travel over a complete cycle, and that will be represented by lambda. So lambda define the wavelength. For 2.4 gigahertz signal, the wavelength is 4.92 inch. For 5 gigahertz signal, the wavelength is 2.36. Okay, so again, this is the mathematical calculation, the length for one cycle, that's the wavelength. Likewise, how we are going to measure the power. So here you can see that RF power, and that is in dB, decibel. If you see the diagram, you'll find that the power is defined, or this amplitude is defined in between two peakest, two peak. One is in the positive direction, for example, one is in the negative direction. So the maximum length in between two peak, that will give you the amplitude. And this amplitude we are going to measure, or it will be measured in either watts or milliwatt. So again, you can see a new term, and terms are coming more and more. So when power is measured in watts or milliwatts, it is considered to be absolute measure. Again, we have one mathematical formula. We're going to discuss about that. But important thing here is that for wireless LAN, the power will lie in between 100 milliwatt to 1 milliwatt, and if you convert in watt, that is 1.1 watt to 0.001 watt. So better will go and measure in milliwatt. So power will be in between 100 to 1 milliwatt for wireless LAN. But for other services, you can see that for AM radio station broadcast, this is 50,000 watt. So you can see how much power it is. So for example, 16,000 watt for FM radio. This is huge power, correct? All right, so let's focus only on the LAN side, on the wireless LAN side, and let's try to understand the mathematics behind that. So suppose if we have three transmitter 1, 2, 3 in the diagram below, and you want to check the relative power between 1 to 3, so you can see now we have one mathematics. Better we'll go and check the mathematical formula. So what will be the power difference between T1, T2, T3? For that, it will be measured in decibel, and decibel is a mathematical formula in the logarithmic function. Now if you just completed your graduation in mathematics or BCA or maybe engineering, then it's very easy and convenient for you to check this formula in dB. So when we have say 10 base 10 P2 by P1, that means that this is 10 log 10 P2. Actually, divide means P2 minus P1. So you can think like this. It's not the exact say 10. I can take 10 as outside because 10 is common. So this means log 10 P2 minus log 10 P1. And suppose if we have some formula, so for example P1 into P2, so that means plus. That's the log function we have. Suppose if you have formula something like this, log P2 into P1, so that means we can take 10 outside. This means log 10 P2 plus log 10 P1. Okay, and absolute means that either it's a plus and minus, we are taking the magnitude of that or the module of that. All right, so now let's try to understand. I'll come back and resolve this, that if we have power 1 and power 10, so what will be the difference? Now we are not going to do the difference of power, rather than what we can do, that will go and measure the dB. Okay, so dB means, so for example T2 by T1, and then you have log 10, and then you have 10, that means that will be 10 log 10 to the 10, that means this will be 1 as per mathematics. So the difference is 10. Okay, I'll come back to this. We'll discuss more on this later on after one or two slides. So let me go and complete the slides first. So then we have three different law for zero. Suppose if we have same power, so the relative power difference will be zero, because if, for example, 10 by 10 will give you 1, and log 10, um, this is the base, so 1 base 10 is 0. Suppose, what is the law of 3? Suppose if you have a difference of 2, so if you are getting the value log 10 base 2, this, that will be 3 dB. And if you have 1 by 2, minus 3 dB. Okay, so what does it mean? It means, suppose 10 by 5 and log 10, and again you have 10, that means you have 10 base 10, and this will be log 10 2 here. Finally it will come to 3 dB. This is again the formula. No need to mug up at this point of time, but if you want, you can take the reference. You can check any mathematical book related to uh, decibel. Okay, all right, so say what is happening actually here. So this, what at this point of time we can mark this thing, that this value is 3. Okay, and 1 by 2 means minus, so this value will minus 3. Later in this same section, after one slide, we'll discuss more about that. Then we have law of 10. What does it mean? So if we have 10 base 10, that will be 1. Okay, so 1 into 10, obviously 10. 1 by 10 means minus, so then you have minus 10. Okay, great. So now we understand the law of 0, law of 3, and law of 10. Let's try to solve some of the questions. So here you can see, first of all, we have the summary table. So if difference is 2, then the power difference will be 3 dB. If it is 1 by 2, minus 3 into 10 plus 10 dB divided by 10 minus 10 dB. But again, what does it mean? So from this example, it will be 100% clear. So you can see in the bottom that A, B, and C, their power consumption in milliwatt, 4, 8, and 16. Now B is how much more than A plus? Okay, so let's try to understand. Now if you go and do B by A, you will find 8 by 4, that will be 2. As per the formula, we know that log 10 2 is 3 dB, correct? So that means B is equal to A plus 3 dB. Now what will be C? So C, again, you can see 16 by 8, that means 2. C will be B plus 3 dB. And what is B? B is A plus 3 dB plus 3 dB. That means A plus 6 dB. Okay, so this is the way that we can go and calculate. Now you can think that, oh, it's a very easy example if I have some complex calculation. So for example, in this diagram, you can see that you have 5 and 200. Okay, so how I can resolve this 5 and 200? So what we can do in this, that you can go and check, sorry, you can go and check like 200 and divided by 5, so that will be how much? uh, 40. Now this 40 will be, the calculation will be 2 into 2 into 10, correct? So 2 means 3 dB plus 3 dB plus 10 dB, correct? So that means that E equal to 6 plus 10, so E equal to D plus 16 dB. So a little bit of mathematical calculation if you do, then you can go and check the relative power between two of the transmitters or two of the antenna. Alright, so these basic knowledge are required when we are going to learn some other wireless technology. So what is dB, what is hertz, what is amplitude, what is wavelength, etc. Alright, so we have three modulation technique that will come under 3 spectrum. So we have FHSS, frequency hopping spread spectrum, DSSS, direct sequence spread spectrum, and OFDM, orthogonal frequency division multiplexing. Now you can see that name itself is big, and we are going to discuss about exactly where they fit in the wireless LAN and which standard match which particular spectrum, correct? So if you go and check the technical detail like the physics and the electronics behind that, you'll find that there are so many things to understand one spectrum. So behind the scene, it's a complex mathematical and physical structure. Uh, so those things we are taking inside our digital world, in our networking world, and we are using it. So let's see that what exactly we are using. Although most of the engineers are using wireless technology, but we are not aware that behind the scene which particular spectrum or the modulation technology we are using with which particular standard, IEEE standard. So first of all, we have the FHSS, that is the early ones, means with the evolution or with the beginning of wireless LAN technology, we have this methodology, we have this modulation technique, we have this spectrum. So here you can see that it has a 79 channel, and you have problem as well, and we have some benefit as well. So what is the problem? Here you can see that the frequency hopping will follow this rule. So channel 2 will move to 25, then 64, then 10, then 45, like that it will jump. Now here in the diagram you can see that first of all it is supporting 2.4 gigahertz spectrum, and then you can see in the diagram that 2, then it is going to 25, then 45, then 64, returning back to 10, and vice versa. Now what is the problem? The problem here is that they are limited to 1 or 2 Mbps speed. Okay, that's one of the big problem, because nowadays we are looking for a speed, and this is one of the biggest problem. Now what is good thing is that whenever we are talking about first evolved technology, it's actually easy to set up and use, etc. Now all other technologies, modulation technologies, are also easy to set up and use, but behind the scene, the circuit, the chip, the coder, encoder, etc., it's a little bit complex, and because it is evolved from one technology to other technology. So what is the solution? So then we have the next approach, a spectrum approach, that is DSSS, direct sequence spread spectrum. Uh, it can give you higher throughput. So for example, we have one summary slide by the end of this slide, so we'll see that. So it is going to give you, say for example, 11 Mbps of speed. That is still not enough, correct? And this is also falling into 2.4 gigahertz band. So here you can see FHSS and DSSS, both are falling in the same spectrum band. Their speed, overall throughput is, although 11 Mbps is good, but it's still, nowadays we are working in digital workplace and all, still it's less. The other disadvantage it has, that because their channels are overlapping, so they have only 3 non-overlapping channel 1, 6 and 11. Now what is the technology behind? So let's try to understand. Here you can see this technology, this diagram, that how the bits are coming, they are getting coded, means they are getting arranged, again they are getting packed inside the block, and then it is getting modulated, and then it is going outside as a signal. So how it is? So first of all, we have the scrambler. What it is doing, the data waiting to be sent in first scrambler, means whenever any request is coming, it's up to a scrambler. It will do some scrambling, and then how the data will go. Now next is the coder, and it's important what coder is doing, that they are converting data into multiple bits. So coder use is to convert the data, whatever it is coming from the scrambler. So you can see that data bit is coming, and then coder is converting that data into multiple bits. Each of new coded bits are called a chip. So here you can see in the diagram, uh, all these bits are called as a chip. Now here we have DSSS usage 2 encoding technology. So maybe somewhere you have seen this short form. We have Barker codes and we have complementary code keying, CCK. That's a coding methodology. Now next we have the interleaver. What interleaver is doing? Again, it's important that whatever input you are getting, so obviously the data bits that you are getting from coder, the interleaver will spread this into separate block. So you have data, then you have bit, and then you have block. Data, bit, block. Finally, we have the modulation. Once the modulation will happen, then it will flow in the air as a RF signal. Okay. Now, more or less, the DSSS and the next technology, that is the OFDM, both are using same technology behind the scene, but in OFDM, you can think that you have parallel processing. So suppose that DSSS or DSSS, that they have this modulation technique for one stream of data. Now, if you do 64 parallel processing, or for example 48 plus 4 parallel processing, obviously your overall throughput will increase. So now suppose if you have 11 Mbps, you can multiply 11 Mbps by, say for example 52. So that much throughput you can get in terms of Mbps. So next technology we have, because we are looking for higher throughput and speed. So we have the OFDM modulation technique. What OFDM is doing, that it helps in parallel processing. That's the main thing. So here you can see that in contrast with OFDM sends data bits in parallel, that's the key, over multiple frequencies, all contained in a single 20 megahertz channel. Now there are technology, so they have guard for 12 subcategory, pilot for 4 subcategory, and data for 48 subcategory. Now guard will be there, but this pilot and 48 subcategory for data is going to be used, and you can think that you have that much parallel processing, or that much parallel signals in a row you have. So here you can see that you have 48 subcategory, and that's huge, correct? Great. So now sometimes you might see that OFDM, and again these are the theoretical things, having 52 subcategories, 48 for data and 4 for palette. This is because 12 guard frequencies are not actually transmitted, but they are silent in the channel spacing. So that's why we have the modulation for each data into 52 times. So you have 52 times subcategory. Now let me go and show in the diagram. So here you can see in the diagram that you have coded data, then you have 48 subcategory, and inside subcategory you can see, and then you have the channel. So you have 20 megahertz channel, and it is a spread across 48 subcategory. Now OFDM, obviously they have to use a scrambling coding, interleaving, and modulation, but for all subcategory, and that's why it's a parallel processing. So whatever we have studied in DSSS, the same thing is happening, say for example, 48 times parallelly. Okay, we have IEEE standard. So let's see that what a standard we have. First of all, this 802.11 was introduced on 1997, and then after 2 years, 802.11b has been introduced. Here you can see that it is supporting 2.4 gigahertz band. The modulation is DSSS, and the data rate support is up to 11 Mbps. Now, 11 Mbps is not a big speed nowadays in the digital world. So that's why we need some higher throughput. So next we have 802.11g, where they are also in the band of 2.4 gigahertz. But here you can see that the data rate starts from 6 Mbps going to 54 Mbps. So it is giving much more throughput with compared to 802.11b was introduced in 2003. Now, still the problem here in this 802.11g, here you can see that although you have the bands, different bands, so we have a note here that G and B use complete different transmission types. One is using DSSS, one is using OFDM, and these technical details we have discussed in the previous section. So that means the devices who are supporting these transmission types, they will not communicate because they have the different communication channel. They have different signals. Okay, and the other thing that they have very less non-overlapping channel as well. So that's why we have 802.11a. Although this will also support 54 Mbps, but it is using different channel. It is using actually different band, 5 gigahertz band, but it has long range of non-overlapping channels. So here you can see that band is different for 802.11a, that is 5 gig band, and they speed from 6 Mbps up to 54 Mbps. Now at this point of time, still we can see that 54 Mbps is not that digital workplace actually looking for, because now we have say 100 of Mbps of LAN speed. We need fast throughput. We have different type of devices in the workplace. We have IoT based devices. We have so many mobile devices. We need fast speed. So that's the evolution or the introduction of 802.11n. That is supporting 600 Mbps. That is the theoretical maximum, but it is supporting a huge bandwidth. The data rate is huge, and they also have very much non-overlapping channels. The good thing about 802.11n is that here you can see in the summary that they are supporting both the band 2.4 and 5. So in this list, you can see that 1997 we have 802.11, where we have both DSSS and FHSS. We have a study about this in our previous section. The speed was 2 Mbps. After 2 years, 11.b came into the picture, whose modulation is D SSS, which is supporting 11 Mbps. Then we have 11A, which is using OFDM, 54 Mbps, but you can see the band is different. So 11A and 11G, you can see the band is different, but they can have the same modulation technique, and their overall throughput is 54 Mbps. Now again in 2009 we have 802.11n, where they are supporting both the bands. Their bandwidth, you can see their modulation is OFDM, but the throughput can be theoretically 600 Mbps. All right, so let's just stop here. Next topic we have interference and effect of physical object. Now interference is nothing but the noise, and this noise, that means that you are sending some signal and it has some overlap. Now here you can see that overlap may be with the same channel, so different transmitter having same channel and they are overlapping. Now in real world, this co-channel interference is often a necessary evil. It's too bad. Means your signal will get degraded as much as. So we should plan it. We should put the access point in a proper manner. So there should be less interference or no interference. Now that's the one thing. So here you can see that two nearby transmitters should never be placed in the same channel because their strong signal would be more likely to interface. That's the one case. The second case we have that if we have the neighboring channel interference, so what is happening that now I have transmitter A with channel 6 and transmitter B with channel 7 and they have the overlap. Even in the 5 gigahertz band, still we know that it has a long list of channels. Means it has so many different channels that the way or the chances that they can overlap is less. Still, the best practice suggests that you should avoid placing a neighboring access point on nearby, even it is a 5 gigahertz. So if you think that still there's chance of doing the interference, but still we should plan the placement of the access point in a way that they should not object or interference the signal of each neighboring access point or the channels or bands. All right. Next topic we have the effect of physical object. So what is happening? Say you place your access point and then it is in contact with a surface who is reflecting the wave. It's very much like light. We know that how the light wave are reacting. If you put light wave in front of mirror and if you put that in a certain angle, it will reflect. Even if your surface is smooth, in that case, the signals, RF signals will also reflected or get reflect. Now, you can see in this diagram that, okay, there may be chance that the receiver is MIMO, multiple input, multiple output. So here you can see in the diagram that the sender is sending the signal with three different direction and receiver, because he know that how to get from the multipath, he can get it. Still this situation is okay, but suppose if you have single uh, radio chain or the receiver has only single radio chain capability, means they can take the signal just from one source. So in that case it will become worse. Obviously you can see the signal will get degraded, say in case of A and C, if we have one A, B, C, like that. Okay, so second thing we have the absorption. What will happen in absorption is that the signal will get reduced. So you have some dense media and behind that dense media you have put your access point. So in that case the signal will get reduced. We should not place our access point in a way that it will get reduced. Then we have the scattering. If you have some sharp surface, so at that point of time, if the signal will land, it will get reflected. Obviously the distortion of the signal will be there. Then we have refraction. Refraction means that again your signal will get distracted. The actual physical meaning, or if you go and check the physics book, you'll find that when RF signal meet the boundary between media of two different density. So if one place you have higher density, other place you have some lower density. Say for example, air and water. So air has low density, water has higher density, and if the signal will travel on those media, obviously it will get refracted. Okay, so these are the evils we have here. You can see that you have reflection, you have absorption, you have a scattering, refraction, and then finally we have the diffraction as well. So suppose on a line of signal, if you have some opaque or if you have some void in between that, so in that case the signal will get distorted, it will get diffracted. So suppose an RF signal approaches an opaque object or one that is able to absorb the energy. So that's the case, you have the diffraction. Obviously, the signal will get degraded. One of the important concepts we have in this is the fringal zone. What is this fringal zone? Before going to that, you can see one of the example of diffraction, that you have the obstacle, you're sending the media, you're sending the frequency, the waves, and you have the media in between who is diffracting the signals. Obviously the signal is getting diffracted, that's the one thing. So what is the solution for that? That you can use line of sight wireless signal. So two big towers, in between that there is nothing. So there is nothing means there is no object or uh, abstraction in between that. So here you can see you don't have big tower in between that, in between two buildings. So your signal can transmit it from here, receive from here. That is one of the solution. But again, what Frenzel law is telling is, according to Frenzel, the rule is even narrow line of sight signal can be affected by diffraction even if an object does not directly block the signal. There is elliptical shaped volume around the line of sight that must also remain free of obstruction. So what is mean? And that's called the Frenzel. You can see here that I have transmitter and receiver in the diagram, but when you send the light or when you send the signal, not light but our radio frequency signal, so when you send the radio waves, at that time what will happen, that it will create some sort of cylindrical volume across it, because still you have air in between, still you have the gravitational force, still you have some invisible, you can say, abstraction in between that. Maybe in some places we have um, so much pollution, so maybe the heavy particle they can um, collide, and there are so many factors for that. So in that case what will happen, they will form this cylindrical type of structure. In between that again you can see that you have a small building in between that, so still is going to degrade the quality of signal. Okay, and then you can see that this curve is showing that you should not have the any abstraction in this curve, and that's again coming from one of the formula. Okay, so these are the things related to the interference and related to the objects, physical objects in between. And again, if you go and check more and more about the reflection, refraction, absorption, and all these things, very much taken from the physics. We have learned a lot in our maybe 12th or in our graduation about all these theorems and theory related to various diffraction and the transmission of signals. All right, so let's stop here. Next basic topic we have is the antenna and type of antennas. So let's understand about antennas as well. Now here you can see that we have different type of antenna, and actually different type of requirement is there, and that's why we have different type of antenna. So sometimes we need focused beam, sometimes we need smooth and surrounded or equal spaced RF frequencies or beam. Sometimes we want long range radio frequencies. Sometimes we need short range radio frequencies that will be inside the room. So that's the main reason you can see here that we have different type of antennas, because the requirements are also different. According to that, we'll go and check that what type of antennas are available and what is the frequency range they are available with. Before that, let's try to understand a few of the basic things. So first of all, here you can see that we have the isotropic antenna, where we have, say, example, here in the diagram you can see that you have X, Y, and Z direction. So at this point of time, suppose if I have two section, one section I have in X direction, that is the horizontal, and one section is in, say for example, Y direction, X and Y direction. Y direction is vertical. And suppose the requirement is that I need equi-space type of radio frequency. So what does it mean? That it simply means that you put the access point in the center, and then from that access point going forward in a circular manner, you have the radio frequencies. So whatever object that is coming in that circular radius in that particular premises, they will get the radio frequency equally. That's the whole idea behind that about the isotropic antennas. But the problem here is that to make isotropic antennas, and that isotropic antenna will fit with all the requirement, is actually not possible. So that's the reason we have a different types of antenna categories. Now here you can see in the diagram that you have horizontal direction, that is azimuthal, and then we have the elevation plane as well, that is the E plane. So we have two plane basically, H plane and E plane. And according to that, if you go and do the cross section, so if you go and do the section here in the diagram bottom, let me try to highlight. So here you can see that how the frequencies in terms of dB, that is increasing as we are going outside to the circle. So here you can see that the outermost circle usually represents the strongest signal strength, and the inner circle represents weaker signal strength, because they are in the minus. So minus 30 is less than minus 5. Minus 5 is obviously bigger than minus 10, and etc. Correct? So outer circles representing higher signal, and that's one of the important point that we should know. So now we understand about the isotropic antenna, and that's actually not possible to build. We have different type of antennas. Then we have the azimuthal and the E plane. Then we know this point that okay, while going forward, your signal strength will increase as per this section, as per E and H, or H or E section. Then what is gain? Now gain is nothing but it's the focus. So suppose if you have antenna, and that antenna, what is the focus, what is the focal, so that's the gain. So again, what does it mean? It simply means, you can think like this. We know at this point of time that we have seen the antennas. If suppose if you have parabolic antenna, and then in center you have the central knob, or you have the center in between, means you are focused on something. So your frequency where you are putting the focus on, that's actually termed as a gain, and we'll see that different antenna, what gain, what capability they have. Okay, all right, so here you can see in the diagram that different type of antenna, either isotropic, omnidirectional, directional. You can see the gain, because the focus is changing, and that's why the gain of the antenna is changing. Again, the new term we have is the beam width. So what is the beam width? Many manufacturer list the beam width of antenna as a measure of antenna focus. Okay, so again, two term. Gain is a measure of how effectively it can focus RF energy in a certain direction. So that's the gain. You focus in certain direction, or your energy in certain direction. And then the beam width. Beam width is nothing but the focus. So your focus and energy in that particular focus. So your focus is your beam width, and energy RF signal in that particular focus is nothing but the gain. All right, so understanding these many terms, now what we can do, that now we can understand the types of antenna. We know that we have the polarization, so that electromagnetic wave is nothing but the polarization. Earlier we have discussed that we have the electromagnetic wave and the magnetic wave. So we have electromagnetic wave, magnetic wave, they are in the 90 direction. So in between, the angle between these waves is 90 degree. All right, so knowing these many facts, now what we can do, we can go and learn about the antenna. Again, if the electromagnetic wave is in the horizontal direction, that is horizontal polarization. If it is in the vertical direction, that will be the vertical polarization. Okay, and that is shown here in the diagram. So if vertically, if signal is going vertically, you can see the signal received. This is vertical direction, or it can be in horizontal direction. Great. So now let's focus on antenna. We have two types of antenna. I will see that subcategories inside these types. So we have omnidirectional and the directional. Now omnidirectional, as name suggests, that it will be equidistance, correct? So let me quickly show you one of the example for omnidirectional, that is the dipole antenna. Dipole antenna, again you can see in the diagram that from the center they are in the equal distance, and their gain is around, again we know what is the gain, so the gain is around +2 to 5 dB. Okay, again you can see the E and H, the horizontal is azimuthal and the E elevation plane, and the cross section here in the diagram. Now again in omnidirectional, so here you can see that omnidirectional, one example for that is a dipole, and again in omnidirection the other example is the monopole. Okay, one of the Cisco is a big vendor for the networking, and one of the AP inside Cisco, they have six tiny antennas, six tiny monopole antennas in their access point. Uh, by the end of this section, we have this summary of whatever we are going to discuss here. So in the summary section, we'll learn more about that. Now, what is happening in the say for example in monopole antenna? So let me quickly show you the summary I have. So here you can see the summary. In omnidirectional, we have dipole, monopole, and integrated. Dipole, we have discussed that the gain is 2.2 up to 3.5. Monopole, you can see that 2.2, 2.2. So we have two spectrum, 2.4 and 5 gigahertz. Obviously, in 5 gigahertz, you will find much more signal strength. 2.4, you have less signal strength, but there are vendor made access point, maybe Cisco or any other vendor who is making this access point. Those access point, they are supporting both the standard 2.4 and 5 gigahertz. Okay, all right. So then you have the monopole. After that, we have the directional antenna. Why we have the directional antenna? Because in certain direction we need much more gain. So here you can see that we have the Cisco patch antenna, and the gain for that Cisco patch antenna is 6 to 8 dB. Okay, this is supporting 2.4 gigahertz. The gain is 6 to 8. In 5 gigahertz, they have 7 to 10 dB support. And here you can see the diagram. In this diagram, clearly you can see that focus is in one direction. Correct. If you go and see the other direction, you can see they are equidistant. Mostly they are equidistant. Say in case of omnidirectional, again if I go back, mostly they are equidistant. But if you go and check the directional antenna, you'll find that the focus is in one direction. So for this antenna, that is the patch antenna, you can see the gain. Next, we have the Yagi antenna. Again, the name of the inventor is the Yagi, so that's why this is the Yagi antenna. In Yagi, again, you can see this is very much focused on one direction, and the gain for these antennas are 10 to 14 for 2.4, and we can see the um, list as well. Cisco does not support or offer 5 gigahertz Yagi. Cisco is not supporting 5 gigahertz Yagi, so that's why it is not there for 5 gigahertz, but here you can see that's 10 to 14 for Yagi. And if I go and check the list, so you can see, yeah, so 5 gigahertz Cisco is not supporting, so it is not listed here. All right, then finally we have the parabolic dish antennas. Again, the gain will increase because the focus will increase in certain direction. So in this case, you can see the linear type of azimuthal and the elevation plane, the horizontal and the E plane, elevation plane. Now the focus, it's quite linear, but again you can see on other hand what gain we have. The gain is 20 to 30 dB, and that's a big. Now again in this summary slide, you can see the directional antenna, the parabolic for 2.4 gig, they have 20 to 30, and 5 gig also they have 20 to 30 gain in this range. Okay, so you can take this particular chart as a reference, and we have discussed about, first of all, the term used inside the antenna, like what is beam width, what is gain, what is polarization, what is azimuthal, what is E-plane, etc., etc. Then we have gone through and checked the types of antenna. In omnidirection, we have dipole, monopole, integrated. In directional, we have patch, Yagi, and parabolic antennas. So what type of wireless network we have? Let's understand different type of wireless network, and then we'll focus on wireless LAN. So here in the diagram, you can see starting from a small WPAN, and then wireless LAN, then WMAN, and then WWAN as well. You have the personal area network. Example is Bluetooth. The distance is from 20 to 30 feet or 7 to 10 meters. Then we have wireless LAN that we are going to study in this particular course. That range is 100 meter, and we know that we have band 2.5 and 5 gigahertz band. Apart from that, we have the metropolitan area network as well. WiMAX is one of the example for that. Obviously, it is for wider range. And then we have the wide area wireless network as well. That is again is for broader area. Example is the mobile services, mobile towers, etc. Okay, so let us focus on wireless local area network. Now we know that we have transmitter, we have a receiver, correct? A transmitter, they are going to send their electromagnetic wave. Receiver, they have to be in the line to receive those signals. If in between there is any interference, any obstacle, any problem, any type of object, then the signal will be degraded, the frequency will be degraded, and the overall performance will be degraded, correct? Now we may have one-way communication, we may have two-way communication, and suppose if we have more number of devices in a group, in a particular wireless area, LAN group, then there is so much interference and the problem. So just to mitigate from this particular problem that we have, we need one central device that can work on behalf of all the devices, correct? And that central device name is access point. Now here in the diagram, you can see that all the devices, all the wireless devices or endpoint, they are going to associate with access point. Now there are so many different terms, and we should understand at this point of time. So in the diagram, you can see that first of all, you have one circle, and that circle is nothing but the, so for example, this point of time, this is the uh, wireless area. Like in OSPF, you have area. At this point of time, just think that this is one of the area set. This is one of the area, for example, area 0. Inside area 0, you have different endpoints and you have the AP. So this AP, the BSSID is nothing but the MAC address of the access point. And obviously MAC addresses are unique for the physical devices. So the physical ID that this device has is the BSSID. Here you can see that you have the basic service set. So complete area 0, you can think that the standard inside complete area 0 is basic service set. So we have the basic service set, we have the access point, we have BSSID. Now what is happening and what is important here is, like routers, what routers are doing, they are advertising their network. Same way, what access point will do, he will advertise his network. And his network identification is nothing but SSID. So SSID, he is advertising. Whoever endpoint will associate that particular SSID, that will become part of that group, part of that set, correct? And that's actually the truth. So here you can see that you have the basic service set, BSS, Inside BSS, you have the BSS ID, that's the AP ID, and this AP is advertising its network, and all the endpoints, they are going and connecting with that particular network. Okay, and that network is nothing but the service set identifier. Again, the endpoints, that's the member, they will go and associate with that particular network. Obviously they will do some sort of negotiation in between that, and then they have to associate with that particular network. Now from AP, if you want to do some sort of access control, that we can do. So here in the diagram you can see that certain group of devices can communicate, or certain members can communicate to each other, certain members will not communicate with each other. Later on we'll discuss more about the packet type and communication, etc. All right, so far we understand that what is AP, what is members, what is SSID, what is BSSID, what is BSS. Now very important thing here is that for each and every wireless network, you should have the core, and that core is nothing but wired network. So behind every wireless network, we have the backbone wired network. And that backbone wired network is termed as a distribution system, DS. So here you can see in the diagram that you have DS, and again behind that you have router, switches, firewall, etc., etc. So how the connection is, we have BSS that is connecting with DS, that may be any L2 or L3 switch. And suppose if we have multiple VLANs, so suppose one VLAN representing one of the SSID, other VLAN representing other SSID, or maybe you have multiple VLANs across your SSID, depends upon what design you have. Now in that case also, the BSS and DS should have trunk link in between that. So we know this concept from our VLAN concept, that if you have multiple VLAN, so there should be trunk in between to allow those VLAN frames. Okay, so that's the concept of DS and the connection with BSS. Now the next concept we have is the extended service set. So what does it mean? Now if you see the diagram, you'll understand. So for example, you have two BSS, BSS1, obviously BSS means BSS having BSS ID. So that means they have their unique MAC addresses. In very easy term, that you have two different access point, and these access point having same network. So their network is nothing but SSID, SSID. So SSID is same, and they are connected with the DS, distribution system, or a switch. So now the BSS, so collection of BSS, you can think as an extended service set. So BSS or N into BSS is equal to ESS, extended services. Now if I have one user here who is associating with one of the AP, and then he's going to the other AP, and he is associating with other AP, so at that time the concept is termed as a roaming. So user is roaming uh, across the network, but we can say that throughout, you it may have different AP, correct? You can see that it has different AP, but they are part of same network. So that concept is nothing but the roaming. All right, so let's stop here. We have covered the basics of the wireless LAN so far. Next, we have 802.11 frame format. Although we know that how 802.3, that is the IEEE MAC based format, how it is working and how it look like. So here you can see that you have preamble, the source destination address, and then you have the data field plus FCS. Switch used to learn all these end host machines, and then depending that do we have L3 communication or L2 communication. For L3 communication, again, if you are crossing the boundary, then the router will come into the picture, but that's the way that the LAN and the broadcast network used to work. In wireless networking, the communication is very different. Why? Because we know that all these end system, first of all, they have to learn the SSID. SSID is nothing but the advertised network from the access point. So they have to learn and associate and authenticate this SSID. After that, they will start the communication. Because we have SSID into the picture, because we have different type of wireless client or different type of end systems, they are part of wireless network, and they can communicate to each other as well, or they can communicate to the machine that is behind the wireless. So wireless will connect with wire, and then wire is connected with some other host machine. So the bottom line is that you may have various mode of communication, and depending upon what type of communication you are doing, that's why we have different type of addresses. So here you can see that you have four different address 1, 2, 3, 4. Then you have the duration ID. Why it is? Because this technology based upon congestion avoidance. See, the Ethernet LAN is something like collision detection, and this is actually a collision avoidance, not congestion, collision avoidance. Now, in case of collision avoidance, what is happening? That you wait, you have some timer, you have some back off algorithm, and you will see. So if it is clear to send, I will send. If the media path is not clear, I will wait till that particular point of time. So that's why it's the collision avoidance mechanism. Now here you can see that you may have end system. Uh, those are the wireless client where you are doing the communication, or you are doing the communication with the machine that is behind the behind this AP, that is in the wired. So wired versus wireless, and that's why we have this DS bit set. So either 0 or 1. So if you have 2 bit, then you can have 4 condition. Say a 0 1, a 0 0, 0 1, 1 0, and 1 1. Now this 0 0 means that two hosts are doing the communication. They are purely part of wireless network. Now this 1 0, you can see that you are doing the communication from wireless to wired network. Then you have this 0 1, that means the bits are coming, the frame is coming from host, from the wired network to the wireless. And finally, if you have access point A and access point B, and if they have some communication, that will be 1 1. Okay, so let's try to understand what about these so many addresses types. Yes, we have 4 different type of address type. Here you can see that first of all, they must have TA, transmitter address and receiver address. Now this address one field always contains RA, that is receive address, though its exact contents may vary depending on where the frame is headed. Likewise, address 2 is always contains TA. So two addresses fixed, address 1 is receive, address 2 is transmit. Correct. Apart from that, obviously when you are sending the frame, then you should have the actual source address, you should have the actual destination address, etc. So let me try to explain this in a diagram. Here in the diagram you can see, and we are going to understand all the address types, address 1, 2, 3, and 4. Remember, in this diagram I don't have AP to AP communication, so that's why address 4 is blank. Okay. Now we have one case that host 1 wants to communicate to host 2. So what will be the source and what will be the destination? So here you can see the source address is uh, the transmission address is this, and the destination address is this. So actual source, actual destination. Now who is the receiver? At this point of time, the access point is the receiver, so that's why his MAC address. Okay, so clearly you can see first of all the addresses, and second the bits. So since you are sending 1 to 0 means wireless to wired, so that's why you can see here that this is going to hit. Okay, and here you can see the address 1 is BSSID, address 2 is the TA, and then the address 3 is the destination. Okay. Now then the host 2 will respond. When host 2 will respond, then source and destination address will get changed. So now who is the source? He is the source. Who is the destination? This guy is destination with respect to host 2. Now what about the MAC address of the BSSID or the AP? That will be the transmit address. So he has received the address and then he is transmitting. You can think the logic like this. That is the transmit address, rest the receive address and the source address, they are going to be changed. Now which is the use case? This one. So here you can see address 1 is RA, who is going to receive. Address 2 is BSSID, who is going to transmit, and the address 3 is the source address, correct? And who is the source? So this guy is the source. Although this is a bit of tricky, so you can pause the recording, you can take snapshot, and you can do your mapping. But this is the way that the frame format look like, and the fields inside the frame format representing these addresses and these DS bits. Let us understand the 802.11 frame types. As we know that we have three different type of plane, normally in SD-WAN also or in routers also. So we have the control plane. We have, as you can think that for frames also we have management frame, control frame, and data frame. Now, what is the use of management frame and why it is important? So let's try to understand all these options that we have. First of all, starting with management frame. Now, this management frame is there to advertise the BSS and its capability to the clients. Now, what are those? So first of all, you can see that you have beacon, and beacon is something that will be sent via the AP. At this point of time, you can think that, okay, beacon, AP is sending the beacon to all of the clients, and if client will go and open and check their wireless network, they can receive those beacons. Now it's up to client that they want to join or not, correct? So if I go to my laptop and if I go and check my wireless connectivity, I can see a range of SSID or BSSID. Generally, those are SSID, not BSSID, but I can see all those SSID. SSIDs are nothing but the network advertised by the AP or the wireless network. So that's nothing but the beacon. That's the one of the management frame. Then probe. What is probe? Probe is something, suppose you want to join to the AP and then you are sending the request to the AP that, hey, AP, I want to join. That will be the probe, and that's why this is the passive. So beacon is a passive scanning and probe is active scanning. Okay, next we have the authentication and deauthentication. Now in wireless networking, we have this authentication option that the clients can authenticate with the AP, and even they can do the deauthentication as well. So the first stage you can see on your laptop that, oh, you can see n number of SSID or so many SSID. Now next thing, if you go and click there, it will ask you some password. What is the password? If you put that correct password, it will get authenticated. If you do not put, it will not get authenticated, correct? So those those frames are actually the management frame. Then we have important terms: association, deassociation, reassociation. So suppose once you are able to discover the network, then you are able to do the authentication, then you are going to do the association with the AP. Now in this association phase, the access point, they are sending a unique association identifier, AID, to the clients who are going to do the association. Suppose if you want to leave, you can do the deassociation. If you want to change one AP to other AP, you can do the reassociation. So different terms are there related to association. Now we have the action frame as well. Suppose you want to roam or you want to extend the wireless capabilities. So at that time, this action frame will come into the picture. So here you can see that you have this management frame. Then we have the control frames, although there are 9 control frames, but these 4 are important. So control frame are, again, it's not the payload, it's not the data, it's the control mechanism. Uh, so for every frame, we are getting the acknowledgements, and that will provide you, so for example, reliability in the channel. We are getting the acknowledgement for block of data as well. Okay. Then we have this power save poll. So what does it mean? That a frame sent from client to AP to request the next frame that was buffered while client's radio was power on is something like a power saving mode. Then finally, and the important one, we have the RTS and CTS. RTS and CTS is something like a timer. So it's something like request to send or clear to send. These are the terms. And why these terms are become important? Because request to send and clear to send, RTS, CTS, they are not only providing the timer to send the frames, but they are used for collision avoidance as well. Okay, so the RTS, CTS are a mechanism to do some sort of collision avoidance in the channel as well. So finally, once you have your management done, once your control done, the next thing is to send or receive the data. For that reason, the data frame will come into the picture. At this point of time, we know from our previous lessons that we have 4 different type of address field. So the source address, the destination address, the AP address, and then you have the destination behind the wireless, that is in the wired network. So you have these 4 addresses, and then the actual communication of data can be happen. Let's understand the client scans for AP and roaming feature. We have already discussed about beacon and probe. We know what does it mean by passive scan. So passive scan means the access point. Here you can see that they are sending their beacon to the host with some time duration, that they are offering their network to the host. Now it's up to host that he can go select that network and then do the authentication and association. That's the passive scan. Now this passive scan is good, but still the drawback there is that the host, they have to wait for certain time duration to get the network or to get the advertised network from the access point. Next, we have the active scan. In that, the client itself is sending the probe, and he's asking that, say, who has this network, and then the access point, they are responding, okay, I am there. You want to authenticate, you want to associate. If you associate, you will get the unique association ID, AID. Now how the host will go and join a particular AP. So here you can see that we have several steps. Step number 1 to 5. That's first of all, the host will do the authentication request. Then he will get the response. Then he will do the association request. He will get the association response and unique AID, association identifier. And then finally, he will go and join that. Okay, and all these steps are listed here. So for example, uh, point number 5 is the response also contains the AID that uniquely identify host 1 as an associated client in effect to AID is host membership, etc. So these are the steps: authentication, obviously request response, association, request response, and then finally they will get the unique AID. Now, if a host or client want to leave it, so he can do the deassociation. Remember here that deauthentication and deassociation are different things. So if you are deassociating, doesn't means that you're deauthenticating or you have to authenticate again next time. You can be deassociated, but you are still authenticated. Correct? Now, next very important topic is roaming. So far, we have studied that suppose if you are moving from one BSS or one area cell to other area cell, that means you are roaming. And suppose different AP having same SSID, so you can roam from one place to other place as per the signal capability. You will go and get the you will go and associate the access point. That's the technical term, association. Now here you can see all the listed steps, what is happening in the roaming. First of all, say your signal strength is getting weak, your signal to noise ratio is getting weak, it's time to roam. So you're not getting proper signal. Here you can see the client is there on the edge and he's away from the AP, but he's near to the other AP, or if you roam, he can get near to the AP and you want to go and associate with a new uh, high bandwidth, or he want to get some high frequency signals. So that's why he want to roam and go to the other SSID. Now in this case, what is happening, that the client will send the probe. Now he will get the probe response. Then here you can see that the association request will initiate. Okay, association request will get initiate, and I want to highlight this point number 5 here, and it's important here. Now in this case, when two device, in this case when client is doing the uh, roaming across the AP or across the wireless network. So at that time, point number 5 is important. So whatever buffer, whatever information that AP1 has, he will go and pass the information to AP2, and then he will use the DS, distribution system. He will go and use the wired media to bypass or to relay the buffer information, and then finally this client number 1 will get associated with AP2. Okay, so you can see all these steps. uh, if you have single access point, we know what are the steps. You will do the authentication, means you will do authentication request response, association request response, and you will be the part of the network or SSID. In case of roaming, when you are getting some issues, you roamed, then you do the probing, and then again you will do the association. Then this APs, they will sync their buffer data, and finally you will be the part of the new access point network, correct? All right. Let's try to understand this wireless architecture. Inside wireless architecture, you'll find that we have several type of architecture, and what is suitable for enterprise level we can discuss. We have some popular one like cloud-based architecture or split MAC. So let's understand all different type of architecture. So first of all, here you can see in the diagram that we have autonomous architecture. Autonomous architecture means that you have access point that is working independently. Okay, so here in the diagram you can see that you have access point connected with the distribution system or connected with the switch. The problem with this design is that although you can manage the SSID, but suppose for all these access point, you have to manage their own management IP. So there is no central authority from where you can manage the common work, or you can manage the common security framework. You can manage the management IPs, etc. So if the network will grow in this case, in this fashion, you'll find that it's difficult to manage, and it's not a good design for a big enterprise network, or even when your AP's number of AP will grow more than, say, for example, 30 to 75 or 100 or 200, etc. It is okay, although for very small type of infrastructure where you have less number of endpoints, where you don't want any third party or any controller type of device that can manage all these access point. So for that reason, it's okay. So this is the first, that is the autonomous architecture. And then next, to reduce the complexity, we have cloud-based architecture. One of the popular cloud-based architecture we have is Cisco Meraki, where you have the cloud-hosted controller, and then you have your Meraki-based access point situated in the branches in the LAN area network, etc. So here you can see that you are responsible, means the APs are responsible for the data plane traffic, but they are getting all the control information from the dashboard that is hosted in the cloud, or we have the cloud hosted control plane. Although the good thing about this that manageability is easy, we can easily manage our infrastructure even from one single place. We can go and log in and check various reports, various configuration, etc. from one central place. That's the key we have with the cloud hosted control plane. Again, when we are talking about cloud based controller, we have the control plane hosted in the cloud, and with the control plane we can do various operation, like we can configure, manage, monitor, create the reports. Even we have some visual representation. We can do the troubleshooting as well. So we have long lists that we can do from the control plane. And again, the data plane is there that is responsible to pass the data. Okay. So now you can see that we have autonomous architecture that evolved to cloud-based architecture, and finally that is our interest for this particular course, is the split MAC architecture, where we have the wireless LAN controller, WLC. Okay, so now here in the diagram you can see that you have two access point. One is the autonomous, that evolved from autonomous architecture, and then we have lightweight access point where they have given their brain to the central location, that is the WLC. So from WLC, what are the things we can do? We can go and we can do the RF management. We have the association and roaming management, client authentication, security management, QoS, etc. There are so many things that you can go and check from the WLC, and you can manage n number of access point or the data plane devices. Again, it depends that which version of WLC controller or LAN controller we are using. According to that capability, we can manage the number of lightweight access point. Now, what data plan device is doing? That they are doing the RF transmit, receive, MAC management, encryption, etc. So now I have one comparison chart. Here you can see that autonomous WLAN and lightweight. Autonomous, just name suggests that they are autonomous access point, configuration of each access point, independent operation, managed via Cisco Works, WLSE, WDS, access point redundancy. These are the independent things. Then managed from the WLC. So they are the lightweight access point configured via Cisco LAN controllers, dependent on Cisco LAN controller, management via Cisco WLC, Cisco wireless LAN controller redundancy. So in this case, in this architecture, we may have primary, secondary, tertiary WLC as per the failure scenario. All right. So here you can see that in this case, the APs, we are telling them as a lightweight access point, and they have to go and register with the central authority, that is the WLC. Now, still the question arises that how the lightweight access point will go and registered with WLC. What about the traffic? How the traffic will move uh, from one client to other client in case both are registered with WLC. So all those things and the protocol between the LAP and the WLC, we will go and discuss in the next recording. We have discussed that the access point and the controller, they have to communicate. So how they are going to communicate is, so they are going to build the CAP-WAP tunnel. Now you can see the full form of CAP-WAP is control and provisioning of wireless access points. And there are so many RFCs that you can go and refer. So here you can see that CAP-WAP is defined in these RFC 5415, 16, 17, and 18, where you can go and learn more about this CAP-WAP tunnel. So let's read this as a CAP-WAP as a short, but you can see the full form as well. Now, when the lightweight access point and the WLC, they are forming the tunnel in between. At that time, we have two different type of tunnel. We have tunnel for control messages or control plane, and then we have the tunnel for data plane as well. Now, if you correlate this with the SD-WAN, and we are thinking now that now we are using SDN and SD-WAN and SD-LAN solution, but this WLC is quite a bit old technology which is using the concept of SDN. Even for example, Cisco Prime, then WLC and other mechanism also was there to manage the infrastructure. In terms of that, we have some central authority who is managing the infrastructure like SDN or SD-WAN, etc. If we go and learn more about the CapBAP information, we'll find that, yeah, truly the tunnel that is building between the WLC and rest of the APs, they have exactly same type of certification process that we have, say, in case of VSmart, that's the control plane, and vEdge, that is the data plane device. So here you can see that CapBAP, they are using UDP port number 5246. They are using secure authenticated DTLS tunnel, because we know, say in case of SD-WAN, we have both the option. Either we can use TCP or we can use UDP. Most of the other SD-WAN technology, they are using UDP based IPsec tunnels or UDP based tunnels. In our WLC, we are using UDP based control tunnel and data tunnel. Now for data tunnel, the DTLS is optional, means the secure tunnel is optional, means this, at least the encryption is optional. If we want, we can use. If we want, we do not use. So here you can see that, but are not encrypted by default. So tunnel in between them. So tunnel is there, but the encryption is optional. If you want, you can use it. Now here you can see that we have two tunnel. We have the data tunnel, we have the control tunnel, and in this manner, the access points, they will go and communicate the WLC. That's the one part. Now what will happen in this case? In this case, uh, behind the scene, what is happening? So these tunnels that you are seeing in between the WLC and the access point, they are using IP address. So that means they are IP based tunnels. Since they are IP based tunnels, so what they can do, and there are two things. First thing, that the VLAN. So whatever VLAN I have in the distribution system, obviously this WLC is connected with switch. So those VLANs information will get passed under the tunnel to the AP's access point, and these SSID information again will go and pass to the distribution system to the switches. Okay, so in that way the communication will happen. So you don't need trunk link here. So that's why you can see that I have the access link. So I don't need trunk link, and then I have to do encapsulation dot 1q, etc., etc. But that's the enhancement, because you're creating the tunnel. So obviously it will send and receive the packet depending upon the tunnel source and destination. In this case, the tunnel source and destination is the IP addresses of AP and the WLC. So suppose if you have more number of tunnels, in other words, you can think that if you have more number of access point, then you have more number of CapBAP tunnels, and then the communication will happen like this. So this is the communication channel that we have. Okay. So now once you have the WLC, so what are the role, what are the activity that WLC can do? So WLC can go and do the dynamic channel assignment, transmit power optimization, self-healing wireless coverage, flexible client roaming, dynamic client load balancing, RF monitoring, security parameters, QoS parameters, etc., etc. So whatnot means we can do n number of things from WLC, because that is the brain I have, that is the central mechanism to manage all the lightweight access points. Correct. Even you can see that we can do the wireless intrusion protection system as well. So this is the usability and use case of the CapBAP tunnel that we have, and this is the mechanism by which the WLC is talking to the access points. Let us continue our discussion and learn about the centralized wireless network architecture and Flex Connect architecture. Now we know at this point of time that the WLC and the AP, they are going to have the cap WAP tunnel in between them, and then the communication will happen. Now before moving further, you can go and check the comparative chart from different type of WLCs that we have in Cisco. Uh, so for example, I have taken snapshot from one of the link from Cisco. Here we can clearly see that we have different type of WLC for different type of purpose. Although we have virtual controller as well, we have controller for ISR G2 starting from 2500, 3650, 5500 going to 8500 and 9. Now we have the 9800 WLCs as well. If we have more number of users, if we want to manage more number of lightweight access point, then obviously we have to move and we have to go to the higher end of WLCs. So it's just the evolution of WLC, how much clients we have, how much APs we have, what security feature, Flex Connect, QoS, etc. Depending upon that, we can go and choose one of the WLC for our organization. Now, once we are done with that, then we can go and deploy the WLC and we can connect the APs with WLC. That's the overall idea, and then the traffic will start flowing. Now we have this centralized solution that all these devices will go and connect or create the tunnel with WLC. Very much at this point of time, we can think that this is hub and a spoke type of topology, where you have your hub as WLC, and then you have the spoke. So spokes, they are making the tunnel with the hub. Now there is one problem with this particular architecture. We'll discuss about that problem and the solution as well. Before coming to the problem, you can see that since you have your central authority to manage each and everything related to access points, so that's why the user identity means, again, the WLC is connected with the ICE and they are talking with each other related to users and profile and roaming profiles as well. Now, user identity or user services or user. So what are the user and its roaming capability? That can be managed from one place because everything is managed from one place. So that's the power we have. We have the centralized authority to manage each and everything. Next, in this diagram, you can see although the physical architecture, although the movement of data in the physical path is different. So here you can see that the actual movement of the data will be from switch 1 to 2 and 3. In short, that in between you may have a number of switches. On top of that, you have created the cap web tunnel. So again, you can see that from access point to the distribution system or the core layer switch, I have the cap web tunnel and then the traffic can go, but the physical movement or the data traffic movement via the link will be different. So that's one interesting thing we have, although we are not concerned about what are the configuration, what are the trunk VLAN passing to the intermediate devices, correct? Because those are, we can think that as transient devices. On top of that, I have my tunnel. So you can see that you have the benefit. Now what is the disadvantage? What disadvantage we have? Now if you see this diagram, you'll find that although I am local to this access point highlighted, so let me quickly highlight that. So I am local to this particular access point and I should not go to my hub and then I should come back, or I should not go to my central location and come back, although I can do this local movement of the traffic or movement of a traffic locally, right? So that's the problem we have, that if you do not give the local intelligence, so all the time the traffic will go, they will go and traverse this cap web tunnel, they will go to the central authority and then they will return back. Now, what's the solution? The solution is the Flex Connect wireless architecture. Now, what will happen in Flex Connect that we can understand from the diagram as well. So we have two type of architecture. First is the split MAC. Split MAC means you have your central authority WLC. You can go to WLC and come back. Again, you can see that you have cap web tunnel, and um, again the same thing you can see in the other diagram as well. So you can go to the WLC, and then suppose if you have local printer to the switch system, you are going there. Although if you go and use the Flex Connect feature, what it will do, that it will give the device as a local intelligence. So what does it mean? It simply mean that for local transmission, you will not go and use the cap web tunnel, although you can go and directly use a printer, because to reach to this path, it's easy. Okay, so here you can see in the diagram that the traffic path during Flex Connect local switching, you are doing things locally. That's the power we have with the Flex Connect. We have a small tip here that Flex Connect was previously known as Hybrid Remote Edge Access Point (HRIP) feature. To maintain connectivity between WLC and branch side LAP, the WAN link should have a round trip latency less than 300 milliseconds for a normal data and less than 100 for the real-time traffic. Okay, so the idea behind is that when we are doing the Flex Connect architecture, so at that time we can do the local switching. Next, we have to learn about how we can implement the controller. Before that, we should understand that what type of interfaces and port available inside the WLC, and what will be the connectivity from the WLC to the switches. We have four different type of port. We have service port, distribution system port, console port, redundancy port. Now the service port will be used for out of band management, system recovery, initial boot. This will always connect as an access port. So we are going to use this as a UB, out of band management. Then we have the most important port, that is the distribution system port. We know this thing that distribution system port means that the WLC you are connecting with the switch. Now we have the capability, or we have the feature that we can do the aggregation. We can use link aggregation protocol, and we can group those interfaces and connect with the switch. Now these ports are always 802.1q, because again we are going to pass multiple VLANs information via the WLC. Then we have the console port, where we can connect the console port for recovery, initial boot, etc. And finally, in case we need multiple WLC for redundancy, for that we have the redundancy port. Now here in the diagram, you can see that we have the distribution system. Obviously, the WLC is connected with the uh, switch, and that's why you have the distribution port. We can have the link aggregation group. Service port is for outer band management. You have the console port, and if you want to have multiple WLC, so we can use the redundant port as well. Then from WLC to AP, we have the cap web tunnel, and then the information will go and get exchanged. Now these are the port, or these are one type of port we have. Again, we'll discuss more about other port analogy as well. At this point of time, we know that the AP and the WLC, they will go and form the cap web tunnel, and the distribution port, they have the we should enable the 802.1q, and we should do the link aggregation protocol, or link aggregation as well, in between the WLC and the distribution switch. All right, so as for the model, you can see that which model have the distribution port and service port listed here in the table. Again, if we want if we have more number of APs, then we should go and check the higher end of the controller, and the capability increase, the throughput will increase, the overall performance will increase, but again the cost will also get increased. Now what is happening? So these are the ports we have. We have service port, distribution system, console, and the redundancy port. But internally, the controller must somehow map these ports to the equivalent logical port. So inside the controller, we have the equivalent logical port. So for example, we have the management interface. Now, what is use of management interface? Obviously, for the management related traffic like radius, authentication, WLC to WLC communication, web-based SSH session, SNMP, NTP, syslog, etc. Okay. Now, in this diagram, you'll find the clear picture about what we are talking. So here you can see that first we have the management interface, then we have the AP manager interface as well. We have the service port. We have discussed just now that service port will do OOB and various tasks related to service port. We have the dynamic interfaces as well. So what is happening here that these VLANs that is coming from the switch side, they are going to map with the AP, and then again this AP somehow has to associate with the access points as well. This AP is the WLC. So let me again read you this. Switch will go and connect with the WLC, and WLC has a connectivity with AP. In between WLC and AP, we have the cap app tunnel. All right, so what is the use of AP manager interface? They are the dynamic interface used to terminate the cap wap tunnel between the controller and AP. So here you're seeing this AP manager, actually the use of this to terminate the cap wap tunnel in between the AP and WLC. Then we have the virtual interfaces. Again, virtual interfaces are they have just the use case. So what use case these virtual interfaces have is that IP address facing wireless client. When the controller is relaying client DHCP requests, performing client web authentication and supporting client mobility. It is used in client mobility. It is used uh, in a way that the WLC can relay the DHCP information to the IP address facing wireless client. Okay. And again, this interface will be less of use, but yeah, we have the interface. Then we have service port interface. We have a study about this, that this is used for the out of band management. Then finally, you can see that you have the dynamic interfaces as well. These dynamic interfaces are, they have to connect VLAN to WLAN. That's the usability. Correct. So we have discussed about management interface. They are there for management traffic, different type of management traffic like HTTPS, SSH, SNMP, NTP, etc. And then you can see that management interface is actually important. So that's the one of the use. And then suppose the other use of this management interface is in case of AP manager interface is not available. So that performance or that task will be performed by the manager interface instead of. Okay, so that's the other use we have with the management interface. All right, so these are the interfaces. Here you can see that these are the ports, and here you can see that these are the interfaces we have in the WLC. So now let's stop here and let's go and do the initial setup. Next we have to perform the lab, and in this we are going to do the initial setup for WLC. I'm using the virtual WLC here, and once you are in the first page, then you can give the username and the password, and then you click start. Once you go and click start, the next page that you will get, this will be like this. So let's do and complete this. I'll go and give the name, say for example, virtual WLC 1, and the country I can go and select anyone. So let me go and select, say for example, any of the nearby countries, say for example, just an example and testing. So I can go and say select London. Then the time, I can see the time zone, and then I can go and give the NTP server. Then we can go and give the management IP.
So that's the management IP in my case. Then the subnet mask for the management IP. Then the default gateway I have in my case. So that is say 19.1.1 or 11.1. Yep. Then the management VLAN ID. At this point of time, we can leave this as default. All right. So now we can go and click next. So I will go here and click next. Next, you can see that we have to create the wireless network, and then we have some of the advanced setting. Let me give the correct default gateway and click next. So what is the network name I have? So I can go and give cloud demo. Then what key? I'll leave this as default, but we have WPA personal and enterprise. Then the passphrase, I'll go and give the passphrase. Let me confirm that. Then what is the management VLAN? We'll leave this as management VLAN. If I have any DHCP server, I can go and give, and then we are very much done with this step. So now you can see that how easy is to do the setup. Now I will go next and we'll verify the advanced setting as well. So we'll go next. Here you can see the virtual IP address, the local mobility group, the service port interface, and these things we have discussed. Now the virtual IP address, it should be say some of the private address, because those private address will be used uh, locally. Suppose if I use any of the address which is not private, and that may be conflict, there may be chances to for the confliction. All right, so here you can see that we are giving the virtual IP address, and then the service port, we are leaving this as default. Now let me scroll up if we have some other parameters. So here you can see, you can go and this is disable RF parameter optimization. You can go and enable it, and then you can see that client density low, typical high, traffic type is data. I can go and use at this point of time the traffic type is data only. All right, so here you can see that please confirm the setting and apply. So this is the setting that we have given: the management IP, the management gateway, the network name, security, passphrase, etc. So once we are okay with this particular summary, we can go and click next, and then we can go and apply as well. So this is the final page. Yes, okay, I want to apply this, and then we can wait. So once the setting apply, then we can go and log in with the management IP. So I logged in here with the management IP, and then you will get this first page. So now you can go and log in here. You can see the management IP 11.10, and then I can go and give the username and the password. So let me go and give username and password. Then we'll get the first page. So this is the first page that we have, and here you will see the monitoring rogues interface, wireless dashboard, etc., etc. uh, Interestingly, in this first page you'll find that we have the best practices as well. So suppose if you want to check the best practices, you can go and verify that in this page, in this first page, because we don't have any API association, we don't have any live traffic, so everything is showing blank. But if you go and click to advanced, you will get this page that we are very much familiar of. Generally, we are using this advanced tab to check each and everything related to the WLC. So in advanced page, you can see that you have the management IP, then you have the service port 00 software version, you can see 8.7,
the name, the uptime, rest of the thing. Then the access point summary, you can see nothing is there, so that's why everything, all the counters are 0. But on the top you can see that you have monitor WLAN. So suppose if you want to create WLANs, you have to go to this section, and then you have to create the wireless WLAN. Again, once you go and create there, then you will get multiple options related to the WLAN. We can go and check this later on. Then the information about the WLC. So here you can see the long list of information that we have, and you can go and click and check each and individual uh, tabs that you have. You have management interface, you have service port, you have virtual port. We have discussed about this, correct? And then we can go to the wireless. At the moment everything is blank. We can go and check the security. Again, you can see the long list of security we have. Management, then if you want to run any command, we have some of the command support that we have. So the page will look like this. Okay, so this is the initial setup for the WLC, and we should go and check the best practices that we have. So if we go and check the best practices, then we can see that what are the Cisco recommendations. So let me quickly show you that. You can go and click on top home here. Once you go and click to the home, you'll go back to the first page that we have opened, and then here you can see the best practices. So best practices related to infrastructure, security, RF management, Apple devices, ICE radius. Okay, and you can go and you can scroll and you can check all these best practices that we have. Okay, so this was the initial baseline setting that we have with the WLC. Let us understand that the discovery of the controllers. We have the document, and we'll understand with that document that what are the steps that AP is going to discover the controller, and then how the AP will go and select a certain WLC, that's the controller. So what is happening that we are going to boot the AP. So the first step is that you will go and boot the AP. So AP boot will happen, and obviously it will go and contact the DHCP server to get the IP. And suppose there are options that we can have the static IP assignment as well, but we have the option for DHCP server as well. Once it get the IP, then it will try to discover the WLC. Now for WLC discovery, again, we will see this. I have separate slides for that in detail, that how WLC discovery happens. But the next step is that the AP will try to build the CAPBAP tunnel with the WLC, and inside that CAPBAP tunnel, obviously we have CAPBAP control tunnel where we have the AP WLC control messages. Now the next step is that the AP will go and send the CAPBAP join request. Now for that request, obviously the WLC will reply for CAPBAP as a CAPBAP join response. So once we have the CAPBAP tunnel built between AP and controller, AP know who is the controller, controller know who is the AP, then it's the role of WLC that you will go and check the image version. So there should not be mismatch in the WLC image and the AP image. So in that case, the AP will go and download the image, and then again it has to reboot. Suppose if the image is okay, then from WLC, the config will get pushed related to RF, service set identifiers, security, QoS, etc. And finally, the device will go into the run state. Now here you can see all the steps that are listed from 1 to 7. Now in some occasions, due to some issue, that WLC wants to reset the AP. So in that case, again, the AP will go and reset, and step number 1 will start. Okay, one point to note here that while the APs they are downloading the image, it may take some time to download and upgrade the image because downloading the image and then booting will take some time. All right, so what's the process for discovering the WLC? There are processes that AP may have knowledge of WLC, or with help of DHCP and DNS, they are getting that information, or the WLC is in some other network and then I have router in between who's relaying the information with help of broadcast. That's the broadcast on the local subnet. So for example, a broadcast on local subnet, what will happen? So suppose if your AP and WLC, they are in different subnet, then you have to go to the router in between and you have to relay that information like IP forward protocol UDP 5246. This is the UDP port for cap wap control tunnel. Then you have the interface VLAN and you can go and give the IP helper address for different type of WLCs. Okay, so that's the one uh, option or one way. The other thing that inside your AP you may have the information of the WLC, and as per the primary, secondary, tertiary, the AP will go and check WLC1, then WLC2, then WLC3, and then they will go and contact or discover the WLC. We have option with DHCP. So once they are getting the IP address at that time, DHCP option 43 will be there to suggest the list of WLC addresses. It can use DNS as well to resolve capwap controller.local domain with the DNS request. Again, if nothing will happen, again the AP will go reset and it will start the discovery process. At this point of time, when we have the discovering of a WLC that is working well, so at that time we have selecting a WLC option also. So what does it mean? It means that AP will go and try for primary, secondary, tertiary, means as per the priority of WLC, they will go and join. The second thing is that suppose if they don't have any primary, if they are not able to discover any primary, secondary, tertiary, then they will go and check in the local subnet. So who is the master controller? According to that, they will go and choose one of the controller. And finally, they can go and check the least loaded controller as well. So as per the controllers and their connectivity, means the controller, how many APs are associated, they can go and select one of the WLC. All right, so these are the methods for discovering and joining process for AP and WLC. We have layer 2 and layer 3 roaming. So let's understand that. We have already discussed this earlier that when we are doing the roaming, say in case of autonomous AP, uh, the client here you can see in the diagram can go and connect with client 2 as per their signal strength. When the signal strength will go decreasing, then he can go and join the other available high strength SSID or the AP. That's the normal way that the roaming is happening. And the other important thing here is that in between that distribution system, that's the switch, he has the state information of this particular client, and then he can go and join. Now this is very normal, easy, standard process that the roaming will happen. Now the problem here is that we are not using this type of architecture in the enterprise network, because enterprise network we have n number of clients, we have n number of AP, we have good amount of WLCs, other controllers. So the methodology that we are using in the enterprise network is purely split MAC architecture. In case of split MAC architecture, what will happen? So let's try to understand that. We know that in split MAC architecture, the APs, they are going to form the CAPWAP tunnel with the WLC. And in that case, if a client want to roam, there are two options. First, that roaming can be layer 2, the roaming can be layer 3. So what will be the difference between that? And there may be chances that I don't have only one WLC. We may have multiple WLCs connected with wired network. So let's try to understand layer 2 roaming. What is the key feature about layer 2 roaming is that in that case, we are in the same subnet. We have the same big IP subnet. Inside that, I want to roam. So here you can see in the diagram that I have a user in 100.0 subnet, and he wants to roam from one AP to other AP. Obviously, you can see that these APs, they have cap web tunnel with their WLC. Suppose I have two WLC and their connected network is wired switch network. Okay, so this is the use case. Now what will happen that when you roam, obviously from one place you have to deassociate, other place you have to associate. So you will go and associate. Now this roaming is quite good, scalable. Why? Because most of the things we are not changing here. So we are not changing, uh, and again it depends upon the use case. So if this is up to us that if we don't want to change the IP address of this client, so in the new when he is going to join the new AP, at that time also the same IP, and even the state information will be sync across WLC1 and WLC2. So in that case, we will get the seamless roaming type of capability, or the experience will be good because usually it will be less than 20 millisecond of the roam. Now the second option we have is the layer 3 roaming. Layer 3 roaming simply means that you are in two different domains. So suppose your exact IP is 100.0 and then you want to roam to 200.0. So you're crossing the subnet and then you want to roam. Again, the structure will be looking like the same, but the cap web tunnel you can see for AP1 and WLC1 and AP2 and WLC2, both are in different IP subnet. So what will happen now if this client want to move and he want to deassociate and associate with other AP, he can do it. But still, because the IP segment will change, here you have 100.0, here you have 200.0. So these WLCs, they are behind the scene forming the cap web tunnel over the switching system. So here you can see in the diagram that 100 is going to change into 200, and then finally they have the cap web tunnel in between that just to exchange the state information of a client associated with AP1 with AP2. Correct? And you will find that naming of these WLCs are also different. So the initial client, when client is attached with one of the AP and he wants to roam, at that point of time that WLC is anchor, and where he is going and he's going to join the new AP associated with WLC, that will be the foreign controller. So from anchor, I'm going to connect with the foreign controller, and then the roaming is happening as a L3 roaming. So here you can see with the help of diagram, it's easy to understand that how I'm connected with one AP and then I'm roaming, but again the state change is happening with help of cap web tunnel in case of L3 roaming. What are the steps we should do while doing the troubleshooting for WLAN? From where should we go and start the troubleshooting? Because we know that in troubleshooting we have either top to bottom or bottom to top approach. So both the things we can do. Now, when we are talking about, so for example, top to bottom, so obviously you are at the level of WLC, that's the top, and then you can go and check the cap web tunnel. You can go and check the access point, maybe access point related issue, maybe some physical issue, maybe memory, CPU, etc. Then you can go and check any authentication in between the endpoint and the access point. So you can go from top to bottom, you can go and check, or you can go from bottom to top and you can go and check. So what are the touch points? So whenever we are talking about the issue, we should go and check the touch points. So what are the things can be there? So here you can see, at this in the diagram, you can see that you can go and check the channel feasibility. You can go and check the access point feasibility. You can go and check the IP reachability in between the uh, access point and the WLC, and then the cap web tunnel related configurations or cap web related issues that we can go and check. Then we can go and check the authentication, the ICE integration, how it is integrated with the WLC. Again, we can go and check in case of dynamic address assignment that the DHCP and the DNS servers are working properly or not. Okay. So let's discuss more about the approach that we have to use or we should use while doing the troubleshooting. So for any troubleshooting, we should define the problem. So we should know what's the problem first. Then to reach out to the solution, we should have the multiple ways. Say for example, if certain destination, say for example, if ISP is down, or say for example, a certain destination is down, a certain website is down, then what are the things you will do? Obviously, we'll do the ping and trace route, and you can check the ping drop. You can go and check the trace route at which particular hop it is dropping. Now with ping, once you come to know that this is the point I'm unable to reach, then you can go log into that particular device, and then you can check that from there what are the issues. So here also we should first of all understand the problem. Is ISP issue or it's a website issue? It's slowness, loss, latency, jitter. Likewise, here we can go and check, is it an authentication issue? It's a AP issue. It's a uh, WLC issue, etc. Okay, so we should know first of all what is the problem. Once we identify the problem, so from problem definition we should identify the problem. So we can go and ask questions related to problem definition, and we should finally know that what's the problem. Then we can go and do the testing. Now the testing means that we should have the basic sets of command. So basic set of command related to the basic troubleshooting. Once we do the basic set of, once we run the basic set of command, then we should go and analyze that in depth, and then we can move to the solution. Now here again you can see that the analysis phase, again we have chance with our questions and with our analysis to redefine the problem statement. Okay, so finding the problem is 50% to solve the problem. That's the thing. If you know the exact problem, where is the problem, that is the 50% of the solution for any type of troubleshooting. All right, so define the problem, understand the possible triggers, know the expected behavior. If we are able to reproduce it, do not jump to the conclusion initially. Understand the client state. We know that if we are using the bottom to top approach, so what is the state of client means the state of the machine who is connecting with AP. So is the application slowness? Are they are getting some IP address or flap in IP address, or they are not getting any IP address? Do any problem with the authentication? Are they able not, are and they are not able to see the SSID, or maybe SSID strength or the signal strength is very slow or less. So those things should be added, and these things should go inside the uh, questions. So what you are doing, that you are going and asking that these questions, what exactly you are facing. So for example, application slowness, that means you have done the authentication, you have the IP address, you have the RF health, you can see the SSID. Again, application slowness can map to the RF health also. So if you have weak signal, then maybe the slowness of the application, correct? So we need to understand, here you can see this chart, that problem, then questions, and while you're doing the analysis, again redefine the problem. That's the important key we have. So let's know where is the process the client is currently at. Key item to know for the effective troubleshooting. Needed to narrow down your problem scope. That's the key. Narrow down your problem. The controller keeps client state for all connected clients. Some items handle on the AP only probes, authentication, etc. We know this thing that yeah, these are the touch points. So you should know the touch point, narrow down the problem, reach out what exactly at which particular point the problem is there, and then solve it. So now again you can see that again if you go and break out this, so at what level? So we are going from the, say for example, if I start from top to bottom, so that means we are going from, actually this is bottom to top. So suppose I have client, and then once I have the client, obviously this client is connected with AP. So here you can see the AP related things that we can go and list. So listen for the beacons that uh, these are again related to clients, correct? So you can go and list out these informations. So you're listening for the beacons. The client can request probe, then they will get the response, the authentication request, authentication response. Here your authentication will go complete. Again, we are going to discuss more about authentication in upcoming section, in the security section. So where we'll go and learn about various ways of authentication and security feature inside wireless. So yeah, so you're listening, then you are sending the probe, and then the authentication is happening. That's the unauthenticated unassociated. So client want to associate with the AP. That's the process, or that's the phase. Then is state 2 where you have authenticated unassociated. So you are getting the network, that's the SSID. You click to the uh, join button, you want to join it, and then your password is working. So that means you're authenticated but still you're unassociated. So what we can do, association request, association response, EAP over LAN authentication, encrypt the data, forward user data. So these are the 10 steps that you'll find that you have issue related to beacon, probe, authentication, association, or any type of authentication in between the user and the Redis server, end-to-end authentication. Next was the connection process. So we have discussed about this process earlier in the last slide. Uh, Probe, you're sending the probe, then you're getting the response, you're sending the association. Remember, authentication and then association. Then you can see that we have this process of 802.1x authentication. We are going to discuss this in the security section, more about the authentication and the security. Then exchange of encryption keys, DHCP, and then finally you will move to the run state. We know this is the final state, run state, where each and everything is working perfectly. Now again, if you want to know all the estates more and more, so we have the policy enforcement module, that's the PIM in short, inside the uh, inside the split MAC architecture, the start till run. So here you can see step number 1 till the last step, start. So 1, 2, 3, 4, 5, 6, 7, 8 8 states we have. And if it is in run state, that means everything is working fine. So uh, initial start of the client, authentication check, 8021x, that is again .1x requirement, L2 authentication completed, WEP, if you have the WEP key, we'll discuss about security later on, then DHCP request, web auth request, and finally in the run state. So in between, you may have any issue that you have to detect at exactly what point you have issue, and then you have to solve it. This is the final flow chart. Here you can see on your screen that is start, check the authentication, then .1x required, then your L2 is completed. If it is not, authentication failure. If it is, then you will go and move to the web required. Web should be 100% successful. Then you will go and move to the next step. Next step, here you can see that you have the DHCP required. Again, DHCP required, then you have web required, webauth required. If it is fail, again it will go and stop. So likewise, you can see the complete chart here where you have L2 policy, .1x, web required, 8021x, OpenSSID, mobility, DHCP web keys, and again, if you don't have any .1x, then it will go to the run state. So it will go and complete the steps. Say for example, it can go like this, and this to reach to the run state. So it doesn't mean that always I have all the policy and it will go and across all the 20 steps or all the steps that we are seeing here. But yeah, these are the steps and these are the touch points where we should go and examine and try to resolve in between that. Okay, so this is the troubleshooting option and how we can go and define the problem and uh, do the solution. So narrow down the problem, reach to the nearby touch point, go there and try to check exactly which technology the problem belongs to, and then try to resolve it. In 3.4, we have to learn about IP services. In that, we have NTP, NAT, first hop redundancy protocol, and then multicast. So let's start with NTP, Network Time Protocol. We used to give the same time, obviously the time and the date, to all the devices in the enterprise network infrastructure. Now, one of the most important use case for this is that nowadays all the devices, they are doing authentication with respect to their certificates. And for all those certificates, all digital certificates, we need to sync the time to all the devices in the IT infrastructure. So that's one of the main use case we have for NTP. Now, how we are going to do that? We'll see that, we'll discuss more about that. But we may have some external server hosted in cloud, or we may have some internal server inside in premises, or we may have any Cisco devices that is working as a NTP master or NTP server. So all these options are available. There are some terminology used inside NTP. Say for example, what is a stratum? So what is happening? That NTP device will form an association with NTP device closer to the time source. So you have your time source nearby, and that measurement is the stratum. So for example, that a stratum 1 versus 2 means that if it is 1, that means your source is nearby. If it is 2, that means your source is 2 hop away. Source means the time source. Okay. Now, how we are going to configure the NTP? We have client server model. We'll see that in the lab section. So one is the NTP master and other will work as a client. We can do peer-to-peer as well. Now, peer-to-peer means, obviously we know peer-to-peer means point-to-point. So peered NTP device can get their time from each other depending on who is the closest. That is the lowest stratum. We'll see that all these things in the lab section. Now NTP, say control packet or NTP message exchange, we can do the encryption as well. So we have that encryption feature for NTP that also we can verify in the lab. Now here in the diagram you can see that you have the time source, and then suppose we are at router D. It's very easy and simple that we can go and simply give NTP server and then the server 1 versus 2. Now for example, if there are 2 server and one you want to give priority, so we have this keyword called prefer. So first will be preferred and then it will go and check the other. The NTP can do the tiered approach as well. So what does it mean? That since you're getting the NTP information from the servers, that's router D, C can get all those information for D as well. So that's the tiered approach. So here you can see that for C, the server is nothing but router D. So I can go to C and then I can tell, okay, NTP server and the server IP is 51111. Okay. Likewise, we can go and do the configuration for router A, and I can tell, okay, for router A, your NTP server is router C. So that hierarchy we can follow. Uh, Suppose in case that you don't have any external time source or maybe internal time source, in that case, any router, we can make that as a authoritative source or the NTP master, and from there it will go and take the NTP information, or it will send the NTP information to all the clients. Again, in the diagram, you can see that we can do the peering as well. So suppose if we want to have some fallback or redundancy type of thing, so we can go and do the peering configuration as well. So here you can see that router D, I want to make as a master. So NTP master is the keyword, and then 10 is the stratum number. We can go to the router D, we can set the time, whatever current time is there, and then we can make that as a master. Then for A and B, here you can see that A and B I can go and make as a peer as well. So suppose if the Ethernet link will go down, because they are peer, they will update their NTP information to each other. So this is the way that we can go and create the master, and obviously we can go and create the client as well. So master will send and client will get the information. We'll see this in the lab section in the upcoming recording. Apart from that, we can go and do the authentication as well. Here you can see that I have NTP master, and then I can go and use NTP authentication, MD5 and then the password. Then I can go to the client side, and those client side I can go and tell, okay, NTP authenticate the key, the NTP trusted key, and what is the NTP server IP. Okay, so this way that master is sending the information to the clients, but the message exchange in between them is the MD5 encrypted, or MD5 actually authenticated. All right. We have some other commands as well. If you want to disable the NTP, we can go to the interface and disable it. If you want to do max association, means how many clients that a master has, so we can go and do the max association, 10, 20, etc. Just to prevent the interfaces, we can go and do the loopback interfaces. So in that case, if any of the physical interface is down, still the NTP is reachable via the loopback, and that's the standard configuration we have in the industry. If you go and check the NTP source, the AAA or radius or maybe TACACS authentication source addresses, TFTP source addresses. Generally, we used to use the loopback addresses because that will be always up, and any physical interface is down, is still that loopback will be reachable. Then there are some verification. We can go and type show clock. We can check the time, show NTP status. It will tell you the detail about the NTP information. And finally, we can go and check the NTP association as well. All right, so let's just stop here, and in next section we'll do the lab related to NTP. Let us perform the lab task. In this lab we have router R1. So let me show you that I have a router that is connected with a switch that is 105. The router interface is 00, switch interface is 00. So over these interfaces I'm going to enable the NTP. First of all, we'll go and check the time. So here you can see the time for router 1 is this. Then I can go and make this as a NTP master. Now my router 1 is NTP master. Then I can go to the switch, and then I can go to the NTP, and then I can give the server IP. Server IP is 10.111.1, and that's it. So I created master, and then I have this client who knows that how to reach to the server, what's the IP of the server. Then we can go and verify this. So we have two main verification command. One is show NTP association and one is show NTP status. Okay, so these are the two commands that we usually um, use to verify. Now suppose if we want to do the authentication. So for authentication, I can go ahead and use the NTP authentication key, say for example MD5 and Cisco. Now from other side, what you have to do is you have to go and do this NTP, first of all authenticate, then NTP authentication key, and that's it. So these are the commands that we should go and use. So here you can see that you should use trusted key as well. Key numbers for trusted times of source, say trusted key. I can go and give one. And if you go to NTP, the options that you can see here, you have the authentication key, and then you can go and use this trusted key as well. So this is the way we can go and check the we can put the authentication in between client and the server, or in between master and the server. Now other options, you can see clearly that you have authentication, you have max associations, you have peer command, you have server command, you have source command, etc. So now I can go and check show NTP association, and in the R1 also we can go and check show NTP association, show NTP status as well. All right, so that's the way that we can go and run and verify the commands related to NTP. We have done the lab for the NTP. That lab I have done actually over the viral, but we haven't seen the exact result that it should come. So then I have created this topology. Obviously, this topology I created for HSRP, another lab, but here I want to show you the NTP configuration. I have made this R2 as a NTP master, and this router 4 and router 5, although I have changed the uh, display, means this is a router, but I have changed the symbol. It is looking like a, PC or end machine. Anyways, I'm going to use these devices as a end machine as well, but R4, R5 and R2, they are part of one LAN segment. Even R3 is also part of LAN segment. uh, I have done the configuration related to NTP to these devices on 4, 5 and 2. So if I go and log into router number 2, say for example I am here, and if I go and show you show run section NTP, so you'll see that here's the master, and what's time? Time is this 18/20/20. Now if I go to R3 and if I go and check show NTP status, you can see that it is synchronized with this IP, and show NTP. What other options we have? Association. So here you can see the association as well. We can go and check show clock. It is getting time from the master. Likewise, I haven't done any configuration to R3. So let me go and this is the R3. So the we have done for R3. Let me see that if I have done the configuration for R4 and R5. So if I go to R4 and we see show run section NTP. Yep, that's configuration is there. And if I go and check show run section NTP, NTP server and some clock period is there, it's okay. So everywhere you can see that this way we can do the lab. You can go and check the association, and you can go and check the status should show synchronized. All right, so let's stop here. In 3.4, we have to learn about network address translation and port address translation. Now, when we are talking about NAT, this is simply that you are translating one IP versus other. So there, actually, if you read the textbook, so it is given that you are translating private to public address, but actually it's not 100% correct. We can translate any IP to any IP, and that's the network address translation. But mainly, we used to translate private address to public address just to save the private address space. And even in this way, we are getting first level of security as well. So now we are doing the translation. At that time, you will find that we may have three model. We may translate, for example, many to few. So for example, many to few means you have many private addresses and then you have less number of public addresses. Or you can do one-to-one translation or static NAT. So that means you may have a dynamic NAT, you may have a static NAT, and then finally there are a chance that you are translating to one IP with multiple port. So that is nothing but port address translation. So these are the variations we have in the NAT, and then we'll learn different type of terminologies used inside the NAT. Obviously in Cisco, what are the things that can be used? Before that, we know that we have public address, that is the internet or routable address. We have private address for class A, B, and C. When we want to do, our aim is to do the private to public address translation. Uh, Somewhere it is written that you are translating unregistered address to registered address. So that's also true. Then what type of NAT we have? We have a static NAT, we have dynamic NAT, we have NAT overload, or we have port address translation. Now, I told you that we have some terminologies in NAT. So what terminologies are there? You have inside local, inside global, outside global, outside local. Wow. So what does it mean? How can I understand that what is inside local, what is inside global, outside local, outside global? So here in the diagram, you can understand, suppose this is the NAT router I have, where I'm enabling the NAT. I have my inside IP, and then I have my uh, inside global. Actually, this is outside IP, but technically it is as per the NAT document that this is your inside, obviously local, that is your private address, and then this is your inside global, that is the outside. Then when you are reaching towards the host B, that's your destination. So for that perspective, the NATed address. So here you can see this NAT. Uh, we are doing the NAT in this particular address. This is the public address from other side. So that will be the global, outside global. And then again, you'll find that your outside local address, actually, this address is represented by 99.1.1.1.2. So that is also the outside local address. So local, global, global means that's the routable from one side. Then you have local and global. Most of the time you'll find that the local and the global outside addresses are the same. Now, if you see the packet flow, so when you are sending the packet and you are doing the NAT and then you are sending to the destination, what is happening? So you know what is your source, you know what is your destination. Now this is the destination host because I can't send packet to private address, correct? I should send this to this particular destination. Obviously, here you can see at the destination end, the NAT will happen and the packet will get delivered to the destination. So you have source and destination. When it came here to the NAT router, so NAT will change the source IP. So here you can see that source IP has been changed to this IP plus port, but your destination address will be the same. Finally, when it reaches to the destination where you have the 99 address, obviously this 99 address will get converted to 1.5, and what he will think that my source is 55. And then same way the reverse uh, route will happen. So this is, so from A to B, and then again B to A will happen in the reverse direction. So what you can think here that at each hop, because the NAT is there, or you can think that whenever you're doing the NAT, obviously NAT will change the source. So here source address is changing, and here when you are reaching to the destination, if you send the return packet again, the source will get changed. Correct. So what is your source here? Whatever destination for A, that will be the source for B. So that means the uh, B destination. So what will be the destination of B? That will be 10.1.1.10, but it should go to 55 address. Correct. So here you can see that destination, it will get reversed. So the source will be 192.168.1.5, but destination will be 55.1.1.1, and then the port number. How we can go and enable on the Cisco devices? We should go, so suppose if you have your Cisco router here and you are enabling the NAT, this is your inside, and obviously this is your outside. So you have to go and give the command IP inside and IP NAT inside and IP NAT outside to these interfaces. Then we have option, we can create the pool for pool of say for example public addresses where I want to do the translation. Then I can create the access list where I can put the private address, and then I have to go and give the NAT statement. This is for dynamic NAT. Then for static NAT, because I don't have the pool of addresses, for example, because I am doing the overload over the interface. So I'll show you the statement for a static for NAT overload and static NAT. Uh, Static NAT will be very easy. So let's check. Say static NAT will be very easy. The one-to-one. Okay. Then you have NAT. So for example, overload, where you want to do the um, translation with respect to interface with various port number, and then you have the dynamic NAT where you have many to many. Remember, many to many translation or many to few many translation. So here you can see that this case dynamic NAT, that I have pool of public address like this. Then I'll go and create the source like this, and then I have to go and give one NAT statement. So what will be the NAT statement? Let me show you the NAT statement in the next slide. Alright, so let me go to the next slide. Here you can see that you have the NAT statement. Let me erase this, and so here you can see that this is your, say for example, this is your access list, this is my private, and this should be first thing. Then this should be second, that you should define your public address, and then you have this NAT statement. So what you are doing basically, IP NAT inside source, so this will call this IP, and then you are translating to this IP, that is 2. So 1 to 2, inside to outside. Now how to do with respect to overload? So for that, let me show you that as well. And obviously we are going to do the lab, so it will be much more clear. Uh, Here you can see that in this case you have interface, you don't have this pool, but you have the interface. Over the interface you are doing the overload. How we can verify it? We have show IP NAT translation, show IP NAT stats. If you want to debug, we can go and do debug IP NAT. If you want to clear the translation table, then we can go and do the clear IP NAT translation. Okay, so let's stop here, and in the next section we'll perform the lab. Let us perform the lab task. So in this lab we have the small network and IP that I'm going to use here is 10110, that's the gateway. This is dot 3, this is dot 4. These routers I'm going to use as a host machine. They are not doing the routing, but they're working as a host. And for outside, I'm going to use 200.1.1.1.0, where at this point I have dot 1 and this point I have dot 2. Okay, so it's very simple topology, and this device is going to work as a NAT device. All right, so let's do that. I have already assigned the IP address. I haven't enabled the NAT on any of the devices. So let's do this. All right, so what we can do as per the diagram, R1, the gig 01 will become outside, 02 will become inside. So I'll go to router number 1, and here I should go and do the configuration. So let me do that. Say 0/1 is working as a IP NAT outside, and then interface gig 0 slash wow. So let me do interface gig 0/2 should work as a IP NAT inside. I'm running this configuration, this lab over the virtual machine, so that's why we are getting some sort of CPU hog errors. That's okay. So I have two interfaces assigned as a outside and inside. Then I should go and do the configuration for NAT. So first of all, I want to do the NAT uh, dynamic NAT configuration. So where what we need to do, we need to create the ACL entries. So I can go and create IP access list, and then I can give a name. So for example, my host having IP range of 10, and let's do like this. I can give a standard as well, because I know that I have the ACL where I want to use only IP addresses. And then I can go and give the name. So for example, host 10. Then I can go and give permit 10.1.1.3, and then permit 10.1.1.4. These are the two IP I have here. 10.1.1.3. You can see that gateway is 10.1.1.1. And then I have 10.1.1.4, its gateway is 10.1.1.1, like that. And we are using no IP routing. That means if you go and check show IP route, you'll find that your routing is disabled. They're working as a host machine. All right, so I have my ACL created, what I want now. Next, I want to create pool of IP addresses. We have IP address, for example, this point, this external interface is 200.1.1.1.1, but let's see that I want to use say 200.1.1.1.5 to 10. So this is the pool of address I want to use. What we can do, that I can go here and I can create IP NAT, and then here you can see that we have pool. So let's create that IP NAT pool. Name of the pool is, say for example, NAT pool. Then what will be the address? So let's go and give the address. 201.1.5. You can see the start address it is asking, and then it is asking the end address. Then I can go and give the net mask 255.255.255 dot anything. Say for example, 248. Okay. Okay, it is telling that it should fall inside 240, so that will be 16 or the 14 valid addresses. All right, so once we have this, then what is the final thing that we need to do? Say IP NAT, and then you have to use the statement. So what is that? Say here you can see that IP NAT, what is your source? That will be the ACL. And what is the ACL? That was host 10. And then what is the pool name? We have the pool name called NAT pool, and that's it. So let's see that my access list name is correct. So host 10, that's 100% correct. And then we can go and verify the NAT configuration. So I can go and check NAT pool. All right, so now we have the correct NAT configuration. I can go here to host number 3 and then host number 4. So if I ping say 200.1.1.2, it should be reachable, right? And if I go here and check the NAT, show IP NAT translation. So let's see, it's not showing any NAT. Show an interface gig 0/1. Let's see the NAT inside and outside. So this is the outside, and if I go and check 2, this is the inside. First of all, let me check that from here I'm able to ping to my gateway or not, and this is working. Then let me go and check that from here I am able to ping to my router outside interface or not. That is also correct. Then from here, do I am able to ping to the NAT address, that is 200.115, and it has some problem. So let's see. And show run interface gig 0/1. So here I can see that I have this address and this subnet mask. If I go and check my host section, alright, so I'll go and try to change this ACL, but you can see that we are doing the correct methodology to do this. Say 10.1.1, for example, 0. Let me see, do I have option to give wildcard? So I'm taking complete range here, and let's see. What's the final result? So I should go and remove few of the statement from here. Let me go and use IP access list standard host 10, and then I'll remove 10, 20, 30. All right, so let's quickly see that what is the configuration. So permit 0, these wildcard bits. Wow. So let me do this one more time. What I want here, I want to permit, and I want to permit 10.1.1.0, 0.0.0.255, And then if you go and check show IP access list, you can understand why this is coming, because the wildcard that I have given was wrong. I should give the correct wildcard, otherwise it will obviously do like this. So we'll go here and we'll remove this line that is 40, and then we can go and verify. Finally, our access list is this, and then we can go here and try to reach the destinations. Say for example this is okay, they should be reachable, 200.111, but what about 200.112? And suppose if it work, then we should have a NAT entry over router 1 show IP NAT translation. So what are the verification commands we have? We have show IP NAT translation, and then we have show IP NAT stats. Okay, so what it is telling, that you have 01. So let's see that I have interface 02, that is inside, 01 is outside. Then we have the ACL, and what's that? 10 pool, NAT pool. Then you have this NAT pool where you have this start IP, this end IP. Okay. Now at this point of time, my IP that I'm using here is not routable. It's not reachable. I don't have the reachable IP address. So what I will do, that this scenario should work, is that I'll go and I should use the NAT overload configuration. So what does it mean? I should go and use IP NAT, and we have the, let's see that what we have. We have IP NAT source, and source is the list, and what was that? Source list, say host 10. Then I'm going to use the PAT. So the interface, now what interface we have? We have the interface gigabit Ethernet, and that interface is nothing but 0/1, 0/1 overload. Now we can go and check the NAT configuration. So we can go and check sure and selection NAT. Let's see. So now we have two statement here, and one statement is related to dynamic NAT, one statement is related to PAT. So if first statement will not work, then it will go and check the second statement. So now if you go and check 200.111.2, still it is not working. And if you go and check the show IP NAT translations and strats, so NAT translation is not working. And then we'll go and check the strats as well. So you can see that the stat is also not working. Now what wrong we have done here is, so if you go and check the syntax, you'll find that, let me remove this statement first. And then I'll go and use a IP. Even let me remove the upper statement as well. 0. Okay. So what is wrong here? Why it is not working? When I'm using this IP NAT, I should use source list. That's the complete statement actually. And then the host, and then we have the pull. That pull is nothing but the NAT pull. That's it. So this is the valid configuration now. You should go and check. At least it should start translating the packets, correct? So if you go and do the ping for 2222, and now if you go check show IP NAT translation and show IP NAT stat translations. I have built the lab over the viral, and in viral we are seeing some issue that NAT is not working properly. Although we have done the configuration, the same configuration I have done in GNS. Here you can see my laptop, all the same type of devices, and only thing that the interface is different, but same IP schema, everything is same, even the configuration and all the rules that I have created, each and everything is the same. Now here you can see that we have IP NAT inside, we have IP NAT outside. So let me show you that I have serial interface, and then I have fast Ethernet interface, and then I have this NAT configuration, then I have the access list 10 configuration. So we have all these configuration that we have studied in the previous recording. I just wanted to show you the verification command. So if you go and check show IP route, this is working as a host machine. I can ping to my gateway, that is 10111, and here you can see the diagram that this interface F00 is 10111, then this is 200.1.1.1.1, and then you have the outside IP that is 200.1.1.1.2. So let's do the verification. If I go and ping 200.1.1.2, you can see I'm able to reach. And if I go here and check show IP NAT translations, so here you can see the translation. I have one entry coming from this. The protocol is ICMP. If I go here to this device, that is the outside device, and if I go and enable say line VTY024 login local, and then if I give the username and the password Cisco, and then if I go here and do the telnet 201.1.2 connection refused by the host. But if I go and check the translation history, you can see that it tried to convert the IP, and on top you can see that I have inside global, inside local. So inside local to inside global, and then outside local and outside global are almost the same, correct? So in the same way, we can go and create the PAT as well. So what was the command for that? Just for a revision, show IP NAT, and we can go and give source, and then we can go and give the interface. We know that the interface I have 0/0, I can use overload. Okay, what are the verification commands we have? We have show IP NAT translation, show IP NAT stats. So these are the command and the verification. Better we can do the lab over the GNS3. In 3.4c, we have to learn about FHRP, and we have to understand the theory, and then we have to perform the lab task as well related to first hop redundancy protocol, that is the hot standby redundancy protocol, HSRP, and then VRRP. All right, so let's start with HSRP. Uh, First of all, why we need first hop redundancy protocol? We need first hop redundancy protocol because you can see this diagram here. You'll find that, okay, I can go and reach to the switch and then I can go out, or I can do anything, correct? The problem here is that suppose if this link will go down, then what we can do? Obviously, all the devices in the network, they will lose the control. Why? Because you have only one path, you have only one dependency. So you don't have triangle in a network, or you don't have loop in a network, or you don't have redundancy. Suppose if you have this type of connection, and then if these devices can work as an active or a standby or primary or secondary, if this link is down, still you have the way that you can go and reach outside, correct? So that's actually the concept, or that's actually the need behind creating the first hop redundancy protocol. Now, doing so, there is one other problem. Suppose if you want to use this path via this switch, so what will be the gateway address to the host? Because generally we used to hard code the gateway address. So either gateway address will be this switch physical interface, so this interface here, or maybe this interface here. Suppose if your switch is down, this end host machine, they can't dynamically change the gateway. So rather than, what is the strategy here is that you should use some virtual gateway, or you should have some virtual router in between these physical devices falling in the same network, and that virtual IP we are going to give as a gateway address to the client. So either if first or maybe second switch will go down, there is no impact in a network. So we have the label of redundancy. Now we have multiple protocols. We are going to discuss about hot standby redundancy protocol. Here you can see that you have switch 1 and switch 2. One is working as a active, one is working as a standby. Rest other devices are the listening router. As per the highest priority, so there is priority. So for example, 200 versus 10, so higher is better. As per the highest priority, one of the device will work as a active, and then rest of them will work as a standby and listening. In a group, we can go and put say 16 devices. So here you can see that you have priority from 0 to 255, and default is 100, higher is better. So what does it mean? It means that although you have the virtual IP, and suppose his priority is 200 and this priority is, although it is written 100 and 150, but let it be, this is 100. So the traffic will go in this direction. Now what will be the fallback? If you have LAN interface will go down, obviously they will do some sort of re-election, and this device, because one is unavailable, so you have one other path that you can go in this direction. But again, there is one question that what will happen if your WAN interface will go down? Okay, so there may be chance that your switch will go and reboot, your this interface will go down, your WAN interface will go down. What will happen with the active traffic? What will happen with the flow of the traffic? How it will converge? How there will be the fault tolerance, etc. Okay, so we can discuss that. Never mind, one by one. First of all, when we have the two routers in a group or two switch in a group, we can go and create, or we can do the HSRP configuration. Then they will go and elect who is the active and who is the standby. And the message that they are going to send across in between devices are, say, initial, learn, listening, speak, standby, and active. So in active state, we have this devices that is actively, means they will form the HSRP neighbor relationship. We can't tell that neighbor relationship, but they will form the HSRP in between them, and one will be the HSRP active, one will be the standby. So here you can see that in the active state, an interface in an active state is the live gateway and will forward traffic sent to the virtual IP addresses. Host will use the virtual IP as their gateway. The active router will respond to the ARP request for the virtual IP and the virtual MAC. So far we have discussed about virtual IP, but we have one other concept as well, that's the virtual MAC. Now the Hello Packet Exchange for HSRP, we have is peak, standby, and active. Okay. All right, so let's quickly discuss about the virtual MAC. And once you go and do the basic configuration, I'll show you that virtual MAC in the next slide. So you can go to the interface, or you can go to the interface VLAN. You can go and use this command standby. You can define the priority. You can go and define the virtual IP, etc., etc. We'll see all these things in the lab. Then here you can see that this is the diagram, although our lab diagram is a bit different. I'll show you in the lab diagram. So these things I'm going to configure in the lab. Instead of interface VLAN, I'm going to use any Ethernet interface or any physical interface. So you can go and do the configuration. Now, important thing here, you can see that the ARP response will come from the virtual MAC. So this particular virtual MAC, what is the format? So here you can see this is the format 000.0C07AC, and then the group number. This XX is in the hex that will represent the group number. So suppose if I go and give the HSRP group as 10, if you convert 10 into the hex, it will come 08. So that's why the final MAC address is 000.0C07AC08. Okay. We have this. If you want, we can do the MAC address manual configuration as well. If you want, we can do the authentication configuration as well. Then we have the concept of preempt. So what is mean by preempt? Suppose this is active and this is a standby, and it will go and reboot. So this will become active, but suppose it will come back online. So if you enable the preempt feature, that means when the active will come, the system will detect, oh, he has the highest priority. So for example, he has a priority 200, he has a priority 100. So this guy has the highest priority. That means again he will become active and he will become the standby if we do the preempt, if we enable the preemption. Otherwise, active will be active, standby will be a standby. After the failure, standby become active, he will be the active. Okay. So we have the command. We can go and use a standby one preempt. If you want, you can disable the preempt as well. Apart from that, we know that we have the timers for HSRP. By default, that will be 3 second and 10 second. 3 second of hello timer, 10 second of dead, means you are sending 3 packets. Fourth packet, you are not getting response. You'll make that your HSRP group partner is not active, maybe some issue, maybe you have a split brain issue, etc. We are using the multicast address to 24002 and the UDP port 1984 for this particular hello exchange. If we want, we can give the time in milliseconds as well. So if you want aggressive timer, if you want fast convergence, you can go and change the hello timer. We have a few of the verification command that we can go and check show a standby. We can go and check show a standby brief. All right, so we have few more slides related to failure as well. So let's complete these slides, and in next session anyways we have to do the lab, so I'll go and discuss more and more in that. Now here you can see that tracking. Say for example, this link is down. Suppose his priority is 150 and this guy priority is 130. So obviously he is active and he is a standby. Now what you can do, you can track the interface that is going to WAN, say 223, and then you can decrement the priority, for example 60. So if we decrement the priority, if this link is down, what will happen? This priority will become 90, and this is what 130, 130. So that means the traffic will go in this direction. And that's the use of the live tracking, or that's the use of the tracking, that you can track the interface, you can decrement the priority, and the standby will become the active, and the traffic will go in that direction. All right, so these are the points you have. At this point of time, you can think that how we can check this link. Obviously, this link is tracked. If this link is down, automatically it will go in this direction. If this device will go, obviously it will go in this direction. If this is down, you should do the track and then decrement some sort of priority. So this direction will go in, and this traffic will go in this direction. All right, so these are the concepts related to HSRP. Let's stop here and perform the lab task. All right, so let's do the lab. I have created this topology in GNS3. Here you can see that I have router 2, I have router 3, and then I have one router. I have changed the display, means I have changed the uh, look for these devices. It's say router, it's showing you as a cloud. Then I have this routers 4 and 5, but it looks like they are the host or end machines. I have assigned the IP addresses as per this schema 10110. This is obviously the LAN segment that you can see behind R2 and behind R3. And then I have a static route going or reaching towards R1 from R2 and R3. Okay, so let's do and enable the HSRP over R2 and R3. Obviously, I'm going to use F00 for these interfaces, and then I'll go and assign the default gateway for R4 and R5. So let's do this. If I am inside R5, let me check that what gateway I have given to these devices. This IP default gateway is 10.1.1.2. That's not correct. Means I should change this. I will go and change this because I want to use the default gateway as the virtual IP. So before changing anything here to these devices, let's go and do the configuration for the HSRP, hot standby redundancy protocol. So we can go to F00 and then you can use the keyword standby. Then you can see that you have options: authentication, delay, IP, MAC, preempt, priority, redirect, timers, track, use BIA, burnt in address, and version. All right, so what we want to give the group, and then I want to give the virtual IP, say for example 10.1.1.2.50. I don't want to make this secondary, so leave it. So now I have assigned the virtual IP here. Then what I will do that I'll go and give the priority as well, because this R2 I want to make as the active at the master, you can think, and the other one will be the backup or standby. So what configuration we have done? We have done only two configuration: standby IP and the priority. I can go to R3. You can see that they try to move from speak standby active, and if I go and check show a standby brief, so he don't know who is the standby, but this state is active. Great. So let's go and do the configuration to R3. We have R2 and R3 connected via the LAN interface. I can go and do the debug as well, so we can see some of the packets. I can go to the fast Ethernet interface and priority I'll give 100. Now you can see that the state disable to init, redundancy, this is the group, disable init, and now you can see the other messages. I'll pause here, you can have a look. Init to listen, passive, active, and the group, this become the backup because it has a lower priority. Then it is telling who is the active, what is the VIP IP, what is the router ID. Uh, then you can see all these messages. Now it is sending the hello packet after every 3 seconds. So since the debug is on this device, I'll go back here and we can check the standby. If I can give the detail. So what I can do here, that I can enter. Here you can see that what's the virtual IP, what's the MAC. We have discussed about this because we have used the group 10, so that's hex is 0A. This is by default running V version 1, the hello and dead timer, the active router is local. Now if you go and check the brief, then you can see who is the active, who is the standby. So it's very easy to actually configure at this point of time what we want. I want to go to these devices and I want to use the IP default gateway as 10.1.1.250. So these devices, they should have the proper gateway. All right. Now what we can do that we can go and test it. So I can go and ping to the R1. R1 has one loopback interface. So what does it mean? If I go to R2 and if I can say for example ping 1111, let's see if it is reachable. Otherwise I'll go and create a static route from R2 to R1. Sure, and let me check the routing section. In R2 I can't see that I have any static route, so I'll do one thing. I'll go and create the static default route for the device 200.1.1.1.2, and if I ping now, yep, like that. If I can go here to R3 and let me undebug all to run section IP route, if we have any routing, no, and what IP we have here. So we have this 201. I can go and create IP route 000 and then the gateway 201.1.1.2, and if I ping 1111, if I can source as well, reachable. So now if I go to this guy here, that is one of the client. I should give the client instead of the R4. So suppose this is client 4, and if I ping 11111, that's the outside. Let's see if I'm able to ping. Yep. And if I do the trace route for 1111, let's see how it is going. So first it is going to the gateway that I have. This is the router from where I'm going, and then I'm going outside, correct? So what we can do here is that we can do the ping, and subsequently we can shut down one of the interface. So what I'm going to do, I'm going to shut down the R2 F00 interface. So I'll go to R2 interface F0/0, shut it down. So in that case, the HSRP will go change, and you can see a standby brief. Both sides you can see now it is unknown, but if you go to R3 and if you go check show standby brief, so he is the active, although his priority is less. Now we haven't done the print at this point of time, so if I go here and interface F0/0, if I do no shut and You can see that this is still active, although his priority is less, and this guy here is, let me show you the full output. Let me just this. So still it is in speak because we haven't enabled the prompt command. So still it is in standby. You can see state is a standby, although the priority is high. So for that reason, what we can do, we can go to 00 and standby 10, and we can go and enable the prompt command. I don't want to use delay and other thing, but if I do the prompt here, you can see the selection has been changed. I should go and do the prompt, oops, here as well. So I can go to R3 and I can enable prompt here as well. Now if you go and check the output, he is active because of the prompt command. Now likewise, if you want to go and check this interface up and down, so that also we can track serial 00 as well in the this present scenario. So what does it mean? My priority is 200 and this guy has priority of 100. I will decrement the priority by 110. So what I can do, I can go to interface 00 and standby 10. We can track the serial interface 0/0, and then we can decrement the priority by, say for example, 110. Correct? Now if I go and make this interface down, so you can see that this is now unreachable. The traffic should redirect and it should go. So let's see that what happened actually. So standby brief. Now this is still showing active, but if I go here to R3, if you go and check show standby brief, what's the priority? 110. And this guy, what's the priority? 90. Okay, so that means the traffic should go, and here you can see that this link is down. So that means now this is the active one. So the traffic should go from here and then it should go and reach to here, although we have the different IP to the subnet, so it's okay. But if you go and let me stop the ping. Now if I do the trace route for 1111, you can see that how it is going. It's try to reach to its fixed gateway. Let me see what's the gateway it has. Show run section default, that's true, and show IP interface brief. So what should be the order here, that it should try and check 1.3, means when I'm doing the trace route, so it should go by this, but actually the problem here is to announce the network in the bottom. So from R3, if we go and check the R3, from R3 I should go and ping 111 and source serial 0/0. Oops, let me see what source it has. 0/1. Yep. So we can see that main idea I want to show you here, that this guy, that's the router number 1, is become active, although it is showing active, but its priority become 90, and this guy is tracking the interface and he is the active one, means now its state is showing a standby. Let's see the configuration. Standby. We'll do the troubleshooting. So what is there? No configuration. And let's see, show run interface F00, where we have done all the configuration. So we haven't done much configuration on R3, and probably that's the reason that is not showing you the result. So even we are seeing the troubleshooting as well. We can go here and give the command standby 10, and your priority by default will be 100, we know that, and then a standby 10 to the prompt if the state is changing, and then we can go and check show. Now you can see something is happening here. Now if I go and do the first route, now you can see that it is going by that path, correct? So that means if I do the ping now, okay, a little bit less, it is happening. And if I go and do the interface serial 00, no shutdown because prompt is enabled, so this link will become active. We'll get the message and do show standby brief. And now if I do the shutdown, so it is down. So see, for some time it is unreachable now, but now it is going from the other side. So now it is this in a speak state. And if you go and check the standby configuration, this is the active. All right, so this is the way that we can go and do the configuration. There are a few configurations as well, like if you want to change the timers, if you want to use the authentication, but this is the main thing that we use to uh, do or perform with respect to HSRP. Next, we have VRRP. VRRP is nothing but Virtual Router Redundancy Protocol, very much similar to the Cisco HSRP. The difference is that this is the industry standard and HSRP is Cisco standard. Almost they are same, but there are a few differences. We'll see that what differences they have. First of all, you can see their timer is 1 second. Then you can see that the MAC address is 224.0.0.18. The VRP prompt is on by default. VRP cannot directly track interfaces. It can track an object which is tied to an interface. Okay, so you can see that there are some difference, and again we are in the existing WAN. If you go to SD-WAN, specifically Cisco Viptela SD-WAN, in that we don't have HSRP, but we can run VRRP, and there we have the customized VRRP that I have explained in my SD-WAN course that you can refer. So VRRP in the existing WAN, VRRP in the SD-WAN, both are very different. Now this VRRP is very much like HSRP. It is working as a gateway, so we can have the virtual IP, we can have the priority. Again, higher priority is better. We can go and tune the timers. We can have the we can go and enable the authentication. We have the reserve MAC address, which is different. There we have the different MAC address. Here you have 4 times 05 E00 dot 01XX. Okay, and here the name of the primary, say active, and the standby is master, and the backup that will go and verify in the lab section. We can go and use no VRRP prompt because by default this will be on. You can go, if you want, you can disable. You can go and check show VRRP. Very much same type of output you'll get that you have in HSRP. Now we have one very interesting topic here, that do VRRP and HSRP can do the load balancing. Because for load balancing we have Cisco proprietary protocol, that is GLBP, that is not in this particular course, but we have discussed earlier in section maybe 1 or section 2 that how this GLBP is working. GLBP is not that popular like VRRP or HSRP due to some GLBP. They have some reason behind that. They have some internal reason. The active forwarder or the standby, they are not able to do a load balancing in failure scenario, etc. Means they have some internal issues with GLBP. You will find that most of the places we are using either HSRP or VRRP. Now suppose you want to do the load balancing. You know that one of the router is active, one is a standby, and suppose if you have thousands of client or endpoint, you want that 500 will go via one router and 500 will go via other 100, the 500 will go via other router, then how we can achieve that? So what I'm telling here, let me try to draw, and even you can see the configuration. That's the manual load balancing configuration we have. So what I'm telling here, that say I have these two devices and they are part of, say for example, VRRP or maybe HSRP. Now we know that one is active and one is standby, or one is master and then backup in case of HSRP and VRRP. And suppose if you have 1,000 users or 1,000 clients, then obviously as per the standard configuration, 1,000 of the devices will go via one gateway, one active gateway. So there is no load balancing. Rather, what we can do, that we can create group. So here you can see that inside VLAN we are creating one group and then we are creating other group. So one group is having higher priority, other group having lower priority. Obviously the VIP is different, virtual IP is different. Likewise, that means that as a whole, this will be the active for 500 users and this will be the active for 500 users, and as a whole they will work as an active load balancer. Okay, now once you have this configuration and you want to check it, verify it, you can go and check show standby brief. So in that output, what you will find, that you will go and get the output related to both the groups. So here you can see that you can see the first and the second device, active standby, standby active. Now this is not the limitation, but actually this is the feature that we can do the manual load balancing across the routers. Alright, so let's stop here. We'll do the VRRP lab that we have done like HSRP, and then we'll check this load balancing methodology as well. Let us perform the lab task. Same lab setup, we'll go and enable the VRRP instead of the HSRP. So let me go and fix the screen. I have VRRP, HSRP enabled on router 1 and 2, so I can do this thing. No standby, say 10, like that. If I can do, interface should be fast Ethernet and 10. Then I'll go and remove the HSRP from R3 as well. So first of all, I will go and do the basic configuration, and once I will do the basic configuration, then we'll go and do the load balancing configuration as well. Right, so here we are in the router number 1. We are in the correct interface. I can go and enable VRRP 10 and we can see what options we have. So I have this IP, say 10.1.1.250, and that's it. Then VRRP 10. What other things we have? We can give the authentication, the prompt, priority, shutdown timers track, and track is event tracking. So here what I can do, that VRRP 10 and the say priority 150, that's the higher priority. Then we can go and check to show VRRP brief. So here you have the master, and we'll go to the other side. Here we can go and make this IPs 10.1.1.1.250. By default priority will be 100, so you will see that you need to backup. Now if I go here and check, so the priority, the prompt, the master address, the group address, so we can see that is the master. And if you go here and check do show VRRP brief, so here's the backup. Okay, so here you can see that the master address, and you can see the master address, and then you have the group address, etc. So it is working fine, there's no problem. It will work. Now what we want here is that I want to create two groups. So for example, one IP will be 250, other I'll create 251. R4 I will put in one group, R5 I will put in another group. So I'll create two group, 10 and 20, and let's do that. So now what I will do that I'll go to R2. I already have the group that is this, whose priority is this. I will go and create one more. So for example 20, and the IP is 10.1.1.251. That is going to be the default gateway IP for 50% of the clients. And then the VRRP 20, the priority, say for example 50. So 150 and 50. Likewise, I'll go to R3 and VRRP 20 IP is 10.1.1.251, and VRRP 20. By default, it will be 100, so we can understand this that will be the master. Now we can go and check show VRRP brief. So here you can see backup master, correct? And if I go here and if I go and check show VRRP brief, so here you can see that master backup. So it is working. Only thing that we need to do that we should go to the client and we should change the gateway address. Rest each and everything will be the same. Now if you want to see the VRRP detail, you can go and check like this. Alright, so let's stop here. You can see that this way we can go and do the lab related to VRRP. In 3.4D, we have to learn about multicast, and we have to learn about multicast routing protocols as well, such as PIM and then IGMP. So let's start. Now, before starting multicast, I'm going to give you a brief introduction about what is multicast, MAC address, the basic stuff related to multicast. So for example, we know that we have three different type of packets, say unicast packet, broadcast, multicast, even we have anycast as well. That's actually the type of communication. So unicast means that one-to-one communication. And there are such protocol, for example, OSPF, BGP, EIGRP and other IGP protocol. They are basically destination based routing protocol, and they are using you can tell that the unicast based routing protocol. Then we have broadcast. Now broadcast means one to all, so someone is sending message to all. Then we have interesting packet type, that is the multicast, and that multicast is one to group. Again, we have anycast as well, that is one to nearby. Okay. In this section, obviously, we are going to focus more on multicast. So multicast means that the method of communication is from one to group. Now here, a very important fact is that if we compare unicast routing protocol and multicast routing protocol, the basic difference is that unicast routing protocol, you are building destination based routing, or you are doing destination based routing. In multicast, we are doing source based routing, means someone is the multicast source and then you have the multicast client. Those clients want to join the multicast source feed. That's the basic difference, and we'll understand more and more about that. So you have to define the group who are interested to join the multicast source. So multicast source is sending the feed, and we'll see that how the feed is sended. There are different methodologies, and then my host, they want to join the feed. Okay, so it's something like a reverse routing tree we are creating, and actually this is nothing but RPF. We'll see that in next section, but let me still focus on basics. So let's continue the basics. We know that we have class A, B, C, D addresses. D is there 224.0.0.239.255.255.255. That is reserved for multicast address. Then we have the link local addresses used for control mechanism or to find the neighbors. So for example 224.0.0.0 up to 224.0.0.255 255. Then we have public and private address ranges for multicast. Here you can see all the link local addresses. A few of them we have used earlier. So for example, OSPF, hello packets, and then the DRBDS selection. For that, we have different multicast link local address, then RIP, then EIGRP, then others as well. Right. So now basic question here is that in multicast, we don't have multicast MAC address. So the question here is that how multicast they are framing their multicast MAC address, correct? We know that MAC address is of 48-bit. So what is happening that whatever IPv4 multicast address we have, they are taking 23 bits from there, and then they are adding 25 bits of this address. So 25 plus 23, you will get 48 bit of MAC address. Now how it will be? So here you can see that this address 00, obviously this is in hex. If you convert this in binary, so 0 means 40, then 1 means 0001, then again 0 and 0, then you have 5, and then you have E, and then last 0. So now you have 8 plus 8 plus 8 plus 1, that means 25 bits. Now what is happening that we are going to add last 23 bit of the IPv4 address. So 8 plus 8 plus 7. So that means up to here. So if you go add this here, so you will get this, correct? Now this address again, if you go and convert into the hexadecimal, so you will find 0 1 0 0, then you have to check this. What is this? So 1 2 4, so that means 5, then 2 4 8, so 8 plus 4 plus 1, like that you have to do the calculation. I'll show you that what it will look like, or how it is look like. You can see here that now the finally it will be looking like this. So this is the multicast MAC address, and here you can see the mathematics for that. So in decimal it is looking like this. In hex, because we are concerned or we are looking for hex format, MAC address is in hex format, so it will look like this. Okay. Now while doing this methodology, we have one problem. What problem we have? So for example, this two address 225 and 231, if you go and convert their MAC address, you will find that the MAC address is same. Why so? Because again, if you go and take 23 bits, so here you can see that 23 bits, so 8 plus 8 plus 7, and 8 plus 8 plus 7, these 23 bits are common, and again first 25 bits are also common because that's fixed. So this 25 plus 23, if you go and add, you'll find the same MAC address for different IPv4 multicast address. Now we have that problem, and truth is that there are 5 different bits. That means there are 32 multicast IP addresses for which we have single MAC address. Okay, why? Because you have 23 bit, that is you are taking from IPv4 address, and then because multicast address should start with 224, so that's why you have these 4 fixed bit. So you have this fixed 23 bits and then 4 fixed bit. You have 5 variable bits that can be anything, and the combination of these 5 bits can have 32 multicast address. So that's the problem we have in the multicast, but the arrangement of the bits and the IPv4 multicast address is in a way that this is not a bigger issue. So it's not a big thing in multicast. All right, so these are the basic things that we have discussed. That's what is multicast and what are the address family, how we are going to construct the multicast address, and what are the common IPv4 multicast address we have. So let's stop here. In next section, we'll discuss more about the multicast routing. Let us discuss about multicast routing protocol or multicast protocol. We have different protocols. We are going to discuss about that one by one. We know that we have a multicast protocol, and if we go and learn a little bit deep about that, you'll come to know that, okay, although we have multicast protocol, but still we need IGP, Interior Gateway Protocol, and the multicast protocol. Both are working hand on hand to provide the final multicast feed from source to the receivers. What protocols we have? We have protocol independent multicast. We have multicast OSPF, distance vector multicast routing protocol, core based trees. Now to enable this on Cisco devices, we have to run a command IP multicast routing. Again, when we'll go and study about PIM, we'll find that they have PIM, dense, sparse, dense mode, etc. Means different variations are there for that protocol. Now, earlier in this uh, section, we have a study that they are going to use reverse path forwarding, or they are going to look that exactly where is my source. So unlike destination protocol like OSPF or EIGRP, multicast is going to form the tree, and that tree will be based on the source. So not based on the destination, but based on the source, they are going to form their multicast tree, and that methodology is reverse path forwarding. Sometimes we'll tell this, okay, we have variations of PIM. So for example, dense mode, so we are flooding and then we are pruning. Or we have other methodology where we are flooding the feeds, and then in whatever link, I don't have the multicast host, so we used to prune that, because obviously I don't have the receivers, so why I will flood those feed in those particular link or locations. Now here you can say that we have different parameters like S and G, source, comma group. You'll find a star comma G as well, that is for rendezvous point, and the group. Group means the multicast address. Source is multicast source. All right, then upstream and downstream. These are the concepts. So upstream means that the link that is going towards or reaching towards the multicast server or the feed, actual feed. And downstream is where you have the receivers. So the link that is going towards the receiver. Here you can see, say for example, for router 1, the link here that is going to the multicast source is the upstream, and then these interfaces are the downstream. One condition is there, that you should have multicast host in the downstream. Otherwise, there is no point of having the downstream if you don't have any multicast host. Okay, so how it is building the tree? First of all, it will send all the feeds, and in that location where there is no multicast host, they will prune those links. They will not send the feed on those links. So that's the flood and prune. At least the prune methodology we have. Now here you can see that we have multicast protocol like PIM, OSPF, multicast OSPF, etc. Then other concept we have is IGMP. Now this is not the PIM, or this is not the multicast OSPF, etc. IGMP is a protocol that is specific to the host or those type of group they want to join the multicast server or multicast source, correct? So for that we have the Internet Group Management Protocol, IGMP. And now you can see that you have version 1, 2, and 3. Now most popular is version 2 and 3. So what is happening in this case? Say, remember, if you see this diagram, you'll find that, okay, you're sending the feed, but you should have interested receiver or receivers who will show the interest for that particular multicast feed. Suppose if you have 3 to 4 different type of sources who are sending the multicast feed, obviously one host can take only one multicast feed, So in that regard, there should be membership for that particular source. And that's the key we have. All right. So let's discuss that how this IGMP is working. Now, it's very easy to enable. You can go and enable the IGMP. Actually, when we are going and creating when we are enabling the multicast, it should enable, or by default in Cisco switches, this multicast is IGMP is enabled. But if you want to change the uh, version, then we have command here. You can see that I can go and change the version, say IP IGMP version 1, because no configuration is required to enable IGMP, except then you have to go and enable IP multicast routing. Okay, so let's try to understand that how this IGMP group protocol is working. So for example, IGMP version 1 router send out query every 60 seconds. Remember the words here, you can see that IGMP version 1 routers, say your end machine, they should have gateway. That means they will connect it with switch, and the switch will go and connect with the router. So now that router, that the nearby router, the gateway router, who is very near to the host or the receivers, the router is sending query every 60 seconds in case of IGMP version 1 to determine if any host need access to multicast server. So because router has built the tree, router know that with help of PIM how he can reach to the multicast source. So he is sending the query. Now this query is the multicast address 224.0.0.1. Now what is happening after that? Interested host must reply with a membership report. That's important. So host, they are replying with membership report for that query, stating that what multicast group they wish to join. Correct? So router is sending query, and host, they are sending the membership report. Just they want to join. Now there is problem with IGMP version 1 because they does not allow host to dynamically leave a group. Instead, if no membership report are received after 3 times the query interval, so router is keep sending query, 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 and you're not sending the membership report, then router will come to know, okay, these guys are not interested. They have turned off their receiving, or they have turned off, or they are not interested to receive the feed. It's something like when we are using, so for example, radio or FM channel, we tune to go to different band, and whatever band we want to use, that particular feed will come and that music will play on. Now suppose you're not interested and you don't want to join any group, so that means you will not respond for the query. Now this is with version 1. Now if you go and check version 2, you'll find that there is enhancement in version 2 related to leave message. So what is happening in version 2? The queries are sent from the router as a general query or group specific query. Additionally, host can send a leave group. So now what is happening, the routers, instead of query, they are sending group specific query to the host, and host, say once they are joined, obviously they have their membership report while they are joining the or they are responding the query. So what the host can do now, that the host can send the leave message as well. Okay, I'm not interested, I'm turning off my receiving capability, I don't want to receive it. Then it will be stopped. Now all versions of IGMP elect one router to be designated querier for the subnet. The router with the lowest IP become the designated. Again, if you go and if you check some more details, suppose in that group, if I have 4 or 5 routers, so they will go and select who will send the query to all the host, and which is the router who will get all the membership report, and then he will forward that message to the multicast source, or who is sending the multicast feed. IGMP version 1 is not compatible with version 2. If any IGMP version 1 router exists on the network, all routers should running version 1. So version 1 and 2 are not compatible. Even in the CCNP core, the syllabus is to know understand version 2 and version 3 as well. Now, so Version 2 is running by default, and it's most of the places you'll find version 2. But still in version 3 we have enhancement. So what enhancement we have in version 3? Version 3 enhancement in V2 by supporting source-based filtering of multicast group. So now we have the filtering for the source. Essentially, when a host responds to an IGMP query with membership report, it can specifically identify which sources within the multicast group to leave or join or not to join. Okay, so that means that uh, we have even more granularity inside version 3 where we can do the source-based filtering as well. Now here you can see that you have multicast source, then you have the router who will send the query, and then the host, they will send the membership report. That membership report is nothing but they want to join or they're willing to join. We know from this that who is the upstream. So FA01 is the upstream, and then downstream you have 3, 2, 3, and 4. But in 04 you can see that there is no multicast host. That means the downstream interfaces are 2 and 3. FA02 and FA03 are the downstream. How we can go and enable it? By default, version 2 is up and running. Once you enable IP multicast routing, you can go and check show IP IGMP groups. If you want to have any static group, you can go and do that. If your IGMP wants to join any specific multicast group, you have both the options, correct? And suppose if you want to filter, so we have the filtering option as well. Here you can see that I have created access list for 10 and 11. These are the multicast address. And then in IGMP access group, we want to join only 10 and 11. Rest anything will come, it will not join. Okay. So let me quickly log into the router, and I'll show you this configuration in CLI. Alright, so we have this topology. I'll go and show you all the commands configuration in router 2. So let me go here in router 2, and in router 2, what interfaces we have? We have A00, and I'm just showing you the configurations, how it look like. So first of all, I should go there and enable IP multicast routing, and then I can go to the interface and I can go and check IP IGMP version, and say for example by default version will be there. So if we go and check this, oops, show IP IGMP, you can see that you have groups, interface, membership. One of the important command we have is the membership. Okay, so at the moment nothing is there, so that's why most of the things are empty. I can go here and okay, let's see that what are the things we have here. You can see that group interface membership, SSM, UDLR, VRF. Okay, leave it. So I'll go here to the interface, save 00 IP IGMP version. So for example, 2. Okay, and then obviously we can go and check show IP IGMP interface, say FA0/0. These are the important commands. So here you can see that the internet address, the IGMP is disabled on interface. Okay, multicast routing is disabled, TTL0, no multicast group, interface is up and running. Later if you go and enable the PIM, and you can go and check the mroute as well, you'll check that later on. Okay, so I want to join any of the group, say IPIJMP, join the group. So let me see if I can see here. Okay, IPIJMP. Yep, you can go to the interface and then you can join the group. Say, as per our example, 226.1, say 5.10. and we'll leave that source show IP IGMP interface FS0/0. Now here you can see that IGMP is enabled version 2, the query interval, the timeout, max time. Okay, so I can see that join interface is this. Now again, I can go to that interface and I want to use the IP IGMP join. And if I go here and check what options we have, so we can go and use the static group as well, and say 226.1.5.11, and we can go and see this. All right. Suppose if you want to filter, so you can go and use the filter as well. Although you can see that the static group is not working, because if we want to do any manual methods, at that time only we are using the static group. But I'll go and use the join group one more time to the interface F00 IP IGMP join group 226.11.5.11 and then 12 and then say. Okay, so you can see that you have these groups, and now if you want to filter, you can go and create the access list 10, say permit these addresses. So I want to permit 10 and 11, and then I want to use this IP IGMP access group, say 10, and then we can go and verify the output. So just I'm showing that this is the way that once you apply this filter, so it will not go and join, although it is showing here in the configuration, but it will not go and join the other group, whatever not mentioned in the ACL list. Right, so let's stop here. Next important topic, we have PIM, that is protocol independent multicast. Now here you can see that PIM has variation. It can run in dense mode, sparse mode, and sparse dense mode. That's the Cisco proprietary. Now we should understand that why and what is the use case of dense mode and then the sparse mode. Now dense mode is something like you are doing the flood and prune method, means you have the multicast source. He is flooding the multicast traffic throughout the network, and then the receivers, uh, if you have receivers, they will join that. If you don't have receivers, it will get pruned, correct? But what is happening in the sparse mode is that is the intelligent way of doing flood and prune method. So in this case, you have one authority termed as a rendezvous point, RP. So what will happen that RP will get selected, and now it's the responsibility of rendezvous point or the RP is to do the flooding in the network. So it's something like you are saving the bandwidth, you are selective throughout the network. You know who has the authority to do the flood and prune, to build the multicast tree. Correct. So in this way, we can save the bandwidth. We will not unnecessarily flood the multicast traffic throughout the network. So it's a bandwidth savior methodology. It's efficient, but again, there is a use case that at what time we should use the dense mode, what time we should use the sparse mode. So here you can see that the key point is that when we are going to use the dense mode, so suppose in a network, if we have the large number of multicast hosts, so in that case, actually it's very easy. So everyone will send the multicast feed, and then pruning will happen. It's very easy, and it's like you can think, if you want to compare, then you can compare that, okay, so for example, RIP versus OSPF. RIP is something, a router RIP and then network command, but OSPF define the area, limit the LSAs, do the things in efficient manner. They will do the SPF calculations and all, correct? Although in other hand, the sparse mode, again, the thing is that you are doing it efficiently, but the use case is that when you have the limited number of multicast hosts. Okay? So both have pros, both have cons, but I recommended that we should use the sparse mode, at least in the enterprise network. All right, so here you can see that in PIM dense mode, you have the multicast source. It's sending the feed to all the throughout the network, and where you don't have the host multicast receivers, so you will go and do the pruning. So here you can see that now finally we have the tree structure that is built towards the receivers. So sender and receiver, source and receivers. Okay. This is the dense mode. Easy to use, very easy to build, but it is consuming the bandwidth. Now the next we have the sparse mode. In sparse mode, suppose if we have two multicast source here who is going to send the feed, first of all they will go and select the rendezvous point. So here you can see the selection of RP will happen. Once you have the selection of RP, rendezvous point, then it's the responsibility of RP that he will send the feed to the selected interfaces where you have the multicast receiver. Obviously, this is the efficient way to build and maintain the multicast routing or multicast feed. Great. Now you can see that you have version 1 and version 2. How we can go and enable it? We can go to the interface, and then we have option either we are running PIM in the dense mode or a sparse mode or a sparse dense mode. Now you have this RP option as well. So RP can be identified manually. Suppose this is your RP. You can go and run the command, manual command, and we have the auto RP in Cisco as well. So if you want to do it manually, the command is IPPIM RP address 192.168.1.1. Again, if you have the multicast source, so these are the feeds. We can go and create the ACL, and with the RP address, we can go and map this ACL entry. Correct. So this thing we have seen earlier as well in the previous section. When we have created the ACL just to limit the number of multicast source, and then if you want, you can map with the RP as well. Okay. Next, the verification and troubleshooting commands. So we can go and check show IP IGMP groups, show IP IGMP neighbors, show IP PIM who is the RP. Then we have debug command, debug IP IGMP, debug IP PIM. Okay, so let's do one thing. Let's stop here, and in next section we'll continue from here, and then I'll show you this CLA command in the GNS lab as well. Let's continue. So we have some commands to do the verification and debug as well. Once we build the multicast tree, then we can go and check show IP mroute. We have already discussed about source comma group entry, and if you have the rendezvous point, you'll find the star comma G entry as well. We have the upstream and the downstream interfaces. Suppose if you go and run show IP mroute in dense mode, you will see the output like this. So here you can see that you have the source, and then you have the multicast group address, the uptime, then incoming interface, the outgoing interface, who is your RPF reverse path forwarding neighbor, and here you can see the interfaces. Okay, so there is flag as well. Suppose if flag is not mentioned, this is dense mode, and if you go and check the flag, so let me show you that. Show IP mroute, and here you can see the flag is showing SC, that is for sparse mode. Okay, and you can see a star comma G entry for the rendezvous point. So if you are running the multicast in the sparse mode, then you will see output like this. Okay, so there are some notes as well. You can go and check the upstream and then downstream interfaces. So notice that SG pairing is labeled as a star comma G entry in the sparse mode. We can have multiple source share with the same multicast tree. The rendezvous point is 10.1.1.10. The flag is SC, that means route is running in a sparse mode. Then you can go and check who is the outgoing interface, who is the incoming interface. So it's just like the dense mode. The incoming interfaces indicates the upstream, means where is your multicast source, and the outgoing interface showing is the downstream, that where is your receivers. Alright, so let me quickly log into the lab, the same lab we have, and I'll run through a few of the important commands just for just to know that the commands are supported and what type of commands we can run in the P mode. Let me go and start this lab. Again, I'll go to R2. We have done some of testing. I'll go to R3, and inside R3, so first of all, we should go and enable IP multicast routing. See, that's the first command. Then I can go to the interface and we can go and run IP PIM, and here you can see that the mode. So we have dense mode, we have a sparse mode, sparse dense mode. Here you can see sparse dense mode, sparse mode, dense mode. So let me go and use this dense mode. Once we go and run the dense mode, then here you can see that DR has been changed, who is the neighbor. So I can go and check show IP PIM neighbors and show IP. Actually, this command is quite useful. Show IP PIM neighbor. It will show you whoever is your neighbor, and even we can go and check the interfaces as well. Okay. So now you can see the DR and DR priority. Now next, what we can do, that suppose if you want to go and check the RP, so we can go and assign that RP address, rendezvous point. So I can go to IP PIM and the RP address. What is that address? Say 192.168.1.1. We can give the ACL as well. I'll show you the ACL formation in this command. So for example, ACL 10 and then permit 226, say 11, 10, 11, 12, etc. And then I can go and assign this to IP PIM RP address 192.168.1.10 and then 10. Okay. So these are the commands that we can go and run. We can go and check that what commands we have used related to PIM and related to RP. Okay, so we have enabled the PIM in dense mode, and then we have enabled the RP as well. If you want to check show IP M route, you can go and check like this. All right, so you can see that all the addresses that we have given, for that we have a star comma G entry, and you can see the flag as well. Now flag is telling that we are running SJC. So S stand for obviously sparse, and then we have the flag J and C. J stand for join the SPT. You have a small s as well, you have big S as well. C is connected. Okay. Show IP PIM and the neighbor. Show IP PIM interfaces detail. We know that we have one interface here. So here you can see that PIM is enabled, PIM version is 2, and everything related to PIM. I can go here and make this as a dense mode. So IP, remember, whenever we are doing say IP PIM in dense mode, okay, so at that time there is no selection of RP, but at the moment you'll go and give the RP address. So here you can see that you are seeing all this rendezvous point and all. That's the reason we are seeing this. So what I'll do here, I'll go quickly and I will remove this statement and this statement, and again I'll go to interface F0/0 IP PIM in dense mode and interface serial 0/0. Let me see that what interface we have. Interface is serial 0/1. So IP PIM in dense mode. For dense mode, nothing is required. Simply, if we run that much command, that is good and enough. So I can go and check show IP mroute, and since this is running in dense mode, so you will see now I should clear this clear IP mroute. Wow, VRF clear IP. So you can see that VRF is there, and we don't have VRF related to that. I just wanted to clear these multicast entry. Alright, so I have cleared the entries, and now I can see that we have the DC, day for dense. Because we have enabled this feature on router 2 as well, and if you go and check, we are getting the feeds from router 2. So if I go and check if I have some configuration related to IGMP and all, so you can see that he is willing to join the IGMP group. We have some access protection as well, and those entries actually I'm getting here. Okay, but the idea of concept behind this, that we have the D, C entry, and now if I go and assign the RP, so IP PIM RP address say 192.168.1.1, and then if you go and check mroute, so you can see the flag will change to sparse. So it is changing from dense to the sparse mode. All right, so let's stop here. In section 4.0, we have to learn about network assurance. Here you can see the topic. We have to learn about various type of troubleshooting mechanism or diagnostic mechanism like trace routing, SNMP, NetFlow, SLA, IPSLA, NetConf, RESTConf, etc. Okay, so what I'm going to do, that as we have done earlier, one by one and section by section, module by module, we are going to discuss each and every topic. So let's start with debug. We have debugs and conditional debugs. We know that in Cisco routers and switches, we used to run debugs to know more about what is happening in the break scenario or what is happening behind the scene. But doing so, whenever we are enabling the debug, there is a chance that we can increase the CPU, obviously, because now you are getting all the informations about what is happening to that particular process. Again, Cisco has given one nice option that we can use conditional debug as well. Now, conditional debug is a way that we can prevent or protect from the utilization of high CPU and memory. We have certain commands to do that we'll go and check in the lab section. So what we can do, that we can go and enable debug. So for that, we should go to the exec mode and run debug, and then we have multiple options to enable that debug. We can go and undebug as well with the command no debug protocol. So enable the protocol or turn on the protocol, take the logs, do the analysis and turn off the protocol. Then we have show debugging option. With that, we can understand that how many debugs that we have used, how many debugs actually are running in that device. Then we have conditional debug. So for example, I can go and use debug condition interface, and over that interface, what is happening we'll get to know. Again, for the conditional debug, we have option to do the no debug for the conditional uh, debug, and conditional interface means debug over that interface. All right, so let me quickly log into the lab section and let me show you the lab topology as well. And then we'll go and enable the debug and we'll play around. So here you can see that I have my lab topology. It's very straightforward lab topology. where you have 4 routers and you can see the network as well. The router 1 has IP 12.0.0.0.1 and router 2 has .2, then 3 has 23.0.0.3, etc. So let me quickly log into the device, and first of all let me show you the IP schema that we are using here. So I can go and run the script, show IP interface brief, select all, send the script. So you can see the IP assigned to the interfaces. So for example, for router number 4, I want to create one loopback as well. So I'll go and assign one loopback address for our future troubleshooting and testing. So here you can see R1, R2, R3, R4. These are the IP addresses. So far, I have assigned only the IP addresses. Later on, we'll go and run any of the routing protocol as well. So what I want to do here is that I want to do the ping to router number 2, and whose IP here you can see 12.0.0.2. So even we can do like this. So I'm going to do the ping to 12.0.0.2. Here you can see that I am sending the ping packet and ping is successful. So what I want to do here, that I will initiate the ping, and I can do the repeat count more number of times. Then I can go to router number 2 and I can enable the debug. So what I can do here, debug IP, and here you can see at what options you have. So we have long list of protocols that is supported. What I want to do here, I want to do the debug for IP. So let me do that. Alright, so debug IP, and then again after IP also you can see that we have options related to so many things. Say ICMP. Enter. Now you can see here at the moment I enable the debug, I can see that echo reply. So this device is sending the echo reply, correct? You can see it is sending the echo reply, and it is so fast because it is coming from here. I can go and stop this. So let me go and complete that, and here you can see there is still whatever requested are there in the buffer, still we can go and see that. Now in this case you can see there is no chance that I can go and turn off the debug because already it is cached, correct? So what you can do, that you can re-log into the device, or otherwise you have to wait to that particular uh, point it will come where you can go and stop the debug. So one thing you can see here, that at the moment I enable the debug, I start getting so many packets, correct? Now while it is going on, let me show you that what other option we have with the debug. Now it's gone seems, so I'll go here, and if you want to stop, you can go and use undebug all. Before doing that, let me show you that what debug we have on. So here you can see that it is showing that your debug is ICMP packet. Now if I go here and use IP packets detail instead of ICMP, and now if I go and show you show debug, now you can see that we have two debugs on. And now if I go and initiate the ping, while initiating the ping, let me reduce the size as well. So for example 3. Now you can see the debug is on and we are getting the output in detail because we have done IP packet detail. So we are getting the ICMP type and code that we are going to discuss in the upcoming session. So here you can see that with help of debug, we are getting much more information about the ping and what is happening behind the scene. Okay. Now next what we can do, next we can go and verify the conditional debug as well. Now before doing conditional debug, if we go and check the IP route, so I have created one IP route here for 2222. Say in router 2 I have one loopback 2.2.2.2. So for that I have created one IP router statement that I can go to the next router and then the next hop. Great. So now if I go and enable, say, debug IP packet details, and if I go and do the ping for 22222, so you can see that we have flood of message. Rather than getting the flood of message, what we can do that we can go and create one condition, say for example IP access list standard or maybe extended, where you can go and define the source and destination. So I want to do, say for example, permit IP host. My source is, say, this, and then I can go and give the destination as 22222. Then inside the debug statement, I can go and use it. So anyways, if I am using debug on this router, I should use the condition here, correct? So I can do this thing. I can copy and paste this condition here, and even here also I can run the debug, correct? So no problem. So here also I'll go and enable the debug IP packets in detail, and here I'll do undebug. Say for example undebug all. Now I can ping to 12.0.0.0.1 with the source of 222, and I can repeat, for example, 4 times. Now here you can see that you have this debug. Again, you have long list of debug packet that you want to shrink or you want to minimize that. So for that we have this option. I can go and use IP debug packets, and then you can see that I can use the ACL, although I don't have option to apply the named based ACL, correct? So I can go and create the same thing with the named based number based ACL. So I can go and create, say, IP access list, not IP access list extended. I can give the number, so we know that the number, so 1333 is my number. Permit IP, who is the source, set let's give the source and the wildcard, correct? So IP is 12.0.0.0.1, 0000 means the host, and then the destination. All right, let me quickly see that what's the issue. If I just wanted to use the extended ACL, and do I have number for extended ACL? Here you can see it's a little bit different than the other. I can go and give the extended ACL number as 100, and then I can go and give permit IP host 12.0.0.1 and then host 2222. Great. Then we can go and apply to debug IP packets 100, correct? Detail. And then if I go and do the testing, so from other side I'll go and ping. So I can come here and I can do that ping one more time. Here it is. Oops. And here you can see that your table has decreased. So initially we have big table. Let me do that one more time. Now you're capturing the source and destination. Okay, so this way that we can go and use condition in terms of we can apply the ACL with the debug. The other variation we have actually is the condition. So I can go here and give the condition, and inside that condition I can go and match the fast Ethernet 0/1. Now you can see that one condition has been set, and then I can go and do the same thing. So let's do the ping. We can go and check here. So in this, what is happening, that the condition will match only fast Ethernet 0/1. You can go and check the condition, and you can see that one flag has been triggered. So this is the way that we can do the debug. So I have shown you the normal debug, then debug with ACL. Then also we can go and use the debug with condition as well. Next topic, we have packet internet grouper or ping. Now, how ping working? Ping depends upon ICMP messages, and with help of ICMP message, we can determine that whether the remote destination is active or inactive, what's the round trip delay, the packet loss. Now, when we are sending the first packet with help of ping, we are sending the echo request, and if we are getting the echo reply in the specified time, that means that the remote destination is up, and then we can get certain information about remote destination. Now here you can see that ICMP type and code, these are the messages and codes the ping is using to get the information about the remote host. So first of all, it is sending the echo, that is the type 8, and then it is waiting for echo reply. Again, you can see that type 3, the destination unreachable, network unreachable, host unreachable, protocol unreachable, etc. So we have long list of type and code. Say for example, other popular one is 11, time exceed code, time to leave exceed in transit, etc. So these are the code messages that we can go and refer while we are doing the troubleshooting. There are other characters as well. We are very much familiar with the exclamatory. That means it is successful. Dot means maybe some issue with the network. It is waiting. Maybe ARP resolution or any other network stuff. U means unreachable. Destination is unreachable. Q means source quench, destination too busy. M stands for could not fragment. Question mark means you don't know to reach to that particular IP in that subnet. Generally in firewall, when we used to ping without some specified information, we are getting this question mark. And then you have this AND, that means the packet life time exceeded. So let me log into the device in the lab section, and let me show you few of the ICMP code messages. All right, so I am in the lab, and here you can see the same lab setup we are using for ping as well. I can go here to R1, and then I can ping to 22222. And if I go and do this, maybe I can do ping from R1, and then I can go and verify in R2. So in R2, I'll go and enable the debug IP packet in detail, and then I can do the ping say 1. So now here you can see that you are getting the information, and now you can go and check the ICMP code. So this is nothing but the echo, and again you can see that you have the echo reply as well. So you have the ICMP here, you can see who's the source, who's the destination. So if I am the source, so here you can see the source and the destination packet. You have the source and the destination packet. Again, you can see the source and destination. Means suppose for the destination, I will be the source. Means that thing will reverse. Again, here you can see that the ICMP type 0, that's the reply, and then ICMP echo. If I go and enable the debug on the source as well, so debug IP packet in detail, and then if I go and do the ping for one time, so here also you can see the message, the type length code, and the message, so 80 and 00. So that's okay. We're sending echo, we are sending the echo packet, and we're getting the response as well. Easy and straightforward. Now I'll go and do some trick. I'll go and go to interface F0/. 0, I'll make this shutdown. And now if I do that thing, so here you can see that now you're sending the echoes, but you will not get the response, correct? Because anyways, the destination is down because the interface is down. And here you can see that we are sending this packet, but we are not getting any response back. So we are sending the echo and the reply is not coming back, correct? So constantly we are sending the echo packets and we are not getting the response. I'll go and make this no shut, and for example, if you go and check the routing, so this time I'll go and change the routing, means let me remove this default router statement. And then if we go and do the ping, so now again I am sending the echo, but we are seeing here that we are getting the dot, means that you don't have network to reach there because you don't have route, correct? So this time we are getting the dot 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 dot. Okay, this time you clearly can see that we are getting the dots. So now I can go here and do this as a this. All right. Next, what I want to do, I'll go to router number 2 or maybe router number 1 also, but I can go to router number 2 and then I can create one access list. Say access list 11 and deny 12.0.0.1, and then I'll go and apply to the interface in the inward direction, in the incoming direction. And then again, if I go and do the ping this time, so it is working. Maybe what exactly I was looking for, it is not the same. So let me quickly go and check. Show IP interface brief. What I want, that the router number 2 should not accept 12.0.0.1 whenever it will come. Okay, so if you go and check 0/0, I have IP access group in the inward direction that should deny show IP access list 10, oh sorry, 11. Yeah, so it should deny, it should not do the ping, and 12.110 will come to this device in the ingress direction and it should drop it. So undebug all. If I do the ping, see, you're getting this unreachable. Say for example, some more. So I just wanted to show you this unreachable, and you can see here in the router number 2 that what type of message you are getting. So yeah, you have the echo, but you have type 3 and 13, that's unreachable as well. Both at the source location and the destination location, you can go and see this. Okay, so far we have discussed about debug, conditional debug, debug with condition, or debug with some access list. Again, you're seeing different type of ping messages and with different type of options as well. Okay, so adding to this, we have a nice advanced option in the ping, that is the conditional ping. So let me show you the simple ping. Whenever you're doing the ping, what is your simple ping? Your simple ping is telling that you are sending some echoes with some repetitive frames, with some timeout, with some uh, frame size or packet size. So for example, 10 times, this is not successful. So let me quickly do one thing. Let me quickly go and remove the ACL, say no IP access group 11 in. And now if you do the ping, first of all, we should understand that we are getting the round trip information as well. How many packet? what is the packet loss, etc. So you have packet loss, round trip, and then the reachability. Three information you are getting correct, but we can do more than this as well. So what I am telling here that you can go and do the extended ping as well. So suppose your destination is this, your repeat count, suppose I want to do this 2 repeat count. The datagram size I can go and give more or less. The timeout in second is okay. And you want to do extended ping? Yes, I want to do. What is the SOAR interface? I will leave this. You have any TOS in your IPv4 frame? We'll leave this as the default. 0 is the default. You want to set any DF bit? We can leave that. That is to not fragment bit. Validate reply data? No, we'll leave that. You have any pattern? You can leave that. So what I want to tell you here, this particular section is very important. Now remember, when you are doing the trace, and again the next topic is related to trace route. So you're going hop by hop by hop by hop. We will see the logic as well in the upcoming section. But you are not getting any information for the reverse direction or reverse route. That you can go and get from the record option. So here you can see that you have loose option, you have a strict option, record, timestamp, and verbose. If you want, you can use all. So if I go and use the loose one, I want to show you all. In loose, it's not that what exact path you want to give. So you have any exact path? If you don't have, that's the loose. If you want that your ping will go with certain route, it will go with certain hop, certain route. So that's the loose and strict. That is not that much informative in case of troubleshooting, but this record will be very much important. Timestamp is again just the timestamp. So at this point of time, I don't have the source root, so I will leave it. But if you have any, you can go and give the source. So here you can see that you have loose and verbose. You can go and you have any sweep range in sizes. You want to have any variable MTU size in between. If you want to give, leave it. Now here you can see that you have this output. Again, it's not that exactly informative that we are looking for. So you will not get much help while doing the troubleshooting related to two options, that is the loose and strict, but although they have their own use cases. But for response, so for response you will get that, okay, not response, that record, you will get that. So let me go and do the same thing. So I'm going to do the ping, and IP is 222. This is my destination IP. Repeat count is 3. The rest of the things I will leave it. Extended, yes. Source interface, leave it, and then say record. By default, it has maximum actually 9 number of hops. You can reduce, but you can't increase from this. So for example, I'll give 4. Now you can see this option is RV, that is record and verbose. I can go. We'll leave that sweep range, but here you can see that reply to request, correct? So how the packet you are sending, how it is coming back. So while it is coming back from here, it is going to this and it is going to this, correct? So that's actually the key we have, that you will not get in the trace route. When you're doing the trace route, you don't know that if in case you have the asymmetric path. So here all the paths, although they are showing the same, because we don't have asymmetry at this point of time, but suppose if you have asymmetry in route, it will catch and it will give you the information about the asymmetry as well. Okay, so you can see the record route started from here, the destination, this is the source and this is the destination actually, but the reply is coming to this and coming to this. So you can think like this: reply to response 0, reply to response 1. Now to add some more visibility here, what I will do, I'll go and uh, run the some sort of IGP in between R1, R2, R3. So let me quickly do here. Router EIGRP 10, network 0000, no auto summary. EIGRP, rather I should take this and then I'll go and run. Copy paste this command to all the devices so I can do some bigger ping and bigger trace route. And then finally here. So that means if I go and check show IP route, we have one loopback at 44444. So I should get the loopback 4444 somewhere. So here you can see this 2222 and then here you can see 444. So if I ping 4444, okay, my ping is there. Now I want to do the extended ping. 444 is the destination. Hop count I will take, say for example, okay, 4 we can take. Datagram is okay, timeout is okay, extended I want to do. Source interface, leave it at this point of time. What I'm looking for is the record option and the verbose with that. So till 9 hop, although it is 4 or 5 hop away, we can go and check the reverse route we are looking for. Now you can see that where is your destination? This is your destination. Now if you go and check the diagram parallelly, so let me show you this diagram as well. In parallel, here you have the destination at what point? So you have 4444 and here you have, then this is dot 3, this is dot 4. So you can see your destination starting from here, then you have dot 4, so here, then you have 23003. See, from here you have 23, this interface, and then you have 12002, this interface. So basically we are talking about which interfaces? Basically we are talking about these interfaces, correct? And then finally you have 12.1. So that should be the response, correct? Response packet. Now if I do the trace route, and we haven't covered trace route at this point of time, but if I do the trace route for 44444 and you can see the output here. So to reach to 4444, how you're going, see, that's the difference. That's the big thing we have. So 12.1.1, here you can see 12.1.1.2, 23.0.0.3 and 34.0.0.3. So reaching here, coming back, it is showing you both the things, correct? Now if clearly you can check the trace route and the record option here, and I'm taking some more time here because this will be useful tool actually to do this. So here you can see that with a trace route we are going here, we are going here, and then we are going here. With the record option, you can see that when we are reaching there, this interface, this interface, this interface, let me correct it. So dot 1, so not this interface. Let me quickly erase and draw both the things. So with the record option, this interface, and this interface, correct? And then you are reaching to 444. Again from 444, how you're coming? This interface, this interface, this interface, means this is covering all the outgoing interface, incoming interface, correct? But with the trace route, outgoing interface, and that's the key, and that's the important information we have with the record option. So I hope you understand the power of ICMP as well, the power of ping as well, and you can utilize it for the troubleshooting. Next tool we have in our toolbox is the traceroute command. How traceroute is working is actually simple, that we know the destination and this testing is based on the destination. So what we are doing, that we are sending the UDP packet with invalid port to the destination. But I don't know that how many hops my destination is away. So for that reason, when I send my first packet, then I'll make TTL as 1. Obviously TTL1 means at the moment it will go and hit the first router, the TTL will got expire, and then I will get message called ICMP exceed time message. That is TEM, time exceed message. So what does it mean? It means that your first 3 packet, actually we are sending 3 packets. So your first 3 packets by default, they reach to first hop, your TTL got expired, and then you are ready to send the next packet, next 3 packets for next hop. So next time we are adding TTL plus 1, so the TTL become 2, and then we are sending the packet. Now suppose at this point of time in our lab also that I am 4 hop away. So again I will go and send the packets uh, because I am 4 hop away, correct? So again I will increase the TTL. Again I will get the message called ICMP time exceed. Next time I'll make my TTL as 4. So this time I have the destination with me. That means my UDP packet will go and reach to the destination. And how could I know that I have reached to the destination is with different type of code, because we are sending the packet to invalid port. So that means we'll get the message ICMP port unreachable, correct? So 2 type of messages we have. First of all, ICMP time to exceed, because I want to bypass that router, I want to add some more TTL and I want to proceed, correct? And at the moment I will go and reach to ICMP port unreachable, that means I reach my destination. And that's the way, actually that's very much hit and trial type of method, but that's the way we are reaching to the destination hop by hop. Now there are some terms, or there are some symbols that you will get. Say for example a star or asterisk, that is the probe timeout. A stands for administratively prohibited if you have any ACL or any other blocking. If you have Q stand for source quench, destination is busy. I stand for user interrupted test. Then U, port unreachability, H, host unreachability, N, network unreachable, P, protocol unreachable, timeout, and unknown packet type. Okay, so let's test this like we have done the ping test. So let me go and log into the lab and verify it. Although we have done the trace route, here you can see that I can go to next hop, next hop, next hop. Here you can see that I am sending 3, and again you can see that packets are in milliseconds. So 72 millisecond, 80 millisecond, and 72 millisecond. 3 packets we are sending for first hop. And here you can see the hops, the first destination, second, and third. At the moment you will go and reach to the destination, you'll get some other code, ICMP code. So let me show you that packet and detail. And if I do the trace route, so here you can see that what type of code messages we are getting, because we have 333. So total you can see how many packets we have sent, and that's why you have these many messages that you're getting here, and still we are getting. Let me go up because we are running EIGRP, so some EIGRP debugs may be coming up. All right, so yep. Let me scroll up. Let me do this thing and debug all, and will not get the debug. Let me scroll up. So here you can see that you have source and destination. This is the source, this is the destination, and you are sending the packet with the destination port. That is invalid, because once it will reach to that particular destination, it will get some invalid code message. So here you can see that type 11 code 0. We can go back to our notes and we can check type 11 code 0 in the ICMP lists. Here you can see type 11 code 0 time exceed, correct? And then we should have the unreachable code as well, that is the invalid port. Let me circle that, or let me spotlight this. So that will be 3 and 3. Type 3 code 3, that is port unreachable. So we are going to get from the destination 3 that's the code, and from the source, obviously whenever we are going to the next hop, that should be 11 time exceed. So let's go back to the lab that we have here, and we can go and check that in the code. So here you can see that you're sending the packet with the variable destination port. It is going to add 37 and then maybe 3839, etc. You can see 3839. You can see the ICMP code when you have the source and destination, and what code you are getting from the destination once you reach to the destination. So here you can see that we have this type 3 code 3, and that's true. That's the port invalid or port unreachable. Now this is not the only way then in Cisco devices that we can go and do the trace route. We have option that we can go and add the probe as well. So number of probes you want to add, then if you want to add the TTL, means from where you want to start and where you want to stop. If you just want to make this little bit small, so you can do like this. Even if you want, you can go and increase the probe. Here you can see probe 10, and then I just want to show you this. So TTL is to 222, for example. So now here you can see if you want to check the latency, if you have to certain destination, you can go and check this. This is actually the round trip delay that we have. Like that we can go and add. Now in trace route also we have the extended trace route. So likewise we have the extended IP. We can go and do that. So here you can see that we are getting the options in the same way that we have in the last or in the extended ping, but obviously because this is trace route, so some of the options are different. Port number if you want to add, otherwise default will be okay. And if you want to record, you can go and record up to maximum 9. I don't want 9, so for example 4 only, and you can go and do like this. Still this is not as much clean that we have with the extended ping, but yeah, we have option to do the extended trace route filtering, all sort of option in the Cisco devices as well. We have the management protocol for the network. That's the simple network management protocol, SNMP. Let's first of all understand the terminologies used in SNMP. Basically, we have three main or major component. We have SNMP manager. You can think this as a collector where it is getting the information from the SNMP agents. So you have agents, that's the network devices, and you have manager where all those information are getting collected with help of MIB. So third very important component, we have the SNMP management information base. Now what is happening? Now these MIBs are nothing but the information that is stored inside the agents, and managers, they are using get, that means to retrieve the information, and suppose if they want to change certain parameters, they can use set. So managers, they are using get and set methodology to get the information, or if they want to change anything, they can change. Now again, the communication channel we'll see that we have versions of SNMP. So for example, community based version, SNMP version 1, SNMP version 2C, and then we have something like authentication or user based SNMP methodology as well, that is the SNMP version 3. But yeah, we have different version as per different RFC standard, and these SNMP or the SNMP protocol in general, they are used to collect the information for the management purposes. So for example, what type of information? Say interface monitoring type of information or protocol monitoring type of information. Now one of the popular tool for SNMP at this point of time we have, so for example, third party SolarWind tool, where we are going to do the testing as well in the upcoming lab session. Uh, Most of the production network, they are using SolarWind, or there are various tools as well. Just they are using SNMP methodology, same methodology that you have manager, you have agent, and then MIB, and then they are collecting information at a common place again for the analysis purpose. Now here you can see that the SNMP get method, we have three type of get method, means we are getting the method, we are getting the information, we are getting the next variable information, or we are getting the information in the bulk as well. So three get methods inside get method we have. And finally we have SNMP notification as well. Now what is SNMP notification? This is again a type of information, and it is referred as a unsolicited asynchronous notification that can be generated as a trap or information. So in the configuration, I will show you that we can use the methods, the agents can use these methods to tell the manager about the various type of information. So in trap or maybe in inform, you have various type of information that you want to tell to the manager, and in the configuration I'll show you that what exactly trap look like. Now we have trap and we have inform. Most popular in these two is trap. That is less reliable as well. So what is happening actually, what's the core difference or basic difference between trap and inform is that trap is a message that the manager is getting that don't have any acknowledgement. On other hand, the inform, they have the acknowledgement as well. So that's the reason the trap is faster, or the trap methodology is faster than the inform method. But yeah, inform method is reliable because it has its acknowledgement as well. So we know the basics terminology used in SNMP. Let's stop here, and next section we are going to study about SNMP MIB and versions of SNMP. Let us understand Cisco MIB and versions of SNMP. Now this MIB is nothing but a database, and this MIB is in form of tree structure. Again, if you want to learn more about MIB, you can go and refer these RFC 1213, and for traps we have 1215. And even with respect to Cisco, if you want to again see the tree structure and the hierarchy, you can go and check Cisco MIB, and you'll get long list of MIB related to most of the things. So for example, the informations related to protocols, the information related to traps, the information related to flaps, information related to CPU, interface, monitoring, etc., etc. And again, major vendors, say for example, who is working on SNMP, SolarWind and others, they are using this MIB, and they have the SNMP manager where they can go and collect all this information that I'll show you in the uh, upcoming session, that how you can retrieve these informations, how you can query. So suppose if I have SNMP manager, I can send the query. That's nothing but the get method. I can send that get method, and once I do this get method, the responder, that is nothing but the agent, they will give me all the information that I query inside this string. Okay, now we have three versions. We have version 1, 2C, and version 3. 1 and 2, SNMP version 1 and 2C, they are very much community based. So obviously they are doing the community based authentication. The method of authentication is the community string. Again, in the lab section, we'll see that we have the community string. Even we can put some sort of ACL ACL as well for that if you want to filter out the uh, number of volume or number of requests we can put inside the ACL. That we'll see in the lab section. Then we have version 3, that's the secure model. We have version 3 is supporting, say for example, message integrity, authentication, and encryption. Now there is huge improvement with respect to version 1 versus 2C, and you see that still most of the organizations, they are using community based version 2C. Why? Because they can do bulk retrieval of data. That's obviously the tables and large quantity of information. Again, these are uh, belonging to the tables. Whenever we are talking about tables, they are belonging to the database system. So maybe MySQL or any type of databases that these managers, they are using behind the scene. So maybe they can use MySQL or any type of database, depending upon those company and their partnership with the database companies. All right, so version 2 can get a large volume of data with less amount of expense. Expense here means the memory, the round trip delay, etc. That's the power we have with respect to 2C versus SNMP version 1. And when we are talking about version 3, this is based on the security model for users or users belonging to group. Now, what is the difference? I have this slide for that. Here you can see that we have model, we have label, authentication, encryption, and what is going to happen. Now, version 1 and 2C, we know that they are community based, so that's why we have the community string for obviously authentication, but they are no auth, no priv, no auth, no priv, no authentication, no priv. Uh, Again, I told you that community is itself a type of a string, or you can think a password just to do the authentication, but it's not exact authentication like you have MD5 SHA that we used to learn inside various other protocol like IPsec and others. Okay, but still you can think that community is a password, or it's a authentication way of protection to do the authentication between the agent and the manager. So for inside V3 again, V3 just not only supporting the authentication and the encryption, but they have uh, no auth, no priv method as well. So you can do username. So uses a username match for the authentication. Then you have auth, no priv. Auth means authentication, no privacy. At that time you have the MD5, maybe SHA. At that time they will go and do the authentication. And finally it has auth and priv, where you are using both the MD5 and DIS56 as a data encryption. Okay, so these are the versions we have related to SNMP. Let us understand the configuration, and obviously we are going to do the configuration in lab. Now, when we are doing the SNMP configuration, we can go and give the SNMP contact location chassis ID. Then we can go and verify as well. So for example, show SNMP contact location and chassis. Now, when we are configuring version 1 and version 2, we know these are the community based versions. And what are the prerequisites then? How we can go and configure? So the prerequisite we have that we should follow these, at least these three things, that who is the manager, and we can put those managers in ACL, and what type of roles they have, like read only, read write, etc. Then if we want to cut down the SNMP MIB view or MIB view, just to protect to get too much information, Obviously, what is happening that you have agent, and suppose you have 4 or 5 different manager, or obviously different IPs, means you have different managers at different location to pull those information. So pull those MIB information related to network management. Now, if you put too much load on a network device, means all the time they are giving so much information to all the managers, there are chances that the CPU spike will be very high. So there may be issues related to CPU, maybe issues related to memory, maybe issues related to congestion. So unnecessarily do not burden your device with full MIB, and that's one of the thing that even the best practice, that we can cut down the MIB database and we can create views, and then that view access will be um, through, or that view access through the community string or through the community, or sometimes we are referring community as a password as well. Then we can have the read and write permission. So three things: define the manager with ACL or ACL, or maybe if you have only one or two manager, then simply you can go and give the manager IP. Define the view if it is required, if you are facing issues related to a spike, CPU, etc. And then we can go and give the read write permission to the community. We'll see that in the lab section, that how this configuration template look likes. Now you can see that's very easy: SNMP server, community string, view, read only, read write, then ACL number. If you want to shut this down means if you want to remove the SNMP, you can go and use no SNMP server community. Again, we can go and check show SNMP community. Now, if you want to give that notification message in terms of trap, so for that we can go and put these configuration here. Either we can go and use trap or inform. So here you can see the configuration is SNMP host ID, trap, inform, version 123, auth, no auth, priv, etc. All right. So in case of version 3, again, it belongs to user, or users belong to group, where we can have authentication and encryption. So we should go and define the group as well. That's why you can see here that we have SNMP server and group, and then group name version 1, 2, 3, auth, no auth, priv, that we have already discussed earlier, and notify and access list. Again, you can go and check with show SNMP group. So let me quickly log in to the lab devices, and let's perform the lab task related to SNMP. Here you can see the lab setup. So I have a switch, actually all these devices except this SNMP server. SNMP server is my local system where I have put the SNMP server. And then I have this host 3. This is nothing but a router. I have made this as a the display is like host, the laptop or a PC. These are connected with the Ethernet port with the router, where I'm using the Ethernet switching capability. Inside VLAN 2, I will go and show you the configuration for this switch one, that is again the router. Just for the simulation, I have made this as a switch. So let me quickly show you the configuration for switch one interface F1/1415, and then the IP addresses of these host, so host 3 and switch 1. Obviously this is going to be my SNMP server. So what I will do, that I will go and pull the information. Okay, so let me show you all those things. Obviously we have to do the configuration for SNMP as well. So here I have, you can see I don't have SNMP configuration at this point of time that I want to put. And with this host, if I go and check show IP interface brief, what IP it has. So here you can see that I have interface 1/15, and who is the gateway? Gateway is .2, and where is .2? So that we can go and check where is the gateway. Gateway is the WLAN 2 actually. So here you can see that do I have WLAN? Switch 1. I don't have VLAN that I want to make it. So how I can do this? Say VLAN database name, if I can give, or maybe we can give like this: VLAN 2 name just. All right. Let us perform the lab task. Here you can see in the lab that I have one SNMP server that is again I'm going to use as a manager. And then the switch one that you are seeing here in the diagram, that is actually router one that I'm going to use as a agent. And then from this host, I will go and generate the traffic. This host is also one router. I have made this to look like as a PC. Okay, so what we can do, first of all, let me show you the configuration for host 3 and switch 1, because anyways this SNMP server is my local system where I'm doing the recording for this session. So let's go and open the CLI. Here you can see this is actually the switch. So let me go and change the name. So this is the switch one I have, and if I can show you the gateway for all the PCs belonging to the VLAN 2, we can go and check show VLAN and then switch. Here you can see that I have VLAN 2 and these two interfaces, 1/14 and 1/15. They are belonging to the VLAN, that is VLAN 2, that you can see here 14 and 15. So the manager and the host, they are belonging to the access VLAN 2. Alright, so what we want to do here, I want to do the SNMP configuration for the switch. So I can go and do the SNMP configuration, say SNMP server, and then I can give the location, say for example EPC, then SNMP server, the chassis ID, and then SNMP server. We have the connection or something, contact. So here you can see contact is okay. And now you can go and check the show SNMP server or show SNMP contact or something. So these things we have seen. You can go and check this thing, contact, and then the chassis ID, etc., etc. What configuration we have done so far? Show run section SNMP. Now I have one template configuration. So here you can see some old configurations are also there. But here you can see that we have the template of configuration that I can copy and paste. Here in this configuration, you can see that the host, that my local system has this particular IP, and I'm using the community name is this RITNESH. Again, I'm going to create one ACL, and inside that ACL, whatever IPs that I have, I'm giving read write permission. Okay. So like that, we can go and do the configuration. Even you'll find in the configuration we have more a number of traps and what is there in the ACL. So I can go and show you this access list where I'm giving permit any, but we can have the list of the managers in the ACL. Okay, so here you can see this configuration look like very straightforward, and then we can go and verify it. Okay, so how we can do the verification? I have one SNMP manager engine installed in my system. I can do the SNMP walk. So I am inside this particular folder in my local system, in my Windows system, and then I can go and do the SNMP walk. Here you can see SNMP walk.exe. Then you can go and give the version. That version is 2, and then I can go and give the community and then the SNMP manager IP. So that is 192.168.56.1. And now here you can see on top that the new window is coming up where I want to use the port, the timeout, the SNMP version. Obviously, I should go and give the agent address. So my agent address is 192.168.56.2. That's the IP of the switch WLAN 2. I should go and give the community like this. Now here you can see this is the root OID. I can go and do the scan. Once I do the scan, you will see that it will go and download one text file that I can open and I can show you that. Now, important thing here is that when we are doing this NMP walk, we should not have blockage for port number 161. Alright, so I disable the firewall port in my local system. And now if I want to ping from here to my agent, that's again the switch we have in between. So you can see that I have reachability. So that means that I can go and do the walk. I should go and change the IP 6856.2 and then the string, that's the password. Scan. Now you can see the OID it's started scanning. And because we are using the root OID, although we have option that we can go and give the string as well. So here you can see that we have this output saved. Let me open this output. Let me open this. Now here you can see this polling, or you can say that this SNMP walk. You can see the OID and what it is doing. So we have the complete output related to interfaces. Let me scroll down. You can see the IP addresses. So we have interfaces, we have IP addresses, the status of the interface, but you can see that it's a long output we have, and that's the power we have with SNMP version 2, that it will go and take all those information that we have, although we have used the root MIB or OID to get this information, but it depends that what exact information you need. According to that, you can go and put the filters. All right, so this is the way that we can go and run the walk. We are going to do a quick revision about the configuration of various versions that we have. We have already studied that how we can go and configure the important version, that is version 2, and C stands for community. Here you can see that it's a straightforward. We can go to the global configuration mode. We can do SNMP community public. Again, it depends that what type of community is string I have, public, private, or if we have any type of restriction, we can go and use with certain ACL as well. So again, here you can see that you can go and give the host version 2C and host version 1 as well. If you want to limit the number of managers, you can go and give even the permission as well. For example, read only or read write, and then mapped with the ACL 4 where I have the group of the manager. Again, we can go and enable various type of trap. We have a long list of trap or notifications that we can go and enable. We can go and give the host in terms of DNS as well or URL as well. Now again, we have the use case related to version 3. We know that version 3 where we have the group or the users belonging to the group. We can have option if we want no authentication, no priv. That means that we want a user-based SNMP version 3 configuration. So here you can see that you have to go here and define the group. So SNMP server, group 1, version 3, no auth. And then we can go and give the user as a remote user part of group 1, and the remote uh, server is 10.12.8.4. Then SNMP server host, and there we have the informs version 3 with no auth. Again, the remote user config. So we can go and give the configuration like that. This is the case with no auth and no priv. Again, if we have case related to authentication with no priv, so again we can go and define the group with auth, and then auth user group remote version 3 auth MD5 password. Correct? Now again, if you have option or if you have use case that you want to give the priv security, so again we can go and define one group with the priv, and now I have the private user with group 3 with this remote location version 3, and again we have the authentication and the priv access. We know that the encryption that we are using is DACE 56 bits of encryption with DACE algorithm. Okay, so here you can see that it include everything, that it include auth and priv. You have the authentication, so here you can see auth MD5 password, and then you have the encryption as well, like priv access for this particular user, that is the private user. Okay, so this was the summary that what we have studied so far. In next section, we have to go and study about the syslog, and we have a small lab related to syslog. Over the network devices, we are getting the log messages. Now we have the buffer limit in the network devices. So what we can do, that we can redirect these log messages to the remote logging server. And again, we can use any industry standard remote log server. Now here, one important thing we have is that we have different type of log messages. So what different type of log messages we have here? You can see that they're starting from emergencies going to debugging, level 0 to 7. So these type of log messages we have, and it is up to us that what type of log messages we want to see over that remote logging server. To set up that, we have option. We can go and use logging, and then the server name where we want to send these log messages. We can go and do logging buffer as well, means how much you want to buffer in your local system, how much you want to redirect. If you want to redirect all the messages, it's fine. We can go and redirect all the messages to the remote login server. Now, once we do that, at that time they are using the syslog messages or syslog server. The communication channel is over UDP port number 514. So if in between we have any ACL or any firewall who is blocking this port, we should go and unblock it. Now, if you want to see that log message is in different timestamp format, then we have option that we can go and use service timestamp log datetime, service timestamp debug datetime. So these commands we have to set the log message in millisecond, and it will show you the time zone as well. Now again, some of the commands, if you want to go and check the logging history, you can go and set the label here. You can see uh, by default, it is showing warning, error, critical alert, and the emergency. So here you can see that emergency alert, critical warning, and errors. So from 0 to 5, it will show. If you want, you can go and set the history label. Even we can go and set the logging history size as well. Okay, so let me quickly log into the system, and in that system, let me show you that how our lab look likes. In my local system, I install DNS, and here you can see that you have your server, you have your host, and you have your switch as well. So what I have done to examine the syslog message over the server, I have installed this TFTP, Jonin TFTP server, and inside that you can see that you have syslog server option. So if you go and click, at the moment we don't have any log message, so it is not showing anything. I can go here and I can set that. So I can go to the switch and I can give okay logging, and this logging I want to the server, so I should go and give the server IP as well. So let me show you these things parallelly, and here you can see that you have your syslog server. So I can go here and I can give logging 192.168.56.1, and then let's see that what other options we have. So if I can do logging buffer, and here you can see that in the buffer also we can go and give the label of the severity starting from 0 to 7. So I can go and give, say for example, up to 5, and here you can see this 5 is warning. Apart from that, if you go and see that what other options we have multiple options with logging, and we can see logging and then question mark. Here you can see that you have options. You can give the address for the remote login server. Buffer, you can go and set the logging buffer. Then exception facility, filter history. Here you can see that you have logging history, host, monitor, etc. So we have multiple options here. If I want to set the trap, and then again if I go and set the informational logging, and then here you can see that you have history. So logging history, and then here I can go and see set the size, history size say 200, and then finally logging history, and the uh, message is say for example informational. Alright, so once we have this log configured, we can go and check the logging, that what configuration that we have put. Here you can see these are the things that we have put. Now if we want to see this in the syslog server, so here you can see it has been started and it is stored at this point 192.168.56.1, and we should get that information over here. So let me go and set this syslog. So if I go to interface 1/5, and if I do shutdown, so we should see here the syslog messages. Here you can see that now it is showing over the screen, but I want to send this, and we should have the communication between my system and the logging server, which is not at this point of time. So let me see, 1/15 is down. So what I can do here, that I should bring up that interface 15 no shutdown. They should be up, otherwise there is no communication in between my log server and my local system. Alright, so we can go and check the log configuration. First of all, it should be correct, and if I try to ping, it's not reachable. If I go to the system and if I try to ping from there to my local switch, let's see if I'm able to ping. Yep. So in between, if we have any firewall rule which is blocking the port number, it will not work. We should check, we should disable that firewall or allow that port at least. All right. So meanwhile, we can go and check the logging message here. And in the local system, you can see that we are getting some sort of messages. So what it is telling, let us see in the local system, logging to this audit disable, link is up, filter is disabled, and here in the local system, we can see that yeah, we are getting the log messages. We should get this in the remote server as well. In my local system, I have disabled the firewall rule. Now you can see that from a switch, I'm able to ping to the TFTP server. Now let's try to generate the log messages. So I can go here to the interface 1/4, and if I do the shutdown for that interface, so at the moment it generates the log. Here you can see in the remote logging server, we are getting the log messages. Now if I go and do the no shutdown, again you will go and see that the log messages will come to the remote logging server. So this is the way that we can go and check the log messages. Next important topic, we have net flow and flexible net flow. Now, as the IT evolve and as we need to analyze more and more data with respect to security analysis, with respect to troubleshooting, with respect to network analysis, we need to learn and understand the flow or the record. So for that reason, we have NetFlow. And again, if you see the versions of NetFlow, you'll find that we have NetFlow from version 1 to 9. 5 is most important and actually most popular. Uh, Now, what's the difference? You will see the main difference here is that in version 1, we have less capability that we can analyze less number of field in the flow or the traffic flow. Rather than if you go and see, say for example, version 9, where you have much capability to analyze the flow, means we have much more option, much more capability to see inside the flow, what type of headers and fields we have. We'll see that how many fields that we can analyze inside a flow in different versions. Now here you can see that, say for example, you have source and you may have destination, and then you are using NetFlow. So what are the things that you can check? Uh, Again, we'll see that we have multiple options to verify, but at least we can go and check the IP addresses, source and destination, the port numbers, source and destination port, protocol, packet send, packet receive, if you have any tagging related to source and destination, and then various TCP flag. Now this information is huge because this is going to answer us 5 different Ws. So who is sending means what is the source and destination IP, what's the port, where it is sending, what is the destination's IP, so who and where, again related to the addresses, what they are sending, so which application they are using, what are the port numbers they have, so who, where, what, how, again you can see that how many packets or bytes they're sending. So here you can see the packet counter, the byte counter, and when they are sending, that's the time stamp, at what time this transaction happened. So again, we are getting 5 W answer: who, where, what, how, and when. And that's important to do the analysis with respect to either security or network analysis. Now again, if you want to correlate this with the phone book, again you will get to know that net flow equal to the flow. Inside that flow, who, what, where, when, all these informations we are getting with respect to flow. Now the next important question is that which version should we use? Again, we have version 1 up to 9, and 5 is most popular. So here you can see that, for example, in the popular version, that's version 5, what are the content and again the description. So we can go and check the addresses, we can check the next hop, the SNMP index, packet flow, total number of L3 byte, system uptime, TCP UDP port, if you have any flag. Again, you can see these key information. Again, the argue is there. So still the version 5 is not giving us each and everything inside the flow. If I want to see more and more number of fields, then what version we should use? So here you can see in this chart that version 5 is giving only 18 exportable fields. There are some limitation as well, that they are fixed with IPv4, they have fixed level length, single flow cache. Okay, so there are advantage with version 5, but there are certain disadvantages as well with version 5. Then we have version 9. Now version 9 is template based, it is much more robust, it can have the MPLS and BGP supported fields as well. It is going to support 104 fields. So you can see 18 versus 104 fields. But again, it has limitations that IPv6 flows are exported inside IPv4. Fixed length field use more memory, slow performance, single flow cache. So you can see, although you have ease of use, but on other side, it is consuming much more resources. So if it is easy to use, it is giving less number of fields. If you are using more much robust uh, options, then at the rate of high memory and slow performance, etc. Okay. Again, we have the flexible net flow, that is again using version 9. So you can think that version 9.1 or 9.2, that's a flexible net flow. This supports flow monitor, supports selectable key fields for IPv6, supports NBAR. Again, this NBAR network-based application recognition protocol, and uh, even the Cisco who has made this NBAR, uh, just to analyze the application, and I have given so much theory related to NBAR in my SD-WAN curriculum, because if it is a Cisco device, so for example ISR or any type of Cisco device, at that time uh, NBAR 2 can recognize the metadata of application, and they can recognize up to 1400 or 1400 plus applications, rather than the other vendors. Also, they are claiming that they can recognize more and more. But again, uh, we can recognize the application with the NVAR, and in this NetFlow, these are supported. In this session, we are going to learn about the terminology, and we are going to learn that how we can collect all these pieces, and then we can go and configure the NetFlow as well. So let's start. First of all, flow. We know that we are going to analyze the traffic flow. So whenever I have a flow, obviously that particular traffic flow or flow having various type of key and non-key. So what does it mean by key and non-key? We will go and understand that. But at this point of time, we can think that there may be some mandatory things. There may be some optional things that we want to collect or measure. Correct? So according to that, we can categorize these as a key and non-key, that we'll see. Starting with flow, they have the key field like source, IP, destination, IP, port number, protocol, etc. Then we have the flow record. Again, the record, you can think as a office and file system. In a file, you're putting all the records of all the customer or clients. So like that, you may have a record what you want to collect. And this record may be key values, this record may be non-key values, or mix of both. Correct? So generally it is key plus non-key value that is there in the record. Then we have flow collector, where you want to collect this flow. What is your destination server, that we can go and give the collector IP. Template based configuration, nowadays we are using, even if you go and check the SD-WAN configuration, inside SD-WAN we have, nowadays we have option for NetFlow plus the SD-WAN own cFlow template. So both the things are there. There we need to create the template as well. Template is again the format where you are putting various parameters. Then the exporter is nothing but you are going to collect the information, and you have the exporter where you want to analyze all these things. Finally, the net flow generator, that is nothing but who is going to generate the flow. That's the devices to whom we want to analyze the flow. Okay. Now again, all these terms, when we are going to do the configuration, at least when we'll see the configuration, we'll find that where we are going to use all these configuration options. The traditional NetFlow configuration is very easy and straightforward. What you have to do that you go and first of all define the export version, then who is your destination and the port number. So destination IP and the port number. This IP is your NetFlow collector IP, maybe any type of server. Which interface you want to enable? I can go and use IP flow ingress. I can go and use IP flow egress. So both options are there. Let me quickly log into the device and let me show you that how you can go and do these configurations. So here I am. I can go to the flow export say version, and here you can see that we have 1, 5 and 9. I can go and use 5. Then IP flow export destination, I can go and give 192.168 say 56.1. That's my server, and then I can go and give the port number say 2055. Then I can go and check the interfaces. So I have interface say for example 15, and I can go and use IP flow, and here you can see that we have option. First of all, I should make this as IP interface, because by default it was the L2 interface. And then I can go and use IP flow ingress. If I want, I can use IP flow egress as well. We can go and check the configuration, and if you want to filter, you can use the flow option. So here you can see that it's very easy and straightforward that you can go and do the configuration for the traditional NetFlow. Now the next very important thing we have is the flexible NetFlow. Most of the places you will see that we are using the flexible NetFlow, and the key term there is that you should know that what is your key item versus your non-key item. So we have the mandatory and optional things. Anything that will start with match option, that will be the key field. So TOS, type of service, protocol, source address, destination address, port number, etc. Then anything that is collecting, that will start with the collect option, that will be the non-key item. Correct? So TCP flag, byte long, packet long, absolute first, etc. Again, this also if you want to do the configuration. So now you can go and give IP flow and what version you want to do here. So IP flow export version, say for example 9, and then we can go and use flow, and let's do the configuration for this as well. Say for example flow record, and we are inside the sampler, say match, and so here we can see that with this particular version, and here you can see the version of the image, the 12.4, flexible NetFlow is not supported. So what we'll do, that we'll check this configuration in the other version where we have the FNF support. So here you can see that you can go and create the flow record. Again, we have learned that NBAR2 is supported inside version 9, and whenever we have this network-based application recognition software or the feature, nowadays Cisco has launched the NBAR VM as well, that you can check inside SD-WAN software module inside Cisco software downloads. So now we have this feature to analyze the application, how actually it is analyzing the application. So here you can see that whenever the traffic will go and hit the router or the device where you have enabled the NVAR capability, So suppose someone is surfing the website and then the packet will go and hit this device and N bar is enabled as per this record. So here you can see that flow record has IPv4 source address, destination address. The key thing here is that they are matching the application name as well. So once they have the application matching criteria enabled inside the net flow, then they can go and hit and match that application. And in the flow, certainly you can go and see that you have the source IP, destination IP, everything, and then you have the application matching name as well. Okay, so that's the power we have with the integration of NetFlow with flexible NetFlow with NBAR. Okay, so NBAR is giving us much more visibility inside the flow of that particular traffic. All right, so how we can go and configure here, you can see that you can go and create the exporter, who is your destination where you want to export. Then you can match the key and non-key items like match and collect keyword. Then inside the monitor, you can call point 1 and point 2, that is the flow exporter and flow record. And then obviously you should go and apply over the interface. Okay, so these are the steps that we can go and use to enable the net flow. Now there are some use cases. The point here is that at what particular point and how much match statement we need, how much collect statement we need, and that depends upon what exactly we want to analyze. So for example, in client and server communication, here you can see that for the client server state, you can go and match the DHCP protocol, addresses, source port, destination port, and in the non-key item, the interface output, bytes, packets, plus the application name. So here the application name, we have the account on resolution. Again, this N bar, it is showing the capability of N bar, that is giving you the visibility for the application to check the application flow as well. Now we have complete replacement for IP accounting keyword, where you can go and check which IPs are using how much volume. So here you can see that we can go and use this IPv4 DHCP bytes long. So that's the counter bytes long, counter packet long, and then they collect application name. So we have application visibility, and then we have the IP accounting, and then we have the DHCP matching as well. If you want to analyze the QoS queue hierarchy for QoS, so this is the QoS configuration. We already know about QoS. We have learned about that. So you have the parent and you have the child policies. Inside child, you have the class map like this, and inside class map, you are matching certain DHCP. Now, how inside the flow we can match it? So again, in the optional field, we have an option that we can go and collect the policy and QoS policy, QoS queue and drops. Again, this is just for the reference that how the protocols fields are getting matched with which type of FNF statement. So we can go and collect the application called SNMP, server, sender, POP, NNTP, SIP applications, HTTP applications. So we have long list of application matching criteria that we can go and check inside the flow. Now, how it is working behind the scene, here you can see that in any of the flow, they will go and extract the URL, the agent, the application refer, the application HTTP host. That's the capability, and that's the visibility we have with respect to NBAR. And finally, we have one uh, example here that you want to have this record option. So here you can see this flow record, and in that record what you want to match. So you want to match the data link MAC, the destination data link MAC, VLAN, TTL toss, protocol, source address, destination address, and then finally you have the optional, that's the key and non-key option as well. Those things you can go and match. Now let's see that how we can go and do the configuration for flexible NetFlow. I'm running 15.0. So first of all, I can go and give the exporter version, and then we can go and create the flow, and then we have this exporter. So let's do that. Say flow exporter, my exporter, and then I can go and give the destination, that is my local server as a destination. Then we should go and create the flow record. So for that we have flow record, say my record, and then I can go and match various parameters. So what is the destination address, then match. These are the key values that we are matching here. Source address. Again, you can see that with match option, what are the things we have. So we have the option to match the application as well for the N bar, and I can go and use the match and then the application name, and we can leave it. So system will automatically understand that which application is going, and it will go and match. Again, you can see that inside the match you have application, data link, flow, interfaces, IPv4, IPv6 routing, and the transport as well. Say routing destination. You can see that we can go and match the AS and the traffic index as well for the BGP. So we have these robust options related to match. Then we can go and use the collect. Inside collect, we can go and use the counter for byte, counter for packets. Again, you can see with the collect option, we can go and collect the application and then the name. Now flow record field is already present. So already we have given this field in the key. So it's not required to give in the non-key as that we have already defined in the key. But you can see that we have options related to uh, non-key item as well. Some of the options are there in key as well. If you define in the key that has a higher preference, that will not go and take in the non-key. Alright, so once we define the flow record, then we can go and create the monitor, and inside monitor we can call all these things that we have created earlier. Means we can go and call the exporter, that is my exporter. I can go and call the record, that is my record, and then finally you have to go and apply this monitor over the interface. So I can go to my interface, and then I can go and use this monitor word, that's a my monitor, in the input direction, and it is taking a while because we have enabled the applications as well. Whenever you are enabling the N bar, that's indirectly the application, it will go and take some time to apply it. Once it is done, then we'll get the line. So these are the things that we should go and check and enable. So define the exporter, define the record, call inside the monitor, and then apply it. I can go to the output as well, and then we can go and check show flow monitor. If you know what is your monitor name, you can go and give the monitor name. Okay. Apart from that, we can go and verify the flow interface. If I know the interface name, I can go and check. Then we have the flow record. If you have multiple records, you can go and select, and you can selectively go and check this. Okay, so this is the way that we can go and enable the flexible net flow. Next important topic we have that capture the packet at the level of data plane. For that, we are using the popular technique, that is switch port analyzer. This is nothing but a technique that we can mirror the port, or we can send one copy of the traffic that is going via the port to certain destination. So here in the diagram, you can see that we have source for the span, means the traffic is coming, and that traffic we want to copy and we want to send to certain destination. So for that, you have to define the source, and then you have to define the destination. Now at the destination end, we can use again the popular tool such as Wireshark to analyze the traffic that will go and verify in our lab section. Now adding span in our tool belt, we have other option with a span as well. Suppose we want to do, or we want to take the copy in case of remote, or we want to have the capture for the remote packet. and that remote packet is layer 2 extended. So in that case, we can go and use the remote span or remote switchport analyzer. Again, you can see that same thing, that you have the source, but you have the destination and you are extending over the layer 2 domain. Then again, at the destination end, you have the sniffing tool where you can go and analyze the packet. So we have option related to a span, related to R span as well. Now here you can see the configuration that is quite straightforward. And again, we are going to have this configuration for local span. So you have to go and define the monitor session. What interface is your source? What interface is your destination? And that's it. Then you can open the sniffer and you can check the packets that is going through. Now, in case of remote span, you have to go and define the VLAN for remote span. And again, you have two configuration. You have configuration related to source, then you have configuration related to destination. So at the level of R span source, you have to go and again enable the monitor session 1 source, monitor session 1 destination. Then at the destination end, again you have to define the source and the destination. Now in some of the switch platform, you have different type of configuration. In some of the switch platform, you have different type of configuration, but obviously the end goal is the same. The last flavor we have is the encapsulated remote span. So here you can see the difference between R span and ER span is that one span section you are extending over layer 2 and other, that is the ER span, you are extending over layer 3 domain. Correct? So in this case, so for example, I'm using GRE as an encapsulation. Again, I have the ER span source and ER span destination, but these packets that I want to analyze, it is expanded over the GRE session. As we discussed earlier that for ER span, we are encapsulating the traffic over source and destination IP with the ER span. So here we can see the configuration for router 1, where we have to go and start the monitor session, type ER span. We should define the source interface and the destination addresses. From the other side, where I have the destination, where I have the Wireshark, at that side of router, we should go and give ER span destination, the destination interface, and then the source, ER span ID, and the IP address. Okay, so this way we can go and capture and then analyze the packets that is coming from the source we are sending to the destination where we have the sniffer, and there we can analyze the packet. Now in this lab, what I want to show you is that how we can go and do the configuration for the span. So one of the interface that we want to create the mirror or the copy of, that we'll go and send those copies to the server. So for example, let me show my diagram. Let me share my diagram. So here you can see that I have one switch and then I have one host connected. What I will do that this particular interface, so let me show you the interface 1/15. This will be the source of the traffic, and then I will send this to the 1/14. That will become the destination for the traffic. So let me quickly open the CLI. Meanwhile, you can see the configuration is very straightforward. For switch, we have VLAN configured, and then for the host, that is also a router, but we are treating this as a host. And here you can see the IP and the configuration as well. Now, if I ping from here to the switch, that is 192.168.56.2, so you can see the reachability is there. Even I can go to the switch, and if I enable the line VTY, say login local, so we can go and check the TCP packets as well if you want. And then I should go and give, say, username admin password, admin, say enable password is also admin. So not only that we can go and test the ping packets or ICMP packets, but we can go and check the telnet packets as well. Now, in the same line, if you're at the line VTY level, and if you want to check the SSH traffic, so you can go here and you can do input output as a SSH, for example, and then you should have some IP domain name configured, and then you have to generate the crypto key and say 1024. So once I have the domain, once I have the key, once I have the transport input configured, then I can go and give the version as to. So I can go and verify the SSH as well, correct? So let's go here to switch number 1 and configure this monitor. Say monitor session 1, what is your source? Source interface is fast Ethernet 1/15. And likewise, we can go and give monitor session 1. The destination interface is fast Ethernet 1/4, 14, where you have connected the sniffer. So here you can see the configuration. Again, we have seen this that with different platform your configuration may vary, but the concept is same. You are mirroring from one place and you are sending to the other place. Now here you can see I have my Wireshark, and I can go and start my capture. So continue without saving. Some other traffic capturing has been started. Alright, so let's go here and first of all, let's do the ping for some bigger number. And then I can go here and I can check show monitor session 1. You can see this is the configuration. Now if I go to the Wireshark, here you can see this is at the server end as per our diagram. Here you can see that here we are sending the span session, and yeah, we are getting the packets. I can go and stop this. Now you're getting this ICMP request and response. If you want to filter it, you can go and filter and you can analyze this. There's no problem on that. Now let's try to get some packets related to telnet and SSH. So still this ping is going on. I should go and stop this. So let me stop this sequence. And then if I do SSH 56.2, and let me go here to the Wireshark. Here you can see that we have the packets for SSH, and yeah, we are able to capture. You can see the encryption and all those things, correct? So likewise, we can go and analyze all type of packets. Right, so we are inside switch number 2, and here you can see your SSH and packet transmission is happening. All right, so this is the way that we can go and enable the span, and then we can verify it as well. Next important topic, we have Cisco IP SLA. Now, Cisco IP SLA is a mechanism in the existing WAN or in the existing network that is giving us the capability that dynamically we can track certain services, certain IPs, and according to that, dynamically again, it can change the path. So suppose if your primary link is down, then you can go via the secondary link, or there is other option as well related to loss, jitter, latency, etc. So let's try to understand this IP SLA workflow, how it is working. We're going to understand about IP SLA, its operation, and then obviously we'll do the configuration and we'll verify as well in the lab. Now, what features that IP SLA provide us? Here you can see that with help of IP SLA, we can go and understand and collect the parameters related to loss, latency, jitter, packet sequencing, path per hop, how it is going, and the connectivity. And according to these parameters, we can go and change it dynamically, correct? So how it look like, how we will go and configure it. We should go and enable the IP SLA. So for example, IP SLA1, I want to check this particular destination. So what I can do that, so for example, I can send uh, the ICMP echo packets just to check that this destination is there or not. And suppose if I have multi-path, so if one path is down, automatically you will go and then because one path is already down, you can go via the second path. That's the overall idea behind this. So this frequency 5, that is the overall rate that we are sending the echo packets to the destination, that is 1111 in this case. We have started this IP SLA and it is a start now, and maybe we can give forever. So life forever is started now. And finally, we have to glue this with the tracking. So again, over the configuration mode, we'll go and enable the track 1 for IP SLA 1 for reachability. So what this track will do, it will start tracking this particular destination with the ICMP echo packet. Now how it is working behind the scene, again we'll see in the lab that for IP route, with IP route actually, I have two IP route statement. We know that by default IP route has a higher AD value with respect to any other protocol, and then you can give some bigger AD value, say for example 30. So the best one is the first line. It will go and hit the first line, so this will be the primary, and then you have enable the track on this. So primary path with tracking, that is ICMP echo of frequency of 5. That means if this track is down, that means if destination is down, obviously you'll get this track is down, you will start going via the other link, correct? Now once you do this configuration, then we have the verification command. We can go and check show IP SLA application, SLA configuration, history, and stats. So let me quickly show you the lab setup. So here you can see that we have the lab setup, and in this lab, say for example, this is my source and 111 over R1 is the destination. You can see that I can reach to R1, loop back via R2, and then I can go and reach via R3. So what configuration I have done, obviously we have the IP assignment to all the interfaces, etc. Let me quickly go and open the putty. So I just wanted to show you here that what configuration I have for router number 1. So for example, at the moment the IPSL is not started, and you can see that we have the IP route command, and we should go and check this R4 because R4 is the source generator. So I can go here and I can show you this. Let me quickly show you this IP route configuration. At the moment it is 3040, so this is the preferred and this is the backup. Uh, Again, it depends upon what type of IP route statements you have. So what does it mean at this point of time with this statement is that 34.3. So this path, because you can see the IP assignment here, this is the IP, and then the IPs over these interfaces are of the range of say 24.0/24, and here the IP address is 10.1.34.0/24. So these are the IPs we are using. Router 2 means .2, router 4 means .4, like that we have the IP convention. Alright, so now here you can see clearly that with this rule, if I do the trace route for the destination, obviously it will go via R3. And now if I go and change this, say for example, this is statement to 50, and if you check this now, so that means this is the lower, the traffic will go via this direction. Okay, and that's the case. What I want this traffic should go via this direction, and we should go and track this with IPSLA. So I can go here and I can enable, say, IPSLA 1, and then I can set the frequency and other stuff. So let's see that what are the other things that we can go and set here. So now you can see that once you go and enable the IPSLA, you have this ICMP echo. What is your destination? You want to check this, and to send the packets, you can go and use the frequency, so for example of 5, and if you have any timeout, you can go and use the timeout 1000. So what does it mean? That within 1 second, so its default is 5000. 5000 millisecond means 5 seconds, so frequency is 5 means per second you are sending one ICMP echo packet. Great. So once we have this, we should go and start this. So here you can see that IPSLA scheduling, and a start time is now, and then the lifetime is forever. Correct. So once we have all the configuration related to IPSLA, we should go and enable the track as well. So what is that? Track, say 1, and then what you want to track, say IPSLA 1 reachability. Correct. Now since we have all this configuration, we should go and apply this track to the IP route statement. So what I can do here, first of all, let me delete this, otherwise you will find multiple entries. Now I can go here and then I can give track as 1. Now the track has been glued, and here you can see this track is glued with the IP SLA. Even you can go and check the route. So you have 2 routes now. One is the primary, one is the secondary, obviously, with the tracking. So now if I go and check show IP track, or let's try to check show track 1, and here you can see this track is up, it is working with a static IP routing. Now what we can do here, that we can go and shut down the interface, any of the interface that will not allow us to reach to this destination. So for example, E1/0 over R2. So I can go here, interface E1/0, I can do shutdown, and then you can go and check the output here on 4. So now here you can see this is track is down because in this direction we have the track. And now if you go and check show IP route, so you will find that the static route entry, so you have seen both. Now it is via 34.3, and the track is also up. So this is the way that we can go and verify the IPSLA. Let's start section 6, that is automation. We are going to learn about Python, JSON, Yang, a few of the API and the RESTconf, netconf. Then 6.6, we can see that we have the EEM script. And finally, we have to know about Chef, Puppet, Ansible, Salt Stack. Okay, so let's start with basics of Python, and then we can proceed according to the content that we have here. 6.1, the basics of Python. Now, Python is one of the languages that you'll find that each and every department, either it's a IT department or non-IT department, it is using. It is heavily used inside machine language, artificial intelligence, and so many different places. Why Python is this much popular? The importance of Python and why it is popular is because this is, for example, free source, portable. It's very easy to learn. Actually, not that very easy, but it's easy to learn, and it's object oriented and functional. Okay, so overall thing is that it's easy to learn and easy to run as well. It's very lightweight, and you can run it very easily. Now, when we are talking about Python, that means that uh, we are going to use the skills of programming inside the networking. As a network engineer, that's the use case we have. So that means my network devices, the modern network devices with modern operating system, they are understanding the script, they are understanding the Python language. So we can write the code like we used to write in terms of C, C++, Java, any other object-oriented program. We can go right and then we can send the instruction in terms of programming. Now, one very important thing here is that why we have programming. Although the devices they can understand CLI and then GUI and then application programming. Why? The answer is this: that if you see the evolution of the network device configuration, you'll find that CLI is good and stable. And again, there are so many different forms inside CLI as well. So, for example, we can do some sort of scripting. So, for example, in Cisco routers, we can go and write TCL script. In other vendors, they are supporting some other interpreter level languages. Likewise, in Cisco routers, we can go and write some EEM script that will come by the end of this particular automation section. So things are there, but it's a small or restricted. Uh, it's not that broader that Python is. So you can learn the Python and you can apply to any of the network devices, irrespective of, say, for example, load balancers or the compute devices or firewalling or security devices or router switches, etc. Although here you can see that there is one con: runs lower than lower level languages. Lower level languages are basically in hex code, or they are very near to the machine. So obviously the compilation will be faster and then execution will be faster. There are other programs as well if we compare to Python, like TCL, Visual Basic. TCL is natively supported in Cisco devices. JavaScript, Perl, PHP, Ruby, C++, Java. But Python is more powerful because it has so many attributes or feature. Obviously, other languages also have, but they have the restriction. Someone is hard to learn, someone is hard to scale, someone is hard to compile. Uh, so overall, you'll find that Python is easy, or at least easier than the other program to use. Now, whenever we are writing the code in Python, uh, the extension is .py, so you can save the file as .py. And then we have so many different environment where you can write and execute. So that's why we have this IDE, integrated development environment. And I have one IDE. I will show you that how you can go at least at which place you can go and install the software. So here you can see that I have Python 3.8, and I'll come back to this particular display. Let me go through few of the slides. So for example, IDE is integrated development environment where you can go and write the code and it will get executed. For more information, you can go and check the wiki. Now, how to launch a program, a Python program? So you have multiple ways. You can go and use directly from the C drive. You can go and uh, do dot slash and myprogram.py. It will get executed, or you can double click. You can go to the IDE. We are going to use IDE in this particular section, and we have other example as well related to, say for example, inside Nexus OS. You can go and simply enable the Python, or maybe if you want, if you have any automation engine, that automation engine you can go and run the Python program in the same network that you have the network devices. So from there also you can go and execute. Uh, you can go and run the program and you can get the result. Those examples we have in the upcoming session. Let us continue. So how we are going to compile the program and how it is going to run. Here you can see that we have the source file called .py. So any program that you have created, you can save as .py. Then it will convert to the bytecode, and that's the reason that the execution is faster. And then it will go and compiled, actually not compiled, but then it go and run to the PVM. That's the Python virtual machine. And then as compared to other program, the execution will be faster, the runtime will be faster. Why? Because of this bytecode conversion. Okay. So now we have the installation step. I have one link here. You can see on your screen that you can go to python.org. From there, you can go and select your operating system. According to that, you can go and install the Python. Now, I have installed in my Windows machine, and I have installed 3.8.3. With that particular installation, at the moment you install, you'll get the IDE. So I have IDE plus I have the Python compiler as well. This is something you can think as inline compiler. So here I can go and say assign some variables. Say for example, A is equal to 2, B equal to 8, and then C equals. So C can go and carry the multiplication of A and say B, and then I can go and I can print C. So here you will see that it's something like bytecode compilation, and it's a interpreter based. It's very fast because everything is interpreting line by line, and behind the scene it is converting into the bytecode, and it is giving the output. Okay. Now what type of data variables, what are the assignments and all we can do in Python? So for example, uh, we can go and create the program.py file. So let me quickly go and show the object models, that whatever objects we can create. So here you can see the list of the objects. We can go and assign the numbers, string, list, dictionaries, tuples, files, set, and other types like booleans and none. So these are the built-in data objects that we can assign to certain variable, and then we can play around with that variable and we can get the desired result. So what are the things we need? We have the building block, that's the object, and then you need some sort of program or algorithm. So you have to fit these objects inside the program as per your desired output. Again, then you have the number, say integer normal, integer long, floating point, complex, that you can have a reference here. So next, what I want to show you here, that I want to show you one program, and let's try to understand that how this program will execute and then how we'll go and get the result related to this particular program. This is one of the program related to swapping of a number. So here you can see that X assigned 5, Y is 10. If you want to write some comment, you can use this hash and then you can give the comment. Anything that is commented that is not used, but when you go and see the program, you'll understand why, what's the meaning of X and Y and what the steps you are doing in the programming or algorithm. So that will be as a comment. So for example here, create a temporary variable. So I'm storing X inside temp and then X equal to Y and then Y equal to temp. Actually, this is the logic. Okay. Now here you can see these are the objects, these are the integers, and this is the logic. And then you can go and you have the printf function, like you can see what will be your output. So what will be your input algorithm and then what will be your output. So output will be these print, and again once you print, X will become 10 and Y will become 5. That's the swap function. So let's do one thing. Let's try to execute this program. I'll go and give X equal to 5, and then I can go and give comment value of X, then value of Y, and then I'll go and give Y equal to 200. I can give any number. Now what we can do, that we want to create a temp to hold the value, and now this temp equal to X, and then X become Y. So temp become X, X become Y, and then Y become temp, that is Y become 5 and X become 200. Correct. Now here I can go and print say X like this also, and then I can go and print Y as well. So here you can see that print X and Y. X initially was 5 and Y was 200. So this is the swap function. The actual algorithm is working here. Again, if you want to print in certain format, you can go and do the print, say for example as per our example. So here you can see bottom as well. Say for example print the value of Y after swapping, and then you can go and use the parenthesis, just the programming type of world we have, and then we can go and use format Y, and then we can close it. So the value of Y after swapping become 5, and I can go and put X here, and then the value of X is 200. So here you can see X was 5, now it become 200, and again it's just a printf function. We are getting in a nice looking output. All right, so there is lot many things inside Python that uh, you can go and learn. Basically, as a network engineers, we are focused on how we can do the automation for the networking devices. So what we are going to do, that in coming next two videos, you'll find that how you can go and run over NX OS, and you can put some sort of NX API or some sort of feature you can go and enable over NX OS. Once you enable, how you can verify as well. So NX OS is there, and then I have the automation engine connected with this in the same network. So from there, from that automation engine, I'll go and run this script for my hostname inventory, that is NX OS or NX operating system. All right, so let's stop here. In this example, we'll see that how from the Python program, I can log into the Nexus, say for example, Nexus 1 device. I can go to conf t, and then I can enable the feature, say feature NX API. Okay, so let me go to the empty putty that I have. Here you can see the program. user bin environment Python 2, and then you can see the comments as well in the blue color. So this comment is for SSH. Then pause the script. A list of the host. Suppose in this case we have only one host. Then what is the login credential for NXOS? So for example, username and password Ansible. Create a new SSH connection. Automatically add SSH host key for each host we wish to connect to. So this will be the output once you log into the once I run this program, then this print output will come. Create a shell session for multiple commands. So say with this connection.connect host 22 is the port for SSH, username password, look for keys false, allow agent false, remote cell, connection invoke cell. So I'm going to create the cell connection for multiple sessions, and then you can see the output here is remote cell receive. That's okay, print the output. So it will print the output that is host. Then what type of commands that I want to run here? So first of all, send the command conft. So I'm going to run the command conft /n is the new line. Sleep for 1 second. Then the output will get the output like this from the remote cell. Then the second command I'm going to run is the enable feature NX API, that is a feature NX API. That will be the second command. Again, it will print the output for us once we run this Python script. Exit the configuration mode, then you can say end, exit, and then print the output. After that, close the SSH session to this particular host. We can reuse all these things, so no worries. What I can do, I can do here, press escape colon Q for quit, because what I want to do here, I want to run this program. You can see Python enable feature.cli. The print output you can see NXOS, then all these banner. What it is doing, say these are the outputs in the program. Conft, you can see the output, then the feature NX API output. That means now this particular device, if I go and log to this particular device, and if I see show feature, so for example, I want what are the features have been enabled. So enable, now you can see NX API has been enabled. And if I go and check, say for example, so NX API output, we can see the output for that. So NX API is enabled. It can be listen on these particular ports. Then even I can go and open via port 80 to this particular Nexus with the GUI mode. So this was a very small example, but later on we are going to add multiple use cases on that. In this section, I'm going to show you that how you can edit that program. So what is the end goal we have? That edit that Python program and add some lines. So while executing the program, I can check show NX API. Okay. So let me go and open the empty putty. All right. So we are inside the Ansible. Let me go and edit this particular program. So I can go to conft, then I can enable the feature, that's okay. And after that, what I want to do here, that I want to see that as well. So how I can do that, I can click insert because I want to add few lines here. And I can go here, first of all, I want to add comment. So for example, I want to show the NX API, say feature status. Then I can give the same thing that you can see this particular place, remote shell dot send And what I want to send here is the show NX API end of the line. That will be the next line, and then close the parenthesis or the bracket. That's the common rule of the programming. Once you open some box or bracket, you have to close that as well. Then here I can give time sleep, say for example 1, complete programming or scripting type of things that we are doing at the moment. Output I can give, say for example I can give a space here, otherwise it will throw in some syntax error. Say remote cell receive, and most of the thing you can see that's the same that I'm using, that is there in the upper lines. Then I can go and give print command, print, because I want to see this output. And here also if I want I can give time dot sleep 1. Alright, so we have successfully edited one small portion of program here. Once we edit this particular program, what we can do, we need to save and come out from this. So for that I need to click say escape and then quit and write, that is QW, enter. Let me check that why write and quit, come out, and then you can go and check the execute this particular program. So it is printing the NXOS V1 line by line. Oh, you can see that here it has error, remote shell. See? So that's the beauty of program. It will go and check line by line all the items, and if you miss anything, it will simply go and tell you, okay, you missed this particular portion. So what it is telling, that this error, this place we have error because the configuration is, the spelling is incorrect. So I should give cell like this, and now I can type escape, write and quit, and then let's run that program one more time. So it is checking all those things. Up to here it's good, and now you can see the output that is running that command, that is the show NX API. So you can see that from Ansible, from one server, I can send the command and I can see the output also. So I don't need to go here to the NX or the Nexus box and SSH and check that output. Even from here also I can check the output. Okay, so that was the edit inside the small program that we have done initially. Next topic we have to construct a valid JSON encoded file. Now JSON is nothing but JavaScript object notation. It's very much like the text file. Here you can see the example as well. This is the format of JSON, but obviously in next example you will get a little bit complex program where you'll find that inside my program I want output in JSON format. So not only that I can use the input in JSON, but I can do the output in JSON as well. Both way it is working. It's very easy to read, it's understand. And where we are using JSON, so JSON we are using when we are running any API, and maybe you have seen this in our earlier SD-WAN API call, where we can get the output, or we are getting output in the JSON format, easy to read. And then it is used, or it may be called inside Python program. Here you can see import JSON inside the Python program, and in between Python and non-Python applications as well. So now here you can see that in the link below you can go and read more about the Python and JSON interaction with Python, I'm going to show you one import JSON example here. In the next video, you'll find that how we can export in JSON as well. Okay. So what you have to do, you have to go and use import JSON, and then I'll create one file where I want to put certain values. Say for example, the name, and then name is say Tom. Once we define the name, and again you can see it's very easy to read in double quotation, and then I'll go and define the age because these are the strings, or these are the characters, so that's why we are putting inside the double quote. But if it is a number, we can use like this. And then finally say address, and then we can go and give place. So we don't know what place. I'll go and give A, B, C, D is the address. All right, what we can do now that we can go and close this. Wow. So next that we can go and load the JSON. So JSON dot loads X, and then I can go and print the output in a dictionary format. So here I can go and give print say Y, and then I want to print the age, for example. Let me close the box. All right, so some mistake is there. You can see in the printf statement. If you click, should close this, and we should correct this print age. So this should be inside here. You can see if you have any type of mistake, you will get the error like this. All right, so apart from that, if you want to print the address, you can go and print the name. And that's the power actually we have, that once we have the program, we can have different type of output as well. So let's just stop here, and in next section you'll find that how we can create a complex program and use JSON as the output. In this section, I'm going to run one lab where you can see that how we can store the output over JSON format inside the local destination. For this, you can go and refer the link below. Say local underscore action. This is the shorthand syntax for execute a task on a local machine where the Ansible playbook instead of the target device. So let me show you this in the lab so you can understand more about this. For reference, you can go and check this link. Once we collect that output in JSON format, then how we can see that output? So what we are going to do, that we are going to create one playbook where in that playbook I'm going to store WLAN 10 interface details. Okay, so let me log into Ansible and show you this particular lab task. We are here in the Ansible. I can go and create the program. Program maybe say local output in JSON format. All right, so let's create this program. Let's create this playbook, and the name, I can give name as a, so let me give the name of this playbook. Say playbook for getting the WLAN 10 interface details in JSON format. Alright, let's start. So the same thing that we used to do, host is all, then gather facts. Yeah, gather facts is no, and then we can start the task. So let's start the task. What I want here, let me start the label under task. Get the interface details. If I want, I can put one comment that WLAN 10 interface details. So interface details store in JSON format. All right. Then inside this name, obviously we have to give NXOS command. So this time I'm going to use a command. What command I'm using? The command that I am using is say commands, simple CLI command like show IP interface VLAN 10 like that. This is the command that I'm going to use. All right. Then you can see here that if I give a space, because this is a programming thing, so here also I should give a space. Otherwise, if I'm not giving any space, then I should not give space to the other place as well. Same label, what I want to do, transport is NX API. Now I'm going to use a register, and that's the thing that you can go and refer the URL. So what is the register here? Register is interface facts. Now I want to give this to the local destination, this particular output. So this output collect to, say, collect to local destination at the rate of JSON format. So local destination at the rate of JSON format. Like that I can give the comment. And here also if I'm maintaining the label, so here also I can maintain the label, no problem. Now we'll move next and give the destination. So I am here now. And let's start with the label. Just label will be the same. Otherwise it will throw an error. So let's do this. All right. Local action. Copy the content. So what is the content we have? Content equal to interface facts that we have here. All right. And what's the destination? So the destination equal to dot slash interface, and then I can give the name. What is the inventory? Host name. And that's it. We are almost done. The format that we are using is JSON. We're done. So let's save this program and try to run in the playbook. This is the local output and inventory. So now we can see that this program execution is successful. Playbook for getting the VLAN interface detail, get the interface detail, copy task copy. So we have two tasks. You can see task 1 and task 2. And now if I want to see the output, I can go and check the interface. You can see this is the output in our program. So let me show you the output format as well. The output format is destination is interface, then host name is NXOS v1. It's like that, correct? So we'll go back here, and if you want to see the output, I can see like this. Now this output, you can see that this is in the JSON format for that particular WLAN 10 interface. You can see the IP address and all those stuff for WLAN 10. But again, this particular format is not that much helpful while we are reading this, because this is not in certain structure. Obviously, if I copy this and if I try to import in or try to convert this output in other formats, it's okay. But this is still not in that way that we can read it. So that's why we are going to convert this JSON format to other format as well. So let's just stop here. This JSON and the export that we have done for this particular task. So the agenda was to show you that how we can give the local destination. In the next upcoming labs, we'll see that how we can convert the formats in the other format. In 6.3, we have to learn about YANG, yet another next generation. Now, before understanding YANG, you can see that we have different type of data format. We have XML, JSON, and YAML. XML, JSON we have discussed earlier. So what I have done that I have given one example related to XML as well. In upcoming video, you'll find one lab related to XML. Basically, in XML language, what is happening that in this markup language, you have to start and you have to end like this. You have tag, value, tag. So you can create the header and footer and subheaders and subfooters, etc. And then inside that close box, you have to write your program. It's useful for netconf, restconf, and NX API. Likewise, we have a study about JSON. It's a very easy format to understand, and it is used by RESTconf and NX API. Again, then next we have yet another markup language that is heavily used inside Ansible, but we have to go and learn about new type of formats. Again, here you have the example, but for XML, just to understand XML, I have one lab for JSON. Also, we have done the lab. You can go and refer those videos that what the JSON format look like, how you can call inside. Actually, the description of the scenario was something like you have to call the JSON as per the curriculum. But we have seen and we have done one lab related to how you can export in JSON format. Basically, you can export in XML and JSON format both. Whatever looks good, we can export on those formats. Again, yet another markup language. Now, if you see the display, one thing is common that all three language overall it's very easy to understand. So even you can think that we are writing some sort of code or program like that high level program, and it's very much like human readable format. We are doing some configuration in Cisco via CLI, so it will look like that, these programs. Now when we are talking about yet another next generation, what I have done that one of the product in Cisco called NSO, Network Service Orchestrations or Orchestrator, they are using this YANG model heavily. So what is happening in NSO model that irrespective of what device you have, like it's a Juniper or F5 or Aruba or Cisco, etc., the same model or the same model driven program you can go and implement to on those devices. So related to that, in upcoming section you'll find, first of all I'll go and define what is NSO, one video, and then subsequent you have 3 videos, one video related to XML, one related to YANG, and again you can see the format of YANG, that you have the list and then you have to define the key, then you have to go and define the leaf type, again you have leaf and type. So it's something like a format where you have to put the data, and those data you can go and take from here you can see in the diagram, let's say if young model, you can take the data and you can have the output in XML, or you can go and take the data and may have the output in JSON or XML format. So yeah, you're going to see a complete program how you can write, although maybe you don't know NSO at this point of time. So you can think that okay, we're writing one program, just our understanding and knowledge, and at least to understand the format of YANG and then XML, that how the program look like. And once you execute the program, how you can go actually and execute the program and how the result look like if you are uh, willing to see the result in XML or in the JSON format. So here you can see this model driven programming YANG. It's very much human readable. You define the list and then the leaf and the type, leaf and the type. So one time leaf is just the name of the route distinguisher. So here you can see that you have the VRF. So this leaf is actually the name of the VRF, and here you can see the CLI. So I have VRF called red and then the RD. Again, you can see that okay, in CLI how easy it is. Go define IP, VRF and RD, and in program you have to write these many number of codes, but the great thing about programs are that you can reuse the code. Again here you don't need to give the value, because those values will come as an input, correct? So you have the program, you are giving the value as an input, and then you are getting the result for that. So what is the key here? Go define the list, leaf and type, leaf and type, and that's it, it will work. Young model supported inside Cisco iOS XE. Suppose in certain image, maybe some old iOS XE, if the model support is not there, then you can go to GitHub and you can download and you can upgrade the patch or update the patch. Cisco is supporting in their iOS XE XR plus Cisco NSO product, and then you have the standard body as well, like IETF, OpenConfig, Open Daylight, and IEEE, etc. All right, so this is the basic introduction of YANG. What is YANG? How the format look like? Now, in upcoming 4 section, at least 3 is for lab and 1 is for understanding of NSO. You can understand about this. Let us discuss about what is NSO. This Cisco Network Service Orchestrator. Actually, this product is evolution of NCS, and that NCS was actually the product of TELEF that has been acquired by Cisco at 2014. Now with help of this NCS or with help of this NSO, what we can achieve, that we can abstract either physical or the virtual devices, and then with help of some programming language, say some model driven programming language, we can assign the services or we can deploy the services. Once we are doing that, then we are bringing the services, means we are applying the services quicker than the normal operational speed that we have. We are improving the service agility, and hence uh, we have this new option, or we have the revenue opportunities to to enhance or to increase that. Obviously, it will increase the operational efficiency. In this particular course, you will find that lot many commands I'm going to use in terms of NCS, like NCS, NCS NetSeam, NCS CLI, because by the end of day, the programming or the operating system was developed by NCS, Network Control Systems. So that's the reason. Let me go to the next slide and let me show you the architecture of NSO. This is the architecture of NSO. You can see what are the key components here. So obviously we have two major key components here. One is the service manager. The second one is the device manager. And apart from that, obviously we can do programming, say in terms of RESTful or in terms of northbound. APIs like REST, RESTconf, NetConf, Java, Python, and other options we have. Now, this portion is something my NED, network element drivers. All my network devices are sitting here, either physical or virtual, say with help of NetConf and YANG. If I have to deploy a service, I can deploy it within few seconds or within few minutes, because by the end of day, what I have to do, I have to you can say that I have to extract my package, or I have to go inside my package, and then I have to enforce, or then I have to run a script. So once I run that script, my services will be enabled. Okay, let us discuss a little bit about the service manager and device manager. As name suggests, the device manager, they are something there to manage all the devices. Okay, manage different devices in a uniform generic way, and irrespective of Cisco or Juniper or any other vendor, they have that uniformity in the uniform way. This device manager managing all the devices. The device manager uses device models written in YANG. That is again very important, because here the concept is that we are using model driven approach. Okay, and we have the network element drivers, where we can unpack the instances or unpack the device models like Cisco, Dell, F5, Juniper, whatever. Okay, so device manager is there that will maintain the uniformity of all the devices, of all the snapshots of the devices. Then we have service manager. Now service manager, so here we know that with help of NSO, the target of NSO is that inside the devices you have to push the services. Okay, let me change the color. So I'm pushing the services inside my device. For that reason, I have two managers. One is the device manager, who is managing the uniformity of the devices with help of YANG. Even the service manager, they are also doing the same thing, means they are also maintaining the uniformity with respect to say F5, Dell, Cisco, Juniper, but they are putting some services. Some services like say L2 VPN, L3 VPN, like that. So each service app is a package, and that's again very important. The services are package. Okay, even everything is a part of package. You have to unpack the package, and you have to push inside the either physical or the virtual environment. Okay, one important thing here to note that the service managers support the full life cycle of a service, like creating, deleting, editing, etc. This comes with a patented built-in algorithm. So this is some patented algorithm, FastMap, and it is used to create, delete, edit all the services inside the NED. Okay, so the goal of NSO service is to map the service model parameter to the device. That's we know. We are mapping the services to the devices. Okay, and finally let us discuss about package, because this package thing come a lot in this section. What is package? Services, application, and NEDs are examples of package. So either my services or my network executable drivers, they are form of package. Okay, the package consists of YANG modules. That's again, this is a model driven approach written in Python or Java or any type of XML template, packages are loaded by NSO at a startup. So this package loading and not unloading, but this package loading you will see in the upcoming sessions, where I will load a package, then I will add some, actually I'm going to add two Cisco device like 2C0 and C1. So at that time you'll come to know more about these packages. Okay, a package is a control way of manage loading and versioning of a custom applications. In this section, we'll edit the service model, that is the YANG model file. So what I'm going to do, I'll go to my SNMP folder, and then I'll go to the YANG, and then with help of my VI editor, I will edit the YANG file, because in this case, I want to edit this in terms of my SNMP service. Okay, so what are the things that I'm going to change into the default program? That obviously those things will be related to my SNMP service. Here I'm going to apply SNMP service to one of my Cisco device where I have my SNMP template. Then I have my SNMP community string, and over that I have either read write or read only access. So this access, you can see that it is done via leaf access in terms of enumeration, read only or read write. Then the community string, so I have this leaf community string defined here, and the leaf device, I can check which device I am going to use from here. Then I have the common SNMP template, which will be here. Okay, so doing all these things, I'm going to import one tailf common function as well. So I will import that as well. Let me show you all these things in CLI. Let me go to the CLI. I have my CLI here. So from here, I can go to my source and then YANG. Okay, if I do ls minus la, you can see this is my YANG file. Let me go inside SNMP YANG. Okay, so here you can see this is my default template, and here I want to add some lines. So let me add all those things. First of all, I want to add, say, import the tailf common, and then prefix is tailf. Close this. Okay, then I have this list SNMP T1. That's okay. Key name I want to give. My key name is, say, community string comstr. That's okay. So here you can see the browsers, they are open, and then we'll check where it is closed. So it is open, means we are writing the common template for my list. Inside this list, I have leaf name. So leaf name, before changing that, let me add info here. Say tailf info, and that is my SNMP server community string. Okay, now what I want to do with this leaf, that my leaf is, say, community string, and then the
type is obviously the string, so that's okay. So we are very much done with this particular section from here to here. Now the next section, you can see that, let me show you the full program here. So we are getting one note here that may replace this with other way of referring the device. So let me change these notes, and what I can do here, that I can write my own notes. Say change this to leaf for one Cisco iOS, something like that. We are writing this code for one device. Now here what I can do, that I can add a leaf. So let me add that. Say leaf device, and I can give, say, tailf info that say pick any one Cisco iOS device, something like that. So what basically I'm doing here, that I'm adding a option that you have to pick a device. Then we have the leaf list device. So let me do one thing here. Because I am writing this only for one device, so what we can do here, we can remove this line. I don't want list, I want only one device. So that's why I've added the information. Rest is okay, this is okay, the path is also correct. Then finally we have this notes that replace with your own stuff here. So what I can do here, I can add, let me scroll down. So I can add my leaf device here, and for that leaf device, what is the access level? Because finally I have to add the access either read, write, or read only. So that's why let's add those things. So let me delete this line, because leaf access I want to give enumeration. Here I can add the info first. So you can see the structured programming, that what I am doing. Specify read only or read write access. Then we can go to the next line. Next line I can add, say, type enumeration. Then what is that type? The type is, say, enum, either read only or read write. Now finally we can put notes here that this is for, say, leaf access. So we come to know that where I am closing my braces. Otherwise, if any of these mismatch parentheses, I will get error while compiling this. Okay, this will be, say, list SNMP template, this one. So let me match it quickly. This one is open, so this is closed here, this is, and this is closed here and here, this is closed here. Type enumeration I need to close. Okay, so you can see that you have to match all the parentheses, and I have to go up here, and I need to close this. So this is closed here, leaf access closed here, then this one, And then finally we have the first program, that is the list T1. So I'm very much done with this program. Let me compile this and let us see if everything is correct. Then without an error it will execute, otherwise we'll get the error. Okay, for that let me go to one step back. Here if I do ls minus la, then you will see that I have this make file. Then what I can do here, I can make, say, clean all, enter. Here you can see that I am getting one error, unterminated statement for enum. Okay, so let me go to yang vi, and where I have this error, let me correct that. So I have to go here and use the semicolon, go here, use the semicolon, then escape, write that. Then again I will go one step down and I will execute this. Okay, so I have again one error here where it is 21 27 35 undefined prefix telf. Okay, so we'll do that as well. So these things you have to do while you're doing the programming. You need to improve all these things. I log to the program and I am correcting it. So whatever tail I have, I need to use tail F. Then again we'll go to one step down. Again we will execute this program. Now it is successful. Okay. In this section we are going to edit our XML template file. So for that I need to go inside my template folder and then I have to open my SNMP XML file. Once I open that file, then that file look like this, where I have to define the device and we have some placeholders. Here you can see that, okay, you can edit these sections. So we will edit these sections, but not only the devices and the name of the device, but we need to add what is our configuration template here, and those things or those variables will be taken from my Yang model. Okay, so I will define those things inside my XML because this XML package I am going to run. Okay, so let me show you that what are the changes I'm going to do in this. So changes here you can see that I need to define. So first of all, what device I'm going to apply this. Then the community, say name is community string. Then what is the access? Either it is a read only or read write. Okay, so once I will define all these things, then I need to execute this. So for that I will go log via maybe Cisco or Juniper style to my NCS, and from there I will reload the package and then we'll check the package. Okay, before reloading the package, what I have done in my device instances, I have added some devices like Alcalucent and F5 load balancer as well. So those instances also will see in the package output. Let me log to the device here. I am inside the template. Let me edit the SNMP XML file. Here it is.
Now what I'll do, I'll remove the placeholders. So let me remove them. And then I want to add, say, device. That device name is okay. Then inside the config, so let me delete these things also, because I'm going to add my configuration here. Let me add those configs. First of all, I want to add the SNMP, say server. So here is XML NS iOS. Close this, go next. Add the community. Inside that, say name, and then I have to define the variable. So let me define the variable here. That is taken from the Yang model. Then let me close this. Name. Okay. Then what I have to do here, I have to define, say, read only, when it will read. So give that as well. Say starts with access. So with, and then I have to define the access. Access will be, say, read only. Close the bracket. Close the parenthesis. So whatever things related to, say, programming, that whenever you are opening a braces you have to close it, you have to use all those things here. Then close this as well, otherwise while compiling it will throw an error. Okay, so the same thing I am going to do here. Only thing here is the read write, and when starts, say, with access, read write. Okay, and then this also we can close. So far we have done the configuration for the community string. Let's close this. Let me close this community. Done. Then let me go and close the SNMP server as well. This is also done. So we are very much done. You can see only 3-4 lines of code, but you need to understand that these things will be called from the Yang model. So we have configured this, say, device, then the device name, then the config, then the access, and then we have closed all these strings. So let me write it. Now next what I want to go to my NCS CLI. Let me log in terms of Cisco, and from here I need to reload. So I need to reload the package. So package reload, and if we get something like successful or two masses for my SNMP XML, that means that configuration is correct. Obviously the package will reload successfully, and then what I can do, that I can check that package status. Okay, the package status means the operational status of the package. So give this to 1 to 2 minutes. Once it will come back, then we'll check the result here itself, and we'll check the operational status. You can see here reload result is successful. Now I can check the packages, say SNMP. I just want to check my operational status as well. Show, say, packages, yeah, operational status. And here we have SNMP, that is up. We are very much done with this section. Now we are done with our service model. In this section, we'll implement it over Cisco IS, and then we'll verify it. Let me go to my CLI. I logged in as a Cisco CLI. Let me configure it. My SNMP, let me check. I have my template. Then what I want community string, say that is my giganet. Then if I type question mark, access, it is asking what access level I have. For this I have read write. Now I can give the device, let's say C0, and we are done. Likewise, I can go to the same template. I can give, say, net giga, access read only, device is C0. Now what I can do here, I can check my, let me go to the top first. Now I can check the commit. So let's do that, commit and then dry run. No capability found, C0 has a sync from device has been performed. So it is telling that you can sync from, let me do that. Will not write this. We'll do one thing, we'll request to sync from. So let me check the available options I have. Yeah, I have sync from option. Let's wait for a minute. Now it has been synced. What I can do here, I can check the package operational status. So let me do that. Say show package. Okay, let's go back and let's do the configuration for my, say, SNMP. Before doing any commit, let me check this, and I want to check commit dry run. Yeah, now it is showing this, that CLI local node data device C0. You can see all these plus these things that I am adding here. Let me add one extra line here. This time what I want say net giga, and then the device access read only. Okay,
Now I can go to top, and again I can verify the dry run. So here we can see that I have iOS SNMP, where read and write and read community. The template is this. Okay. Now what I can do here, let me commit this. Commit is completed. Now I can go out from here. If I type SNMP, say giganet, we'll check the sync info in sync. Likewise, the netgiga will also in the sync. Let us verify the SNMP T1 and SNMP giganet. Okay, then netgiga, that is also okay. Now if I exit from here, if I do switch CLI and configure, if I go to the Juniper mode, from here if I check show SNMP T1, now you can see this in the Juniper mode as well. Let me go back to the Cisco mode. So this is the way we can check. Now what I want to do here, let me go back to my NSO, and inside NSO if I go to netsim CLIC say C0, so if you are in the correct folder it will give you the output. Yeah, so I am inside C0, you can see this. Now from here also if I check show running configuration, say SNMP server, now we have this expression or this configuration that is we are using in Cisco iOS. Okay, so this is also there. So you have seen three things here, that from NCS admin I can go to Juniper, I can go to Cisco, check those things. Then what I can do, I can go to my NSO, and then from NSO I can go to my netsim. From there I can go to that device, and then I can check in that native Cisco format. Okay, so you can see this much of options and possibilities we have that we can verify. Okay, let me log back to my NCS. So I can go to NCS CLI U admin Cisco, and from there if I want to check the metadata, so that option is also with me. I can go to C0 and then say iOS. Let me type question mark here. So what I want to do here, that I want to check the config first. Seems that I'm missing something. Say device, and that is the thing, if you are running in Juniper mode, then you have to use some other strings. If you are running in Cisco mode, then you have to use some other strings. Okay, so that is also one thing that we can learn. I want to check the config. That config is iOS SNMP
Then it is asking about exec and default. So let me check this. That option is there in the Juniper mode. So you have to type this show device 0 config iOS. SNMP server display service metadata. If you press enter, then you will see here what is the reference count, because this time we have created these service model just to refer one device. So you can see the reference count and the string, all those things. 6.4, we have to go and understand the API related to DNS Center and vManage. Now, the API related to vManage, I have already covered. So you can go and check, or you can refer the lecture 164 and 165 in the same series. And in the upcoming 6.5, I'm going to cover the API for Cisco DNA, and we are going to learn more and more about that. Next important topic we have is RESTful API related to DNA. Now, before coming here, you please complete 164 and 165, where I have explained about the vManage API, and those are the lectures. Now, coming back to DNA RESTful API, here you can see first of all the overall structure of DNA, where in bottom you have intent-based infrastructure, where you have the endpoint devices and all IT related devices, correct? Then we have the DNS center, that's the software that is going to glue the intent based infrastructure and the open platform. Now, when we are talking about open platform, that means you can go and uh, integrate with so many different type of open available softwares. Obviously that will increase the agility, and that will overall that will increase the performance of DNA in terms of when we are using all of the capabilities. So obviously the total cost of ownership will get reduced. The overall end-to-end network optimization plus visibility will get very much improved. Now here you can see that we have integration with the IT management tools, say for example ITSM, IPAM, Infoblox, etc. Third party integration is there. We can go and connect with the SD-WAN, ACI, security, Stealth Watch. Those are used inside the security monitoring. But even Stealth Watch is doing more than that. Even Stealth Watch can take the input and send somewhere for further analysis or other stuffs as well. So, but overall, we have the integration with other domain, cross domain as well. But where is the intent? Now, intent you can see an intent based API, you can see on the top where you have the business and network intent, where we have the application, policy, assurance, plug and play topology, wireless provisioning, network discovery, software management, etc. So the list is long, and here we are using the API. At this point of time, we know that when we are using RESTful API, obviously we are doing HTTPS call, and the methods are, say, get is something like show command, means you are getting the output or result. Post if you want to create a new object. Put if you want to update object. Delete means if you want to delete any object. Okay, so means the important thing here is to understand that whatever technology we have, either it's a ACI or SD-WAN or DNA, every year you'll find that same type of a structure is has been used for RESTful API. So once you understand the API and the calls, then that is applicable for all the cross network domain or all the other domains where this API, RESTful API, is going to be used. Now again, if we use this approach, overall uh, cost of ownership will reduce, the optimization for network will improve, and again we can add, or we can have new capabilities in the network. How we can do that? I'll show you. I'll log into the DNA and I'll show you that where you'll get it. But if it is a new installation, you can go to the software update. So here you can see that we can go to software update, and then we can go and install the software update. Here in the bottom you can see that we have the updates. Now once you do the installation, then you should go and enable the DNS Enter REST API. Once you enable DNS Enter REST API, then you can go to the development toolkit. Inside development toolkit, you can see now you have the get, post, put, all those methods. Suppose if you want to check the health of the network or health of the devices, so this particular first API get site health, it will give you the health of site, return overall health information of all the site. So once you do this get method, means you want to see, this is something like show command. If you want to see that health of the network, you can go there, click run, and then it will go behind the scene. This particular API will run and you will get the output. So here in case you can see that you are going to use this REST API, where you have the DNA intent API version 1 network devices, and then you will go and as per the query you will get the result. Now while you're getting the result, if the code is 200, that means successful. And likewise, you have all the codes here. So for example, 403, that means server recognizes the authentication, but client is not authorized to perform the request. So likewise, we have all these um, success code, the messages. A success code is 200, but suppose if you are running the API, and how could you know that which particular state you are in? So if you go and check these codes, you'll come to know that up to which particular point you have any issue related to REST API. All right, again, so here you can see the model schema for the API, and you can go and click run, and you will get the output in the JSON format, but again you can convert the output as per the desired. All right, so let's stop, and next section I'll log into DNA and I'll show you that where you will find this API. Alright, so let me show you that how you can go and verify any of the API. So once I log in inside the DNA, here you can see the dashboard, and it's quite robust. You can go deep inside the DNA dashboard and you can see so many things here. So what we want to do here, that first of all let me show you that where you'll get the information about the API. So here you can go to the document section. Here you can see that you have the API references. You can open this particular page and you can get the information about the API. Let me open this and let me show you this particular page, that once you open how it look like. So here you can see that developed by DevNet, and then you can go and see the intent based APIs, and there's so many revisions and you can learn a lot from this place, correct? So you have the SDA APIs, how it is going to work, what are the methods we have like post, get, put, delete, etc. Each and everything you can go and understand from here in detail. So this is the documentation page for the DNA API. All right, so let me walk you through that. If you are doing this first time, from where you have to go to enable it, and then how to use it. So for that reason, you can go and check the platform. Once you are inside the platform, here you can see that you have the bundle. Now in the bundle, you can see bundles are easy to use features set for consuming intent based API. So if you go and click there, now here you can see that suppose your API REST API is not active. So what you have to do, you'll get one button called enable. You can click there and it will get enabled. So for example, ITSM service now is not enabled, and other integrations are also, you can see that not enabled, but our RESTful API is enabled. If it is not, you can go and click enable it. Now, once you do the enablement, then on the top you can see that you have the manage bundles and configuration. You can just go and verify the configuration as well. But if you want to check the REST API, so for that you have to go inside the developer toolkit. Here you can see that you have the developer toolkit and API. You can go there, and then you will get the RESTful API related to authentication, know your network, site management, connectivity, operation task, policy, etc. So suppose if I go here and click know your network, and inside know your network you can go and check the site, topology, device, clients, user, etc. Then site management, you can go and check the site management related stuffs. In policy you can go and check the policy related stuffs. Again you can see the color coding is also there, and that's true for all these methods in most of the API runner. So for example SD-WAN we have Swagger where we are running the APIs. So here you can see that the green yellows for get and then put and then post and delete is red. Okay, so what I want, suppose I want to know my network, and say for example if I go to topology, inside topology I want to know that what type of VLANs I have. So here you can see this particular API will run. Let me go back. So here you can see that you have this get the VLAN. You can go and click here to this blue get VLAN detail, or you have three dots. You can go here and then try it. Both is okay. You can go to any of the place and click it. So now you can see that the public URL, and you want to run this API, and success code is 200. That means correct, and then you are getting the response. So all the VLAN in your infrastructure you are able to get from here. If I go and click here also, so here you can see that this is the API, and again it is telling all these codes that we have seen earlier. Then here you can see that route map option response and version. So here you have little bit much more output, and that is adding the model schemas as well. Now again if you run, it will go and reach to this place and you'll get the output. Okay, so this is the way that we can go and execute the API, and we can go and check all different methods as well. Next important topic we have event management. Now this event management is actually on box, so that's why it is embedded event management. What does it mean by on box automation and the off box? You can see, say on box means that my device or my operating system has the capability to do n number of tasks. And yes, you can see that we can go and use TCL script, EM scripts we can write. We have POAP, power on auto provisioning, smart install, micros. Also, people are using micros a lot, and then the embedded Python programming as well. Whereas we can go and integrate with REST API, RESTconf, SDK, software development kits, DevOps tools, and Linux as well. So both the features are there, but at this point of time, suppose if you don't have off-box capability, even Cisco devices has that much capability and power that we can go and do the scripting. We can write the scripting. Now, important thing here is that when we are writing this script, say for example, embedded event management script, what are the benefits we have? How we are going to get benefit from this? Here you can see that nowadays the EM is quite powerful, and we have more than 20 different type of events. Based upon that, we can go and write the scripts. So what does it mean? Before dealing more about this, let's try to understand the architecture. Let's try to understand some more terms about EM. So first of all, and this is the one of the most important thing we should understand, that the architecture. So when we are talking about architecture, first thing we know that this is on box, that is within the box within the device, first thing. Now this is modular and it consists of event detector. Event detector means that whenever you are writing the EM script via CLI, and second point is the CLI interface. So whenever you're writing this script via the CLI interface or you're taking help from TCL language or TCL, at that time based on event detector. So what type of event detectors we have? So for example, based on syslog messages, based on certain other events, nowadays we have 20 plus events. So let me quickly show you the events on which you can go and write the program. So here you can see syslog, timer, gold, XML, RF, SNMP, IPSLA, OIR counter, etc. So on the basis of these, we can go and write the EM script. Now those are termed as event detector. Then we have event manager server as well. And then the action that we are putting, those are called as a policy. So three terms: event detector, event manager server, and the policy. So detector, server, and policy. We can go and use the CLI interface to write the policy. We have the policy scheduler as well, means when this event will go and trigger. And you may have multi-threading triggers as well. So for example, high CPU case. Now it is reported that in a day, 2 or 3 times the CPU of that particular device is going high or there is a spike. Now it's very difficult for an engineer that you are there and you're checking the device all the time. So when the CPU spike will come, you'll go and run some commands and you'll get the output. Rather than related to high CPU commands, so for example, 4 to 5 important commands, we can put inside EEM script. Whenever the system will trigger a syslog message like high CPU, at that time that script will run. It will execute 3 4 commands. Those commands will go stored inside the file that you can go and use it for the troubleshooting purpose. Correct? Now we have a lot much enhancement inside EM script. So we have enhancement in EEM email action, EEM security enhancement, supporting MD5 SHA-1 with the ethical policy. So we have the checksum. Then we have enhancement in the resource management. So manually set the CPU, memory, EMQ thresholds. We have enhancement in the detectors as well. So more and more detector has been added. So for example, IPv6 routing event detector, syslog event detector, and others as well. And now we have the EM usability enhancement as well. So you can go and write, you can put those EM script as per the use case. There is again one a very important use case we have related to, say for example, security and ICE. The few of the customer, they are writing EM script. Suppose we know that ICE how it works. You do the authentication and then you get the authorization. Suppose if your ICE server is unavailable at that time because you haven't done the authentication, you'll not get the authorization. So you can write a script that once the ICE is unavailable, so you can use IPSLA to check the ICE is up or not. So suppose if it is down for example, or it's not down but unreachable for 5 to 10 seconds, then automatically the ACLs that we have over the interfaces, they will give allow or permit any. So again, condition-based policies and rules we can go and write depending upon what type of use case and what type of problem or troubleshooting we are doing it. Now here in the diagram, you can see the architecture that we have the detectors, we have event management server. Inside that container, we have application event detector. That's again going to IO subsystem. We can go and use TCL or TCL to create EM script, or we have option that directly we can go and use the EM applet CLI based policy that we are going to do in the next session. So let's stop here, and next section we'll go and create one high CPU related policy to learn more, to understand more about EM scripts. We are going to understand one of the use case. So for example, in case of high CPU. So I'm going to write one script, and in this case here you can see that the threshold is set to 80 here. It should be the production threshold, but in my case I'll make this 20 so I can get the alert. So once I get the alert, so first of all, what type of alert I'm going to get? So I'll get one syslog message like CPU rising threshold. Let me show you the diagram first. Say I have only one switch here connected in the GNS, and then what I have done that I have used this configuration. So if you use this configuration, that means it will go and generate the syslog message. So I'm going to use this particular syslog message to write my EEM script. So here you can see that I have this syslog message, and it should start with this. That's the percentage. So here you can see that this is the syslog pattern. What will happen at the moment I will detect this, means at the moment the system will detect this. So this EM script will go and give message that high CPU detected. Then the device itself will enable. It will go and write these commands. So show process CPU sorted, CPU monitor, CPU history, CPU sorted, excluding 00, extended history, etc. And then these things will be uh, go and it will write over flash and this CPU text file that again we can go and check. Now the use case is this, that this will happen at the time of trigger. And what is the trigger and what is the detector? Detector is syslog. Syslog will generate message, and then this script will go and run. Correct? So let me copy and paste this configuration to the switch. I will go to the switch, and here we can go and write this. Now I should have all these commands configuration that we are putting here supported in the device. Now what will happen? We'll wait for a next trigger. So at the moment the trigger will happen, you will see that all those configurations will be written over flash and the CPU high CPU.txt. Now if I go and check the flash now, so for example show flash and include high. So at the moment I don't have any trigger, and that's the reason we don't have this file there, high CPU text. Now we can go and check. So process CPU sorted. What's the CPU? Okay, so CPU spike is 1 minute 34%, 5 minute 30%, more than that. And what's the condition that we have put? That we can go and check show run section process. All right, so here you can see that CPU process total rising 20%, and then all the process related command that we have given inside the EM script, it is like this. Okay, so let's wait for the trigger. So although we are waiting and trigger is not coming, so what I will do, I'll go and change the process CPU. Say you can see the command as well, threshold, and then when it is asking about type, I can go and give process related rise, say rising 20, interval, I can go and give 5 is the minimum, enter. So instead of giving total means that it was uh, two major process plus interrupt means the hardware process and then the traffic. That was the interrupt. So high CPU is having two. Uh, you can think that two function or two component whenever we are measuring the high CPU. Now if you go and put total here, so it will calculate both the things. It will calculate the interrupt plus the process and then it will give the output. Now here you can see that high CPU has been detected. Here you can see 64%, 10, etc. So one is the process, other one is the interrupt. Process and interrupt. Now if we go and check show flash and the high, so we should have that text file in the, yes, here you can see text file in the flash. And then if you want to check that, so we can go and check high CPU like this. So which is the trigger iOS E having this much. Different processes are there. So that's the one output. Further, we can go and check the others as well. So whatever we have put inside the EM script, you can go here and check, and then at least we can get the idea that what happened to trigger this particular event. So which particular process or maybe interrupt causing to trigger this event. All right, so yeah, so that's the way we can run this. Even you can also practice this in your GNS environment. And I have taken only one switch, but you can create one loop related to STP or maybe so many SNMP poll or maybe some sort of DOS attack related to traffic or maybe BGP high traffic utilization. Those things can be simulated, and then you can check that which particular process or interrupt is causing the problem in the lab environment. All right, so let's stop here. This is the last session for this particular course. We have to understand the agent and agentless tool such as Ceph, Puppet, Ansible, and SaltStack. So let's start understanding these things. Before understanding this, let's quickly do the revision that what about the other aspect to configuring the device. So we know that we started our career as a CLI network engineer. So we used to type the commands, copy paste in the notepad, and then creating same type of configuration, changing certain IP interfaces, etc. And then we are putting that notepad configuration to rest of the devices. Then there is evolution of GUI. So for example, one of the good example for GUI based networking device is, say, for example, Cisco ICE or maybe ASA firewall ASDM. Those are very popular. And now if you compare the security appliances related to networking router and switch devices, you'll find that in security appliances you have to do so many things that's very difficult to do via CLI. Means it's time consuming and there are chances of error as well. So then there is evolution of GUI. If you see in the market at present, you'll find that few of the vendors, even though they are not supporting CLI. So for example, VMware VeloCloud. There you have option either you can configure via GUI or API. Those options are there. So like that the evolution of networking happened, that we move from CLI to GUI and API. And now when we are talking about API, then we have the integration with third parties as well. Now these API, they can use the methods such as SSH, HTTP or HTTPS to manage the devices. And when we are managing the devices with the API, the biggest advantage we have is that we can manage n number of devices with same type of API or same type of calls or the routine calls, etc. That is, although it's not possible with the CLI, because whenever we are talking about CLI, the scale is missing. The scalability factor is not there in CLI. So that's why the companies, organization, enterprise, network, they are looking for the solution where the scale will be there. Now, in the same line, we'll find that again there are several evolution. So there is evolution in the virtualization world. Here you can see in the list that we have enterprise system operations. So for example, VMware vCenter, Microsoft System Center, vRealize, BMC, HP. Now what is happening that we have the orchestration tool, you can say, or you can say the management tool to manage the virtual system or virtual machine. So for example, VMware vCenter, where you have the hypervisors. Again, I'll go back. So the physical system, on top of that you have hypervisor, on top of that you can have guest operating system. Now suppose if you have n number of infrastructure like this, then you can go and manage via VMware vCenter. So from VMware vCenter, you can go and manage n number of ESXi. Now this n should be some limited number, but you can manage more number of systems. Likewise, Microsoft or vRealize. Now this is the enterprise system operation. Then on other hand, if we go and check Cisco solution, Cisco has their own Cisco ACI application centric infra to do the automation for the data center. Then SDN controllers, then Cisco has WAN automation engine, then we have NSO, network service orchestration, then we have application policy infra, we have APKM. These are the Cisco solutions that we have, means to overall manage everything from the either GUI or API. All options are there. Then here in the bottom you can see that we have open source software as well, and they are also big and popular. So we have Ansible, which is very easy to understand and do the configuration, Puppet, Chef, Salt, Stack, Python, Ruby. These are come under open source software. Now the important category here is that we have agent versus agentless orchestrator or management tool. Now what is agent based? So here you can see the Puppet, Chef and Salt stack. Actually they are agent based tool. So how they are working is that you have servers. So you have servers somewhere, and then you have a small agent located at different locations. Now, when we are having agents at different locations, so those agents, they are local obviously, and they are taking the configuration, they are taking the uh, management things, they are taking the stuff, they are taking the input. Now those agents at different locations, they are going to communicate with the server, and as per the server programming, as per the server rule base, they will go and react. Now that rule base that we have in the server in terms of programming language, and here the programming language is Ruby, R-U-B-Y, they are generally termed as a cookbook. So we have, so here you can see that the agent would be running on all servers which have to configure. The agent will pull the cookbook from the masters. So you have created the policy to the master and masters. So all the agents will go and push the rule book or the cookbook or policy from the master, and then they can react. Now you can find there is community also, and the URL link also. If you want to know and learn more about Ceph, you can go and check. Now the next similar type of orchestration or management tool we have is Puppet. Puppet is also Ruby based. So what's the difference between Chef and Puppet is that Chef cookbooks are more developer centric, while Puppet is developed by keeping system admins in mind. So in case of manageability, you'll find Puppet is uh, managed or the system admins in mind while they wrote this Puppet orchestration tool. Now both the Puppet and Ceph, they are based on agent and server. So agents will go actually and pull the cookbook or playbook or the policy. from the master, and then they will work. Again, for more information, you can go and check the Puppet Forge, or these are the links. Again, the third thing is the salt stack. Now here you can see Puppet and Ceph and Puppet. Salt stack is doing the same thing, same manner, means the architecture is same, but there is one big difference in this. Instead, those agents, they are going and asking, or they are pulling the cookbook from the master. Now here there is freedom for the agents that they can go and contact with the other agents as well, and they can pull the cookbook or the rule book from the other agents as well. So what does it mean? See, it means that the Ceph and Puppet, they are very much hub and spoke type of architecture. But when we are talking about salt stack, this is something like full mesh, any to any type of architecture. So any spoke can communicate with any other spoke and take the information, and that's why salt stack is very fast with compared to Puppet and Chef. Now the final orchestration tool we have here is the Ansible. This is also one of the popular tool orchestration or management tool we have. Ansible is one of the programming language like Python, but it's quite popular because it's very easy. It's using YAML format, yet another markup language, to do the configuration, to do the programming. And the difference between a Puppet, Chef, and Salt Stack is that the Ansible is agentless. Since this is agentless, that means it's lightweight. And you can see the use cases with Ansible, that Ansible is also supporting n number of vendors, since it's multi-vendor supported, and it's very lightweight, it's very easy to use, it's very easy to code, and that's the popularity of Ansible. Ansible is quite a popular orchestration and management tool. All right, so let's stop here.